3. Of the Ground of Induction. Section 1. Induction properly so called, as distinguished from those mental operations, sometimes, though improperly, designated by the name, which I have attempted in the preceding chapter to characterize, may, then, be summarily defined as generalization from experience. It consists in inferring from some individual instances in which a phenomenon is observed to occur, that it occurs in all instances of a certain class, namely, in all which resemble the former, in what are regarded as the material circumstances. In what way the material circumstances are to be distinguished from those which are immaterial, or why some of the circumstances are material and others not so, we are not yet ready to point out. We must first observe, that there is a principle implied in the very statement of what induction is, an assumption with regard to the course of nature and the order of the universe, namely, that there are such things in nature as parallel cases. That what happens once, will, under a sufficient degree of similarity of circumstances, happen again, and not only again, but as often as the same circumstances recur. This, I say, is an assumption, involved in every case of induction. And, if we consult the actual course of nature, we find that the assumption is warranted. The universe, so far as known to us, is so constituted, that whatever is true in any one case, is true in all cases of a certain description. The only difficulty is, to find what description. This universal fact, which is our warrant for all inferences from experience, has been described by different philosophers in different forms of language, that the course of nature is uniform. That the universe is governed by general laws, and the like. One of the most usual of these modes of expression, but also one of the most inadequate, is that which has been brought into familiar use by the metaphysicians of the school of Reid and Stuart. The disposition of the human mind to generalize from experience, a propensity considered by these philosophers as an instinct of our nature, they usually describe under some such name as our intuitive conviction that the future will resemble the past. Now it has been well pointed out by Mr. Bailey 107 that, whether the tendency be or not an original and ultimate element of our nature, time, in its modifications of past, present, and future, has no concern either with the belief itself, or with the grounds of it. We believe that fire will burn tomorrow, because it burned today and yesterday, but we believe, on precisely the same grounds, that it burned before we were born, and that it burns this very day in Cochin China. It is not from the past to the future, as past and future, that we infer, but from the known to the unknown, from facts observed to facts unobserved. From what we have perceived, or been directly conscious of, to what has not come within our experience. In this last predicament is the whole region of the future, but also the vastly greater portion of the present and of the past. Whatever be the most proper mode of expressing it, the proposition that the course of nature is uniform, is the fundamental principle, or general axiom of induction. It would yet be a great error to offer this large generalization as any explanation of the inductive process. On the contrary, I hold it to be itself an instance of induction, and induction by no means of the most obvious kind. Far from being the first induction we make, it is one of the last, or at all events one of those which are latest in attaining strict philosophical accuracy. As a general maxim, indeed, it has scarcely entered into the minds of any but philosophers. Nor even by them, as we shall have many opportunities of remarking, have its extent and limits been always very justly conceived. The truth is, that this great generalization is itself founded on prior generalizations. The obscurer laws of nature were discovered by means of it, but the more obvious ones must have been understood and assented to as general truths before it was ever heard of. We should never have thought of affirming that all phenomena take place according to general laws, if we had not first arrived, in the case of a great multitude of phenomena, at some knowledge of the laws themselves. Which could be done no otherwise than by induction. In what sense, then, can a principle, which is so far from being our earliest induction, be regarded as our warrant for all the others? In the only sense, in which, as we have already seen, the general propositions which we place at the head of our reasonings when we throw them into syllogisms, ever really contribute to their validity. As Archbishop Whately remarks, every induction is a syllogism with the major premise suppressed, or, as I prefer expressing it, every induction may be thrown into the form of a syllogism, by supplying a major premise. If this be actually done, the principle which we are now considering, that of the uniformity of the course of nature, will appear as the ultimate major premise of all inductions, and will, therefore, stand to all inductions in the relation in which, as has been shown at so much length, the major proposition of a syllogism always stands to the conclusion. Not contributing at all to prove it, but being a necessary condition of its being proved, since no conclusion is proved, for which there cannot be found a true major premise. 108. The statement, that the uniformity of the course of nature is the ultimate major premise in all cases of induction, may be thought to require some explanation. The immediate major premise in every inductive argument, it certainly is not. Of that, Archbishop Whately's must be held to be the correct account. The induction, John, Peter, etc. are mortal, therefore all mankind are mortal, may, as he justly says, be thrown into a syllogism by prefixing as a major premise, what is at any rate a necessary condition of the validity of the argument, namely, that what is true of John, Peter, etc. is true of all mankind. But how came we by this major premise? It is not self-evident, nay, in all cases of unwarranted generalization, it is not true. How, then, is it arrived at? Necessarily either by induction or ratiocination. And if by induction, the process, like all other inductive arguments, may be thrown into the form of a syllogism. This previous syllogism it is, therefore, necessary to construct. There is, in the long run, only one possible construction. The real proof that what is true of John, Peter, etc., is true of all mankind, can only be, that a different supposition would be inconsistent with the uniformity which we know to exist in the course of nature. Whether there would be this inconsistency or not, may be a matter of long and delicate inquiry, but unless there would, we have no sufficient ground for the major of the inductive syllogism. It hence appears, that if we throw the whole course of any inductive argument into a series of syllogisms, we shall arrive by more or fewer steps at an ultimate syllogism, which will have for its major premise the principle, or axiom, of the uniformity of the course of nature. 109. It was not to be expected that in the case of this axiom, any more than of other axioms, there should be unanimity among thinkers with respect to the grounds on which it is to be received as true. I have already stated that I regard it as itself a generalization from experience. Others hold it to be a principle which, antecedently to any verification by experience, we are compelled by the constitution of our thinking faculty to assume as true. Having so recently, and at so much length, combated a similar doctrine as applied to the axioms of mathematics, by arguments which are in a great measure applicable to the present case, I shall defer the more particular discussion of this controverted point in regard to the fundamental axiom of induction, until a more advanced period of our inquiry. 110. At present it is of more importance to understand thoroughly the import of the axiom itself. For the proposition, that the course of nature is uniform, possesses rather the brevity suitable to popular, than the precision requisite in philosophical language, its terms require to be explained, and a stricter than their ordinary signification given to them, before the truth of the assertion can be admitted. Section 2. Every person's consciousness assures him that he does not always expect uniformity in the course of events, he does not always believe that the unknown will be similar to the known, that the future will resemble the past. Nobody believes that the succession of rain and fine weather will be the same in every future year as in the present. Nobody expects to have the same dreams repeated every night. On the contrary, everybody mentions it as something extraordinary, if the course of nature is constant, and resembles itself, in these particulars. To look for constancy where constancy is not to be expected, as for instance that a day which has once brought good fortune will always be a fortunate day, is justly accounted superstition. The course of nature, in truth, is not only uniform, it is also infinitely various. Some phenomena are always seen to recur in the very same combinations in which we met with them at first, others seem altogether capricious. While some, which we have been accustomed to regard as bound down exclusively to a particular set of combinations, we unexpectedly find detached from some of the elements with which we had hitherto found them conjoined, and united to others of quite a contrary description. To an inhabitant of Central Africa, 50 years ago, no fact probably appeared to rest on more uniform experience than this, that all human beings are black. To Europeans, not many years ago, the proposition, all swans are white, appeared an equally unequivocal instance of uniformity in the course of nature. Further experience has proved to both that they were mistaken. But they had to wait 50 centuries for this experience. During that long time, mankind believed in a uniformity of the course of nature where no such uniformity really existed. According to the notion which the ancients entertained of induction, the foregoing were cases of as legitimate inference as any inductions whatever. In these two instances, in which, the conclusion being false, the ground of inference must have been insufficient, there was, nevertheless, as much ground for it as this conception of induction admitted of. The induction of the ancients has been well described by Bacon, under the name of inductio per enumerationem simplicem, ubi non reperitur instantia contradictoria. It consists in ascribing the character of general truths to all propositions which are true in every instance that we happen to know of. This is the kind of induction which is natural to the mind when unaccustomed to scientific methods. The tendency, which some call an instinct, and which others account for by association, to infer the future from the past, the known from the unknown, is simply a habit of expecting that what has been found true once or several times, and never yet found false, will be found true again. Whether the instances are few or many, conclusive or inconclusive, does not much affect the matter. These are considerations which occur only on reflection. The unprompted tendency of the mind is to generalize its experience, provided this points all in one direction, provided no other experience of a conflicting character comes unsought. The notion of seeking it, of experimenting for it, of interrogating nature, to use Bacon's expression, is of much later growth. The observation of nature, by uncultivated intellects, is purely passive. They accept the facts which present themselves. Without taking the trouble of searching for more, it is a superior mind only which asks itself what facts are needed to enable it to come to a safe conclusion, and then looks out for these. But though we have always a propensity to generalize from unvarying experience, we are not always warranted in doing so. Before we can be at liberty to conclude that something is universally true because we have never known an instance to the contrary, we must have reason to believe that if there were in nature any instances to the contrary, we should have known of them. This assurance, in the great majority of cases, we cannot have, or can have only in a very moderate degree. The possibility of having it, is the foundation on which we shall see hereafter that induction by simple enumeration may in some remarkable cases amount practically to proof. 111 No such assurance, however, can be had, on any of the ordinary subjects of scientific inquiry. Popular notions are usually founded on induction by simple enumeration. In science it carries us but a little way. We are forced to begin with it. We must often rely on it provisionally, in the absence of means of more searching investigation. But, for the accurate study of nature, we require a surer and a more potent instrument. It was, above all, by pointing out the insufficiency of this rude and loose conception of induction, that Bacon merited the title so generally awarded to him, of founder of the inductive philosophy. The value of his own contributions to a more philosophical theory of the subject has certainly been exaggerated. Although, along with some fundamental errors, his writings contain, more or less fully developed, several of the most important principles of the inductive method, physical investigation has now far outgrown the Baconian conception of induction. Moral and political inquiry, indeed, are as yet far behind that conception. The current and approved modes of reasoning on these subjects are still of the same vicious description against which Bacon protested. The method almost exclusively employed by those professing to treat such matters inductively, is the very inductio per enumerationem simplicem which he condemns. And the experience which we hear so confidently appealed to by all sects, parties, and interests, is still, in his own emphatic words, mera palpatio. Section 3. In order to a better understanding of the problem which the logician must solve if he would establish a scientific theory of induction, let us compare a few cases of incorrect inductions with others which are acknowledged to be legitimate. Some, we know, which were believed for centuries to be correct, were nevertheless incorrect. That all swans are white cannot have been a good induction, since the conclusion has turned out erroneous. The experience, however, on which the conclusion rested, was genuine. From the earliest records, the testimony of the inhabitants of the known world was unanimous on the point. The uniform experience, therefore, of the inhabitants of the known world, agreeing in a common result, without one known instance of deviation from that result, is not always sufficient to establish a general conclusion. But let us now turn to an instance apparently not very dissimilar to this. Mankind were wrong, it seems, in concluding that all swans were white. Are we also wrong, when we conclude that all men's heads grow above their shoulders, and never below, in spite of the conflicting testimony of the naturalist Pliny? As there were black swans, though civilized people had existed for 3,000 years on the earth without meeting with them, may there not also be men whose heads do grow beneath their shoulders? Notwithstanding a rather less perfect unanimity of negative testimony from observers, most persons would answer no. It was more credible that a bird should vary in its color, than that men should vary in the relative position of their principal organs. And there is no doubt that in so saying they would be right, but to say why they are right, would be impossible, without entering more deeply than is usually done, into the true theory of induction. Again, there are cases in which we reckon with the most unfailing confidence upon uniformity, and other cases in which we do not count upon it at all. In some we feel complete assurance that the future will resemble the past, the unknown be precisely similar to the known. In others, however invariable may be the result obtained from the instances which have been observed, we draw from them no more than a very feeble presumption that the like result will hold in all other cases. That a straight line is the shortest distance between 2 points, we do not doubt to be true even in the region of the fixed stars. 112 When a chemist announces the existence and properties of a newly discovered substance, if we confide in his accuracy, we feel assured that the conclusions he has arrived at will hold universally, though the induction be founded but on a single instance. We do not withhold our assent, waiting for a repetition of the experiment, or if we do, it is from a doubt whether the one experiment was properly made, not whether if properly made it would be conclusive. Here, then, is a general law of nature, inferred without hesitation from a single instance, a universal proposition from a singular one. Now mark another case, and contrast it with this. Not all the instances which have been observed since the beginning of the world, in support of the general proposition that all crows are black, would be deemed a sufficient presumption of the truth of the proposition. To outweigh the testimony of one unexceptionable witness who should affirm that in some region of the earth not fully explored, he had caught and examined a crow, and had found it to be gray. Why is a single instance, in some cases, sufficient for a complete induction, while in others, myriads of concurring instances, without a single exception known or presumed, go such a very little way toward establishing a universal proposition? Whoever can answer this question knows more of the philosophy of logic than the wisest of the ancients, and has solved the problem of induction. 4. Of Laws of Nature. Section 1. In the contemplation of that uniformity in the course of nature, which is assumed in every inference from experience, one of the first observations that present themselves is, that the uniformity in question is not properly uniformity, but uniformities. The general regularity results from the coexistence of partial regularities. The course of nature in general is constant, because the course of each of the various phenomena that compose it is so. A certain fact invariably occurs whenever certain circumstances are present, and does not occur when they are absent, the like is true of another fact, and so on. From these separate threads of connection between parts of the great whole which we term nature, a general tissue of connection unavoidably weaves itself, by which the whole is held together. If A is always accompanied by D, B by E, and C by F, it follows that AB is accompanied by DE, AC by DF, B, C by E, F, and finally A, B, C by D, E, F. And thus the general character of regularity is produced, which, along with and in the midst of infinite diversity, pervades all nature. The first point, therefore, to be noted in regard to what is called the uniformity of the course of nature, is, that it is itself a complex fact, compounded of all the separate uniformities which exist in respect to single phenomena. These various uniformities, when ascertained by what is regarded as a sufficient induction, we call, in common parlance, laws of nature. Scientifically speaking, that title is employed in a more restricted sense, to designate the uniformities when reduced to their most simple expression. Thus in the illustration already employed, there were 7 uniformities. All of which, if considered sufficiently certain, would, in the more lax application of the term, be called laws of nature. But of the 7, 3 alone are properly distinct and independent, these being presupposed, the others follow of course. The first 3, therefore, according to the stricter acceptation, are called laws of nature, the remainder not, because they are in truth mere cases of the first 3, virtually included in them. Said, therefore, to result from them, whoever affirms those 3 has already affirmed all the rest. To substitute real examples for symbolical ones, the following are 3 uniformities, or call them laws of nature: the law that air has weight, the law that pressure on a fluid is propagated equally in all directions, and the law that pressure in one direction, not opposed by equal pressure in the contrary direction, produces motion, which does not cease until equilibrium is restored. From these 3 uniformities we should be able to predict another uniformity, namely, the rise of the mercury in the Torricellian tube. This, in the stricter use of the phrase, is not a law of nature. It is the result of laws of nature. It is a case of each and every one of the 3 laws, and is the only occurrence by which they could all be fulfilled. If the mercury were not sustained in the barometer, and sustained at such a height that the column of mercury were equal in weight to a column of the atmosphere of the same diameter, here would be a case, either of the air not pressing upon the surface of the mercury with the force which is called its weight, or of the downward pressure on the mercury not being propagated equally in an upward direction, or of a body pressed in one direction and not in the direction opposite, either not moving in the direction in which it is pressed, or stopping before it had attained equilibrium. If we knew, therefore, the 3 simple laws, but had never tried the Torricellian experiment, we might deduce its result from those laws. The known weight of the air, combined with the position of the apparatus, would bring the mercury within the first of the 3 inductions. The first induction would bring it within the second, and the second within the third, in the manner which we characterized in treating of ratiocination. We should thus come to know the more complex uniformity, independently of specific experience, through our knowledge of the simpler ones from which it results. Though, for reasons which will appear hereafter, verification by specific experience would still be desirable, and might possibly be indispensable. Complex uniformities which, like this, are mere cases of simpler ones, and have, therefore, been virtually affirmed in affirming those, may with propriety be called laws, but can scarcely, in the strictness of scientific speech, be termed laws of nature. It is the custom in science, wherever regularity of any kind can be traced, to call the general proposition which expresses the nature of that regularity, a law. As when, in mathematics, we speak of the law of decrease of the successive terms of a converging series. But the expression law of nature has generally been employed with a sort of tacit reference to the original sense of the word law, namely, the expression of the will of a superior. When, therefore, it appeared that any of the uniformities which were observed in nature, would result spontaneously from certain other uniformities, no separate act of creative will being supposed necessary for the production of the derivative uniformities, these have not usually been spoken of as laws of nature. According to one mode of expression, the question, what are the laws of nature, may be stated thus: what are the fewest and simplest assumptions, which being granted, the whole existing order of nature would result? Another mode of stating it would be thus: what are the fewest general propositions from which all the uniformities which exist in the universe might be deductively inferred? Every great advance which marks an epoch in the progress of science, has consisted in a step made toward the solution of this problem. Even a simple colligation of inductions already made, without any fresh extension of the inductive inference, is already an advance in that direction. When Kepler expressed the regularity which exists in the observed motions of the heavenly bodies, by the three general propositions called his laws, he, in so doing, pointed out three simple suppositions which, instead of a much greater number, would suffice to construct the whole scheme of the heavenly motions, so far as it was known up to that time. A similar and still greater step was made when these laws, which at first did not seem to be included in any more general truths, were discovered to be cases of the three laws of motion. As obtaining among bodies which mutually tend toward one another with a certain force, and have had a certain instantaneous impulse originally impressed upon them. After this great discovery, Kepler's three propositions, though still called laws, would hardly, by any person accustomed to use language with precision, be termed laws of nature. That phrase would be reserved for the simpler and more general laws into which Newton is said to have resolved them. According to this language, every well-grounded inductive generalization is either a law of nature, or a result of laws of nature, capable, if those laws are known, of being predicted from them. And the problem of inductive logic may be summed up in two questions: how to ascertain the laws of nature, and how, after having ascertained them, to follow them into their results. On the other hand, we must not suffer ourselves to imagine that this mode of statement amounts to a real analysis, or to anything but a mere verbal transformation of the problem. For the expression, laws of nature, means nothing but the uniformities which exist among natural phenomena, or, in other words, the results of induction, when reduced to their simplest expression. It is, however, something to have advanced so far, as to see that the study of nature is the study of laws, not a law. Of uniformities, in the plural number, that the different natural phenomena have their separate rules or modes of taking place, which, though much intermixed and entangled with one another, may, to a certain extent, be studied apart, that, to resume our former metaphor, the regularity which exists in nature is a web composed of distinct threads, and only to be understood by tracing each of the threads separately. For which purpose it is often necessary to unravel some portion of the web, and exhibit the fibers apart. The rules of experimental inquiry are the contrivances for unraveling the web. Section 2. In thus attempting to ascertain the general order of nature by ascertaining the particular order of the occurrence of each one of the phenomena of nature, the most scientific proceeding can be no more than an improved form of that which was primitively pursued by the human understanding, while undirected by science. When mankind first formed the idea of studying phenomena according to a stricter and surer method than that which they had in the first instance spontaneously adopted, they did not, conformably to the well-meant but impracticable precept of Descartes, set out from the supposition that nothing had been already ascertained. Many of the uniformities existing among phenomena are so constant, and so open to observation, as to force themselves upon involuntary recognition. Some facts are so perpetually and familiarly accompanied by certain others, that mankind learned, as children learn, to expect the one where they found the other, long before they knew how to put their expectation into words by asserting, in a proposition, the existence of a connection between those phenomena. No science was needed to teach that food nourishes, that water drowns, or quenches thirst, that the sun gives light and heat, that bodies fall to the ground. The first scientific inquirers assumed these and the like as known truths, and set out from them to discover others which were unknown, nor were they wrong in so doing, subject, however, as they afterward began to see, to an ulterior revision of these spontaneous generalizations themselves, when the progress of knowledge pointed out limits to them, or showed their truth to be contingent on some circumstance not originally attended to. It will appear, I think, from the subsequent part of our inquiry, that there is no logical fallacy in this mode of proceeding. But we may see already that any other mode is rigorously impracticable, since it is impossible to frame any scientific method of induction, or test of the correctness of inductions, unless on the hypothesis that some inductions deserving of reliance have been already made. Let us revert, for instance, to one of our former illustrations, and consider why it is that, with exactly the same amount of evidence, both negative and positive, we did not reject the assertion that there are black swans, while we should refuse credence to any testimony which asserted that there were men wearing their heads underneath their shoulders. The first assertion was more credible than the latter. But why more credible? So long as neither phenomenon had been actually witnessed, what reason was there for finding the one harder to be believed than the other? Apparently because there is less constancy in the colors of animals, than in the general structure of their anatomy. But how do we know this? Doubtless, from experience. It appears, then, that we need experience to inform us, in what degree, and in what cases, or sorts of cases, experience is to be relied on. Experience must be consulted in order to learn from it under what circumstances arguments from it will be valid. We have no ulterior test to which we subject experience in general, but we make experience its own test. Experience testifies, that among the uniformities which it exhibits or seems to exhibit, some are more to be relied on than others. An uniformity, therefore, may be presumed, from any given number of instances, with a greater degree of assurance, in proportion as the case belongs to a class in which the uniformities have hitherto been found more uniform. This mode of correcting one generalization by means of another, a narrower generalization by a wider, which common sense suggests and adopts in practice, is the real type of scientific induction. All that art can do is but to give accuracy and precision to this process, and adapt it to all varieties of cases, without any essential alteration in its principle. There are of course no means of applying such a test as that above described, unless we already possess a general knowledge of the prevalent character of the uniformities existing throughout nature. The indispensable foundation, therefore, of a scientific formula of induction, must be a survey of the inductions to which mankind have been conducted in unscientific practice, with the special purpose of ascertaining what kinds of uniformities have been found perfectly invariable, pervading all nature, and what are those which have been found to vary with difference of time, place, or other changeable circumstances. Section 3. The necessity of such a survey is confirmed by the consideration, that the stronger inductions are the touchstone to which we always endeavor to bring the weaker. If we find any means of deducing one of the less strong inductions from stronger ones, it acquires, at once, all the strength of those from which it is deduced, and even adds to that strength. Since the independent experience on which the weaker induction previously rested, becomes additional evidence of the truth of the better established law in which it is now found to be included. We may have inferred, from historical evidence, that the uncontrolled power of a monarch, of an aristocracy, or of the majority, will often be abused, but we are entitled to rely on this generalization with much greater assurance when it is shown to be a corollary from still better established facts. The very low degree of elevation of character ever yet attained by the average of mankind, and the little efficacy, for the most part, of the modes of education hitherto practiced, in maintaining the predominance of reason and conscience over the selfish propensities. It is at the same time obvious that even these more general facts derive an accession of evidence from the testimony which history bears to the effects of despotism. The strong induction becomes still stronger when a weaker one has been bound up with it. On the other hand, if an induction conflicts with stronger inductions, or with conclusions capable of being correctly deduced from them, then, unless on reconsideration it should appear that some of the stronger inductions have been expressed with greater universality than their evidence warrants, the weaker one must give way. The opinion so long prevalent that a comet, or any other unusual appearance in the heavenly regions, was the precursor of calamities to mankind, or to those at least who witnessed it, the belief in the veracity of the oracles of Delphi or Dodona, the reliance on astrology, or on the weather prophecies in almanacs, were doubtless inductions supposed to be grounded on experience. 113 And faith in such delusions seems quite capable of holding out against a great multitude of failures, provided it be nourished by a reasonable number of casual coincidences between the prediction and the event. What has really put an end to these insufficient inductions, is their inconsistency with the stronger inductions subsequently obtained by scientific inquiry, respecting the causes on which terrestrial events really depend. And where those scientific truths have not yet penetrated, the same or similar delusions still prevail. It may be affirmed as a general principle, that all inductions, whether strong or weak, which can be connected by ratiocination, are confirmatory of one another. While any which lead deductively to consequences that are incompatible, become mutually each other's test, showing that one or other must be given up, or at least more guardedly expressed. In the case of inductions which confirm each other, the one which becomes a conclusion from ratiocination rises to at least the level of certainty of the weakest of those from which it is deduced. While in general all are more or less increased in certainty. Thus the Torricellian experiment, though a mere case of 3 more general laws, not only strengthened greatly the evidence on which those laws rested, but converted one of them, the weight of the atmosphere, from a still doubtful generalization into a completely established doctrine. If, then, a survey of the uniformities which have been ascertained to exist in nature, should point out some which, as far as any human purpose requires certainty, may be considered quite certain and quite universal, then by means of these uniformities we may be able to raise multitudes of other inductions to the same point in the scale. For if we can show, with respect to any inductive inference, that either it must be true, or one of these certain and universal inductions must admit of an exception, the former generalization will attain the same certainty, and indefeasibleness within the bounds assigned to it, which are the attributes of the latter. It will be proved to be a law. And if not a result of other and simpler laws, it will be a law of nature. There are such certain and universal inductions, and it is because there are such, that a logic of induction is possible. V. Of the Law of Universal Causation. Section 1. The phenomena of nature exist in 2 distinct relations to one another, that of simultaneity, and that of succession. Every phenomenon is related, in a uniform manner, to some phenomena that coexist with it, and to some that have preceded and will follow it. Of the uniformities which exist among synchronous phenomena, the most important, on every account, are the laws of number, and next to them those of space, or, in other words, of extension and figure. The laws of number are common to synchronous and successive phenomena. That 2 and 2 make 4, is equally true whether the second 2 follow the first 2 or accompany them. It is as true of days and years as of feet and inches. The laws of extension and figure, in other words, the theorems of geometry, from its lowest to its highest branches, are, on the contrary, laws of simultaneous phenomena only. The various parts of space, and of the objects which are said to fill space, coexist, and the unvarying laws which are the subject of the science of geometry, are an expression of the mode of their coexistence. This is a class of laws, or in other words, of uniformities, for the comprehension and proof of which it is not necessary to suppose any lapse of time, any variety of facts or events succeeding one another. The propositions of geometry are independent of the succession of events. All things which possess extension, or, in other words, which fill space, are subject to geometrical laws. Possessing extension, they possess figure. Possessing figure, they must possess some figure in particular, and have all the properties which geometry assigns to that figure. If one body be a sphere and another a cylinder, of equal height and diameter, the one will be exactly 2/3 of the other, let the nature and quality of the material be what it will. Again, each body, and each point of a body, must occupy some place or position among other bodies. And the position of 2 bodies relatively to each other, of whatever nature the bodies be, may be unerringly inferred from the position of each of them relatively to any third body. In the laws of number, then, and in those of space, we recognize in the most unqualified manner, the rigorous universality of which we are in quest. Those laws have been in all ages the type of certainty, the standard of comparison for all inferior degrees of evidence. Their invariability is so perfect, that it renders us unable even to conceive any exception to them. And philosophers have been led, though, as I have endeavored to show, erroneously, to consider their evidence as lying not in experience, but in the original constitution of the intellect. If, therefore, from the laws of space and number, we were able to deduce uniformities of any other description, this would be conclusive evidence to us that those other uniformities possessed the same rigorous certainty. But this we cannot do. From laws of space and number alone, nothing can be deduced but laws of space and number. Of all truths relating to phenomena, the most valuable to us are those which relate to the order of their succession. On a knowledge of these is founded every reasonable anticipation of future facts, and whatever power we possess of influencing those facts to our advantage. Even the laws of geometry are chiefly of practical importance to us as being a portion of the premises from which the order of the succession of phenomena may be inferred. Inasmuch as the motion of bodies, the action of forces, and the propagation of influences of all sorts, take place in certain lines and over definite spaces. The properties of those lines and spaces are an important part of the laws to which those phenomena are themselves subject. Again, motions, forces, or other influences, and times, are numerable quantities, and the properties of number are applicable to them as to all other things. But though the laws of number and space are important elements in the ascertainment of uniformities of succession, they can do nothing toward it when taken by themselves. They can only be made instrumental to that purpose when we combine with them additional premises, expressive of uniformities of succession already known. By taking, for instance, as premises these propositions, that bodies acted upon by an instantaneous force move with uniform velocity in straight lines, that bodies acted upon by a continuous force move with accelerated velocity in straight lines, and that bodies acted upon by two forces in different directions move in the diagonal of a parallelogram, whose sides represent the direction and quantity of those forces. We may by combining these truths with propositions relating to the properties of straight lines and of parallelograms, as that a triangle is half a parallelogram of the same base and altitude, deduce another important uniformity of succession, viz. that a body moving round a center of force describes areas proportional to the times. But unless there had been laws of succession in our premises, there could have been no truths of succession in our conclusions. A similar remark might be extended to every other class of phenomena really peculiar, and, had it been attended to, would have prevented many chimerical attempts at demonstrations of the indemonstrable, and explanations which do not explain. It is not, therefore, enough for us that the laws of space, which are only laws of simultaneous phenomenon, and the laws of number, which though true of successive phenomena do not relate to their succession, possess the rigorous certainty and universality of which we are in search. We must endeavor to find some law of succession which has those same attributes, and is therefore fit to be made the foundation of processes for discovering, and of a test for verifying, all other uniformities of succession. This fundamental law must resemble the truths of geometry in their most remarkable peculiarity, that of never being, in any instance whatever, defeated or suspended by any change of circumstances. Now among all those uniformities in the succession of phenomena, which common observation is sufficient to bring to light, there are very few which have any, even apparent, pretension to this rigorous indefeasibility, and of those few, one only has been found capable of completely sustaining it. In that one, however, we recognize a law which is universal also in another sense, it is coextensive with the entire field of successive phenomena, all instances whatever of succession being examples of it. This law is the law of causation. The truth that every fact which has a beginning has a cause, is coextensive with human experience. This generalization may appear to some minds not to amount to much, since after all it asserts only this: it is a law, that every event depends on some law, it is a law, that there is a law for everything. We must not, however, conclude that the generality of the principle is merely verbal, it will be found on inspection to be no vague or unmeaning assertion, but a most important and really fundamental truth. Section 2. The notion of cause being the root of the whole theory of induction, it is indispensable that this idea should, at the very outset of our inquiry, be, with the utmost practicable degree of precision, fixed and determined. If, indeed, it were necessary for the purpose of inductive logic that the strife should be quelled, which has so long raged among the different schools of metaphysicians, respecting the origin and analysis of our idea of causation. The promulgation, or at least the general reception, of a true theory of induction, might be considered desperate for a long time to come. But the science of the investigation of truth by means of evidence, is happily independent of many of the controversies which perplex the science of the ultimate constitution of the human mind, and is under no necessity of pushing the analysis of mental phenomenon to that extreme limit which alone ought to satisfy a metaphysician. I premise, then, that when in the course of this inquiry I speak of the cause of any phenomenon, I do not mean a cause which is not itself a phenomenon. I make no research into the ultimate or ontological cause of anything. To adopt a distinction familiar in the writings of the Scotch metaphysicians, and especially of Reid, the causes with which I concern myself are not efficient, but physical causes. They are causes in that sense alone, in which one physical fact is said to be the cause of another. Of the efficient causes of phenomena, or whether any such causes exist at all, I am not called upon to give an opinion. The notion of causation is deemed, by the schools of metaphysics most in vogue at the present moment, to imply a mysterious and most powerful tie, such as cannot, or at least does not, exist between any physical fact and that other physical fact on which it is invariably consequent, and which is popularly termed its cause, and thence is deduced the supposed necessity of ascending higher into the essences and inherent constitution of things, to find the true cause, the cause which is not only followed by, but actually produces, the effect. No such necessity exists for the purposes of the present inquiry, nor will any such doctrine be found in the following pages. The only notion of a cause, which the theory of induction requires, is such a notion as can be gained from experience. The law of causation, the recognition of which is the main pillar of inductive science, is but the familiar truth. That invariability of succession is found by observation to obtain between every fact in nature and some other fact which has preceded it, independently of all considerations respecting the ultimate mode of production of phenomena, and of every other question regarding the nature of things in themselves. Between the phenomena, then, which exist at any instant, and the phenomena which exist at the succeeding instant, there is an invariable order of succession. And, as we said in speaking of the general uniformity of the course of nature, this web is composed of separate fibers, this collective order is made up of particular sequences, obtaining invariably among the separate parts. To certain facts always do, and, as we believe, will continue to, succeed. The invariable antecedent is termed the cause, the invariable consequent, the effect. And the universality of the law of causation consists in this, that every consequent is connected in this manner with some particular antecedent, or set of antecedents. Let the fact be what it may, if it has begun to exist, it was preceded by some fact or facts, with which it is invariably connected. For every event there exists some combination of objects or events, some given concurrence of circumstances, positive and negative, the occurrence of which is always followed by that phenomenon. We may not have found out what this concurrence of circumstances may be, but we never doubt that there is such a one, and that it never occurs without having the phenomenon in question as its effect or consequence. On the universality of this truth depends the possibility of reducing the inductive process to rules. The undoubted assurance we have that there is a law to be found if we only knew how to find it, will be seen presently to be the source from which the canons of the inductive logic derive their validity. Section 3. It is seldom, if ever, between a consequent and a single antecedent, that this invariable sequence subsists. It is usually between a consequent and the sum of several antecedents. The concurrence of all of them being requisite to produce, that is, to be certain of being followed by, the consequent. In such cases it is very common to single out one only of the antecedents under the denomination of cause, calling the others merely conditions. Thus, if a person eats of a particular dish, and dies in consequence, that is, would not have died if he had not eaten of it, people would be apt to say that eating of that dish was the cause of his death. There needs not, however, be any invariable connection between eating of the dish and death. But there certainly is, among the circumstances which took place, some combination or other on which death is invariably consequent, as, for instance, the act of eating of the dish, combined with a particular bodily constitution. a particular state of present health, and perhaps even a certain state of the atmosphere. The whole of which circumstances perhaps constituted in this particular case the conditions of the phenomenon, or, in other words, the set of antecedents which determined it, and but for which it would not have happened. The real cause is the whole of these antecedents, and we have, philosophically speaking, no right to give the name of cause to one of them, exclusively of the others. What, in the case we have supposed, disguises the incorrectness of the expression, is this, that the various conditions, except the single one of eating the food, were not events, that is, instantaneous changes, or successions of instantaneous changes, but states, possessing more or less of permanency, and might therefore have preceded the effect by an indefinite length of duration, for want of the event which was requisite to complete the required concurrence of conditions, while as soon as that event, eating the food, occurs, no other cause is waited for, but the effect begins immediately to take place, and hence the appearance is presented of a more immediate and close connection between the effect and that one antecedent, than between the effect and the remaining conditions. But though we may think proper to give the name of cause to that one condition, the fulfillment of which completes the tale, and brings about the effect without further delay, this condition has really no closer relation to the effect than any of the other conditions has. All the conditions were equally indispensable to the production of the consequent. And the statement of the cause is incomplete, unless in some shape or other we introduce them all. A man takes mercury, goes out of doors, and catches cold. We say, perhaps, that the cause of his taking cold was exposure to the air. It is clear, however, that his having taken mercury may have been a necessary condition of his catching cold. And though it might consist with usage to say that the cause of his attack was exposure to the air, to be accurate we ought to say that the cause was exposure to the air while under the effect of mercury. If we do not, when aiming at accuracy, enumerate all the conditions, it is only because some of them will in most cases be understood without being expressed, or because for the purpose in view they may without detriment be overlooked. For example, when we say, the cause of a man's death was that his foot slipped in climbing a ladder, we omit as a thing unnecessary to be stated the circumstance of his weight, though quite as indispensable a condition of the effect which took place. When we say that the assent of the Crown to a bill makes it law, we mean that the assent, being never given until all the other conditions are fulfilled, makes up the sum of the conditions, though no one now regards it as the principal one. When the decision of a legislative assembly has been determined by the casting vote of the chairman, we sometimes say that this one person was the cause of all the effects which resulted from the enactment. Yet we do not really suppose that his single vote contributed more to the result than that of any other person who voted in the affirmative. But, for the purpose we have in view, which is to insist on his individual responsibility, the part which any other person had in the transaction is not material. In all these instances the fact which was dignified with the name of cause, was the one condition which came last into existence. But it must not be supposed that in the employment of the term this or any other rule is always adhered to. Nothing can better show the absence of any scientific ground for the distinction between the cause of a phenomenon and its conditions, than the capricious manner in which we select from among the conditions that which we choose to denominate the cause. However numerous the conditions may be, there is hardly any of them which may not, according to the purpose of our immediate discourse, obtain that nominal preeminence. This will be seen by analyzing the conditions of some one familiar phenomenon. For example, a stone thrown into water falls to the bottom. What are the conditions of this event? In the first place there must be a stone, and water, and the stone must be thrown into the water. But these suppositions forming part of the enunciation of the phenomenon itself, to include them also among the conditions would be a vicious tautology. And this class of conditions, therefore, have never received the name of cause from any but the Aristotelians, by whom they were called the material cause, causa materialis. The next condition is, there must be an earth, and accordingly it is often said, that the fall of a stone is caused by the earth, or by a power or property of the earth, or a force exerted by the earth, all of which are merely roundabout ways of saying that it is caused by the earth, or, lastly, the earth's attraction. which also is only a technical mode of saying that the earth causes the motion, with the additional particularity that the motion is toward the earth, which is not a character of the cause, but of the effect. Let us now pass to another condition. It is not enough that the earth should exist, the body must be within that distance from it, in which the earth's attraction preponderates over that of any other body. Accordingly we may say, and the expression would be confessedly correct, that the cause of the stone's falling is its being within the sphere of the earth's attraction. We proceed to a further condition. The stone is immersed in water, it is therefore a condition of its reaching the ground, that its specific gravity exceed that of the surrounding fluid, or in other words that it surpass in weight an equal volume of water. Accordingly anyone would be acknowledged to speak correctly who said, that the cause of the stone's going to the bottom is its exceeding in specific gravity the fluid in which it is immersed. Thus we see that each and every condition of the phenomenon may be taken in its turn, and, with equal propriety in common parlance, but with equal impropriety in scientific discourse, may be spoken of as if it were the entire cause. And in practice, that particular condition is usually styled the cause, whose share in the matter is superficially the most conspicuous, or whose requisiteness to the production of the effect we happen to be insisting on at the moment. So great is the force of this last consideration, that it sometimes induces us to give the name of cause even to one of the negative conditions. We say, for example, the army was surprised because the sentinel was off his post. But since the sentinel's absence was not what created the enemy, or put the soldiers asleep, how did it cause them to be surprised? All that is really meant is, that the event would not have happened if he had been at his duty. His being off his post was no producing cause, but the mere absence of a preventing cause, it was simply equivalent to his non-existence. From nothing, from a mere negation, no consequences can proceed. All effects are connected, by the law of causation, with some set of positive conditions. Negative ones, it is true, being almost always required in addition. In other words, every fact or phenomenon which has a beginning, invariably arises when some certain combination of positive facts exists, provided certain other positive facts do not exist. There is, no doubt, a tendency, which our first example, that of death from taking a particular food, sufficiently illustrates, to associate the idea of causation with the proximate antecedent event, rather than with any of the antecedent states. Or permanent facts, which may happen also to be conditions of the phenomenon. The reason being that the event not only exists, but begins to exist immediately previous, while the other conditions may have pre-existed for an indefinite time. And this tendency shows itself very visibly in the different logical fictions which are resorted to, even by men of science. To avoid the necessity of giving the name of cause to anything which had existed for an indeterminate length of time before the effect. Thus, rather than say that the earth causes the fall of bodies, they ascribe it to a force exerted by the earth, or an attraction by the earth, abstractions which they can represent to themselves as exhausted by each effort. And therefore constituting at each successive instant a fresh fact, simultaneous with, or only immediately preceding, the effect. Inasmuch as the coming of the circumstance which completes the assemblage of conditions, is a change or event. It thence happens that an event is always the antecedent in closest apparent proximity to the consequent, and this may account for the illusion which disposes us to look upon the proximate event as standing more peculiarly in the position of a cause than any of the antecedent states. But even this peculiarity, of being in closer proximity to the effect than any other of its conditions, is, as we have already seen, far from being necessary to the common notion of a cause. With which notion, on the contrary, any one of the conditions, either positive or negative, is found, on occasion, completely to accord. 114. The cause, then, philosophically speaking, is the sum total of the conditions, positive and negative taken together, the whole of the contingencies of every description, which being realized, the consequent invariably follows. The negative conditions, however, of any phenomenon, a special enumeration of which would generally be very prolix, may be all summed up under one head, namely, the absence of preventing or counteracting causes. The convenience of this mode of expression is mainly grounded on the fact, that the effects of any cause in counteracting another cause may in most cases be, with strict scientific exactness, regarded as a mere extension of its own proper and separate effects. If gravity retards the upward motion of a projectile, and deflects it into a parabolic trajectory, it produces, in so doing, the very same kind of effect, and even, as mathematicians know, the same quantity of effect, as it does in its ordinary operation of causing the fall of bodies when simply deprived of their support. If an alkaline solution mixed with an acid destroys its sourness, and prevents it from reddening vegetable blues, it is because the specific effect of the alkali is to combine with the acid, and form a compound with totally different qualities. This property, which causes of all descriptions possess, of preventing the effects of other causes by virtue, for the most part, of the same laws according to which they produce their own, 115 enables us, by establishing the general axiom that all causes are liable to be counteracted in their effects by one another, to dispense with the consideration of negative conditions entirely, and limit the notion of cause to the assemblage of the positive conditions of the phenomenon, one negative condition invariably understood, and the same in all instances, namely, the absence of counteracting causes, being sufficient, along with the sum of the positive conditions, to make up the whole set of circumstances on which the phenomenon is dependent. Section 4. Among the positive conditions, as we have seen that there are some to which, in common parlance, the term cause is more readily and frequently awarded, so there are others to which it is, in ordinary circumstances, refused. In most cases of causation a distinction is commonly drawn between something which acts, and some other thing which is acted upon, between an agent and a patient. Both of these, it would be universally allowed, are conditions of the phenomenon. But it would be thought absurd to call the latter the cause, that title being reserved for the former. The distinction, however, vanishes on examination, or rather is found to be only verbal, arising from an incident of mere expression, namely, that the object said to be acted upon, and which is considered as the scene in which the effect takes place, is commonly included in the phrase by which the effect is spoken of. So that if it were also reckoned as part of the cause, the seeming incongruity would arise of its being supposed to cause itself. In the instance which we have already had, of falling bodies, the question was thus put: what is the cause which makes a stone fall? And if the answer had been, the stone itself, the expression would have been in apparent contradiction to the meaning of the word cause. The stone, therefore, is conceived as the patient, and the earth, or, according to the common and most unphilosophical practice, an occult quality of the earth, is represented as the agent or cause. But that there is nothing fundamental in the distinction may be seen from this, that it is quite possible to conceive the stone as causing its own fall, provided the language employed be such as to save the mere verbal incongruity. We might say that the stone moves toward the earth by the properties of the matter composing it, and according to this mode of presenting the phenomenon, the stone itself might without impropriety be called the agent. Though, to save the established doctrine of the inactivity of matter, men usually prefer here also to ascribe the effect to an occult quality, and say that the cause is not the stone itself, but the weight or gravitation of the stone. Those who have contended for a radical distinction between agent and patient, have generally conceived the agent as that which causes some state of, or some change in the state of, another object which is called the patient. But a little reflection will show that the license we assume of speaking of phenomena as states of the various objects which take part in them, an artifice of which so much use has been made by some philosophers, Brown in particular. For the apparent explanation of phenomena, is simply a sort of logical fiction, useful sometimes as one among several modes of expression, but which should never be supposed to be the enunciation of a scientific truth. Even those attributes of an object which might seem with greatest propriety to be called states of the object itself, its sensible qualities, its color, hardness, shape, and the like, are in reality, as no one has pointed out more clearly than Brown himself, phenomena of causation, in which the substance is distinctly the agent, or producing cause, the patient being our own organs, and those of other sentient beings. What we call states of objects, are always sequences into which the objects enter, generally as antecedents or causes, and things are never more active than in the production of those phenomena in which they are said to be acted upon. Thus, in the example of a stone falling to the earth, according to the theory of gravitation, the stone is as much an agent as the earth, which not only attracts, but is itself attracted by, the stone. In the case of a sensation produced in our organs, the laws of our organization, and even those of our minds, are as directly operative in determining the effect produced, as the laws of the outward object. Though we call prussic acid the agent of a person's death, the whole of the vital and organic properties of the patient are as actively instrumental as the poison, in the chain of effects which so rapidly terminates his sentient existence. In the process of education, we may call the teacher the agent, and the scholar only the material acted upon. Yet in truth all the facts which pre-existed in the scholar's mind exert either cooperating or counteracting agencies in relation to the teacher's efforts. It is not light alone which is the agent in vision, but light coupled with the active properties of the eye and brain, and with those of the visible object. The distinction between agent and patient is merely verbal. Patients are always agents. In a great proportion, indeed, of all natural phenomena, they are so to such a degree as to react forcibly on the causes which acted upon them, and even when this is not the case, they contribute, in the same manner as any of the other conditions, to the production of the effect of which they are vulgarly treated as the mere theatre. All the positive conditions of a phenomenon are alike agents, alike active. And in any expression of the cause which professes to be complete, none of them can with reason be excluded, except such as have already been implied in the words used for describing the effect. Nor by including even these would there be incurred any but a merely verbal impropriety. Section 5. There is a case of causation which calls for separate notice, as it possesses a peculiar feature, and presents a greater degree of complexity than the common case. It often happens that the effect, or one of the effects, of a cause, is, not to produce of itself a certain phenomenon, but to fit something else for producing it. In other words, there is a case of causation in which the effect is to invest an object with a certain property. When sulfur, charcoal, and niter are put together in certain proportions and in a certain manner, the effect is, not an explosion, but that the mixture acquires a property by which, in given circumstances, it will explode. The various causes, natural and artificial, which educate the human body or the human mind, have for their principal effect, not to make the body or mind immediately do anything, but to endow it with certain properties, in other words, to give assurance that in given circumstances certain results will take place in it, or as consequences of it. Physiological agencies often have for the chief part of their operation to predispose the constitution to some mode of action. To take a simpler instance than all these, putting a coat of white paint upon a wall does not merely produce in those who see it done, the sensation of white, it confers on the wall the permanent property of giving that kind of sensation. Regarded in reference to the sensation, the putting on of the paint is a condition of a condition, it is a condition of the wall's causing that particular fact. The wall may have been painted years ago, but it has acquired a property which has lasted till now, and will last longer. The antecedent condition necessary to enable the wall to become in its turn a condition, has been fulfilled once for all. In a case like this, where the immediate consequent in the sequence is a property produced in an object, no one now supposes the property to be a substantive entity, inherent, in the object. What has been produced is what, in other language, may be called a state of preparation in an object for producing an effect. The ingredients of the gunpowder have been brought into a state of preparation for exploding as soon as the other conditions of an explosion shall have occurred. In the case of the gunpowder, this state of preparation consists in a certain collocation of its particles relatively to one another. In the example of the wall, it consists in a new collocation of two things relatively to each other, the wall and the paint. In the example of the molding influences on the human mind, its being a collocation at all is only conjectural. For, even on the materialistic hypothesis, it would remain to be proved that the increased facility with which the brain sums up a column of figures when it has been long trained to calculation, is the result of a permanent new arrangement of some of its material particles. We must, therefore, content ourselves with what we know, and must include among the effects of causes, the capacities given to objects of being causes of other effects. This capacity is not a real thing existing in the objects. It is but a name for our conviction that they will act in a particular manner when certain new circumstances arise. We may invest this assurance of future events with a fictitious objective existence, by calling it a state of the object. But unless the state consists, as in the case of the gunpowder it does, in a collocation of particles, it expresses no present fact, it is but the contingent future fact brought back under another name. It may be thought that this form of causation requires us to admit an exception to the doctrine that the conditions of a phenomenon, the antecedents required for calling it into existence, must all be found among the facts immediately, not remotely preceding its commencement. But what we have arrived at is not a correction, it is only an explanation, of that doctrine. In the enumeration of the conditions required for the occurrence of any phenomenon, it always has to be included that objects must be present, possessed of given properties. It is a condition of the phenomenon explosion that an object should be present, of one or other of certain kinds, which for that reason are called explosive. The presence of one of these objects is a condition immediately precedent to the explosion. The condition which is not immediately precedent is the cause which produced, not the explosion, but the explosive property. The conditions of the explosion itself were all present immediately before it took place, and the general law, therefore, remains intact. Section 6. It now remains to advert to a distinction which is of first-rate importance both for clearing up the notion of cause, and for obviating a very specious objection often made against the view which we have taken of the subject. When we define the cause of anything, in the only sense in which the present inquiry has any concern with causes, to be the antecedent which it invariably follows. We do not use this phrase as exactly synonymous with the antecedent which it invariably has followed in our past experience. Such a mode of conceiving causation would be liable to the objection very plausibly urged by Dr. Reid, namely, that according to this doctrine night must be the cause of day, and day the cause of night. Since these phenomena have invariably succeeded one another from the beginning of the world. But it is necessary to our using the word cause, that we should believe not only that the antecedent always has been followed by the consequent, but that, as long as the present constitution of things 1:16 endures, it always will be so. And this would not be true of day and night. We do not believe that night will be followed by day under all imaginable circumstances, but only that it will be so provided the sun rises above the horizon. If the sun ceased to rise, which, for aught we know, may be perfectly compatible with the general laws of matter, night would be, or might be, eternal. On the other hand, if the sun is above the horizon, his light not extinct, and no opaque body between us and him, we believe firmly that unless a change takes place in the properties of matter, this combination of antecedents will be followed by the consequent, day. That if the combination of antecedents could be indefinitely prolonged, it would be always day, and that if the same combination had always existed, it would always have been day, quite independently of night as a previous condition. Therefore is it that we do not call night the cause, nor even a condition, of day. The existence of the sun, or some such luminous body, and there being no opaque medium in a straight line 117 between that body and the part of the earth where we are situated, are the sole conditions. And the union of these, without the addition of any superfluous circumstance, constitutes the cause. This is what writers mean when they say that the notion of cause involves the idea of necessity. If there be any meaning which confessedly belongs to the term necessity, it is unconditionalness. That which is necessary, that which must be, means that which will be, whatever supposition we may make in regard to all other things. The succession of day and night evidently is not necessary in this sense. It is conditional on the occurrence of other antecedents. That which will be followed by a given consequent when, and only when, some third circumstance also exists, is not the cause, even though no case should ever have occurred in which the phenomenon took place without it. Invariable sequence, therefore, is not synonymous with causation, unless the sequence, besides being invariable, is unconditional. There are sequences, as uniform in past experience as any others whatever, which yet we do not regard as cases of causation, but as conjunctions in some sort accidental. Such, to an accurate thinker, is that of day and night. The one might have existed for any length of time, and the other not have followed the sooner for its existence. It follows only if certain other antecedents exist, and where those antecedents existed, it would follow in any case. No one, probably, ever called night the cause of day. Mankind must so soon have arrived at the very obvious generalization, that the state of general illumination which we call day would follow from the presence of a sufficiently luminous body, whether darkness had preceded or not. We may define, therefore, the cause of a phenomenon, to be the antecedent, or the concurrence of antecedents, on which it is invariably and unconditionally consequent. Or if we adopt the convenient modification of the meaning of the word cause, which confines it to the assemblage of positive conditions without the negative, then instead of unconditionally, we must say subject to no other than negative conditions. To some it may appear, that the sequence between night and day being invariable in our experience, we have as much ground in this case as experience can give in any case, for recognizing the two phenomena as cause and effect. And that to say that more is necessary, to require a belief that the succession is unconditional, or, in other words, that it would be invariable under all changes of circumstances, is to acknowledge in causation an element of belief not derived from experience. The answer to this is, that it is experience itself which teaches us that one uniformity of sequence is conditional and another unconditional. When we judge that the succession of night and day is a derivative sequence, depending on something else, we proceed on grounds of experience. It is the evidence of experience which convinces us that day could equally exist without being followed by night, and that night could equally exist without being followed by day. To say that these beliefs are not generated by our mere observation of sequence, 118 is to forget that twice in every 24 hours, when the sky is clear, we have an experimentum crucis that the cause of day is the sun. We have an experimental knowledge of the sun which justifies us on experimental grounds in concluding, that if the sun were always above the horizon there would be day, though there had been no night. And that if the sun were always below the horizon there would be night, though there had been no day. We thus know from experience that the succession of night and day is not unconditional. Let me add, that the antecedent which is only conditionally invariable, is not the invariable antecedent. Though a fact may, in experience, have always been followed by another fact, yet if the remainder of our experience teaches us that it might not always be so followed, or if the experience itself is such as leaves room for a possibility that the known cases may not correctly represent all possible cases, the hitherto invariable antecedent is not accounted the cause. But why? Because we are not sure that it is the invariable antecedent. Such cases of sequence as that of day and night not only do not contradict the doctrine which resolves causation into invariable sequence, but are necessarily implied in that doctrine. It is evident, that from a limited number of unconditional sequences, there will result a much greater number of conditional ones. Certain causes being given, that is, certain antecedents which are unconditionally followed by certain consequents. The mere coexistence of these causes will give rise to an unlimited number of additional uniformities. If two causes exist together, the effects of both will exist together. And if many causes coexist, these causes, by what we shall term hereafter the intermixture of their laws, will give rise to new effects, accompanying or succeeding one another in some particular order. Which order will be invariable while the causes continue to coexist, but no longer. The motion of the Earth in a given orbit round the Sun, is a series of changes which follow one another as antecedents and consequents, and will continue to do so while the Sun's attraction and the force with which the Earth tends to advance in a direct line through space, continue to coexist in the same quantities as at present. But vary either of these causes, and this particular succession of motions would cease to take place. The series of the Earth's motions, therefore, though a case of sequence invariable within the limits of human experience, is not a case of causation. It is not unconditional. This distinction between the relations of succession which, so far as we know, are unconditional, and those relations, whether of succession or of coexistence, which, like the earth's motions, or the succession of day and night, depend on the existence or on the coexistence of other antecedent facts, corresponds to the great division which Dr. Whewell and other writers have made of the field of science, into the investigation of what they term the laws of phenomena, and the investigation of causes. A phraseology, as I conceive, not philosophically sustainable, inasmuch as the ascertainment of causes, such causes as the human faculties can ascertain, namely, causes which are themselves phenomena, is, therefore, merely the ascertainment of other and more universal laws of phenomena. And let me here observe, that Dr. Whewell, and in some degree even Sir John Herschel, seem to have misunderstood the meaning of those writers who, like M. Kant, limit the sphere of scientific investigation to laws of phenomena, and speak of the inquiry into causes as vain and futile. The causes which M. Kant designates as inaccessible, are efficient causes. The investigation of physical, as opposed to efficient, causes, including the study of all the active forces in nature, considered as facts of observation, is as important a part of M. Kant's conception of science as of Dr. Whewell's. His objection to the word cause is a mere matter of nomenclature, in which, as a matter of nomenclature, I consider him to be entirely wrong. Those, it is justly remarked by Mr. Bailey 119, who, like M. Kant, object to designate events as causes, are objecting without any real ground to a mere but extremely convenient generalization, to a very useful common name, the employment of which involves, or needs involve, no particular theory. To which it may be added, that by rejecting this form of expression, M. Kant leaves himself without any term for marking a distinction which, however incorrectly expressed, is not only real, but is one of the fundamental distinctions in science. Indeed, it is on this alone, as we shall hereafter find, that the possibility rests of framing a rigorous canon of induction. And as things left without a name are apt to be forgotten, a canon of that description is not one of the many benefits which the philosophy of induction has received from M. Kant's great powers. Section 7. Does a cause always stand with its effect in the relation of antecedent and consequent? Do we not often say of two simultaneous facts that they are cause and effect, as when we say that fire is the cause of warmth, the sun and moisture the cause of vegetation, and the like? Since a cause does not necessarily perish because its effect has been produced, the two things do very generally coexist. And there are some appearances, and some common expressions, seeming to imply not only that causes may, but that they must, be contemporaneous with their effects. Cessant causas cessit ite effectus, has been a dogma of the schools, the necessity for the continued existence of the cause in order to the continuance of the effect, seems to have been once a generally received doctrine. Kepler's numerous attempts to account for the motions of the heavenly bodies on mechanical principles were rendered abortive by his always supposing that the agency which set those bodies in motion must continue to operate in order to keep up the motion which it at first produced. Yet there were at all times many familiar instances of the continuance of effects, long after their causes had ceased. A coup de soleil gives a person brain fever. Will the fever go off as soon as he is moved out of the sunshine? A sword is run through his body. Must the sword remain in his body in order that he may continue dead? A plowshare once made, remains a plowshare, without any continuance of heating and hammering, and even after the man who heated and hammered it has been gathered to his fathers. On the other hand, the pressure which forces up the mercury in an exhausted tube must be continued in order to sustain it in the tube. This, it may be replied, is because another force is acting without intermission, the force of gravity, which would restore it to its level, unless counterpoised by a force equally constant. But again, a tight bandage causes pain, which pain will sometimes go off as soon as the bandage is removed. The illumination which the sun diffuses over the earth ceases when the sun goes down. There is, therefore, a distinction to be drawn. The conditions which are necessary for the first production of a phenomenon, are occasionally also necessary for its continuance, though more commonly its continuance requires no condition except negative ones. Most things, once produced, continue as they are, until something changes or destroys them, but some require the permanent presence of the agencies which produced them at first. These may, if we please, be considered as instantaneous phenomena, requiring to be renewed at each instant by the cause by which they were at first generated. Accordingly, the illumination of any given point of space has always been looked upon as an instantaneous fact, which perishes and is perpetually renewed as long as the necessary conditions subsist. If we adopt this language, we avoid the necessity of admitting that the continuance of the cause is ever required to maintain the effect. We may say, it is not required to maintain, but to reproduce, the effect, or else to counteract some force tending to destroy it. And this may be a convenient phraseology. But it is only a phraseology. The fact remains, that in some cases, though those are a minority, the continuance of the conditions which produced an effect is necessary to the continuance of the effect. As to the ulterior question, whether it is strictly necessary that the cause, or assemblage of conditions, should precede, by ever so short an instant, the production of the effect, a question raised and argued with much ingenuity by Sir John Herschel in an essay already quoted, 120. The inquiry is of no consequence for our present purpose. There certainly are cases in which the effect follows without any interval perceptible by our faculties, and when there is an interval, we cannot tell by how many intermediate links imperceptible to us that interval may really be filled up. But even granting that an effect may commence simultaneously with its cause, the view I have taken of causation is in no way practically affected. Whether the cause and its effect be necessarily successive or not, the beginning of a phenomenon is what implies a cause, and causation is the law of the succession of phenomena. If these axioms be granted, we can afford, though I see no necessity for doing so, to drop the words antecedent and consequent as applied to cause and effect. I have no objection to define a cause, the assemblage of phenomena, which occurring, some other phenomenon invariably commences, or has its origin. Whether the effect coincides in point of time with, or immediately follows, the hindmost of its conditions, is immaterial. At all events, it does not precede it. And when we are in doubt, between two coexistent phenomena, which is cause and which effect, we rightly deem the question solved if we can ascertain which of them preceded the other. Section 8. It continually happens that several different phenomena, which are not in the slightest degree dependent or conditional on one another, are found all to depend, as the phrase is, on one and the same agent. In other words, one and the same phenomenon is seen to be followed by several sorts of effects quite heterogeneous, but which go on simultaneously one with another. Provided, of course, that all other conditions requisite for each of them also exist. Thus, the sun produces the celestial motions, it produces daylight, and it produces heat. The earth causes the fall of heavy bodies, and it also, in its capacity of a great magnet, causes the phenomena of the magnetic needle. A crystal of galena causes the sensations of hardness, of weight, of cubical form, of gray color, and many others between which we can trace no interdependence. The purpose to which the phraseology of properties and powers is specially adapted, is the expression of this sort of cases. When the same phenomenon is followed, either subject or not to the presence of other conditions, by effects of different and dissimilar orders, it is usual to say that each different sort of effect is produced by a different property of the cause. Thus we distinguish the attractive or gravitative property of the earth, and its magnetic property, the gravitative, luminiferous, and calorific properties of the sun, the color, shape, weight, and hardness of a crystal. These are mere phrases, which explain nothing, and add nothing to our knowledge of the subject. But, considered as abstract names denoting the connection between the different effects produced and the object which produces them, they are a very powerful instrument of abridgment. And of that acceleration of the process of thought which abridgment accomplishes. This class of considerations leads to a conception which we shall find to be of great importance, that of a permanent cause, or original natural agent. There exist in nature a number of permanent causes, which have subsisted ever since the human race has been in existence, and for an indefinite and probably an enormous length of time previous. The sun, the earth, and planets, with their various constituents, air, water, and other distinguishable substances, whether simple or compound, of which nature is made up, are such permanent causes. These have existed, and the effects or consequences which they were fitted to produce have taken place, as often as the other conditions of the production met, from the very beginning of our experience. But we can give no account of the origin of the permanent causes themselves. Why these particular natural agents existed originally and no others, or why they are commingled in such and such proportions, and distributed in such and such a manner throughout space, is a question we cannot answer. More than this, we can discover nothing regular in the distribution itself, we can reduce it to no uniformity, to no law. There are no means by which, from the distribution of these causes or agents in one part of space, we could conjecture whether a similar distribution prevails in another. The coexistence, therefore, of primeval causes ranks, to us, among merely casual concurrences, and all those sequences or coexistences among the effects of several such causes, which, though invariable while those causes coexist, would, if the coexistence terminate along with it, we do not class as cases of causation, or laws of nature, we can only calculate on finding these sequences or coexistences where we know by direct evidence that the natural agents on the properties of which they ultimately depend, are distributed in the requisite manner. These permanent causes are not always objects, they are sometimes events, that is to say, periodical cycles of events, that being the only mode in which events can possess the property of permanence. Not only, for instance, is the earth itself a permanent cause, or primitive natural agent, but the earth's rotation is so too, it is a cause which has produced, from the earliest period, by the aid of other necessary conditions, the succession of day and night, the ebb and flow of the sea, and many other effects, while, as we can assign no cause, except conjecturally, for the rotation itself, it is entitled to be ranked as a primeval cause. It is, however, only the origin of the rotation which is mysterious to us, once begun. Its continuance is accounted for by the first law of motion, that of the permanence of rectilinear motion once impressed, combined with the gravitation of the parts of the earth toward one another. All phenomena without exception which begin to exist, that is, all except the primeval causes, are effects either immediate or remote of those primitive facts or of some combination of them. There is no thing produced, no event happening, in the known universe, which is not connected by a uniformity, or invariable sequence, with some one or more of the phenomena which preceded it. Insomuch that it will happen again as often as those phenomena occur again, and as no other phenomenon having the character of a counteracting cause shall coexist. These antecedent phenomena, again, were connected in a similar manner with some that preceded them, and so on, until we reach, as the ultimate step attainable by us, either the properties of some one primeval cause, or the conjunction of several. The whole of the phenomena of nature were therefore the necessary, or, in other words, the unconditional, consequences of some former collocation of the permanent causes. The state of the whole universe at any instant, we believe to be the consequence of its state at the previous instant. Insomuch that one who knew all the agents which exist at the present moment, their collocation in space, and all their properties, in other words, the laws of their agency, could predict the whole subsequent history of the universe. At least unless some new volition of a power capable of controlling the universe should supervene. 121 And if any particular state of the entire universe could ever recur a second time, all subsequent states would return too, and history would, like a circulating decimal of many figures, periodically repeat itself. Jam redit edi Virgo. Redunt Satinia regna. Alter erit tum typhus, altera quae vehat argo. Delectos heroas, erunt quoque altera bella. Ac iterum ad Trojam magnus mittiter Achilles. And though things do not really revolve in this eternal round, the whole series of events in the history of the universe, past and future, is not the less capable, in its own nature, of being constructed a priori by any one whom we can suppose acquainted with the original distribution of all natural agents, and with the whole of their properties, that is, the laws of succession existing between them and their effects, saving the far more than human powers of combination and calculation which would be required, even in one possessing the data, for the actual performance of the task. Section 9. Since everything which occurs is determined by laws of causation and collocations of the original causes, it follows that the coexistences which are observable among effects cannot be themselves the subject of any similar set of laws. Distinct from laws of causation. Uniformities there are, as well of coexistence as of succession, among effects, but these must in all cases be a mere result either of the identity or of the coexistence of their causes. If the causes did not coexist, neither could the effects. And these causes being also effects of prior causes, and these of others, until we reach the primeval causes. It follows that, except in the case of effects which can be traced immediately or remotely to one and the same cause, the coexistences of phenomena can in no case be universal. Unless the coexistences of the primeval causes to which the effects are ultimately traceable can be reduced to a universal law, but we have seen that they cannot. There are, accordingly, no original and independent, in other words no unconditional, uniformities of coexistence, between effects of different causes. If they coexist, it is only because the causes have casually coexisted. The only independent and unconditional coexistences which are sufficiently invariable to have any claim to the character of laws, are between different and mutually independent effects of the same cause. In other words, between different properties of the same natural agent. This portion of the laws of nature will be treated of in the latter part of the present book, under the name of the specific properties of kinds. Section 10. Since the first publication of the present treatise, the sciences of physical nature have made a great advance in generalization, through the doctrine known as the conservation or persistence of force. This imposing edifice of theory, the building and laying out of which has for some time been the principal occupation of the most systematic minds among physical inquirers, consists of two stages, one, of ascertained fact. The other containing a large element of hypothesis. To begin with the first. It is proved by numerous facts, both natural and of artificial production, that agencies which have been regarded as distinct and independent sources of force, heat, electricity, chemical action, nervous and muscular action, momentum of moving bodies, are interchangeable, indefinite and fixed quantities, with one another. It had long been known that these dissimilar phenomena had the power, under certain conditions, of producing one another. What is new in the theory is a more accurate estimation of what this production consists in. What happens is, that the whole or part of the one kind of phenomena disappears, and is replaced by phenomena of one of the other descriptions. And that there is an equivalence in quantity between the phenomena that have disappeared and those which have been produced, insomuch that if the process be reversed, the very same quantity which had disappeared will reappear, without increase or diminution. Thus the amount of heat which will raise the temperature of a pound of water 1 degree of the thermometer, will, if expended, say in the expansion of steam, lift a weight of 772 pounds 1 foot. Or a weight of 772 pound-feet, and the same exact quantity of heat can, by certain means, be recovered, through the expenditure of exactly that amount of mechanical motion. The establishment of this comprehensive law has led to a change in the language in which the scientific world had been accustomed to speak of what are called the forces of nature. Before this correlation between phenomena most unlike one another had been ascertained, their unlikeness had caused them to be referred to so many distinct forces. Now that they are known to be convertible into one another without loss, they are spoken of as all of them results of one and the same force, manifesting itself in different modes. This force, it is said, can only produce a limited and definite quantity of effect, but always does produce that definite quantity. And produces it, according to circumstances, in one or another of the forms, or divides it among several, but so as, according to a scale of numerical equivalence established by experiment, always to make up the same sum. And no one of the manifestations can be produced, save by the disappearance of the equivalent quantity of another, which in its turn, in appropriate circumstances, will reappear undiminished. This mutual interchangeability of the forces of nature, according to fixed numerical equivalence, is the part of the new doctrine which rests on irrefragable fact. To make the statement true, however, it is necessary to add, that an indefinite and perhaps immense interval of time may elapse between the disappearance of the force in one form and its reappearance in another. A stone thrown up into the air with a given force, and falling back immediately, will, by the time it reaches the earth, recover the exact amount of mechanical momentum which was expended in throwing it up. Deduction being made of a small portion of motion which has been communicated to the air. But if the stone has lodged on a height, it may not fall back for years, or perhaps ages, and until it does, the force expended in raising it is temporarily lost, being represented only by what, in the language of the new theory, is called potential energy. The coal embedded in the earth is considered by the theory as a vast reservoir of force, which has remained dormant for many geological periods, and will so remain until, by being burned, it gives out the stored-up force in the form of heat. Yet it is not supposed that this force is a material thing which can be confined by bounds, as used to be thought of latent heat when that important phenomenon was first discovered. What is meant is that when the coal does at last, by combustion, generate a quantity of heat, transformable like all other heat into mechanical momentum, and the other forms of force. This extrication of heat is the reappearance of a force derived from the sun's rays, expended myriads of ages ago in the vegetation of the organic substances which were the material of the coal. Let us now pass to the higher stage of the theory of conservation of force, the part which is no longer a generalization of proved fact, but a combination of fact and hypothesis. Stated in few words, it is as follows, that the conservation of force is really the conservation of motion, that in the various interchanges between the forms of force, it is always motion that is transformed into motion. To establish this, it is necessary to assume motions which are hypothetical. The supposition is, that there are motions which manifest themselves to our senses only as heat, electricity, etc., being molecular motions. Oscillations, invisible to us, among the minute particles of bodies, and that these molecular motions are transmutable into molar motions, motions of masses, and molar motions into molecular. Now there is a real basis of fact for this supposition. We have positive evidence of the existence of molecular motion in these manifestations of force. In the case of chemical action, for instance, the particles separate and form new combinations, often with a great visible disturbance of the mass. In the case of heat, the evidence is equally conclusive, since heat expands bodies, that is, causes their particles to move from one another. And if of sufficient amount, changes their mode of aggregation from solid to liquid, or from liquid to gaseous. Again, the mechanical actions which produce heat, friction, and the collision of bodies, must from the nature of the case produce a shock, that is, an internal motion of particles, which indeed, we find, is often so violent as to break them permanently asunder. Such facts are thought to warrant the inference, that it is not, as was supposed, heat that causes the motion of particles, but the motion of particles that causes heat. The original cause of both being the previous motion, whether molar or molecular, collision of bodies or combustion of fuel, which formed the heating agency. This inference already contains hypothesis. But at least the supposed cause, the intestine motion of molecules, is a vera causa. But in order to reduce the conservation of force to conservation of motion, it was necessary to attribute to motion the heat propagated, through apparently empty space, from the sun. This required the supposition, already made for the explanation of the laws of light, of a subtle ether pervading space, which, though impalpable to us, must have the property which constitutes matter, that of resistance. Since waves are propagated through it by an impulse from a given point. The ether must be supposed, a supposition not required by the theory of light, to penetrate into the minute interstices of all bodies. The vibratory motion supposed to be taking place in the heated mass of the sun, is considered as imparted from that mass to the particles of the surrounding ether, and through them to the particles of the same ether in the interstices of terrestrial bodies. And this, too, with a sufficient mechanical force to throw the particles of those bodies into a state of similar vibration, producing the expansion of their mass, and the sensation of heat in sentient creatures. All this is hypothesis, though, of its legitimacy as hypothesis, I do not mean to express any doubt. It would seem to follow as a consequence from this theory, that force may and should be defined, matter in motion. This definition, however, will not stand, for, as has already been seen, the matter needs not be in actual motion. It is not necessary to suppose that the motion afterward manifested, is actually taking place among the molecules of the coal during its sojourn in the earth. 122 Certainly not in the stone which is at rest on the eminence to which it has been raised. The true definition of force must be, not motion, but potentiality of motion. And what the doctrine, if established, amounts to, is, not that there is at all times the same quantity of actual motion in the universe, but that the possibilities of motion are limited to a definite quantity, which cannot be added to, but which cannot be exhausted, and that all actual motion which takes place in nature is a draft upon this limited stock. It needs not all of it have ever existed as actual motion. There is a vast amount of potential motion in the universe in the form of gravitation, which it would be a great abuse of hypothesis to suppose to have been stored up by the expenditure of an equal amount of actual motion in some former state of the universe. Nor does the motion produced by gravity take place, so far as we know, at the expense of any other motion, either molar or molecular. It is proper to consider whether the adoption of this theory as a scientific truth, involving as it does a change in the conception hitherto entertained of the most general physical agencies, requires any modification in the view I have taken of causation as a law of nature. As it appears to me, none whatever. The manifestations which the theory regards as modes of motion, are as much distinct and separate phenomena when referred to a single force, as when attributed to several. Whether the phenomenon is called a transformation of force or the generation of one, it has its own set or sets of antecedents, with which it is connected by invariable and unconditional sequence. And that set, or those sets, of antecedents are its cause. The relation of the conservation theory to the principle of causation is discussed in much detail, and very instructively, by Professor Bain, in the second volume of his Logic. The chief practical conclusion drawn by him, bearing on causation, is, that we must distinguish in the assemblage of conditions which constitutes the cause of a phenomenon, two elements: one, the presence of a force; the other, the collocation or position of objects which is required in order that the force may undergo the particular transmutation which constitutes the phenomenon. Now, it might always have been said with acknowledged correctness, that a force and a collocation were both of them necessary to produce any phenomenon. The law of causation is, that change can only be produced by change. Along with any number of stationary antecedents, which are collocations, there must be at least one changing antecedent, which is a force. To produce a bonfire, there must not only be fuel, and air, and a spark, which are collocations, but chemical action between the air and the materials, which is a force. To grind corn, there must be a certain collocation of the parts composing a mill, relatively to one another and to the corn, but there must also be the gravitation of water, or the motion of wind, to supply a force. But as the force in these cases was regarded as a property of the objects in which it is embodied, it seemed tautology to say that there must be the collocation and the force. As the collocation must be a collocation of objects possessing the force-giving property, the collocation, so understood, included the force. How, then, shall we have to express these facts, if the theory be finally substantiated that all force is reducible to a previous motion? We shall have to say, that one of the conditions of every phenomenon is an antecedent motion. But it will have to be explained that this needs not be actual motion. The coal which supplies the force exerted in combustion is not shown to have been exerting that force in the form of molecular motion in the pit. It was not even exerting pressure. The stone on the eminence is exerting a pressure, but only equivalent to its weight, not to the additional momentum it would acquire by falling. The antecedent, therefore, is not a force in action. And we can still only call it a property of the objects, by which they would exert a force on the occurrence of a fresh collocation. The collocation, therefore, still includes the force. The force said to be stored up, is simply a particular property which the object has acquired. The cause we are in search of, is a collocation of objects possessing that particular property. When, indeed, we inquire further into the cause from which they derive that property, the new conception introduced by the conservation theory comes in: the property is itself an effect, and its cause, according to the theory, is a former motion of exactly equivalent amount, which has been impressed on the particles of the body, perhaps at some very distant period. But the case is simply one of those we have already considered, in which the efficacy of a cause consists in its investing an object with a property. The force said to be laid up, and merely potential, is no more a really existing thing than any other properties of objects are really existing things. The expression is a mere artifice of language, convenient for describing the phenomena. It is unnecessary to suppose that anything has been in continuous existence except an abstract potentiality. A force suspended in its operation, neither manifesting itself by motion nor by pressure, is not an existing fact, but a name for our conviction that in appropriate circumstances a fact would take place. We know that a pound weight, were it to fall from the earth into the sun, would acquire in falling a momentum equal to millions of pounds. But we do not credit the pound weight with more of actually existing force than is equal to the pressure it is now exerting on the earth, and that is exactly a pound. We might as well say that a force of millions of pounds exists in a pound, as that the force which will manifest itself when the coal is burned is a real thing existing in the coal. What is fixed in the coal is only a certain property; it has become fit to be the antecedent of an effect called combustion, which partly consists in giving out, under certain conditions, a given definite quantity of heat. We thus see that no new general conception of causation is introduced by the conservation theory. The indestructibility of force no more interferes with the theory of causation than the indestructibility of matter, meaning by matter the element of resistance in the sensible world. It only enables us to understand better than before the nature and laws of some of the sequences. This better understanding, however, enables us, with Mr. Bain, to admit, as one of the tests for distinguishing causation from mere concomitance, the expenditure or transfer of energy. If the effect, or any part of the effect, to be accounted for, consists in putting matter in motion, then any of the objects present which has lost motion has contributed to the effect. And this is the true meaning of the proposition that the cause is that one of the antecedents which exerts active force. Section 11. It is proper in this place to advert to a rather ancient doctrine respecting causation, which has been revived during the last few years in many quarters, and at present gives more signs of life than any other theory of causation at variance with that set forth in the preceding pages. According to the theory in question, mind, or to speak more precisely, will, is the only cause of phenomena. The type of causation, as well as the exclusive source from which we derive the idea, is our own voluntary agency. Here, and here only, it is said, we have direct evidence of causation. We know that we can move our bodies. Respecting the phenomena of inanimate nature, we have no other direct knowledge than that of antecedents and sequence. But in the case of our voluntary actions, it is affirmed that we are conscious of power before we have experience of results. An act of volition, whether followed by an effect or not, is accompanied by a consciousness of effort, of force exerted, of power in action, which is necessarily causal, or causative. This feeling of energy or force, inherent in an act of will, is knowledge a priori, assurance, prior to experience, that we have the power of causing effects. Volition, therefore, it is asserted, is something more than an unconditional antecedent. It is a cause, in a different sense from that in which physical phenomena are said to cause one another; it is an efficient cause. From this the transition is easy to the further doctrine, that volition is the sole efficient cause of all phenomena. It is inconceivable that dead force could continue unsupported for a moment beyond its creation. We cannot even conceive of change or phenomena without the energy of a mind. The word action, itself, says another writer of the same school, has no real significance except when applied to the doings of an intelligent agent. Let any one conceive, if he can, of any power, energy, or force inherent in a lump of matter. Phenomena may have the semblance of being produced by physical causes, but they are in reality produced, say these writers, by the immediate agency of mind. All things which do not proceed from a human, or, I suppose, an animal, will proceed, they say, directly from divine will. The earth is not moved by the combination of a centripetal and a projectile force. This is but a mode of speaking, which serves to facilitate our conceptions. It is moved by the direct volition of an omnipotent being, in a path coinciding with that which we deduce from the hypothesis of these two forces. As I have so often observed, the general question of the existence of efficient causes does not fall within the limits of our subject. But a theory which represents them as capable of being subjects of human knowledge, and which passes off as efficient causes what are only physical or phenomenal causes, belongs as much to logic as to metaphysics, and is a fit subject for discussion here. To my apprehension, a volition is not an efficient, but simply a physical cause. Our will causes our bodily actions in the same sense, and in no other, in which cold causes ice, or a spark causes an explosion of gunpowder. The volition, a state of our mind, is the antecedent, the motion of our limbs in conformity to the volition, is the consequent. This sequence I conceive to be not a subject of direct consciousness, in the sense intended by the theory. The antecedent, indeed, and the consequent, are subjects of consciousness. But the connection between them is a subject of experience. I cannot admit that our consciousness of the volition contains in itself any a priori knowledge that the muscular motion will follow. If our nerves of motion were paralyzed, or our muscles stiff and inflexible, and had been so all our lives, I do not see the slightest ground for supposing that we should ever, unless by information from other people, have known anything of volition as a physical power, or been conscious of any tendency in feelings of our mind to produce motions of our body, or of other bodies. I will not undertake to say whether we should in that case have had the physical feeling which I suppose is meant when these writers speak of consciousness of effort. I see no reason why we should not, since that physical feeling is probably a state of nervous sensation beginning and ending in the brain, without involving the motory apparatus, but we certainly should not have designated it by any term equivalent to effort, since effort implies consciously aiming at an end, which we should not only in that case have had no reason to do, but could not even have had the idea of doing. If conscious at all of this peculiar sensation, we should have been conscious of it, I conceive, only as a kind of uneasiness, accompanying our feelings of desire. It is well argued by Sir William Hamilton against the theory in question, that it is refuted by the consideration that between the overt fact of corporeal movement of which we are cognizant, and the internal act of mental determination of which we are also cognizant, there intervenes a numerous series of intermediate agencies of which we have no knowledge. And, consequently, that we can have no consciousness of any causal connection between the extreme links of this chain, the volition to move and the limb moving, as this hypothesis asserts. No one is immediately conscious, for example, of moving his arm through his volition. Previously to this ultimate movement, muscles, nerves, a multitude of solid and fluid parts, must be set in motion by the will, but of this motion we know, from consciousness, absolutely nothing. A person struck with paralysis is conscious of no inability in his limb to fulfill the determinations of his will. And it is only after having willed, and finding that his limbs do not obey his volition, that he learns by this experience, that the external movement does not follow the internal act. But as the paralytic learns after the volition that his limbs do not obey his mind, so it is only after volition that the man in health learns, that his limbs do obey the mandates of his will. 123. Those against whom I am contending have never produced, and do not pretend to produce, any positive evidence. 124 That the power of our will to move our bodies would be known to us independently of experience. What they have to say on the subject is, that the production of physical events by a will seems to carry its own explanation with it, while the action of matter upon matter seems to require something else to explain it, and is even, according to them, inconceivable, on any other supposition than that some will intervenes between the apparent cause and its apparent effect. They thus rest their case on an appeal to the inherent laws of our conceptive faculty, mistaking, as I apprehend, for the laws of that faculty its acquired habits, grounded on the spontaneous tendencies of its uncultured state. The succession between the will to move a limb and the actual motion is one of the most direct and instantaneous of all sequences which come under our observation, and is familiar to every moment's experience from our earliest infancy. More familiar than any succession of events exterior to our bodies, and especially more so than any other case of the apparent origination, as distinguished from the mere communication, of motion. Now, it is the natural tendency of the mind to be always attempting to facilitate its conception of unfamiliar facts by assimilating them to others which are familiar. Accordingly, our voluntary acts, being the most familiar to us of all cases of causation, are, in the infancy and early youth of the human race, spontaneously taken as the type of causation in general. And all phenomena are supposed to be directly produced by the will of some sentient being. This original fetishism I shall not characterize in the words of Hume, or of any follower of Hume, but in those of a religious metaphysician, Dr. Reid, in order more effectually to show the unanimity which exists on the subject among all competent thinkers. When we turn our attention to external objects, and begin to exercise our rational faculties about them, we find that there are some motions and changes in them which we have power to produce. And that there are many which must have some other cause. Either the objects must have life and active power, as we have, or they must be moved or changed by something that has life and active power, as external objects are moved by us. Our first thought seemed to be, that the objects in which we perceive such motion have understanding and active power as we have. Savages, says the Abbé Raynal, wherever they see motion which they cannot account for, there they suppose a soul. All men may be considered as savages in this respect, until they are capable of instruction, and of using their faculties in a more perfect manner than savages do. The Abbé Raynal's observation is sufficiently confirmed, both from fact, and from the structure of all languages. Rude nations do really believe sun, moon, and stars, earth, sea, and air, fountains, and lakes, to have understanding and active power. To pay homage to them, and implore their favor, is a kind of idolatry natural to savages. All languages carry in their structure the marks of their being formed when this belief prevailed. The distinction of verbs and participles into active and passive, which is found in all languages, must have been originally intended to distinguish what is really active from what is merely passive. And in all languages, we find active verbs applied to those objects, in which, according to the Abbé Raynal's observation, savages suppose a soul. Thus we say the sun rises and sets, and comes to the meridian, the moon changes, the sea ebbs and flows, the winds blow. Languages were formed by men who believed these objects to have life and active power in themselves. It was therefore proper and natural to express their motions and changes by active verbs. There is no surer way of tracing the sentiments of nations before they have records, than by the structure of their language, which, notwithstanding the changes produced in it by time, will always retain some signatures of the thoughts of those by whom it was invented. When we find the same sentiments indicated in the structure of all languages, those sentiments must have been common to the human species when languages were invented. When a few, of superior intellectual abilities, find leisure for speculation, they begin to philosophize, and soon discover, that many of those objects which at first they believe to be intelligent and active are really lifeless and passive. This is a very important discovery. It elevates the mind, emancipates from many vulgar superstitions, and invites to further discoveries of the same kind. As philosophy advances, life and activity in natural objects retires, and leaves them dead and inactive. Instead of moving voluntarily, we find them to be moved necessarily. Instead of acting, we find them to be acted upon. And nature appears as one great machine, where one wheel is turned by another, that by a third, and how far this necessary succession may reach, the philosopher does not know. 125. There is, then, a spontaneous tendency of the intellect to account to itself for all cases of causation by assimilating them to the intentional acts of voluntary agents like itself. This is the instinctive philosophy of the human mind in its earliest stage, before it has become familiar with any other invariable sequences than those between its own volitions or those of other human beings and their voluntary acts. As the notion of fixed laws of succession among external phenomena gradually establishes itself, the propensity to refer all phenomena to voluntary agency slowly gives way before it. The suggestions, however, of daily life continuing to be more powerful than those of scientific thought, the original instinctive philosophy maintains its ground in the mind, underneath the growths obtained by cultivation, and keeps up a constant resistance to their throwing their roots deep into the soil. The theory against which I am contending derives its nourishment from that substratum. Its strength does not lie in argument, but in its affinity to an obstinate tendency of the infancy of the human mind. That this tendency, however, is not the result of an inherent mental law, is proved by superabundant evidence. The history of science, from its earliest dawn, shows that mankind have not been unanimous in thinking either that the action of matter upon matter was not conceivable, or that the action of mind upon matter was. To some thinkers, and some schools of thinkers, both in ancient and in modern times, this last has appeared much more inconceivable than the former. Sequences entirely physical and material, as soon as they had become sufficiently familiar to the human mind, came to be thought perfectly natural, and were regarded not only as needing no explanation themselves, but as being capable of affording it to others, and even of serving as the ultimate explanation of things in general. One of the ablest recent supporters of the volitional theory has furnished an explanation, at once historically true and philosophically acute, of the failure of the Greek philosophers in physical inquiry, in which, as I conceive, he unconsciously depicts his own state of mind. Their stumbling block was one as to the nature of the evidence they had to expect for their conviction. They had not seized the idea that they must not expect to understand the processes of outward causes, but only their results. And consequently, the whole physical philosophy of the Greeks was an attempt to identify mentally the effect with its cause, to feel after some not only necessary but natural connection. Where they meant by natural that which would per se carry some presumption to their own mind. They wanted to see some reason why the physical antecedent should produce this particular consequent, and their only attempts were in directions where they could find such reasons. 126 In other words, they were not content merely to know that one phenomenon was always followed by another. They thought that they had not attained the true aim of science. Unless they could perceive something in the nature of the one phenomenon from which it might have been known or presumed previous to trial that it would be followed by the other, just what the writer, who has so clearly pointed out their error, thinks that he perceives in the nature of the phenomenon volition. And to complete the statement of the case, he should have added that these early speculators not only made this their aim, but were quite satisfied with their success in it. Not only sought for causes which should carry in their mere statement evidence of their efficiency, but fully believed that they had found such causes. The reviewer can see plainly that this was an error, because he does not believe that there exist any relations between material phenomena which can account for their producing one another. But the very fact of the persistency of the Greeks in this error, shows that their minds were in a very different state. They were able to derive from the assimilation of physical facts to other physical facts the kind of mental satisfaction which we connect with the word explanation, and which the reviewer would have us think can only be found in referring phenomena to a will. When Thales and Hippo held that moisture was the universal cause, an external element, of which all other things were but the infinitely various sensible manifestations. When Anaximenes predicated the same thing of air, Pythagoras of numbers, and the like, they all thought that they had found a real explanation, and were content to rest in this explanation as ultimate. The ordinary sequences of the external universe appeared to them, no less than to their critic, to be inconceivable without the supposition of some universal agency to connect the antecedents with the consequents. But they did not think that volition, exerted by minds, was the only agency which fulfilled this requirement. Moisture, or air, or numbers, carried to their minds a precisely similar impression of making intelligible what was otherwise inconceivable, and gave the same full satisfaction to the demands of their conceptive faculty. It was not the Greeks alone, who wanted to see some reason why the physical antecedent should produce this particular consequent, some connection, which would per se carry some presumption to their own mind. Among modern philosophers, Leibniz laid it down as a self-evident principle that all physical causes without exception must contain in their own nature something which makes it intelligible that they should be able to produce the effects which they do produce. Far from admitting volition as the only kind of cause which carried internal evidence of its own power, and as the real bond of connection between physical antecedents and their consequents, he demanded some naturally and per se efficient physical antecedent as the bond of connection between volition itself and its effects. He distinctly refused to admit the will of God as a sufficient explanation of anything except miracles, and insisted upon finding something that would account better for the phenomena of nature than a mere reference to divine volition. 127. Again, and conversely, the action of mind upon matter, which, we are now told, not only needs no explanation itself, but is the explanation of all other effects, has appeared to some thinkers to be itself the grand inconceivability. It was to get over this very difficulty that the Cartesians invented the system of occasional causes. They could not conceive that thoughts in a mind could produce movements in a body, or that bodily movements could produce thoughts. They could see no necessary connection, no relation a priori, between a motion and a thought. And as the Cartesians, more than any other school of philosophical speculation before or since, made their own minds the measure of all things, and refused, on principle, to believe that nature had done what they were unable to see any reason why she must do, they affirmed it to be impossible that a material and a mental fact could be causes one of another. They regarded them as mere occasions on which the real agent, God, thought fit to exert his power as a cause. When a man wills to move his foot, it is not his will that moves it, but God, they said, moves it on the occasion of his will. God, according to this system, is the only efficient cause, not qua mind, or qua endowed with volition, but qua omnipotent. This hypothesis was, as I said, originally suggested by the supposed inconceivability of any real mutual action between mind and matter. But it was afterward extended to the action of matter upon matter, for on a nicer examination they found this inconceivable too, and therefore, according to their logic, impossible. The deus ex machina was ultimately called in to produce a spark on the occasion of a flint and steel coming together, or to break an egg on the occasion of its falling on the ground. All this, undoubtedly, shows that it is the disposition of mankind in general, not to be satisfied with knowing that one fact is invariably antecedent and another consequent, but to look out for something which may seem to explain their being so. But we also see that this demand may be completely satisfied by an agency purely physical, provided it be much more familiar than that which it is invoked to explain. To Thales and Anaximenes, it appeared inconceivable that the antecedents which we see in nature should produce the consequence, but perfectly natural that water, or air, should produce them. The writers whom I oppose declare this inconceivable, but can conceive that mind, or volition, is per se an efficient cause, while the Cartesians could not conceive even that, but peremptorily declared that no mode of production of any fact whatever was conceivable, except the direct agency of an omnipotent being. Thus giving additional proof of what finds new confirmation in every stage of the history of science, that both what persons can, and what they cannot, conceive, is very much an affair of accident, and depends altogether on their experience and their habits of thought. That by cultivating the requisite associations of ideas, people may make themselves unable to conceive any given thing, and may make themselves able to conceive most things, however inconceivable these may at first appear. And the same facts in each person's mental history which determine what is or is not conceivable to him, determine also which among the various sequences in nature will appear to him so natural and plausible, as to need no other proof of their existence. To be evident by their own light, independent equally of experience and of explanation. By what rule is any one to decide between one theory of this description and another? The theorists do not direct us to any external evidence. They appeal each to his own subjective feelings. One says, the succession C-B appears to me more natural, conceivable, and credible per se, than the succession A-B. You are therefore mistaken in thinking that B depends upon A. I am certain, though I can give no other evidence of it, that C comes in between A and B, and is the real and only cause of B. The other answers, the successions C, B and A, B appear to me equally natural and conceivable, or the latter more so than the former. A is quite capable of producing B without any other intervention. A third agrees with the first in being unable to conceive that A can produce B, but finds the sequence D, B still more natural than C, B, or of nearer kin to the subject matter, and prefers his D theory to the C theory. It is plain that there is no universal law operating here, except the law that each person's conceptions are governed and limited by his individual experiences and habits of thought. We are warranted in saying of all three, what each of them already believes of the other two, namely, that they exalt into an original law of the human intellect and of outward nature one particular sequence of phenomena, which appears to them more natural and more conceivable than other sequences, only because it is more familiar. And from this judgment I am unable to accept the theory, that volition is an efficient cause. I am unwilling to leave the subject without adverting to the additional fallacy contained in the corollary from this theory. In the inference that because volition is an efficient cause, therefore it is the only cause, and the direct agent in producing even what is apparently produced by something else. Volitions are not known to produce anything directly except nervous action, for the will influences even the muscles only through the nerves. Though it were granted, then, that every phenomenon has an efficient, and not merely a phenomenal cause, and that volition, in the case of the peculiar phenomena which are known to be produced by it, is that efficient cause. Are we therefore to say, with these writers, that since we know of no other efficient cause, and ought not to assume one without evidence, there is no other, and volition is the direct cause of all phenomena? A more outrageous stretch of inference could hardly be made. Because among the infinite variety of the phenomena of nature there is one, namely, a particular mode of action of certain nerves, which has for its cause, and as we are now supposing for its efficient cause, a state of our mind. And because this is the only efficient cause of which we are conscious, being the only one of which in the nature of the case we can be conscious, since it is the only one which exists within ourselves. Does this justify us in concluding that all other phenomena must have the same kind of efficient cause with that one eminently special, narrow, and peculiarly human or animal, phenomenon? The nearest parallel to this specimen of generalization is suggested by the recently revived controversy on the old subject of plurality of worlds, in which the contending parties have been so conspicuously successful in overthrowing one another. Here also we have experience only of a single case, that of the world in which we live, but that this is inhabited we know absolutely, and without possibility of doubt. Now if on this evidence any one were to infer that every heavenly body without exception, sun, planet, satellite, comet, fixed star or nebula, is inhabited, and must be so from the inherent constitution of things, his inference would exactly resemble that of the writers who conclude that because volition is the efficient cause of our own bodily motions, it must be the efficient cause of everything else in the universe. It is true there are cases in which, with acknowledged propriety, we generalize from a single instance to a multitude of instances. But they must be instances which resemble the one known instance, and not such as have no circumstance in common with it except that of being instances. I have, for example, no direct evidence that any creature is alive except myself, yet I attribute, with full assurance, life and sensation to other human beings and animals. But I do not conclude that all other things are alive merely because I am. I ascribe to certain other creatures a life like my own, because they manifest it by the same sort of indications by which mine is manifested. I find that their phenomena and mine conform to the same laws, and it is for this reason that I believe both to arise from a similar cause. Accordingly I do not extend the conclusion beyond the grounds for it. Earth, fire, mountains, trees, are remarkable agencies, but their phenomena do not conform to the same laws as my actions do, and I therefore do not believe earth or fire, mountains or trees, to possess animal life. But the supporters of the volition theory ask us to infer that volition causes everything, for no reason except that it causes one particular thing. Although that one phenomenon, far from being a type of all natural phenomena, is eminently peculiar, its laws bearing scarcely any resemblance to those of any other phenomenon, whether of inorganic or of organic nature. Note supplementary to the preceding chapter. The author of the second Burnett Prize essay, Dr. Tulloch, who has employed a considerable number of pages in controverting the doctrines of the preceding chapter, has somewhat surprised me by denying a fact, which I imagine too well known to require proof, that there have been philosophers who found in physical explanations of phenomena the same complete mental satisfaction which we are told is only given by volitional explanation, and others who denied the volitional theory on the same ground of inconceivability on which it is defended. The assertion of the essayist is countersigned still more positively by an able reviewer of the essay, 128. Two illustrations, says the reviewer, are advanced by Mr. Mill, the case of Thales and Anaximenes, stated by him to have maintained, the one moisture and the other air to be the origin of all things. And that of Descartes and Leibniz, whom he asserts to have found the action of mind upon matter the grand inconceivability. In counterstatement as to the first of these cases the author shows, what we believe now hardly admits of doubt, that the Greek philosophers distinctly recognized as beyond and above their primal material source, the new omicron, or divine intelligence, as the efficient and originating source of all. And as to the second, by proof that it was the mode, not the fact, of that action on matter, which was represented as inconceivable. A greater quantity of historical error has seldom been comprised in a single sentence. With regard to Thales, the assertion that he considered water as a mere material in the hands of new omicron rests on a passage of Cicero de Natura Deorum. And whoever will refer to any of the accurate historians of philosophy, will find that they treat this as a mere fancy of Cicero, resting on no authority, opposed to all the evidence, and make surmises as to the manner in which Cicero may have been led into the error. See Rutter, Volume 1, page 211, 2d edition, Brandis, Volume 1, pages 118-9, first edition, Preller, Historia Philosophiae Greco-Romani, page 10. Schief Ansicht, Durchus zu Verwerfen, Augenscheinlich Folgernd Stat zu Berichten, Cabus vera sententia Thalitis plain detorquitur, are the expressions of these writers. As for Anaximenes, he even according to Cicero, maintained, not that air was the material out of which God made the world, but that the air was a god, Anaximenes era deum statuit, or, according to St. Augustine, that it was the material out of which the gods were made, non tamen ab ipsis, diis, aerum factum, sed ipsos ex aer ordos creditit. Those who are not familiar with the metaphysical terminology of antiquity, must not be misled by finding it stated that Anaximenes attributed ψ kai, translated soul, or life, to his universal element, the air. The Greek philosophers acknowledged several kinds of ψ kai, the nutritive, the sensitive, and the intellective. 129. Even the moderns, with admitted correctness, attribute life to plants. As far as we can make out the meaning of Anaximenes, he made choice of air as the universal agent, on the ground that it is perpetually in motion, without any apparent cause external to itself, so that he conceived it as exercising spontaneous force, and as the principle of life and activity in all things, men and gods inclusive. If this be not representing it as the efficient cause, the dispute altogether has no meaning. If either Anaximenes, or Thales, or any of their contemporaries, had held the doctrine that nu omicron was the efficient cause, that doctrine could not have been reputed, as it was throughout antiquity, to have originated with Anaxagoras. The testimony of Aristotle, in the first book of his Metaphysics, is perfectly decisive with respect to these early speculations. After enumerating 4 kinds of causes, or rather 4 different meanings of the word cause, viz. the essence of a thing, the matter of it, the origin of motion, efficient cause, and the end or final cause, he proceeds to say, that most of the early philosophers recognized only the second kind of cause, the matter of a thing. Tau nu lambda eta epsilon delta epsilon iota mu nu alpha theta eta sigma alpha nu rho chi epsilon nu alpha iota pi nu tau omega nu. As his first example he specifies Thales, whom he describes as taking the lead in this view of the subject, tau tau omicron iota alpha tau eta rho chi eta gamma phi iota lambda omicron sigma omicron phi alpha, and goes on to Hippon, Anaximenes, Diogenes, of Apollonia, Hippasus of Metapontum, Heraclitus, and Empedocles. Anaxagoras, however, he proceeds to say, taught a different doctrine, as we know, and it is alleged that Hermotimus of Clazomenae taught it before him. Anaxagoras represented, that even if these various theories of the universal material were true, there would be need of some other cause to account for the transformations of the materials. Since the material cannot originate its own changes, omicron gamma rho delta tau gamma epsilon pi omicron kappa epsilon mu omicron nu alpha tau pi omicron iota epsilon mu epsilon tau alpha beta lambda lambda epsilon iota nu alpha tau omicron. Lambda gamma omega delta omicron nu omicron tau epsilon tau xi lambda omicron nu omicron tau epsilon chi alpha lambda kappa alpha tau iota tau omicron mu epsilon tau alpha beta lambda lambda epsilon iota nu kappa tau epsilon rho omicron nu alpha tau nu omicron delta pi omicron iota epsilon tau mu nu xi lambda omicron nu kappa lambda nu eta nu delta chi alpha lambda kappa nu delta rho iota nu tau alpha lambda lambda tau epsilon rho nu tau iota tau mu epsilon tau alpha beta omicron lambda alpha tau iota omicron nu, viz. The other kind of cause, theta epsilon nu rho chi tau kappa iota nu sigma epsilon omega, an efficient cause. Aristotle expresses great approbation of this doctrine, which he says made its author appear the only sober man among persons raving, omicron nu phi omega nu phi nu eta pi alpha rho epsilon kappa lambda gamma omicron nu tau alpha tau omicron pi rho tau epsilon rho omicron nu. But while describing the influence which it exercised over subsequent speculation, he remarks that the philosophers against whom this, as he thinks, insuperable difficulty was urged, had not felt it to be any difficulty, omicron delta nu delta upsilon sigma chi epsilon rho nu alpha upsilon tau omicron. It is surely unnecessary to say more in proof of the matter of fact which Dr. Tulloch and his reviewer disbelieve. Having pointed out what he thinks the error of these early speculators in not recognizing the need of an efficient cause, Aristotle goes on to mention two other efficient causes to which they might have had recourse, instead of intelligence, tau chi eta, chance, and tau alpha tau omicron nu, spontaneity. He indeed puts these aside as not sufficiently worthy causes for the order in the universe, omicron delta alpha tau omega alpha tau omicron mu tau kappa alpha tau chi tau omicron sigma omicron tau omicron nu pi iota tau rho psi alpha iota pi rho gamma mu alpha kappa alpha lambda epsilon chi epsilon nu. But he does not reject them as incapable of producing any effect, but only as incapable of producing that effect. He himself recognizes tau chi eta and tau alpha tau omicron nu as coordinate agents with mind in producing the phenomena of the universe. The department allotted to them being composed of all the classes of phenomena which are not supposed to follow any uniform law. By thus including chance among efficient causes, Aristotle fell into an error which philosophy has now outgrown, but which is by no means so alien to the spirit even of modern speculation as it may at first sight appear. Up to quite a recent period philosophers went on ascribing, and many of them have not yet ceased to ascribe, a real existence to the results of abstraction. Chance could make out as good a title to that dignity as many other of the mind's abstract creations, it had had a name given to it, and why should it not be a reality? As for tau alpha tau omicron nu, it is recognized even yet as one of the modes of origination of phenomena by all those thinkers who maintain what is called the freedom of the will. The same self-determining power which that doctrine attributes to volitions was supposed by the ancients to be possessed also by some other natural phenomena, a circumstance which throws considerable light on more than one of the supposed invincible necessities of belief. I have introduced it here, because this belief of Aristotle, or rather of the Greek philosophers generally, is as fatal as the doctrines of Thales and the Ionic school to the theory that the human mind is compelled by its constitution to conceive volition as the origin of all force, and the efficient cause of all phenomena. 130. With regard to the modern philosophers, Leibniz and the Cartesians, whom I had cited as having maintained that the action of mind upon matter, so far from being the only conceivable origin of material phenomena, is itself inconceivable. The attempt to rebut this argument by asserting that the mode, not the fact, of the action of mind on matter was represented as inconceivable, is an abuse of the privilege of writing confidently about authors without reading them. For any knowledge whatever of Leibniz would have taught those who thus speak of him, that the inconceivability of the mode, and the impossibility of the thing, were in his mind convertible expressions. What was his famous principle of the sufficient reason, the very cornerstone of his philosophy, from which the pre-established harmony, the doctrine of monads, and all the opinions most characteristic of Leibniz, were corollaries? It was, that nothing exists, the existence of which is not capable of being proved and explained a priori, the proof and explanation in the case of contingent facts being derived from the nature of their causes. Which could not be the causes unless there was something in their nature showing them to be capable of producing those particular effects. And this something, which accounts for the production of physical effects, he was able to find in many physical causes, but could not find it in any finite minds. Which therefore he unhesitatingly asserted to be incapable of producing any physical effects whatever. En any sorate concevoir, he says, une action réciproque de la matière et de l'intelligence l'un sur l'autre, and there is therefore, he contends, no choice but between the occasional causes of the Cartesians and his own pre-established harmony. According to which there is no more connection between our volitions and our muscular actions than there is between two clocks which are wound up to strike at the same instant. But he felt no similar difficulty as to physical causes. And throughout his speculations, as in the passage I have already cited respecting gravitation, he distinctly refuses to consider as part of the order of nature any fact which is not explicable from the nature of its physical cause. With regard to the Cartesians, not Descartes, I did not make that mistake, though the reviewer of Dr. Tulloch's essay attributes it to me. I take a passage almost at random from Malebranche, who is the best known of the Cartesians, and, though not the inventor of the system of occasional causes, is its principal expositor. In Part 2, Chapter 3 of his sixth book, having first said that matter cannot have the power of moving itself, he proceeds to argue that neither can mind have the power of moving it. Quand on examine l'idée qu'elle a de tous les esprits finis, on n'y voit point de liaison nécessaire entre leur volonté et le mouvement de quelque corps soit, on voit au contraire qu'ilny en a point. Et qu'ilny peut avoir, there is nothing in the idea of finite mind which can account for its causing the motion of a body. On doit aussi conclure, si on vent raisonner silen ses lumières, qu'ilny a aucun esprit que puisse remuer quelque corps soit comme cause véritable en principali. De même qu'elle a dit qu'aucun corps ne pouvait remuer soi-même, thus the idea of mind is according to him as incompatible as the idea of matter with the exercise of active force. But when, he continues, we consider not a created but a divine mind, the case is altered, for the idea of a divine mind includes omnipotence, and the idea of omnipotence does contain the idea of being able to move bodies. Thus it is the nature of omnipotence which renders the motion of bodies even by the divine mind credible or conceivable, while, so far as depended on the mere nature of mind, it would have been inconceivable and incredible. If Malebranche had not believed in an omnipotent being, he would have held all action of mind on body to be a demonstrated impossibility. 131. A doctrine more precisely the reverse of the volitional theory of causation cannot well be imagined. The volitional theory is, that we know by intuition or by direct experience the action of our own mental volitions on matter. That we may hence infer all other action upon matter to be that of volition, and might thus know, without any other evidence, that matter is under the government of a divine mind. Leibniz and the Cartesians, on the contrary, maintain that our volitions do not and cannot act upon matter, and that it is only the existence of an all-governing being, and that being omnipotent, which can account for the sequence between our volitions and our bodily actions. When we consider that each of these two theories, which, as theories of causation, stand at the opposite extremes of possible divergence from one another, invokes not only as its evidence, but as its sole evidence, the absolute inconceivability of any theory but itself. We are enabled to measure the worth of this kind of evidence, and when we find the volitional theory entirely built upon the assertion that by our mental constitution we are compelled to recognize our volitions as efficient causes, and then find other thinkers maintaining that we know that they are not and cannot be such causes, and cannot conceive them to be so, I think we have a right to say that this supposed law of our mental constitution does not exist. Dr. Tulloch, pages 45 to 47, thinks it a sufficient answer to this, that Leibniz and the Cartesians were theists, and believed the will of God to be an efficient cause. Doubtless they did, and the Cartesians even believed, though Leibniz did not, that it is the only such cause. Dr. Tulloch mistakes the nature of the question. I was not writing on theism, as Dr. Tulloch is, but against a particular theory of causation, which, if it be unfounded, can give no effective support to theism or to anything else. I found it asserted that volition is the only efficient cause, on the ground that no other efficient cause is conceivable. To this assertion I oppose the instances of Leibniz and of the Cartesians, who affirmed with equal positiveness that volition as an efficient cause is itself not conceivable, and that omnipotence, which renders all things conceivable, can alone take away the impossibility. This I thought, and think, a conclusive answer to the argument on which this theory of causation avowedly depends. But I certainly did not imagine that theism was bound up with that theory, nor expected to be charged with denying Leibniz and the Cartesians to be theists because I denied that they held the theory. 6. On the composition of causes. Section 1. To complete the general notion of causation on which the rules of experimental inquiry into the laws of nature must be founded, one distinction still remains to be pointed out, a distinction so radical, and of so much importance, as to require a chapter to itself. The preceding discussions have rendered us familiar with the case in which several agents, or causes, concur as conditions to the production of an effect. A case, in truth, almost universal, there being very few effects to the production of which no more than one agent contributes. Suppose, then, that two different agents, operating jointly, are followed, under a certain set of collateral conditions, by a given effect. If either of these agents, instead of being joined with the other, had operated alone, under the same set of conditions in all other respects, some effect would probably have followed, which would have been different from the joint effect of the two, and more or less dissimilar to it. Now, if we happen to know what would be the effect of each cause when acting separately from the other, we are often able to arrive deductively, or a priori, at a correct prediction of what will arise from their conjunct agency. To render this possible, it is only necessary that the same law which expresses the effect of each cause acting by itself, shall also correctly express the part due to that cause of the effect which follows from the two together. This condition is realized in the extensive and important class of phenomena commonly called mechanical, namely the phenomena of the communication of motion, or of pressure, which is tendency to motion, from one body to another. In this important class of cases of causation, one cause never, properly speaking, defeats or frustrates another, both have their full effect. If a body is propelled in two directions by two forces, one tending to drive it to the north and the other to the east, it is caused to move in a given time exactly as far in both directions as the two forces would separately have carried it, and is left precisely where it would have arrived if it had been acted upon first by one of the two forces, and afterward by the other. This law of nature is called, in dynamics, the principle of the composition of forces. And in imitation of that well-chosen expression, I shall give the name of the composition of causes to the principle which is exemplified in all cases in which the joint effect of several causes is identical with the sum of their separate effects. This principle, however, by no means prevails in all departments of the field of nature. The chemical combination of two substances produces, as is well known, a third substance, with properties different from those of either of the two substances separately, or of both of them taken together. Not a trace of the properties of hydrogen or of oxygen is observable in those of their compound, water. The taste of sugar of lead is not the sum of the tastes of its component elements, acetic acid and lead or its oxide. Nor is the color of blue vitriol a mixture of the colors of sulfuric acid and copper. This explains why mechanics is a deductive or demonstrative science, and chemistry not. In the one, we can compute the effects of combinations of causes, whether real or hypothetical, from the laws which we know to govern those causes when acting separately. Because they continue to observe the same laws and in combination which they observe when separate, whatever would have happened in consequence of each cause taken by itself, happens when they are together, and we have only to cast up the results. Not so in the phenomena which are the peculiar subject of the science of chemistry. There most of the uniformities to which the causes conform when separate, cease altogether when they are conjoined. And we are not, at least in the present state of our knowledge, able to foresee what result will follow from any new combination until we have tried the specific experiment. If this be true of chemical combinations, it is still more true of those far more complex combinations of elements which constitute organized bodies, and in which those extraordinary new uniformities arise which are called the laws of life. All organized bodies are composed of parts similar to those composing inorganic nature, and which have even themselves existed in an inorganic state. But the phenomena of life, which result from the juxtaposition of those parts in a certain manner, bear no analogy to any of the effects which would be produced by the action of the component substances considered as mere physical agents. To whatever degree we might imagine our knowledge of the properties of the several ingredients of a living body to be extended and perfected, it is certain that no mere summing up of the separate actions of those elements will ever amount to the action of the living body itself. The tongue, for instance, is, like all other parts of the animal frame, composed of gelatin, fibrin, and other products of the chemistry of digestion. But from no knowledge of the properties of those substances could we ever predict that it could taste, unless gelatin or fibrin could themselves taste, for no elementary fact can be in the conclusion which was not in the premises. There are thus two different modes of the conjunct action of causes, from which arise two modes of conflict, or mutual interference, between laws of nature. Suppose, at a given point of time and space, two or more causes, which, if they acted separately, would produce effects contrary, or at least conflicting with each other, one of them tending to undo, wholly or partially, what the other tends to do. Thus the expansive force of the gases generated by the ignition of gunpowder tends to project a bullet toward the sky, while its gravity tends to make it fall to the ground. A stream running into a reservoir at one end tends to fill it higher and higher, while a drain at the other extremity tends to empty it. Now, in such cases as these, even if the two causes which are in joint action exactly annul one another, still the laws of both are fulfilled. The effect is the same as if the drain had been open for half an hour first, 1:32, and the stream had flowed in for as long afterward. Each agent produces the same amount of effect as if it had acted separately, though the contrary effect which was taking place during the same time obliterated it as fast as it was produced. Here, then, are two causes, producing by their joint operations an effect which at first seems quite dissimilar to those which they produce separately, but which on examination proves to be really the sum of those separate effects. It will be noticed that we here enlarge the idea of the sum of two effects, so as to include what is commonly called their difference, but which is in reality the result of the addition of opposites. A conception to which mankind are indebted for that admirable extension of the algebraical calculus, which has so vastly increased its powers as an instrument of discovery, by introducing into its reasonings, with the sign of subtraction prefixed. And under the name of negative quantities, every description whatever of positive phenomena, provided they are of such a quality in reference to those previously introduced, that to add the one is equivalent to subtracting an equal quantity of the other. There is, then, one mode of the mutual interference of laws of nature, in which, even when the concurrent causes annihilate each other's effects, each exerts its full efficacy according to its own law, its law as a separate agent. But in the other description of cases, the agencies which are brought together cease entirely, and a totally different set of phenomena arise, as in the experiment of two liquids which, when mixed in certain proportions, instantly become not a larger amount of liquid, but a solid mass. Section 2. This difference between the case in which the joint effect of causes is the sum of their separate effects, and the case in which it is heterogeneous to them, between laws which work together without alteration, and laws which, when called upon to work together, cease and give place to others, is one of the fundamental distinctions in nature. The former case, that of the composition of causes, is the general one, the other is always special and exceptional. There are no objects which do not, as to some of their phenomena, obey the principle of the composition of causes. None that have not some laws which are rigidly fulfilled in every combination into which the objects enter. The weight of a body, for instance, is a property which it retains in all the combinations in which it is placed. The weight of a chemical compound, or of an organized body, is equal to the sum of the weights of the elements which compose it. The weight either of the elements or of the compound will vary, if they be carried farther from their center of attraction, or brought nearer to it, but whatever affects the one affects the other. They always remain precisely equal. So, again, the component parts of a vegetable or animal substance do not lose their mechanical and chemical properties as separate agents, when, by a peculiar mode of juxtaposition, they, as an aggregate whole, acquire physiological or vital properties in addition. Those bodies continue, as before, to obey mechanical and chemical laws, in so far as the operation of those laws is not counteracted by the new laws which govern them as organized beings. When, in short, a concurrence of causes takes place which calls into action new laws bearing no analogy to any that we can trace in the separate operation of the causes, the new laws, while they supersede one portion of the previous laws, may coexist with another portion, and may even compound the effect of those previous laws with their own. Again, laws which were themselves generated in the second mode, may generate others in the first. Though there are laws which, like those of chemistry and physiology, owe their existence to a breach of the principle of composition of causes, it does not follow that these peculiar, or, as they might be termed, heteropathic laws, are not capable of composition with one another. The causes which by one combination have had their laws altered, may carry their new laws with them unaltered into their ulterior combinations. And hence there is no reason to despair of ultimately raising chemistry and physiology to the condition of deductive sciences. For though it is impossible to deduce all chemical and physiological truths from the laws or properties of simple substances or elementary agents, they may possibly be deducible from laws which commence when these elementary agents are brought together into some moderate number of not very complex combinations. The laws of life will never be deducible from the mere laws of the ingredients, but the prodigiously complex facts of life may all be deducible from comparatively simple laws of life. Which laws, depending indeed on combinations, but on comparatively simple combinations, of antecedents, may, in more complex circumstances, be strictly compounded with one another, and with the physical and chemical laws of the ingredients. The details of the vital phenomena, even now, afford innumerable exemplifications of the composition of causes. And in proportion as these phenomena are more accurately studied, there appears more reason to believe that the same laws which operate in the simpler combinations of circumstances do, in fact, continue to be observed in the more complex. This will be found equally true in the phenomena of mind, and even in social and political phenomena, the results of the laws of mind. It is in the case of chemical phenomena that the least progress has yet been made in bringing the special laws under general ones from which they may be deduced. But there are even in chemistry many circumstances to encourage the hope that such general laws will hereafter be discovered. The different actions of a chemical compound will never, undoubtedly, be found to be the sums of the actions of its separate elements. But there may exist, between the properties of the compound and those of its elements, some constant relation, which, if discoverable by a sufficient induction, would enable us to foresee the sort of compound which will result from a new combination before we have actually tried it, and to judge of what sort of element some new substance is compounded before we have analyzed it. The law of definite proportions, first discovered in its full generality by Dalton, is a complete solution of this problem in one, though but a secondary aspect, that of quantity. And in respect to quality, we have already some partial generalizations, sufficient to indicate the possibility of ultimately proceeding farther. We can predicate some common properties of the kind of compounds which result from the combination, in each of the small number of possible proportions, of any acid whatever with any base. We have also the curious law, discovered by Berthollet, that two soluble salts mutually decompose one another whenever the new combinations which result produce an insoluble compound, or one less soluble than the two former. Another uniformity is that called the law of isomorphism, the identity of the crystalline forms of substances which possess in common certain peculiarities of chemical composition. 133 Thus it appears that even heteropathic laws, such laws of combined agency as are not compounded of the laws of the separate agencies, are yet, at least in some cases, derived from them according to a fixed principle. There may, therefore, be laws of the generation of laws from others dissimilar to them. And in chemistry, these undiscovered laws of the dependence of the properties of the compound on the properties of its elements, may, together with the laws of the elements themselves, furnish the premises by which the science is perhaps destined one day to be rendered deductive. It would seem, therefore, that there is no class of phenomena in which the composition of causes does not obtain, that as a general rule, causes in combination produce exactly the same effects as when acting singly, but that this rule, though general, is not universal, that in some instances, at some particular points in the transition from separate to united action, the laws change, and an entirely new set of effects are either added to, or take the place of those which arise from the separate agency of the same causes, the laws of these new effects being again susceptible of composition, to an indefinite extent, like the laws which they superseded. Section 3. That effects are proportional to their causes is laid down by some writers as an axiom in the theory of causation. And great use is sometimes made of this principle in reasonings respecting the laws of nature, though it is encumbered with many difficulties and apparent exceptions, which much ingenuity has been expended in showing not to be real ones. This proposition, in so far as it is true, enters as a particular case into the general principle of the composition of causes, the causes compounded being, in this instance, homogeneous. In which case, if in any, their joint effect might be expected to be identical with the sum of their separate effects. If a force equal to 100 weight will raise a certain body along an inclined plane, a force equal to 200 weight will raise two bodies exactly similar, and thus the effect is proportional to the cause. But does not a force equal to 200 weight actually contain in itself two forces each equal to 100 weight, which, if employed apart, would separately raise the two bodies in question? The fact, therefore, that when exerted jointly they raise both bodies at once, results from the composition of causes, and is a mere instance of the general fact that mechanical forces are subject to the law of composition. And so in every other case which can be supposed. For the doctrine of the proportionality of effects to their causes cannot of course be applicable to cases in which the augmentation of the cause alters the kind of effect. That is, in which the surplus quantity superadded to the cause does not become compounded with it, but the two together generate an altogether new phenomenon. Suppose that the application of a certain quantity of heat to a body merely increases its bulk, that a double quantity melts it, and a triple quantity decomposes it, these three effects being heterogeneous, no ratio, whether corresponding or not to that of the quantities of heat applied, can be established between them. Thus the supposed axiom of the proportionality of effects to their causes fails at the precise point where the principle of the composition of causes also fails, viz. where the concurrence of causes is such as to determine a change in the properties of the body generally, and render it subject to new laws, more or less dissimilar to those to which it conformed in its previous state. The recognition, therefore, of any such law of proportionality is superseded by the more comprehensive principle, in which as much of it as is true is implicitly asserted. 134. The general remarks on causation, which seemed necessary as an introduction to the theory of the inductive process, may here terminate. That process is essentially an inquiry into cases of causation. All the uniformities which exist in the succession of phenomena, and most of the uniformities in their coexistence, are either, as we have seen, themselves laws of causation, or consequences resulting from, and corollaries capable of being deduced from, such laws. If we could determine what causes are correctly assigned to what effects, and what effects to what causes, we should be virtually acquainted with the whole course of nature. All those uniformities which are mere results of causation might then be explained and accounted for. And every individual fact or event might be predicted, provided we had the requisite data, that is, the requisite knowledge of the circumstances which, in the particular instance, preceded it. To ascertain, therefore, what are the laws of causation which exist in nature, to determine the effect of every cause, and the causes of all effects, is the main business of induction. And to point out how this is done is the chief object of inductive logic. 7. On Observation and Experiment. Section 1. It results from the preceding exposition, that the process of ascertaining what consequents, in nature, are invariably connected with what antecedents, or in other words what phenomena are related to each other as causes and effects, is in some sort a process of analysis. That every fact which begins to exist has a cause, and that this cause must be found in some fact or concourse of facts which immediately preceded the occurrence, may be taken for certain. The whole of the present facts are the infallible result of all past facts, and more immediately of all the facts which existed at the moment previous. Here, then, is a great sequence, which we know to be uniform. If the whole prior state of the entire universe could again recur, it would again be followed by the present state. The question is, how to resolve this complex uniformity into the simpler uniformities which compose it, and assign to each portion of the vast antecedent the portion of the consequent which is attendant on it. This operation, which we have called analytical, inasmuch as it is the resolution of a complex whole into the component elements, is more than a merely mental analysis. No mere contemplation of the phenomena, and partition of them by the intellect alone, will of itself accomplish the end we have now in view. Nevertheless, such a mental partition is an indispensable first step. The order of nature, as perceived at a first glance, presents at every instant a chaos followed by another chaos. We must decompose each chaos into single facts. We must learn to see in the chaotic antecedent a multitude of distinct antecedents, in the chaotic consequent a multitude of distinct consequents. This, supposing it done, will not of itself tell us on which of the antecedents each consequent is invariably attendant. To determine that point, we must endeavor to effect a separation of the facts from one another, not in our minds only, but in nature. The mental analysis, however, must take place first. And every one knows that in the mode of performing it, one intellect differs immensely from another. It is the essence of the act of observing. For the observer is not he who merely sees the thing which is before his eyes, but he who sees what parts that thing is composed of. To do this well is a rare talent. One person, from inattention, or attending only in the wrong place, overlooks half of what he sees, another sets down much more than he sees, confounding it with what he imagines, or with what he infers. Another takes note of the kind of all the circumstances, but being inexpert in estimating their degree, leaves the quantity of each vague and uncertain. Another sees indeed the whole, but makes such an awkward division of it into parts, throwing things into one mass which require to be separated, and separating others which might more conveniently be considered as one. That the result is much the same, sometimes even worse, than if no analysis had been attempted at all. It would be possible to point out what qualities of mind, and modes of mental culture, fit a person for being a good observer. That, however, is a question not of logic, but of the theory of education, in the most enlarged sense of the term. There is not properly an art of observing. There may be rules for observing. But these, like rules for inventing, are properly instructions for the preparation of one's own mind. For putting it into the state in which it will be most fitted to observe, or most likely to invent. They are, therefore, essentially rules of self-education, which is a different thing from logic. They do not teach how to do the thing, but how to make ourselves capable of doing it. They are an art of strengthening the limbs, not an art of using them. The extent and minuteness of observation which may be requisite, and the degree of decomposition to which it may be necessary to carry the mental analysis, depend on the particular purpose in view. To ascertain the state of the whole universe at any particular moment is impossible, but would also be useless. In making chemical experiments, we do not think it necessary to note the position of the planets. Because experience has shown, as a very superficial experience is sufficient to show, that in such cases that circumstance is not material to the result, and accordingly, in the ages when men believed in the occult influences of the heavenly bodies, it might have been unphilosophical to omit ascertaining the precise condition of those bodies at the moment of the experiment. As to the degree of minuteness of the mental subdivision, if we were obliged to break down what we observe into its very simplest elements, that is, literally into single facts, it would be difficult to say where we should find them. We can hardly ever affirm that our divisions of any kind have reached the ultimate unit. But this, too, is fortunately unnecessary. The only object of the mental separation is to suggest the requisite physical separation, so that we may either accomplish it ourselves, or seek for it in nature. And we have done enough when we have carried the subdivision as far as the point at which we are able to see what observations or experiments we require. It is only essential, at whatever point our mental decomposition of facts may for the present have stopped, that we should hold ourselves ready and able to carry it further as occasion requires. And should not allow the freedom of our discriminating faculty to be imprisoned by the swathes and bands of ordinary classification. As was the case with all early speculative inquirers, not excepting the Greeks, to whom it seldom occurred that what was called by one abstract name might, in reality, be several phenomena. Or that there was a possibility of decomposing the facts of the universe into any elements but those which ordinary language already recognized. Section 2. The different antecedents and consequents being, then, supposed to be, so far as the case requires, ascertained and discriminated from one another, we are to inquire which is connected with which. In every instance which comes under our observation, there are many antecedents and many consequents. If those antecedents could not be severed from one another except in thought, or if those consequents never were found apart, it would be impossible for us to distinguish, a posteriori at least, the real laws, or to assign to any cause its effect, or to any effect its cause. To do so, we must be able to meet with some of the antecedents apart from the rest, and observe what follows from them, or some of the consequents, and observe by what they are preceded. We must, in short, follow the Baconian rule of varying the circumstances. This is, indeed, only the first rule of physical inquiry, and not, as some have thought, the sole rule, but it is the foundation of all the rest. For the purpose of varying the circumstances, we may have recourse, according to a distinction commonly made, either to observation or to experiment. We may either find an instance in nature suited to our purposes, or, by an artificial arrangement of circumstances, make one. The value of the instance depends on what it is in itself, not on the mode in which it is obtained. Its employment for the purposes of induction depends on the same principles in the one case and in the other. As the uses of money are the same whether it is inherited or acquired. There is, in short, no difference in kind, no real logical distinction, between the two processes of investigation. There are, however, practical distinctions to which it is of considerable importance to advert. Section 3. The first and most obvious distinction between observation and experiment is, that the latter is an immense extension of the former. It not only enables us to produce a much greater number of variations in the circumstances than nature spontaneously offers, but also, in thousands of cases, to produce the precise sort of variation which we are in want of for discovering the law of the phenomenon. A service which nature, being constructed on a quite different scheme from that of facilitating our studies, is seldom so friendly as to bestow upon us. For example, in order to ascertain what principle in the atmosphere enables it to sustain life, the variation we require is that a living animal should be immersed in each component element of the atmosphere separately. But nature does not supply either oxygen or azote in a separate state. We are indebted to artificial experiment for our knowledge that it is the former, and not the latter, which supports respiration. And for our knowledge of the very existence of the two ingredients. Thus far the advantage of experimentation over simple observation is universally recognized. All are aware that it enables us to obtain innumerable combinations of circumstances which are not to be found in nature. And so add to nature's experiments a multitude of experiments of our own. But there is another superiority, or, as Bacon would have expressed it, another prerogative, of instances artificially obtained over spontaneous instances, of our own experiments over even the same experiments when made by nature, which is not of less importance, and which is far from being felt and acknowledged in the same degree. When we can produce a phenomenon artificially, we can take it, as it were, home with us, and observe it in the midst of circumstances with which in all other respects we are accurately acquainted. If we desire to know what are the effects of the cause A, and are able to produce a by means at our disposal, we can generally determine at our own discretion, so far as is compatible with the nature of the phenomenon A, the whole of the circumstances which shall be present along with it, and thus, knowing exactly the simultaneous state of everything else which is within the reach of A's influence, we have only to observe what alteration is made in that state by the presence of A. For example, by the electric machine we can produce, in the midst of known circumstances, the phenomena which nature exhibits on a grander scale in the form of lightning and thunder. Now let any one consider what amount of knowledge of the effects and laws of electric agency mankind could have obtained from the mere observation of thunderstorms, and compare it with that which they have gained, and may expect to gain, from electrical and galvanic experiments. This example is the more striking, now that we have reason to believe that electric action is of all natural phenomena, except heat, the most pervading and universal, which, therefore, it might antecedently have been supposed could stand least in need of artificial means of production to enable it to be studied. While the fact is so much the contrary, that without the electric machine, the Leyden jar, and the voltaic battery, we probably should never have suspected the existence of electricity as one of the great agents in nature. The few electric phenomena we should have known of would have continued to be regarded either as supernatural, or as a sort of anomalies and eccentricities in the order of the universe. When we have succeeded in insulating the phenomenon which is the subject of inquiry, by placing it among known circumstances, we may produce further variations of circumstances to any extent, and of such kinds as we think best calculated to bring the laws of the phenomenon into a clear light. By introducing one well-defined circumstance after another into the experiment, we obtain assurance of the manner in which the phenomenon behaves under an indefinite variety of possible circumstances. Thus, chemists, after having obtained some newly discovered substance in a pure state, that is, having made sure that there is nothing present which can interfere with and modify its agency, introduce various other substances, one by one, to ascertain whether it will combine with them, or decompose them, and with what result. And also apply heat, or electricity, or pressure, to discover what will happen to the substance under each of these circumstances. But if, on the other hand, it is out of our power to produce the phenomenon, and we have to seek for instances in which nature produces it, the task before us is very different. Instead of being able to choose what the concomitant circumstances shall be, we now have to discover what they are, which, when we go beyond the simplest and most accessible cases, it is next to impossible to do with any precision and completeness. Let us take, as an exemplification of a phenomenon which we have no means of fabricating artificially, a human mind. Nature produces many. But the consequence of our not being able to produce them by art is, that in every instance in which we see a human mind developing itself, or acting upon other things, we see it surrounded and obscured by an indefinite multitude of unascertainable circumstances, rendering the use of the common experimental methods almost delusive. We may conceive to what extent this is true, if we consider, among other things, that whenever nature produces a human mind, she produces, in close connection with it, a body. That is, a vast complication of physical facts, in no two cases perhaps exactly similar, and most of which, except the mere structure, which we can examine in a sort of coarse way after it has ceased to act, are radically out of the reach of our means of exploration. If, instead of a human mind, we suppose the subject of investigation to be a human society or state, all the same difficulties recur in a greatly augmented degree. We have thus already come within sight of a conclusion, which the progress of the inquiry will, I think, bring before us with the clearest evidence, namely, that in the sciences which deal with phenomena in which artificial experiments are impossible, as in the case of astronomy, or in which they have a very limited range, as in mental philosophy, social science, and even physiology. Induction from direct experience is practiced at a disadvantage in most cases equivalent to impracticability. From which it follows that the methods of those sciences, in order to accomplish anything worthy of attainment, must be to a great extent, if not principally, deductive. This is already known to be the case with the first of the sciences we have mentioned, astronomy. That it is not generally recognized as true of the others, is probably one of the reasons why they are not in a more advanced state. Section 4. If what is called pure observation is at so great a disadvantage, compared with artificial experimentation, in one department of the direct exploration of phenomena, there is another branch in which the advantage is all on the side of the former. Inductive inquiry having for its object to ascertain what causes are connected with what effects. We may begin this search at either end of the road which leads from the one point to the other. We may either inquire into the effects of a given cause or into the causes of a given effect. The fact that light blackens chloride of silver might have been discovered either by experiments on light, trying what effect it would produce on various substances, or by observing that portions of the chloride had repeatedly become black. And inquiring into the circumstances. The effect of the Urali poison might have become known either by administering it to animals, or by examining how it happened that the wounds which the Indians of Guyana inflict with their arrows prove so uniformly mortal. Now it is manifest from the mere statement of the examples, without any theoretical discussion, that artificial experimentation is applicable only to the former of these modes of investigation. We can take a cause, and try what it will produce. But we cannot take an effect, and try what it will be produced by. We can only watch till we see it produced, or are enabled to produce it by accident. This would be of little importance, if it always depended on our choice from which of the two ends of the sequence we would undertake our inquiries. But we have seldom any option. As we can only travel from the known to the unknown, we are obliged to commence at whichever end we are best acquainted with. If the agent is more familiar to us than its effects, we watch for, or contrive, instances of the agent, under such varieties of circumstances as are open to us, and observe the result. If, on the contrary, the conditions on which a phenomenon depends are obscure, but the phenomenon itself familiar, we must commence our inquiry from the effect. If we are struck with the fact that chloride of silver has been blackened, and have no suspicion of the cause, we have no resource but to compare instances in which the fact has chanced to occur. Until by that comparison we discover that in all those instances the substances had been exposed to light. If we knew nothing of the Indian arrows but their fatal effect, accident alone could turn our attention to experiments on the Urali. In the regular course of investigation, we could only inquire, or try to observe, what had been done to the arrows in particular instances. Wherever, having nothing to guide us to the cause, we are obliged to set out from the effect, and to apply the rule of varying the circumstances to the consequence, not the antecedents. We are necessarily destitute of the resource of artificial experimentation. We cannot, at our choice, obtain consequence, as we can antecedents, under any set of circumstances compatible with their nature. There are no means of producing effects but through their causes, and by the supposition the causes of the effect in question are not known to us. We have, therefore, no expedient but to study it where it offers itself spontaneously. If nature happens to present us with instances sufficiently varied in their circumstances, and if we are able to discover, either among the proximate antecedents or among some other order of antecedents, something which is always found when the effect is found, however various the circumstances, and never found when it is not, we may discover, by mere observation without experiment, a real uniformity in nature. But though this is certainly the most favorable case for sciences of pure observation, as contrasted with those in which artificial experiments are possible, there is in reality no case which more strikingly illustrates the inherent imperfection of direct induction when not founded on experimentation. Suppose that, by a comparison of cases of the effect, we have found an antecedent which appears to be, and perhaps is, invariably connected with it. We have not yet proved that antecedent to be the cause until we have reversed the process, and produced the effect by means of that antecedent. If we can produce the antecedent artificially, and if, when we do so, the effect follows, the induction is complete, that antecedent is the cause of that consequent. Point 135. But we have then added the evidence of experiment to that of simple observation. Until we had done so, we had only proved invariable antecedents within the limits of experience, but not unconditional antecedents, or causation. Until it had been shown by the actual production of the antecedent under known circumstances, and the occurrence thereupon of the consequent, that the antecedent was really the condition on which it depended. The uniformity of succession which was proved to exist between them might, for aught we knew, be, like the succession of day and night, not a case of causation at all. Both antecedent and consequent might be successive stages of the effect of an ulterior cause. Observation, in short, without experiment, supposing no aid from deduction, can ascertain sequences and coexistences, but cannot prove causation. In order to see these remarks verified by the actual state of the sciences, we have only to think of the condition of natural history. In zoology, for example, there is an immense number of uniformities ascertained, some of coexistence, others of succession, to many of which, notwithstanding considerable variations of the attendant circumstances, we know not any exception, but the antecedents, for the most part, are such as we cannot artificially produce. Or if we can, it is only by setting in motion the exact process by which nature produces them. And this being to us a mysterious process, of which the main circumstances are not only unknown but unobservable, we do not succeed in obtaining the antecedents under known circumstances. What is the result? That on this vast subject, which affords so much and such varied scope for observation, we have made most scanty progress in ascertaining any laws of causation. We know not with certainty, in the case of most of the phenomena that we find conjoined, which is the condition of the other. Which is cause, and which effect, or whether either of them is so, or they are not rather conjunct effects of causes yet to be discovered, complex results of laws hitherto unknown. Although some of the foregoing observations may be, in technical strictness of arrangement, premature in this place, it seemed that a few general remarks on the difference between sciences of mere observation and sciences of experimentation, and the extreme disadvantage under which directly inductive inquiry is necessarily carried on in the former, were the best preparation for discussing the methods of direct induction. A preparation rendering superfluous much that must otherwise have been introduced, with some inconvenience, into the heart of that discussion. To the consideration of these methods we now proceed. 8. Of the 4 methods of experimental inquiry. Section 1. The simplest and most obvious modes of singling out from among the circumstances which precede or follow a phenomenon, those with which it is really connected by an invariable law, are 2 in number. One is, by comparing together different instances in which the phenomenon occurs. The other is, by comparing instances in which the phenomenon does occur, with instances in other respects similar in which it does not. These 2 methods may be respectively denominated, the method of agreement, and the method of difference. In illustrating these methods, it will be necessary to bear in mind the twofold character of inquiries into the laws of phenomena, which may be either inquiries into the cause of a given effect, or into the effects or properties of a given cause. We shall consider the methods in their application to either order of investigation, and shall draw our examples equally from both. We shall denote antecedents by the large letters of the alphabet, and the consequents corresponding to them by the small. Let A, then, be an agent or cause, and let the object of our inquiry be to ascertain what are the effects of this cause. If we can either find, or produce, the agent A in such varieties of circumstances that the different cases have no circumstance in common except A, then whatever effect we find to be produced in all our trials, is indicated as the effect of A. Suppose, for example, that A is tried along with B and C, and that the effect is A B C, and suppose that A is next tried with D and E, but without B and C, and that the effect is A D E. Then we may reason thus: B and C are not effects of A, for they were not produced by it in the second experiment, nor are D and E, for they were not produced in the first. Whatever is really the effect of A must have been produced in both instances. Now this condition is fulfilled by no circumstance except A. The phenomenon A cannot have been the effect of B or C, since it was produced where they were not, nor of D or E, since it was produced where they were not. Therefore it is the effect of A. For example, let the antecedent A be the contact of an alkaline substance and an oil. This combination being tried under several varieties of circumstances, resembling each other in nothing else. The results agree in the production of a greasy and detersive or saponaceous substance. It is therefore concluded that the combination of an oil and an alkali causes the production of a soap. It is thus we inquire, by the method of agreement, into the effect of a given cause. In a similar manner we may inquire into the cause of a given effect. Let A be the effect. Here, as shown in the last chapter, we have only the resource of observation without experiment. We cannot take a phenomenon of which we know not the origin, and try to find its mode of production by producing it. If we succeeded in such a random trial it could only be by accident. But if we can observe A in two different combinations, A, B, C and A, D, E, and if we know, or can discover, that the antecedent circumstances in these cases respectively were A, B, C and A, D, E, we may conclude by a reasoning similar to that in the preceding example, that A is the antecedent connected with the consequent A by a law of causation. B and C, we may say, cannot be causes of A, since on its second occurrence they were not present, nor are D and E, for they were not present on its first occurrence. A, alone of the five circumstances, was found among the antecedents of A in both instances. For example, let the effect A be crystallization. We compare instances in which bodies are known to assume crystalline structure, but which have no other point of agreement. And we find them to have one, and as far as we can observe, only one, antecedent in common, the deposition of a solid matter from a liquid state, either a state of fusion or of solution. We conclude, therefore, that the solidification of a substance from a liquid state is an invariable antecedent of its crystallization. In this example we may go further, and say, it is not only the invariable antecedent but the cause. Or at least the proximate event which completes the cause. For in this case we are able, after detecting the antecedent A, to produce it artificially, and by finding that A follows it, verify the result of our induction. The importance of thus reversing the proof was strikingly manifested when, by keeping a phial of water charged with silicious particles undisturbed for years, a chemist, I believe Dr. Wollaston, succeeded in obtaining crystals of quartz. And in the equally interesting experiment in which Sir James Hall produced artificial marble by the cooling of its materials from fusion under immense pressure, two admirable examples of the light which may be thrown upon the most secret processes of nature by well-contrived interrogation of her. But if we cannot artificially produce the phenomenon A, the conclusion that it is the cause of A remains subject to very considerable doubt. Though an invariable, it may not be the unconditional antecedent of A, but may precede it as day precedes night or night day. This uncertainty arises from the impossibility of assuring ourselves that A is the only immediate antecedent common to both the instances. If we could be certain of having ascertained all the invariable antecedents, we might be sure that the unconditional invariable antecedent, or cause, must be found somewhere among them. Unfortunately it is hardly ever possible to ascertain all the antecedents, unless the phenomenon is one which we can produce artificially. Even then, the difficulty is merely lightened, not removed. Men knew how to raise water in pumps long before they adverted to what was really the operating circumstance in the means they employed, namely, the pressure of the atmosphere on the open surface of the water. It is, however, much easier to analyze completely a set of arrangements made by ourselves, than the whole complex mass of the agencies which nature happens to be exerting at the moment of the production of a given phenomenon. We may overlook some of the material circumstances in an experiment with an electrical machine, but we shall, at the worst, be better acquainted with them than with those of a thunderstorm. The mode of discovering and proving laws of nature, which we have now examined, proceeds on the following axiom: whatever circumstances can be excluded, without prejudice to the phenomenon, or can be absent notwithstanding its presence. is not connected with it in the way of causation. The casual circumstances being thus eliminated, if only one remains, that one is the cause which we are in search of, if more than one, they either are, or contain among them, the cause, and so, mutatis mutandis, of the effect. As this method proceeds by comparing different instances to ascertain in what they agree, I have termed it the method of agreement, and we may adopt as its regulating principle the following canon. First canon. If two or more instances of the phenomenon under investigation have only one circumstance in common, the circumstance in which alone all the instances agree, is the cause, or effect, of the given phenomenon. Quitting for the present the method of agreement, to which we shall almost immediately return, we proceed to a still more potent instrument of the investigation of nature, the method of difference. Section 2. In the method of agreement, we endeavored to obtain instances which agreed in the given circumstance but differed in every other. In the present method we require, on the contrary, two instances resembling one another in every other respect, but differing in the presence or absence of the phenomenon we wish to study. If our object be to discover the effects of an agent A, we must procure A in some set of ascertained circumstances, as ABC, and having noted the effects produced, compare them with the effect of the remaining circumstances BC, when A is absent. If the effect of ABC is ABC, and the effect of BC BC, it is evident that the effect of A is A. So again, if we begin at the other end, and desire to investigate the cause of an effect A, we must select an instance, as ABC, in which the effect occurs, and in which the antecedents were ABC. And we must look out for another instance in which the remaining circumstances, BC, occur without A. If the antecedents, in that instance, are BC, we know that the cause of A must be A, either A alone, or A in conjunction with some of the other circumstances present. It is scarcely necessary to give examples of a logical process to which we owe almost all the inductive conclusions we draw in daily life. When a man is shot through the heart, it is by this method we know that it was the gunshot which killed him, for he was in the fullness of life immediately before, all circumstances being the same, except the wound. The axioms implied in this method are evidently the following. Whatever antecedent cannot be excluded without preventing the phenomenon, is the cause, or a condition, of that phenomenon. Whatever consequent can be excluded, with no other difference in the antecedents than the absence of a particular one, is the effect of that one. Instead of comparing different instances of a phenomenon, to discover in what they agree, this method compares an instance of its occurrence with an instance of its non-occurrence, to discover in what they differ. The canon which is the regulating principle of the method of difference may be expressed as follows. Second canon. If an instance in which the phenomenon under investigation occurs, and an instance in which it does not occur, have every circumstance in common save one, that one occurring only in the former, the circumstance in which alone the two instances differ, is the effect, or the cause, or an indispensable part of the cause, of the phenomenon. Section 3. The two methods which we have now stated have many features of resemblance, but there are also many distinctions between them. Both are methods of elimination. This term, employed in the theory of equations to denote the process by which one after another of the elements of a question is excluded, and the solution made to depend on the relation between the remaining elements only, is well suited to express the operation, analogous to this, which has been understood since the time of Bacon to be the foundation of experimental inquiry, namely, the successive exclusion of the various circumstances which are found to accompany a phenomenon in a given instance, in order to ascertain what are those among them which can be absent consistently with the existence of the phenomenon. The method of agreement stands on the ground that whatever can be eliminated, is not connected with the phenomenon by any law. The method of difference has for its foundation, that whatever cannot be eliminated, is connected with the phenomenon by a law. Of these methods, that of difference is more particularly a method of artificial experiment, while that of agreement is more especially the resource employed where experimentation is impossible. A few reflections will prove the fact, and point out the reason of it. It is inherent in the peculiar character of the method of difference, that the nature of the combinations which it requires is much more strictly defined than in the method of agreement. The two instances which are to be compared with one another must be exactly similar, in all circumstances except the one which we are attempting to investigate. They must be in the relation of A, B, C and B, C, or of A, B, C and B, C. It is true that this similarity of circumstances needs not extend to such as are already known to be immaterial to the result. And in the case of most phenomena we learn at once, from the commonest experience, that most of the coexistent phenomena of the universe may be either present or absent without affecting the given phenomenon. Or, if present, are present indifferently when the phenomenon does not happen and when it does. Still, even limiting the identity which is required between the two instances, A, B, C and B, C, to such circumstances as are not already known to be indifferent, it is very seldom that nature affords two instances, of which we can be assured that they stand in this precise relation to one another. In the spontaneous operations of nature there is generally such complication and such obscurity, they are mostly either on so overwhelmingly large or on so inaccessibly minute a scale. We are so ignorant of a great part of the facts which really take place, and even those of which we are not ignorant are so multitudinous, and therefore so seldom exactly alike in any two cases, that a spontaneous experiment, of the kind required by the method of difference, is commonly not to be found. When, on the contrary, we obtain a phenomenon by an artificial experiment, a pair of instances such as the method requires is obtained almost as a matter of course, provided the process does not last a long time. A certain state of surrounding circumstances existed before we commenced the experiment, this is BC. We then introduce A. Say, for instance, by merely bringing an object from another part of the room, before there has been time for any change in the other elements. It is, in short, as M. Kant observes, the very nature of an experiment, to introduce into the pre-existing state of circumstances a change perfectly definite. We choose a previous state of things with which we are well acquainted, so that no unforeseen alteration in that state is likely to pass unobserved, and into this we introduce, as rapidly as possible, the phenomenon which we wish to study. So that in general we are entitled to feel complete assurance that the pre-existing state, and the state which we have produced, differ in nothing except the presence or absence of that phenomenon. If a bird is taken from a cage, and instantly plunged into carbonic acid gas, the experimentalist may be fully assured, at all events after one or two repetitions, that no circumstance capable of causing suffocation had supervened in the interim, except the change from immersion in the atmosphere to immersion in carbonic acid gas. There is one doubt, indeed, which may remain in some cases of this description: the effect may have been produced not by the change, but by the means employed to produce the change. The possibility, however, of this last supposition generally admits of being conclusively tested by other experiments. It thus appears that in the study of the various kinds of phenomena which we can, by our voluntary agency, modify or control, we can in general satisfy the requisitions of the method of difference. But that by the spontaneous operations of nature those requisitions are seldom fulfilled. The reverse of this is the case with the method of agreement. We do not here require instances of so special and determinate a kind. Any instances whatever, in which nature presents us with a phenomenon, may be examined for the purposes of this method, and if all such instances agree in anything, a conclusion of considerable value is already attained. We can seldom, indeed, be sure that the one point of agreement is the only one, but this ignorance does not, as in the method of difference, vitiate the conclusion. The certainty of the result, as far as it goes, is not affected. We have ascertained one invariable antecedent or consequent, however many other invariable antecedents or consequents may still remain unascertained. If A, B, C, A, D, E, A, F, G, are all equally followed by A, then A is an invariable consequent of A. If A, B, C, A, D, E, A, F, G, all number A among their antecedents, then A is connected as an antecedent, by some invariable law, with A. But to determine whether this invariable antecedent is a cause, or this invariable consequent an effect, we must be able, in addition, to produce the one by means of the other. Or, at least, to obtain that which alone constitutes our assurance of having produced anything, namely, an instance in which the effect, A, has come into existence, with no other change in the pre-existing circumstances than the addition of A. And this, if we can do it, is an application of the method of difference, not of the method of agreement. It thus appears to be by the method of difference alone that we can ever, in the way of direct experience, arrive with certainty at causes. The method of agreement leads only to laws of phenomena, as some writers call them, but improperly, since laws of causation are also laws of phenomena, that is, to uniformities, which either are not laws of causation, or in which the question of causation must for the present remain undecided. The method of agreement is chiefly to be resorted to, as a means of suggesting applications of the method of difference, as in the last example the comparison of A B C, A D E, A F G, suggested that A was the antecedent on which to try the experiment whether it could produce A. Or as an inferior resource, in case the method of difference is impracticable, which, as we before showed, generally arises from the impossibility of artificially producing the phenomena. And hence it is that the method of agreement, though applicable in principle to either case, is more emphatically the method of investigation on those subjects where artificial experimentation is impossible. Because on those it is, generally, our only resource of a directly inductive nature. While, in the phenomena which we can produce at pleasure, the method of difference generally affords a more efficacious process, which will ascertain causes as well as mere laws. Section 4. There are, however, many cases in which, though our power of producing the phenomenon is complete, the method of difference either cannot be made available at all, or not without a previous employment of the method of agreement. This occurs when the agency by which we can produce the phenomenon is not that of one single antecedent, but a combination of antecedents, which we have no power of separating from each other, and exhibiting apart. For instance, suppose the subject of inquiry to be the cause of the double refraction of light. We can produce this phenomenon at pleasure, by employing any one of the many substances which are known to refract light in that peculiar manner. But if, taking one of those substances, as Iceland spar, for example, we wish to determine on which of the properties of Iceland spar this remarkable phenomenon depends, we can make no use, for that purpose, of the method of difference. For we cannot find another substance precisely resembling Iceland spar except in some one property. The only mode, therefore, of prosecuting this inquiry is that afforded by the method of agreement. By which, in fact, through a comparison of all the known substances which have the property of doubly refracting light, it was ascertained that they agree in the circumstance of being crystalline substances. And though the converse does not hold, though all crystalline substances have not the property of double refraction, it was concluded, with reason, that there is a real connection between these two properties. That either crystalline structure, or the cause which gives rise to that structure, is one of the conditions of double refraction. Out of this employment of the method of agreement arises a peculiar modification of that method, which is sometimes of great avail in the investigation of nature. In cases similar to the above, in which it is not possible to obtain the precise pair of instances which our second canon requires, instances agreeing in every antecedent except A, or in every consequent except A, we may yet be able, by a double employment of the method of agreement, to discover in what the instances which contain A or A differ from those which do not. If we compare various instances in which A occurs, and find that they all have in common the circumstance A, and, as far as can be observed, no other circumstance, the method of agreement, so far, bears testimony to a connection between A and A. In order to convert this evidence of connection into proof of causation by the direct method of difference, we ought to be able, in some one of these instances, as for example, ABC, to leave out A, and observe whether by doing so, A is prevented. Now supposing, what is often the case, that we are not able to try this decisive experiment, yet, provided we can by any means discover what would be its result if we could try it, the advantage will be the same. Suppose, then, that as we previously examined a variety of instances in which A occurred, and found them to agree in containing A, so we now observe a variety of instances in which it does not occur, and find them agree in not containing A. Which establishes, by the method of agreement, the same connection between the absence of A and the absence of A, which was before established between their presence. As, then, it had been shown that whenever A is present A is present, so, it being now shown that when A is taken away A is removed along with it, we have by the one proposition A B C, by the other B C, the positive and negative instances which the method of difference requires. This method may be called the indirect method of difference, or the joint method of agreement and difference, and consists in a double employment of the method of agreement, each proof being independent of the other, and corroborating it. But it is not equivalent to a proof by the direct method of difference. For the requisitions of the method of difference are not satisfied, unless we can be quite sure either that the instances affirmative of A agree in no antecedent whatever but A, or that the instances negative of A agree in nothing but the negation of A. Now, if it were possible, which it never is, to have this assurance, we should not need the joint method, for either of the two sets of instances separately would then be sufficient to prove causation. This indirect method, therefore, can only be regarded as a great extension and improvement of the method of agreement, but not as participating in the more cogent nature of the method of difference. The following may be stated as its canon. Third canon. If two or more instances in which the phenomenon occurs have only one circumstance in common, while two or more instances in which it does not occur have nothing in common save the absence of that circumstance. The circumstance in which alone the two sets of instances differ, is the effect, or the cause, or an indispensable part of the cause, of the phenomenon. We shall presently see that the joint method of agreement and difference constitutes, in another respect not yet adverted to, an improvement upon the common method of agreement, namely, in being unaffected by a characteristic imperfection of that method, the nature of which still remains to be pointed out. But as we cannot enter into this exposition without introducing a new element of complexity into this long and intricate discussion, I shall postpone it to a subsequent chapter, and shall at once proceed to a statement of two other methods, which will complete the enumeration of the means which mankind possess for exploring the laws of nature by specific observation and experience. Section 5. The first of these has been aptly denominated the method of residues. Its principle is very simple. Subducting from any given phenomenon all the portions which, by virtue of preceding inductions, can be assigned to known causes, the remainder will be the effect of the antecedents which had been overlooked, or of which the effect was as yet an unknown quantity. Suppose, as before, that we have the antecedents A B C, followed by the consequence A B C, and that by previous inductions, founded, we will suppose, on the method of difference, we have ascertained the causes of some of these effects, or the effects of some of these causes, and are then surprised that the effect of A is A, and that the effect of B is B. Subtracting the sum of these effects from the total phenomenon, there remains C, which now, without any fresh experiments, we may know to be the effect of C. This method of residues is in truth a peculiar modification of the method of difference. If the instance ABC, ABC, could have been compared with a single instance AB, AB, we should have proved C to be the cause of C, by the common process of the method of difference. In the present case, however, instead of a single instance AB, we have had to study separately the causes A and B, and to infer from the effects which they produce separately what effect they must produce in the case ABC, where they act together. Of the two instances, therefore, which the method of difference requires, the one positive, the other negative, the negative one, or that in which the given phenomenon is absent, is not the direct result of observation and experiment, but has been arrived at by deduction. As one of the forms of the method of difference, the method of residues partakes of its rigorous certainty, provided the previous inductions, those which gave the effects of A and B, were obtained by the same infallible method, and provided we are certain that C is the only antecedent to which the residual phenomenon C can be referred, the only agent of which we had not already calculated and subducted the effect. But as we can never be quite certain of this, the evidence derived from the method of residues is not complete unless we can obtain C artificially, and try it separately, or unless its agency, when once suggested, can be accounted for and proved deductively from known laws. Even with these reservations, the method of residues is one of the most important among our instruments of discovery. Of all the methods of investigating laws of nature, this is the most fertile in unexpected results, often informing us of sequences in which neither the cause nor the effect were sufficiently conspicuous to attract of themselves the attention of observers. The agent C may be an obscure circumstance, not likely to have been perceived unless sought for, nor likely to have been sought for until attention had been awakened by the insufficiency of the obvious causes to account for the whole of the effect. And C may be so disguised by its intermixture with A and B, that it would scarcely have presented itself spontaneously as a subject of separate study. Of these uses of the method, we shall presently cite some remarkable examples. The canon of the method of residues is as follows. Fourth canon. Subduct from any phenomenon such part as is known by previous inductions to be the effect of certain antecedents, and the residue of the phenomenon is the effect of the remaining antecedents. Section 6. There remains a class of laws which it is impracticable to ascertain by any of the three methods which I have attempted to characterize, namely, the laws of those permanent causes, or indestructible natural agents, which it is impossible either to exclude or to isolate, which we can neither hinder from being present, nor contrive that they shall be present alone. It would appear at first sight that we could by no means separate the effects of these agents from the effects of those other phenomena with which they cannot be prevented from coexisting. In respect, indeed, to most of the permanent causes, no such difficulty exists. Since, though we cannot eliminate them as coexisting facts, we can eliminate them as influencing agents, by simply trying our experiment in a local situation beyond the limits of their influence. The pendulum, for example, has its oscillations disturbed by the vicinity of a mountain. We remove the pendulum to a sufficient distance from the mountain, and the disturbance ceases. From these data we can determine by the method of difference the amount of effect due to the mountain. And beyond a certain distance everything goes on precisely as it would do if the mountain exercised no influence whatever, which, accordingly, we, with sufficient reason, conclude to be the fact. The difficulty, therefore, in applying the methods already treated of to determine the effects of permanent causes, is confined to the cases in which it is impossible for us to get out of the local limits of their influence. The pendulum can be removed from the influence of the mountain, but it cannot be removed from the influence of the earth. We cannot take away the earth from the pendulum, nor the pendulum from the earth. To ascertain whether it would continue to vibrate if the action which the earth exerts upon it were withdrawn. On what evidence, then, do we ascribe its vibrations to the earth's influence? Not on any sanctioned by the method of difference, for one of the two instances, the negative instance, is wanting. Nor by the method of agreement. For though all pendulums agree in this, that during their oscillations the earth is always present, why may we not as well ascribe the phenomenon to the sun, which is equally a coexistent fact in all the experiments? It is evident that to establish even so simple a fact of causation as this, there was required some method over and above those which we have yet examined. As another example, let us take the phenomenon heat. Independently of all hypothesis as to the real nature of the agency so called, this fact is certain, that we are unable to exhaust any body of the whole of its heat. It is equally certain that no one ever perceived heat not emanating from a body. Being unable, then, to separate body and heat, we cannot effect such a variation of circumstances as the foregoing three methods require. We cannot ascertain, by those methods, what portion of the phenomena exhibited by any body is due to the heat contained in it. If we could observe a body with its heat, and the same body entirely divested of heat, the method of difference would show the effect due to the heat, apart from that due to the body. If we could observe heat under circumstances agreeing in nothing but heat, and therefore not characterized also by the presence of a body, we could ascertain the effects of heat. From an instance of heat with a body and an instance of heat without a body, by the method of agreement. Or we could determine by the method of difference what effect was due to the body, when the remainder which was due to the heat would be given by the method of residues. But we can do none of these things. And without them the application of any of the three methods to the solution of this problem would be illusory. It would be idle, for instance, to attempt to ascertain the effect of heat by subtracting from the phenomena exhibited by a body all that is due to its other properties. For as we have never been able to observe any bodies without a portion of heat in them, effects due to that heat might form a part of the very results which we were effecting to subtract. In order that the effect of heat might be shown by the residue. If, therefore, there were no other methods of experimental investigation than these three, we should be unable to determine the effects due to heat as a cause. But we have still a resource. Though we cannot exclude an antecedent altogether, we may be able to produce, or nature may produce for us some modification in it. By a modification is here meant, a change in it not amounting to its total removal. If some modification in the antecedent A is always followed by a change in the consequent A, the other consequents B and C remaining the same. Or vice versa, if every change in A is found to have been preceded by some modification in A, none being observable in any of the other antecedents, we may safely conclude that A is, wholly or in part, an effect traceable to A. Or at least in some way connected with it through causation. For example, in the case of heat, though we cannot expel it altogether from any body, we can modify it in quantity, we can increase or diminish it. And doing so, we find by the various methods of experimentation or observation already treated of, that such increase or diminution of heat is followed by expansion or contraction of the body. In this manner we arrive at the conclusion, otherwise unattainable by us, that one of the effects of heat is to enlarge the dimensions of bodies, or, what is the same thing in other words, to widen the distances between their particles. A change in a thing, not amounting to its total removal, that is, a change which leaves it still the same thing it was, must be a change either in its quantity, or in some of its variable relations to other things. Of which variable relations the principal is its position in space. In the previous example, the modification which was produced in the antecedent was an alteration in its quantity. Let us now suppose the question to be, what influence the moon exerts on the surface of the earth. We cannot try an experiment in the absence of the moon, so as to observe what terrestrial phenomena her annihilation would put an end to. But when we find that all the variations in the position of the moon are followed by corresponding variations in the time and place of high water, the place being always either the part of the earth which is nearest to, or that which is most remote from, the moon, we have ample evidence that the moon is, wholly or partially, the cause which determines the tides. It very commonly happens, as it does in this instance, that the variations of an effect are correspondent, or analogous, to those of its cause. As the moon moves farther toward the east, the high water point does the same, but this is not an indispensable condition, as may be seen in the same example. For along with that high water point there is at the same instant another high water point diametrically opposite to it, and which, therefore, of necessity, moves toward the west, as the moon, followed by the nearer of the tide waves, advances toward the east, and yet both these motions are equally effects of the moon's motion. That the oscillations of the pendulum are caused by the earth, is proved by similar evidence. Those oscillations take place between equidistant points on the two sides of a line, which, being perpendicular to the earth, varies with every variation in the earth's position either in space or relatively to the object. Speaking accurately, we only know by the method now characterized, that all terrestrial bodies tend to the earth, and not to some unknown fixed point lying in the same direction. In every 24 hours, by the earth's rotation, the line drawn from the body at right angles to the earth coincides successively with all the radii of a circle. And in the course of 6 months the place of that circle varies by nearly 200 millions of miles. Yet in all these changes of the earth's position, the line in which bodies tend to fall continues to be directed toward it, which proves that terrestrial gravity is directed to the earth, and not, as was once fancied by some, to a fixed point of space. The method by which these results were obtained may be termed the method of concomitant variations. It is regulated by the following canon. Fifth canon. Whatever phenomenon varies in any manner whenever another phenomenon varies in some particular manner, is either a cause or an effect of that phenomenon, or is connected with it through some fact of causation. The last clause is subjoined, because it by no means follows when two phenomena accompany each other in their variations, that the one is cause and the other effect. The same thing may, and indeed must happen, supposing them to be two different effects of a common cause, and by this method alone it would never be possible to ascertain which of the suppositions is the true one. The only way to solve the doubt would be that which we have so often adverted to, viz., by endeavoring to ascertain whether we can produce the one set of variations by means of the other. In the case of heat, for example, by increasing the temperature of a body we increase its bulk, but by increasing its bulk we do not increase its temperature. On the contrary, as in the rarefaction of air under the receiver of an air pump, we generally diminish it, therefore heat is not an effect, but a cause, of increase of bulk. If we cannot ourselves produce the variations, we must endeavor, though it is an attempt which is seldom successful, to find them produced by nature in some case in which the pre-existing circumstances are perfectly known to us. It is scarcely necessary to say, that in order to ascertain the uniform concomitance of variations in the effect with variations in the cause, the same precautions must be used as in any other case of the determination of an invariable sequence. We must endeavor to retain all the other antecedents unchanged, while that particular one is subjected to the requisite series of variations. Or, in other words, that we may be warranted in inferring causation from concomitance of variations, the concomitance itself must be proved by the method of difference. It might at first appear that the method of concomitant variations assumes a new axiom, or law of causation in general, namely, that every modification of the cause is followed by a change in the effect. And it does usually happen that when a phenomenon A causes a phenomenon A, any variation in the quantity or in the various relations of A, is uniformly followed by a variation in the quantity or relations of A. To take a familiar instance, that of gravitation. The sun causes a certain tendency to motion in the earth, here we have cause and effect. But that tendency is toward the sun, and therefore varies in direction as the sun varies in the relation of position. And, moreover, the tendency varies in intensity, in a certain numerical correspondence to the sun's distance from the earth, that is, according to another relation of the sun. Thus we see that there is not only an invariable connection between the sun and the earth's gravitation, but that two of the relations of the sun, its position with respect to the earth and its distance from the earth, are invariably connected as antecedents with the quantity and direction of the earth's gravitation. The cause of the earth's gravitating at all, is simply the sun, but the cause of its gravitating with a given intensity and in a given direction, is the existence of the sun in a given direction and at a given distance. It is not strange that a modified cause, which is in truth a different cause, should produce a different effect. Although it is for the most part true that a modification of the cause is followed by a modification of the effect, the method of concomitant variations does not, however, presuppose this as an axiom. It only requires the converse proposition, that anything on whose modifications of an effect are invariably consequent, must be the cause, or connected with the cause, of that effect, a proposition, the truth of which is evident. For if the thing itself had no influence on the effect, neither could the modifications of the thing have any influence. If the stars have no power over the fortunes of mankind, it is implied in the very terms that the conjunctions or oppositions of different stars can have no such power. Although the most striking applications of the method of concomitant variations take place in the cases in which the method of difference, strictly so called, is impossible, its use is not confined to those cases. It may often usefully follow after the method of difference, to give additional precision to a solution which that has found. When by the method of difference it has first been ascertained that a certain object produces a certain effect, the method of concomitant variations may be usefully called in. To determine according to what law the quantity or the different relations of the effect follow those of the cause. Section 7. The case in which this method admits of the most extensive employment, is that in which the variations of the cause are variations of quantity. Of such variations we may in general affirm with safety, that they will be attended not only with variations, but with similar variations, of the effect, the proposition that more of the cause is followed by more of the effect. Being a corollary from the principle of the composition of causes, which, as we have seen, is the general rule of causation. Cases of the opposite description, in which causes change their properties on being conjoined with one another, being, on the contrary, special and exceptional. Suppose, then, that when a changes in quantity, A also changes in quantity, and in such a manner that we can trace the numerical relation which the changes of the one bear to such changes of the other as take place within our limits of observation. We may then, with certain precautions, safely conclude that the same numerical relation will hold beyond those limits. If, for instance, we find that when A is double, A is double, that when A is treble or quadruple, A is treble or quadruple. We may conclude that if A were a half or a third, would be a half or a third, and finally, that if A were annihilated, A would be annihilated, and that A is wholly the effect of A, or wholly the effect of the same cause with A. And so with any other numerical relation according to which A and A would vanish simultaneously, as, for instance, if A were proportional to the square of A. If, on the other hand, A is not wholly the effect of A, but yet varies when A varies, it is probably a mathematical function not of A alone, but of A in something else. Its changes, for example, may be such as would occur if part of it remained constant, or varied on some other principle, and the remainder varied in some numerical relations to the variations of A. In that case, when A diminishes, A will be seen to approach not toward zero, but toward some other limit. And when the series of variations is such as to indicate what that limit is, if constant, or the law of its variation, if variable, the limit will exactly measure how much of A is the effect of some other and independent cause. And the remainder will be the effect of A, or of the cause of A. These conclusions, however, must not be drawn without certain precautions. In the first place, the possibility of drawing them at all, manifestly supposes that we are acquainted not only with the variations, but with the absolute quantities both of A and A. If we do not know the total quantities, we cannot, of course, determine the real numerical relation according to which those quantities vary. It is, therefore, an error to conclude, as some have concluded, that because increase of heat expands bodies, that is, increases the distance between their particles, therefore the distance is wholly the effect of heat. And that if we could entirely exhaust the body of its heat, the particles would be in complete contact. This is no more than a guess, and of the most hazardous sort, not a legitimate induction, for since we neither know how much heat there is in any body, nor what is the real distance between any two of its particles, we cannot judge whether the contraction of the distance does or does not follow the diminution of the quantity of heat according to such a numerical relation that the two quantities would vanish simultaneously. In contrast with this, let us consider a case in which the absolute quantities are known, the case contemplated in the first law of motion, viz. that all bodies in motion continue to move in a straight line with uniform velocity until acted upon by some new force. This assertion is in open opposition to first appearances. All terrestrial objects, when in motion, gradually abate their velocity, and at last stop, which accordingly the ancients, with their inductio per enumerationem simplicem, imagined to be the law. Every moving body, however, encounters various obstacles, as friction, the resistance of the atmosphere, etc., which we know by daily experience to be causes capable of destroying motion. It was suggested that the whole of the retardation might be owing to these causes. How was this inquired into? If the obstacles could have been entirely removed, the case would have been amenable to the method of difference. They could not be removed, they could only be diminished, and the case, therefore, admitted only of the method of concomitant variations. This accordingly being employed, it was found that every diminution of the obstacles diminished the retardation of the motion, and inasmuch as in this case, unlike the case of heat, the total quantities both of the antecedent and of the consequent were known, it was practicable to estimate, with an approach to accuracy, both the amount of the retardation and the amount of the retarding causes, or resistances, and to judge how near they both were to being exhausted. And it appeared that the effect dwindled as rapidly, and at each step was as far on the road toward annihilation, as the cause was. The simple oscillation of a weight suspended from a fixed point, and moved a little out of the perpendicular, which in ordinary circumstances lasts but a few minutes, was prolonged in Borda's experiments to more than 30 hours. By diminishing as much as possible the friction at the point of suspension, and by making the body oscillate in a space exhausted as nearly as possible of its air. There could therefore be no hesitation in assigning the whole of the retardation of motion to the influence of the obstacles. And since, after subducting this retardation from the total phenomenon, the remainder was a uniform velocity, the result was the proposition known as the first law of motion. There is also another characteristic uncertainty affecting the inference that the law of variation which the quantities observe within our limits of observation, will hold beyond those limits. There is, of course, in the first instance, the possibility that beyond the limits, and in circumstances therefore of which we have no direct experience, some counteracting cause might develop itself. Either a new agent or a new property of the agents concerned, which lies dormant in the circumstances we are able to observe. This is an element of uncertainty which enters largely into all our predictions of effects. But it is not peculiarly applicable to the method of concomitant variations. The uncertainty, however, of which I am about to speak, is characteristic of that method. Especially in the cases in which the extreme limits of our observation are very narrow, in comparison with the possible variations in the quantities of the phenomena. Anyone who has the slightest acquaintance with mathematics, is aware that very different laws of variation may produce numerical results which differ but slightly from one another within narrow limits. And it is often only when the absolute amounts of variation are considerable, that the difference between the results given by one law and by another becomes appreciable. When, therefore, such variations in the quantity of the antecedents as we have the means of observing are small in comparison with the total quantities, there is much danger lest we should mistake the numerical law, and be led to miscalculate the variations which would take place beyond the limits. A miscalculation which would vitiate any conclusion respecting the dependence of the effect upon the cause, that could be founded on those variations. Examples are not wanting of such mistakes. The formulae, says Sir John Herschel 136, which have been empirically deduced for the elasticity of steam, till very recently, and those for the resistance of fluids, and other similar subjects, when relied on beyond the limits of the observations from which they were deduced, have almost invariably failed to support the theoretical structures which have been erected on them. In this uncertainty, the conclusion we may draw from the concomitant variations of A and A, to the existence of an invariable and exclusive connection between them, or to the permanency of the same numerical relation between their variations when the quantities are much greater or smaller than those which we have had the means of observing, cannot be considered to rest on a complete induction. All that in such a case can be regarded as proved on the subject of causation is, that there is some connection between the two phenomena, that A, or something which can influence A, must be one of the causes which collectively determine A. We may, however, feel assured that the relation which we have observed to exist between the variations of A and A, will hold true in all cases which fall between the same extreme limits. That is, wherever the utmost increase or diminution in which the result has been found by observation to coincide with the law, is not exceeded. The four methods which it has now been attempted to describe, are the only possible modes of experimental inquiry, of direct induction a posteriori, as distinguished from deduction. At least, I know not, nor am able to imagine any others. And even of these, the method of residues, as we have seen, is not independent of deduction, though, as it also requires specific experience, it may, without impropriety, be included among methods of direct observation and experiment. These, then, with such assistance as can be obtained from deduction, compose the available resources of the human mind for ascertaining the laws of the succession of phenomena. Before proceeding to point out certain circumstances by which the employment of these methods is subjected to an immense increase of complication and of difficulty, it is expedient to illustrate the use of the methods by suitable examples drawn from actual physical investigations. These, accordingly, will form the subject of the succeeding chapter. 9. Miscellaneous examples of the four methods. Section 1. I shall select, as a first example, an interesting speculation of one of the most eminent of theoretical chemists, Baron Liebig. The object in view is to ascertain the immediate cause of the death produced by metallic poisons. Arsenious acid, and the salts of lead, bismuth, copper, and mercury, if introduced into the animal organism, except in the smallest doses, destroy life. These facts have long been known, as insulated truths of the lowest order of generalization. But it was reserved for Liebig, by an apt employment of the first two of our methods of experimental inquiry, to connect these truths together by a higher induction, pointing out what property, common to all these deleterious substances, is the really operating cause of their fatal effect. When solutions of these substances are placed in sufficiently close contact with many animal products, albumin, milk, muscular fiber, and animal membranes, the acid or salt leaves the water in which it was dissolved, and enters into combination with the animal substance, which substance, after being thus acted upon, is found to have lost its tendency to spontaneous decomposition, or putrefaction. Observation also shows, in cases where death has been produced by these poisons, that the parts of the body with which the poisonous substances have been brought into contact, do not afterward putrefy. And, finally, when the poison has been supplied in too small a quantity to destroy life, eschars are produced, that is, certain superficial portions of the tissues are destroyed, which are afterward thrown off by the reparative process taking place in the healthy parts. These three sets of instances admit of being treated according to the method of agreement. In all of them the metallic compounds are brought into contact with the substances which compose the human or animal body. And the instances do not seem to agree in any other circumstance. The remaining antecedents are as different, and even opposite, as they could possibly be made. For in some the animal substances exposed to the action of the poisons are in a state of life, in others only in a state of organization, in others not even in that. And what is the result which follows in all the cases? The conversion of the animal substance, by combination with the poison, into a chemical compound, held together by so powerful a force as to resist the subsequent action of the ordinary causes of decomposition. Now, organic life, the necessary condition of sensitive life, consisting in a continual state of decomposition and recomposition of the different organs and tissues, whatever incapacitates them for this decomposition destroys life. And thus the proximate cause of the death produced by this description of poisons is ascertained, as far as the method of agreement can ascertain it. Let us now bring our conclusion to the test of the method of difference. Setting out from the cases already mentioned, in which the antecedent is the presence of substances forming with the tissues a compound incapable of putrefaction, and a fortiori incapable of the chemical actions which constitute life. And the consequent is death, either of the whole organism, or of some portion of it. Let us compare with these cases other cases, as much resembling them as possible, but in which that effect is not produced. And, first, many insoluble basic salts of arsenious acid are known not to be poisonous. The substance called alcargen, discovered by Bunsen, which contains a very large quantity of arsenic, and approaches very closely in composition to the organic arsenious compounds found in the body, has not the slightest injurious action upon the organism. Now when these substances are brought into contact with the tissues in any way, they do not combine with them, they do not arrest their progress to decomposition. As far, therefore, as these instances go, it appears that when the effect is absent, it is by reason of the absence of that antecedent which we had already good ground for considering as the proximate cause. But the rigorous conditions of the method of difference are not yet satisfied. For we cannot be sure that these unpoisonous bodies agree with the poisonous substances in every property, except the particular one of entering into a difficultly decomposable compound with the animal tissues. To render the method strictly applicable, we need an instance, not of a different substance, but of one of the very same substances, in circumstances which would prevent it from forming, with the tissues, the sort of compound in question. And then, if death does not follow, our case is made out. Now such instances are afforded by the antidotes to these poisons. For example, in case of poisoning by arsenious acid, if hydrated peroxide of iron is administered, the destructive agency is instantly checked. Now this peroxide is known to combine with the acid, and form a compound, which, being insoluble, cannot act at all on animal tissues. So, again, sugar is a well-known antidote to poisoning by salts of copper. And sugar reduces those salts either into metallic copper, or into the red suboxide, neither of which enters into combination with animal matter. The disease called painter's colic, so common in manufactories of white lead, is unknown where the workmen are accustomed to take, as a preservative, sulfuric acid lemonade, a solution of sugar rendered acid by sulfuric acid. Now diluted sulfuric acid has the property of decomposing all compounds of lead with organic matter, or of preventing them from being formed. There is another class of instances, of the nature required by the method of difference, which seem at first sight to conflict with the theory. Soluble salts of silver, such for instance as the nitrate, have the same stiffening antiseptic effect on decomposing animal substances as corrosive sublimate and the most deadly metallic poisons. And when applied to the external parts of the body, the nitrate is a powerful caustic, depriving those parts of all active vitality, and causing them to be thrown off by the neighboring living structures, in the form of an eschar. The nitrate and the other salts of silver ought, then, it would seem, if the theory be correct, to be poisonous, yet they may be administered internally with perfect impunity. From this apparent exception arises the strongest confirmation which the theory has yet received. Nitrate of silver, in spite of its chemical properties, does not poison when introduced into the stomach. But in the stomach, as in all animal liquids, there is common salt, and in the stomach there is also free muriatic acid. These substances operate as natural antidotes, combining with the nitrate, and if its quantity is not too great, immediately converting it into chloride of silver, a substance very slightly soluble, and therefore incapable of combining with the tissues, although to the extent of its solubility it has a medicinal influence, though an entirely different class of organic actions. The preceding instances have afforded an induction of a high order of conclusiveness, illustrative of the two simplest of our four methods, though not rising to the maximum of certainty which the method of difference, in its most perfect exemplification, is capable of affording. For, let us not forget, the positive instance and the negative one which the rigor of that method requires, ought to differ only in the presence or absence of one single circumstance. Now, in the preceding argument, they differ in the presence or absence not of a single circumstance, but of a single substance, and as every substance has innumerable properties, there is no knowing what number of real differences are involved in what is nominally and apparently only one difference. It is conceivable that the antidote, the peroxide of iron for example, may counteract the poison through some other of its properties than that of forming an insoluble compound with it. And if so, the theory would fall to the ground, so far as it is supported by that instance. This source of uncertainty, which is a serious hindrance to all extensive generalizations in chemistry, is, however, reduced in the present case to almost the lowest degree possible, when we find that not only one substance, but many substances possess the capacity of acting as antidotes to metallic poisons, and that all these agree in the property of forming insoluble compounds with the poisons, while they cannot be ascertained to agree in any other property whatsoever. We have thus, in favor of the theory, all the evidence which can be obtained by what we term the indirect method of difference, or the joint method of agreement in difference. The evidence of which, though it never can amount to that of the method of difference properly so called, may approach indefinitely near to it. Section 2. Let the object be 137 to ascertain the law of what is termed induced electricity. To find under what conditions any electrified body, whether positively or negatively electrified, gives rise to a contrary electric state in some other body adjacent to it. The most familiar exemplification of the phenomenon to be investigated is the following. Around the prime conductors of an electrical machine the atmosphere to some distance, or any conducting surface suspended in that atmosphere, is found to be in an electric condition opposite to that of the prime conductor itself. Near and around the positive prime conductor there is negative electricity, and near and around the negative prime conductor there is positive electricity. When pith balls are brought near to either of the conductors, they become electrified with the opposite electricity to it. Either receiving a share from the already electrified atmosphere by conduction, or acted upon by the direct inductive influence of the conductor itself, they are then attracted by the conductor to which they are in opposition. Or, if withdrawn in their electrified state, they will be attracted by any other oppositely charged body. In like manner the hand, if brought near enough to the conductor, receives or gives an electric discharge. Now we have no evidence that a charged conductor can be suddenly discharged unless by the approach of a body oppositely electrified. In the case, therefore, of the electric machine, it appears that the accumulation of electricity in an insulated conductor is always accompanied by the excitement of the contrary electricity in the surrounding atmosphere. And in every conductor placed near the former conductor. It does not seem possible, in this case, to produce one electricity by itself. Let us now examine all the other instances which we can obtain, resembling this instance in the given consequent, namely, the evolution of an opposite electricity in the neighborhood of an electrified body. As one remarkable instance we have the Leyden jar. And after the splendid experiments of Faraday in complete and final establishment of the substantial identity of magnetism and electricity, we may cite the magnet, both the natural and the electromagnet. In neither of which it is possible to produce one kind of electricity by itself, or to charge one pole without charging an opposite pole with the contrary electricity at the same time. We cannot have a magnet with one pole. If we break a natural lodestone into 1,000 pieces, each piece will have its two oppositely electrified poles complete within itself. In the voltaic circuit, again, we cannot have one current without its opposite. In the ordinary electric machine, the glass cylinder or plate, and the rubber, acquire opposite electricities. From all these instances, treated by the method of agreement, a general law appears to result. The instances embrace all the known modes in which a body can become charged with electricity. And in all of them there is found, as a concomitant or consequent, the excitement of the opposite electric state in some other body or bodies. It seems to follow that the two facts are invariably connected. And that the excitement of electricity in any body has for one of its necessary conditions the possibility of a simultaneous excitement of the opposite electricity in some neighboring body. As the two contrary electricities can only be produced together, so they can only cease together. This may be shown by an application of the method of difference to the example of the Leyden jar. It need scarcely be here remarked that in the Leyden jar, electricity can be accumulated and retained in considerable quantity, by the contrivance of having two conducting surfaces of equal extent, and parallel to each other through the whole of that extent, with a non-conducting substance such as glass between them. When one side of the jar is charged positively, the other is charged negatively, and it was by virtue of this fact that the Leyden jar served just now as an instance in our employment of the method of agreement. Now it is impossible to discharge one of the coatings unless the other can be discharged at the same time. A conductor held to the positive side cannot convey away any electricity unless an equal quantity be allowed to pass from the negative side. If one coating be perfectly insulated, the charge is safe. The dissipation of one must proceed pari passu with that of the other. The law thus strongly indicated admits of corroboration by the method of concomitant variations. The Leyden jar is capable of receiving a much higher charge than can ordinarily be given to the conductor of an electrical machine. Now in the case of the Leyden jar, the metallic surface which receives the induced electricity is a conductor exactly similar to that which receives the primary charge, and is therefore as susceptible of receiving and retaining the one electricity as the opposite surface of receiving and retaining the other. But in the machine, the neighboring body which is to be oppositely electrified is the surrounding atmosphere, or any body casually brought near to the conductor. And as these are generally much inferior in their capacity of becoming electrified, to the conductor itself, their limited power imposes a corresponding limit to the capacity of the conductor for being charged. As the capacity of the neighboring body for supporting the opposition increases, a higher charge becomes possible, and to this appears to be owing the great superiority of the Leyden jar. A further and most decisive confirmation by the method of difference is to be found in one of Faraday's experiments in the course of his researches on the subject of induced electricity. Since common or machine electricity, and voltaic electricity, may be considered for the present purpose to be identical, Faraday wished to know whether, as the prime conductor develops opposite electricity upon a conductor in its vicinity, so a voltaic current running along a wire would induce an opposite current upon another wire laid parallel to it at a short distance. Now this case is similar to the cases previously examined, in every circumstance except the one to which we have ascribed the effect. We found in the former instances that whenever electricity of one kind was excited in one body, electricity of the opposite kind must be excited in a neighboring body. But in Faraday's experiment this indispensable opposition exists within the wire itself. From the nature of a voltaic charge, the two opposite currents necessary to the existence of each other are both accommodated in one wire. And there is no need of another wire placed beside it to contain one of them, in the same way as the Leyden jar must have a positive and a negative surface. The exciting cause can and does produce all the effect which its laws require, independently of any electric excitement of a neighboring body. Now the result of the experiment with the second wire was, that no opposite current was produced. There was an instantaneous effect at the closing and breaking of the voltaic circuit, electric inductions appeared when the two wires were moved to and from one another, but these are phenomena of a different class. There was no induced electricity in the sense in which this is predicated of the Leyden jar. There was no sustained current running up the one wire while an opposite current ran down the neighboring wire. And this alone would have been a true parallel case to the other. It thus appears by the combined evidence of the method of agreement, the method of concomitant variations, and the most rigorous form of the method of difference, that neither of the two kinds of electricity can be excited without an equal excitement of the other and opposite kind, that both are effects of the same cause, that the possibility of the one is a condition of the possibility of the other, and the quantity of the one an impassable limit to the quantity of the other. A scientific result of considerable interest in itself, and illustrating those three methods in a manner both characteristic and easily intelligible. 138. Section 3. Our third example shall be extracted from Sir John Herschel's Discourse Course on the Study of Natural Philosophy, a work replete with happily selected exemplifications of inductive processes from almost every department of physical science, and in which alone, of all books which I have met with, the four methods of induction are distinctly recognized, though not so clearly characterized and defined, nor their correlation so fully shown, as has appeared to me desirable. The present example is described by Sir John Herschel as one of the most beautiful specimens, which can be cited, of inductive experimental inquiry lying within a moderate compass, the theory of dew, first promulgated by the late Dr. Wells, and now universally adopted by scientific authorities. The passages in inverted commas are extracted verbatim from the Discourse. 139. Suppose dew were the phenomenon proposed, whose cause we would know. In the first place, we must determine precisely what we mean by dew, what the fact really is whose cause we desire to investigate. We must separate dew from rain, and the moisture of fogs, and limit the application of the term to what is really meant, which is the spontaneous appearance of moisture on substances exposed in the open air when no rain or visible wet is falling. This answers to a preliminary operation which will be characterized in the ensuing book, treating of operations subsidiary to induction. 140. Now, here we have analogous phenomena in the moisture which bedews a cold metal or stone when we breathe upon it, that which appears on a glass of water fresh from the well in hot weather, that which appears on the inside of windows when sudden rain or hail chills the external air, that which runs down our walls when, after a long frost, a warm, moist thaw comes on. Comparing these cases, we find that they all contain the phenomenon which was proposed as the subject of investigation. Now, all these instances agree in one point, the coldness of the object dewed, in comparison with the air in contact with it. But there still remains the most important case of all, that of nocturnal dew. Does the same circumstance exist in this case? Is it a fact that the object dewed is colder than the air? Certainly not. one would at first be inclined to say. For what is to make it so? But, the experiment is easy. We have only to lay a thermometer in contact with the dewed substance, and hang one at a little distance above it, out of reach of its influence. The experiment has been therefore made, the question has been asked, and the answer has been invariably in the affirmative. Whenever an object contracts dew, it is colder than the air. Here, then, is a complete application of the method of agreement, establishing the fact of an invariable connection between the deposition of dew on a surface, and the coldness of that surface compared with the external air. But which of these is cause, and which effect? Or are they both effects of something else? On this subject the method of agreement can afford us no light, we must call in a more potent method. We must collect more facts, or, which comes to the same thing, vary the circumstances, since every instance in which the circumstances differ is a fresh fact, and especially, we must note the contrary or negative cases, i.e. where no dew is produced, a comparison between instances of dew and instances of no dew, being the condition necessary to bring the method of difference into play. Now, first, no dew is produced on the surface of polished metals, but it is very copiously on glass, both exposed with their faces upward, and in some cases the underside of a horizontal plate of glass is also dewed. Here is an instance in which the effect is produced, and another instance in which it is not produced. But we cannot yet pronounce, as the canon of the method of difference requires, that the latter instance agrees with the former in all its circumstances except one. For the differences between glass and polished metals are manifold, and the only thing we can as yet be sure of is, that the cause of dew will be found among the circumstances by which the former substance is distinguished from the latter. But if we could be sure that glass, and the various other substances on which dew is deposited, have only one quality in common, and that polished metals and the other substances on which dew is not deposited have also nothing in common but the one circumstance of not having the one quality which the others have, the requisitions of the method of difference would be completely satisfied, and we should recognize, in that quality of the substances, the cause of dew. This, accordingly, is the path of inquiry which is next to be pursued. In the cases of polished metal and polished glass, the contrast shows evidently that the substance has much to do with the phenomenon. Therefore let the substance alone be diversified as much as possible, by exposing polished surfaces of various kinds. This done, a scale of intensity becomes obvious. Those polished substances are found to be most strongly dewed which conduct heat worst, while those which conduct heat well, resist dew most effectually. The complication increases. Here is the method of concomitant variations called to our assistance, and no other method was practicable on this occasion, for the quality of conducting heat could not be excluded, since all substances conduct heat in some degree. The conclusion obtained is, that caeteris paribus the deposition of dew is in some proportion to the power which the body possesses of resisting the passage of heat. And that this, therefore, or something connected with this, must be at least one of the causes which assist in producing the deposition of dew on the surface. But if we expose rough surfaces instead of polished, we sometimes find this law interfered with. Thus, roughened iron, especially if painted over or blackened, becomes dewed sooner than varnished paper. The kind of surface, therefore, has a great influence. Expose, then, the same material in very diversified states, as to surface, that is, employ the method of difference to ascertain concomitants of variations, and another scale of intensity becomes at once apparent. Those surfaces which part with their heat most readily by radiation are found to contract dew most copiously. Here, therefore, are the requisites for a second employment of the method of concomitant variations, which in this case also is the only method available, since all substances radiate heat in some degree or other. The conclusion obtained by this new application of the method is, that caeteris paribus the deposition of dew is also in some proportion to the power of radiating heat. And that the quality of doing this abundantly, or some cause on which that quality depends, is another of the causes which promote the deposition of dew on the substance. Again, the influence ascertained to exist of substance and surface leads us to consider that of texture, and here, again, we are presented on trial with remarkable differences, and with a third scale of intensity. Pointing out substances of a close, firm texture, such as stones, metals, etc., as unfavorable, but those of a loose one, as cloth, velvet, wool, eiderdown, cotton, etc., as eminently favorable to the contraction of dew. The method of concomitant variations is here, for the third time, had recourse to. And, as before, from necessity, since the texture of no substance is absolutely firm or absolutely loose. Looseness of texture, therefore, or something which is the cause of that quality, is another circumstance which promotes the deposition of dew. But this third course resolves itself into the first, viz. The quality of resisting the passage of heat, for substances of loose texture, are precisely those which are best adapted for clothing, or for impeding the free passage of heat from the skin into the air, so as to allow their outer surfaces to be very cold, while they remain warm within. And this last is, therefore, an induction, from fresh instances, simply corroborative of a former induction. It thus appears that the instances in which much dew is deposited, which are very various, agree in this, and, so far as we are able to observe, in this only, that they either radiate heat rapidly or conduct it slowly, qualities between which there is no other circumstance of agreement than that by virtue of either the body tends to lose heat from the surface more rapidly than it can be restored from within. The instances, on the contrary, in which no dew, or but a small quantity of it, is formed, and which are also extremely various, agree, as far as we can observe, in nothing except in not having this same property. We seem, therefore, to have detected the characteristic difference between the substances on which dew is produced and those on which it is not produced. And thus have been realized the requisitions of what we have termed the indirect method of difference, or the joint method of agreement and difference. The example afforded of this indirect method, and of the manner in which the data are prepared for it by the methods of agreement and of concomitant variations, is the most important of all the illustrations of induction afforded by this interesting speculation. We might now consider the question, on what the deposition of dew depends, to be completely solved, if we could be quite sure that the substances on which dew is produced differ from those on which it is not. In nothing but in the property of losing heat from the surface faster than the loss can be repaired from within. And though we never can have that complete certainty, this is not of so much importance as might at first be supposed. For we have, at all events, ascertained that even if there be any other quality hitherto unobserved which is present in all the substances which contract dew, and absent in those which do not, this other property must be one which, in all that great number of substances, is present or absent exactly where the property of being a better radiator than conductor is present or absent. An extent of coincidence which affords a strong presumption of a community of cause, and a consequent invariable coexistence between the two properties. So that the property of being a better radiator than conductor, if not itself the cause, almost certainly always accompanies the cause, and for purposes of prediction, no error is likely to be committed by treating it as if it were really such. Reverting now to an earlier stage of the inquiry, let us remember that we had ascertained that, in every instance where dew is formed, there is actual coldness of the surface below the temperature of the surrounding air. But we were not sure whether this coldness was the cause of dew, or its effect. This doubt we are now able to resolve. We have found that, in every such instance, the substance is one which, by its own properties or laws, would, if exposed in the night, become colder than the surrounding air. The coldness, therefore, being accounted for independently of the dew, while it is proved that there is a connection between the two, it must be the dew which depends on the coldness, or, in other words, the coldness is the cause of the dew. This law of causation, already so amply established, admits, however, of efficient additional corroboration in no less than 3 ways. First, by deduction from the known laws of aqueous vapor when diffused through air or any other gas. And though we have not yet come to the deductive method, we will not omit what is necessary to render this speculation complete. It is known by direct experiment that only a limited quantity of water can remain suspended in the state of vapor at each degree of temperature, and that this maximum grows less and less as the temperature diminishes. From this it follows, deductively, that if there is already as much vapor suspended as the air will contain at its existing temperature, any lowering of that temperature will cause a portion of the vapor to be condensed and become water. But again, we know deductively, from the laws of heat, that the contact of the air with a body colder than itself will necessarily lower the temperature of the stratum of air immediately applied to its surface. And will, therefore, cause it to part with a portion of its water, which accordingly will, by the ordinary laws of gravitation or cohesion, attach itself to the surface of the body, thereby constituting dew. This deductive proof, it will have been seen, has the advantage of at once proving causation as well as coexistence. And it has the additional advantage that it also accounts for the exceptions to the occurrence of the phenomenon, the cases in which, although the body is colder than the air, yet no dew is deposited. By showing that this will necessarily be the case when the air is so undersupplied with aqueous vapor, comparatively to its temperature, that even when somewhat cooled by the contact of the colder body it can still continue to hold in suspension all the vapor which was previously suspended in it. Thus in a very dry summer there are no dews, in a very dry winter no hoarfrost. Here, therefore, is an additional condition of the production of dew, which the methods we previously made use of failed to detect, and which might have remained still undetected, if recourse had not been had to the plan of deducing the effect from the ascertained properties of the agents known to be present. The second corroboration of the theory is by direct experiment, according to the canon of the method of difference. We can, by cooling the surface of any body, find in all cases some temperature, more or less inferior to that of the surrounding air, according to its hygrometric condition, at which dew will begin to be deposited. Here, too, therefore, the causation is directly proved. We can, it is true, accomplish this only on a small scale, but we have ample reason to conclude that the same operation, if conducted in nature's great laboratory, would equally produce the effect. And, finally, even on that great scale we are able to verify the result. The case is one of those rare cases, as we have shown them to be, in which nature works the experiment for us in the same manner in which we ourselves perform it. Introducing into the previous state of things a single and perfectly definite new circumstance, and manifesting the effect so rapidly that there is not time for any other material change in the pre-existing circumstances. It is observed that dew is never copiously deposited in situations much screened from the open sky, and not at all in a cloudy night. But if the clouds withdraw even for a few minutes, and leave a clear opening, a deposition of dew presently begins, and goes on increasing. Dew formed in clear intervals will often even evaporate again when the sky becomes thickly overcast. The proof, therefore, is complete, that the presence or absence of an uninterrupted communication with the sky causes the deposition or non-deposition of dew. Now, since a clear sky is nothing but the absence of clouds, and it is a known property of clouds, as of all other bodies between which and any given object nothing intervenes but an elastic fluid, that they tend to raise or keep up the superficial temperature of the object by radiating heat to it, we see at once that the disappearance of clouds will cause the surface to cool. So that nature, in this case, produces a change in the antecedent by definite and known means, and the consequent follows accordingly, a natural experiment which satisfies the requisitions of the method of difference. 141. The accumulated proof of which the theory of dew has been found susceptible, is a striking instance of the fullness of assurance which the inductive evidence of laws of causation may attain. In cases in which the invariable sequence is by no means obvious to a superficial view. Section 4. The admirable physiological investigations of Dr. Brown-Sequard afford brilliant examples of the application of the inductive methods to a class of inquiries in which, for reasons which will presently be given, direct induction takes place under peculiar difficulties and disadvantages. As one of the most apt instances, I select his speculation, in the Proceedings of the Royal Society for May 16, 1861, on the relations between muscular irritability, cadaveric rigidity, and putrefaction. The law which Dr. Brown-Sequard's investigation tends to establish, is the following: the greater the degree of muscular irritability at the time of death, the later the cadaveric rigidity sets in, and the longer it lasts, and the later also putrefaction appears. And the slower it progresses. One would say at first sight that the method here required must be that of concomitant variations. But this is a delusive appearance, arising from the circumstance that the conclusion to be tested is itself a fact of concomitant variations. For the establishment of that fact any of the methods may be put in requisition, and it will be found that the fourth method, though really employed, has only a subordinate place in this particular investigation. The evidences by which Dr. Brown-Sequard establishes the law may be enumerated as follows. First, paralyzed muscles have greater irritability than healthy muscles. Now, paralyzed muscles are later in assuming the cadaveric rigidity than healthy muscles, the rigidity lasts longer, and putrefaction sets in later, and proceeds more slowly. Both these propositions had to be proved by experiment. And for the experiments which prove them, science is also indebted to Dr. Brown-Sequard. The former of the two, that paralyzed muscles have greater irritability than healthy muscles, he ascertained in various ways. But most decisively by comparing the duration of irritability in a paralyzed muscle and in the corresponding healthy one of the opposite side, while they are both submitted to the same excitation. He often found, in experimenting in that way, that the paralyzed muscle remained irritable twice, 3 times, or even 4 times as long as the healthy one. This is a case of induction by the method of difference. The two limbs, being those of the same animal, were presumed to differ in no circumstance material to the case except the paralysis, to the presence and absence of which, therefore, the difference in the muscular irritability was to be attributed. This assumption of complete resemblance in all material circumstances save one, evidently could not be safely made in any one pair of experiments. Because the two legs of any given animal might be accidentally in very different pathological conditions. But if, besides taking pains to avoid any such difference, the experiment was repeated sufficiently often in different animals to exclude the supposition that any abnormal circumstance could be present in them all, the conditions of the method of difference were adequately secured. In the same manner in which Dr. Brown-Sequard proved that paralyzed muscles have greater irritability, he also proved the correlative proposition respecting cadaveric rigidity and putrefaction. Having, by section of the roots of the sciatic nerve, and again of a lateral half of the spinal cord, produced paralysis in one hind leg of an animal while the other remained healthy. He found that not only did muscular irritability last much longer in the paralyzed limb, but rigidity set in later and ended later, and putrefaction began later and was less rapid than on the healthy side. This is a common case of the method of difference, requiring no comment. A further and very important corroboration was obtained by the same method. When the animal was killed, not shortly after the section of the nerve, but a month later, the effect was reversed, rigidity set in sooner, and lasted a shorter time, than in the healthy muscles. But after this lapse of time, the paralyzed muscles, having been kept by the paralysis in a state of rest, had lost a great part of their irritability, and instead of more, had become less irritable than those on the healthy side. This gives the ABC, ABC, and BC, BC, of the method of difference. One antecedent, increased irritability, being changed, and the other circumstances being the same, the consequence did not follow. And, moreover, when a new antecedent, contrary to the first, was supplied, it was followed by a contrary consequent. This instance is attended with the special advantage of proving that the retardation and prolongation of the rigidity do not depend directly on the paralysis, since that was the same in both the instances. But specifically on one effect of the paralysis, namely, the increased irritability, since they ceased when it ceased, and were reversed when it was reversed. 2d. Diminution of the temperature of muscles before death increases their irritability. But diminution of their temperature also retards cadaveric rigidity and putrefaction. Both these truths were first made known by Dr. Brown-Sequard himself, through experiments which conclude according to the method of difference. There is nothing in the nature of the process requiring specific analysis. 3d. Muscular exercise, prolonged to exhaustion, diminishes the muscular irritability. This is a well-known truth, dependent on the most general laws of muscular action, and proved by experiments under the method of difference, constantly repeated. Now, it has been shown by observation that overdriven cattle, if killed before recovery from their fatigue, become rigid and putrefy in a surprisingly short time. A similar fact has been observed in the case of animals hunted to death. Cocks killed during or shortly after a fight, and soldiers slain in the field of battle. These various cases agree in no circumstance, directly connected with the muscles, except that these have just been subjected to exhausting exercise. Under the canon, therefore, of the method of agreement, it may be inferred that there is a connection between the two facts. The method of agreement, indeed, as has been shown, is not competent to prove causation. The present case, however, is already known to be a case of causation, it being certain that the state of the body after death must somehow depend upon its state at the time of death. We are, therefore, warranted in concluding that the single circumstance in which all the instances agree, is the part of the antecedent which is the cause of that particular consequent. Fourth. In proportion as the nutrition of muscles is in a good state, their irritability is high. This fact also rests on the general evidence of the laws of physiology, grounded on many familiar applications of the method of difference. Now, in the case of those who die from accident or violence, with their muscles in a good state of nutrition, the muscular irritability continues long after death, rigidity sets in late, and persists long without the putrefactive change. On the contrary, in cases of disease in which nutrition has been diminished for a long time before death, all these effects are reversed. These are the conditions of the joint method of agreement and difference. The cases of retarded and long-continued rigidity here in question agree only in being preceded by a high state of nutrition of the muscles, the cases of rapid and brief rigidity agree only in being preceded by a low state of muscular nutrition. A connection is, therefore, inductively proved between the degree of the nutrition and the slowness and prolongation of the rigidity. Fifth, convulsions, like exhausting exercise, but in a still greater degree, diminish the muscular irritability. Now, when death follows violent and prolonged convulsions, as in tetanus, hydrophobia, some cases of cholera, and certain poisons, rigidity sets in very rapidly, and after a very brief duration, gives place to putrefaction. This is another example of the method of agreement, of the same character with number 3. Sixth. The series of instances which we shall take last, is of a more complex character, and requires a more minute analysis. It has long been observed that in some cases of death by lightning, cadaveric rigidity either does not take place at all, or is of such extremely brief duration as to escape notice, and that in these cases putrefaction is very rapid. In other cases, however, the usual cadaveric rigidity appears. There must be some difference in the cause, to account for this difference in the effect. Now, death by lightning may be the result of, first, a syncope by fright, or in consequence of a direct or reflex influence of lightning on the par vagum, 2d, hemorrhage in or around the brain, or in the lungs, the pericardium, etc. 3d, concussion, or some other alteration in the brain, none of which phenomena have any known property capable of accounting for the suppression, or almost suppression, of the cadaveric rigidity. But the cause of death may also be that the lightning produces a violent convulsion of every muscle in the body, of which, if of sufficient intensity, the known effect would be that muscular irritability ceases almost at once. If Dr. Brown-Sequard's generalization is a true law, these will be the very cases in which rigidity is so much abridged as to escape notice. And the cases in which, on the contrary, rigidity takes place as usual, will be those in which the stroke of lightning operates in some of the other modes which have been enumerated. How, then, is this brought to the test? By experiments, not on lightning, which cannot be commanded at pleasure, but on the same natural agency in a manageable form, that of artificial galvanism. Dr. Brown-Sequard galvanized the entire bodies of animals immediately after death. Galvanism cannot operate in any of the modes in which the stroke of lightning may have operated, except the single one of producing muscular convulsions. If, therefore, after the bodies have been galvanized, the duration of rigidity is much shortened and putrefaction much accelerated, it is reasonable to ascribe the same effects when produced by lightning to the property which galvanism shares with lightning, and not to those which it does not. Now this Dr. Brown-Sequard found to be the fact. The galvanic experiment was tried with charges of very various degrees of strength. And the more powerful the charge, the shorter was found to be the duration of rigidity, and the more speedy and rapid the putrefaction. In the experiment in which the charge was strongest, and the muscular irritability most promptly destroyed, the rigidity only lasted 15 minutes. On the principle, therefore, of the method of concomitant variations, it may be inferred that the duration of the rigidity depends on the degree of the irritability, and that if the charge had been as much stronger than Dr. Brown-Sequard's strongest, as a stroke of lightning must be stronger than any electric shock which we can produce artificially, the rigidity would have been shortened in a corresponding ratio, and might have disappeared altogether. This conclusion having been arrived at, the case of an electric shock, whether natural or artificial, becomes an instance, in addition to all those already ascertained, of correspondence between the irritability of the muscle and the duration of rigidity. All these instances are summed up in the following statement, that when the degree of muscular irritability at the time of death is considerable, either in consequence of a good state of nutrition, as in persons who die in full health from an accidental cause, or in consequence of rest, as in cases of paralysis, or on account of the influence of cold, cadaveric rigidity in all these cases sets in late and lasts long. And putrefaction appears late, and progresses slowly. But that when the degree of muscular irritability at the time of death is slight, either in consequence of a bad state of nutrition, or of exhaustion from overexertion, or from convulsions caused by disease or poison, cadaveric rigidity sets in and ceases soon, and putrefaction appears and progresses quickly. These facts present, in all their completeness, the conditions of the joint method of agreement and difference. Early and brief rigidity takes place in cases which agree only in the circumstance of a low state of muscular irritability. Rigidity begins late and lasts long in cases which agree only in the contrary circumstance, of a muscular irritability high and unusually prolonged. It follows that there is a connection through causation between the degree of muscular irritability after death, and the tardiness and prolongation of the cadaveric rigidity. This investigation places in a strong light the value and efficacy of the joint method. For, as we have already seen, the defect of that method is, that like the method of agreement, of which it is only an improved form, it cannot prove causation. But in the present case, as in one of the steps in the argument which led up to it, causation is already proved. Since there could never be any doubt that the rigidity altogether, and the putrefaction which follows it, are caused by the fact of death, the observations and experiments on which this rests are too familiar to need analysis, and fall under the method of difference. It being, therefore, beyond doubt that the aggregate antecedent, the death, is the actual cause of the whole train of consequence. Whatever of the circumstances attending the death can be shown to be followed in all its variations by variations in the effect under investigation, must be the particular feature of the fact of death on which that effect depends. The degree of muscular irritability at the time of death fulfills this condition. The only point that could be brought into question, would be whether the effect depended on the irritability itself, or on something which always accompanied the irritability, and this doubt is set at rest by establishing, as the instances do, that by whatever cause the high or low irritability is produced, the effect equally follows, and cannot, therefore, depend upon the causes of irritability, nor upon the other effects of those causes, which are as various as the causes themselves, but upon the irritability, solely. Section 5. The last two examples will have conveyed to any one by whom they have been duly followed, so clear a conception of the use and practical management of 3 of the 4 methods of experimental inquiry, as to supersede the necessity of any further exemplification of them. The remaining method, that of residues, not having found a place in any of the preceding investigations, I shall quote from Sir John Herschel some examples of that method, with the remarks by which they are introduced. It is by this process, in fact, that science, in its present advanced state, is chiefly promoted. Most of the phenomena which nature presents are very complicated. And when the effects of all known causes are estimated with exactness, and subducted, the residual facts are constantly appearing in the form of phenomena altogether new, and leading to the most important conclusions. For example, the return of the comet predicted by Professor Yook a great many times in succession, and the general good agreement of its calculated with its observed place during any one of its periods of visibility, would lead us to say that its gravitation toward the sun and planets is the sole and sufficient cause of all the phenomena of its orbital motion. But when the effect of this cause is strictly calculated and subducted from the observed motion, there is found to remain behind a residual phenomenon, which would never have been otherwise ascertained to exist. Which is a small anticipation of the time of its reappearance, or a diminution of its periodic time, which cannot be accounted for by gravity, and whose cause is therefore to be inquired into. Such an anticipation would be caused by the resistance of a medium disseminated through the celestial regions. And as there are other good reasons for believing this to be a vera causa, an actually existing antecedent, it has therefore been ascribed to such a resistance. 142. M. Arago, having suspended a magnetic needle by a silk thread, and set it in vibration, observed, that it came much sooner to a state of rest when suspended over a plate of copper, than when no such plate was beneath it. Now, in both cases there were two very causae, antecedents known to exist, why it should come at length to rest, viz., the resistance of the air, which opposes, and at length destroys, all motions performed in it, and the want of perfect mobility in the silk thread. But the effect of these causes being exactly known by the observation made in the absence of the copper, and being thus allowed for and subducted, a residual phenomenon appeared, in the fact that a retarding influence was exerted by the copper itself. And this fact, once ascertained, speedily led to the knowledge of an entirely new and unexpected class of relations. This example belongs, however, not to the method of residues but to the method of difference, the law being ascertained by a direct comparison of the results of two experiments, which differed in nothing but the presence or absence of the plate of copper. To have made it exemplify the method of residues, the effect of the resistance of the air and that of the rigidity of the silk should have been calculated a priori, from the laws obtained by separate and foregone experiments. Unexpected and peculiarly striking confirmations of inductive laws frequently occur in the form of residual phenomena, in the course of investigations of a widely different nature from those which gave rise to the inductions themselves. A very elegant example may be cited in the unexpected confirmation of the law of the development of heat in elastic fluids by compression, which is afforded by the phenomena of sound. The inquiry into the cause of sound had led to conclusions respecting its mode of propagation, from which its velocity in the air could be precisely calculated. The calculations were performed. But, when compared with fact, though the agreement was quite sufficient to show the general correctness of the cause and mode of propagation assigned, yet the whole velocity could not be shown to arise from this theory. There was still a residual velocity to be accounted for, which placed dynamical philosophers for a long time in great dilemma. At length Laplace struck on the happy idea, that this might arise from the heat developed in the act of that condensation which necessarily takes place at every vibration by which sound is conveyed. The matter was subjected to exact calculation, and the result was at once the complete explanation of the residual phenomenon, and a striking confirmation of the general law of the development of heat by compression, under circumstances beyond artificial imitation. Many of the new elements of chemistry have been detected in the investigation of residual phenomena. Thus Arfwedson discovered lithia by perceiving an excess of weight in the sulfate produced from a small portion of what he considered as magnesia present in a mineral he had analyzed. It is on this principle, too, that the small concentrated residues of great operations in the arts are almost sure to be the lurking places of new chemical ingredients, witness iodine, brome, selenium, and the new metals accompanying platina in the experiments of Wollaston and Tennant. It was a happy thought of Glauber to examine what everybody else threw away. 143. Almost all the greatest discoveries in astronomy, says the same author 144, have resulted from the consideration of residual phenomena of a quantitative or numerical kind. It was thus that the grand discovery of the precession of the equinoxes resulted as a residual phenomenon, from the imperfect explanation of the return of the seasons by the return of the sun to the same apparent place among the fixed stars. Thus, also, aberration and nutation resulted as residual phenomena from that portion of the changes of the apparent places of the fixed stars which was left unaccounted for by precession. And thus again the apparent proper motions of the stars are the observed residues of their apparent movements outstanding and unaccounted for by strict calculation of the effects of precession, nutation, and aberration. The nearest approach which human theories can make to perfection is to diminish this residue, this caput mortuum of observation, as it may be considered, as much as practicable, and, if possible, to reduce it to nothing. Either by showing that something has been neglected in our estimation of known causes, or by reasoning upon it as a new fact, and on the principle of the inductive philosophy ascending from the effect to its cause or causes. The disturbing effects mutually produced by the earth and planets upon each other's motions were first brought to light as residual phenomena, by the difference which appeared between the observed places of those bodies, and the places calculated on a consideration solely of their gravitation toward the sun. It was this which determined astronomers to consider the law of gravitation as obtaining between all bodies whatever, and therefore between all particles of matter. Their first tendency having been to regard it as a force acting only between each planet or satellite and the central body to whose system it belonged. Again, the catastrophists, in geology, be their opinion right or wrong, supported on the plea, that after the effect of all causes now in operation has been allowed for, there remains in the existing constitution of the earth a large residue of facts, proving the existence at former periods either of other forces, or of the same forces in a much greater degree of intensity. To add one more example, those who assert, what no one has shown any real ground for believing, that there is in one human individual, one sex, or one race of mankind over another, an inherent and inexplicable superiority in mental faculties, could only substantiate their proposition by subtracting from the differences of intellect which we in fact see, all that can be traced by known laws either to the ascertained differences of physical organization, or to the differences which have existed in the outward circumstances in which the subjects of the comparison have hitherto been placed. What these causes might fail to account for would constitute a residual phenomenon, which alone would be evidence of an ulterior original distinction, and the measure of its amount. But the assertors of such supposed differences have not provided themselves with these necessary logical conditions of the establishment of their doctrine. The spirit of the method of residues being, it is hoped, sufficiently intelligible from these examples, and the other three methods having already been so fully exemplified, we may here close our exposition of the four methods, considered as employed in the investigation of the simpler and more elementary order of the combinations of phenomena. Section 6. Dr. Wool has expressed a very unfavorable opinion of the utility of the four methods, as well as of the aptness of the examples by which I have attempted to illustrate them. His words are these, 145. Upon these methods, the obvious thing to remark is, that they take for granted the very thing which is most difficult to discover, the reduction of the phenomena to formulae such as are here presented to us, when we have any set of complex facts offered to us. For instance, those which were offered in the cases of discovery which I have mentioned, the facts of the planetary paths, of falling bodies, of refracted rays, of cosmical motions, of chemical analysis. And when, in any of these cases, we would discover the law of nature which governs them, or, if any one chooses so to term it, the feature in which all the cases agree, where are we to look for our A, B, C, and A, B, C? Nature does not present to us the cases in this form, and how are we to reduce them to this form? You say when we find the combination of ABC with ABC and ABD with ABD, then we may draw our inference. Granted. But when and where are we to find such combinations? Even now that the discoveries are made, who will point out to us what are the A, B, C, and A, B, C, elements of the cases which have just been enumerated? Who will tell us which of the methods of inquiry those historically real and successful inquiries exemplify? Who will carry these formulae through the history of the sciences, as they have really grown up, and show us that these four methods have been operative in their formation? Or that any light is thrown upon the steps of their progress by reference to these formulae? He adds that, in this work, the methods have not been applied to a large body of conspicuous and undoubted examples of discovery, extending along the whole history of science. Which ought to have been done in order that the methods might be shown to possess the advantage, which he claims as belonging to his own, of being those by which all great discoveries in science have really been made. p. 277. There is a striking similarity between the objections here made against canons of induction, and what was alleged, in the last century, by as able men as Dr. Wool, against the acknowledged canon of ratiocination. Those who protested against the Aristotelian logic said of the syllogism, what Dr. Wool says of the inductive methods, that it takes for granted the very thing which is most difficult to discover, the reduction of the argument to formulae such as are here presented to us. The grand difficulty, they said, is to obtain your syllogism, not to judge of its correctness when obtained. On the matter of fact, both they and Dr. Wool are right. The greatest difficulty in both cases is, first, that of obtaining the evidence, and next, of reducing it to the form which tests its conclusiveness. But if we try to reduce it without knowing what it is to be reduced to, we are not likely to make much progress. It is a more difficult thing to solve a geometrical problem, than to judge whether a proposed solution is correct, but if people were not able to judge of the solution when found, they would have little chance of finding it. And it cannot be pretended that to judge of an induction when found is perfectly easy, is a thing for which aids and instruments are superfluous. For erroneous inductions, false inferences from experience, are quite as common, on some subjects much commoner than true ones. The business of inductive logic is to provide rules and models, such as the syllogism and its rules are for ratiocination, to which if inductive arguments conform, those arguments are conclusive, and not otherwise. This is what the four methods profess to be, and what I believe they are universally considered to be by experimental philosophers, who had practiced all of them long before any one sought to reduce the practice to theory. The assailants of the syllogism had also anticipated Dr. Wool in the other branch of his argument. They said that no discoveries were ever made by syllogism, and Dr. Wool says, or seems to say, that none were ever made by the four methods of induction. To the former objectors, Archbishop Whately very pertinently answered, that their argument, if good at all, was good against the reasoning process altogether. For whatever cannot be reduced to syllogism, is not reasoning. And Dr. Wool's argument, if good at all, is good against all inferences from experience. In saying that no discoveries were ever made by the four methods, he affirms that none were ever made by observation and experiment, for assuredly if any were, it was by processes reducible to one or other of those methods. This difference between us accounts for the dissatisfaction which my examples give him. For I did not select them with a view to satisfy anyone who required to be convinced that observation and experiment are modes of acquiring knowledge. I confess that in the choice of them I thought only of illustration, and of facilitating the conception of the methods by concrete instances. If it had been my object to justify the processes themselves as means of investigation, there would have been no need to look far off, or make use of recondite or complicated instances. As a specimen of a truth ascertained by the method of agreement, I might have chosen the proposition, dogs bark. This dog, and that dog, and the other dog, answer to A B C, A D E, A F G. The circumstance of being a dog answers to A. Barking answers to A. As a truth made known by the method of difference, fire burns, might have sufficed. Before I touch the fire I am not burned. This is BC, I touch it, and am burned, this is ABC, ABC. Such familiar experimental processes are not regarded as inductions by Dr. Whewell, but they are perfectly homogeneous with those by which, even on his own showing, the pyramid of science is supplied with its base. In vain he attempts to escape from this conclusion by laying the most arbitrary restrictions on the choice of examples admissible as instances of induction. They must neither be such as are still matter of discussion, p. 265, nor must any of them be drawn from mental and social subjects, page 269, nor from ordinary observation in practical life, pages 241 to 247. They must be taken exclusively from the generalizations by which scientific thinkers have ascended to great and comprehensive laws of natural phenomena. Now it is seldom possible, in these complicated inquiries, to go much beyond the initial steps, without calling in the instrument of deduction, and the temporary aid of hypothesis, as I myself, in common with Dr. Whewell, have maintained against the purely empirical school. Since, therefore, such cases could not conveniently be selected to illustrate the principles of mere observation and experiment, Dr. Whewell is misled by their absence into representing the experimental methods as serving no purpose in scientific investigation. Forgetting that if those methods had not supplied the first generalizations, there would have been no materials for his own conception of induction to work upon. His challenge, however, to point out which of the four methods are exemplified in certain important cases of scientific inquiry, is easily answered. The planetary paths, as far as they are a case of induction at all, 146 fall under the method of agreement. The law of falling bodies, namely, that they describe spaces proportional to the squares of the times, was historically a deduction from the first law of motion. But the experiments by which it was verified, and by which it might have been discovered, were examples of the method of agreement. And the apparent variation from the true law, caused by the resistance of the air, was cleared up by experiments in vacuo, constituting an application of the method of difference. The law of refracted rays, the constancy of the ratio between the signs of incidence and of refraction for each refracting substance, was ascertained by direct measurement, and therefore by the method of agreement. The cosmical motions were determined by highly complex processes of thought, in which deduction was predominant, but the methods of agreement and of concomitant variations had a large part in establishing the empirical laws. Every case without exception of chemical analysis constitutes a well-marked example of the method of difference. To anyone acquainted with the subjects, to Dr. Whewell himself, there would not be the smallest difficulty in setting out the A, B, C and A, B, C elements of these cases. If discoveries are ever made by observation and experiment without deduction, the four methods are methods of discovery, but even if they were not methods of discovery, it would not be the less true that they are the sole methods of proof. And in that character, even the results of deduction are amenable to them. The great generalizations which begin as hypotheses, must end by being proved, and are in reality, as will be shown hereafter, proved, by the four methods. Now it is with proof, as such, that logic is principally concerned. This distinction has indeed no chance of finding favor with Dr. Whewell, for it is the peculiarity of his system, not to recognize, in cases of induction, any necessity for proof. If, after assuming an hypothesis and carefully collating it with facts, nothing is brought to light inconsistent with it, that is, if experience does not disprove it, he is content, at least until a simpler hypothesis, equally consistent with experience, presents itself. If this be induction, doubtless there is no necessity for the four methods. But to suppose that it is so, appears to me a radical misconception of the nature of the evidence of physical truths. So real and practical is the need of a test for induction, similar to the syllogistic test of ratiocination. That inferences which bid defiance to the most elementary notions of inductive logic are put forth without misgiving by persons eminent in physical science, as soon as they are off the ground on which they are conversant with the facts, and not reduced to judge only by the arguments. And as for educated persons in general, it may be doubted if they are better judges of a good or a bad induction than they were before Bacon wrote. The improvement in the results of thinking has seldom extended to the processes, or has reached, if any process, that of investigation only, not that of proof. A knowledge of many laws of nature has doubtless been arrived at, by framing hypotheses and finding that the facts corresponded to them. And many errors have been got rid of by coming to a knowledge of facts which were inconsistent with them, but not by discovering that the mode of thought which led to the errors was itself faulty, and might have been known to be such independently of the facts which disproved the specific conclusion. Hence it is, that while the thoughts of mankind have on many subjects worked themselves practically right, the thinking power remains as weak as ever, and on all subjects on which the facts which would check the result are not accessible. As in what relates to the invisible world, and even, as has been seen lately, to the visible world of the planetary regions, men of the greatest scientific acquirements argue as pitiably as the merest ignoramus. For though they have made many sound inductions, they have not learned from them, and Dr. Wool thinks there is no necessity that they should learn, the principles of inductive evidence. Of plurality of causes, and of the intermixture of effects. Section 1. In the preceding exposition of the four methods of observation and experiment, by which we contrive to distinguish among a mass of coexistent phenomena the particular effect due to a given cause, or the particular cause which gave birth to a given effect, it has been necessary to suppose, in the first instance, for the sake of simplification, that this analytical operation is encumbered by no other difficulties than what are essentially inherent in its nature. And to represent to ourselves, therefore, every effect, on the one hand as connected exclusively with a single cause, and on the other hand as incapable of being mixed and confounded with any other coexistent effect. We have regarded A, B, C, D, E, the aggregate of the phenomena existing at any moment, as consisting of dissimilar facts, A, B, C, D, and E, for each of which one, and only one, cause needs be sought. The difficulty being only that of singling out this one cause from the multitude of antecedent circumstances, A, B, C, D, and E. The cause indeed may not be simple, it may consist of an assemblage of conditions. But we have supposed that there was only one possible assemblage of conditions from which the given effect could result. If such were the fact, it would be comparatively an easy task to investigate the laws of nature. But the supposition does not hold in either of its parts. In the first place, it is not true that the same phenomenon is always produced by the same cause, the effect A may sometimes arise from A, sometimes from B. And, secondly, the effects of different causes are often not dissimilar, but homogeneous, and marked out by no assignable boundaries from one another. A and B may produce not A and B, but different portions of an effect A. The obscurity and difficulty of the investigation of the laws of phenomena is singularly increased by the necessity of adverting to these two circumstances, intermixture of effects, and plurality of causes. To the latter, being the simpler of the two considerations, we shall first direct our attention. It is not true, then, that one effect must be connected with only one cause, or assemblage of conditions. That each phenomenon can be produced only in one way. There are often several independent modes in which the same phenomenon could have originated. One fact may be the consequent in several invariable sequences. It may follow, with equal uniformity, any one of several antecedents or collections of antecedents. Many causes may produce mechanical motion, many causes may produce some kinds of sensation, many causes may produce death. A given effect may really be produced by a certain cause, and yet be perfectly capable of being produced without it. Section 2. One of the principal consequences of this fact of plurality of causes is, to render the first of the inductive methods, that of agreement, uncertain. To illustrate that method, we supposed two instances, ABC followed by ABC, and ADE followed by ADE. From these instances it might apparently be concluded that A is an invariable antecedent of A, and even that it is the unconditional invariable antecedent, or cause, if we could be sure that there is no other antecedent common to the two cases. That this difficulty may not stand in the way, let us suppose the two cases positively ascertained to have no antecedent in common except A. The moment, however, that we let in the possibility of a plurality of causes, the conclusion fails. For it involves a tacit supposition, that a must have been produced in both instances by the same cause. If there can possibly have been two causes, those two may, for example, be C and E, the one may have been the cause of A in the former of the instances, the other in the latter, A having no influence in either case. Suppose, for example, that two great artists or great philosophers, that two extremely selfish or extremely generous characters, were compared together as to the circumstances of their education and history. And the two cases were found to agree only in one circumstance. Would it follow that this one circumstance was the cause of the quality which characterized both those individuals? Not at all, for the causes which may produce any type of character are very numerous, and the two persons might equally have agreed in their character, though there had been no manner of resemblance in their previous history. This, therefore, is a characteristic imperfection of the method of agreement, from which imperfection the method of difference is free. For if we have two instances, A, BC and BC, of which BC gives BC, and A being added converts it into ABC, it is certain that in this instance at least, A was either the cause of A, or an indispensable portion of its cause. Even though the cause which produces it in other instances may be altogether different. Plurality of causes, therefore, not only does not diminish the reliance due to the method of difference, but does not even render a greater number of observations or experiments necessary. Two instances, the one positive and the other negative, are still sufficient for the most complete and rigorous induction. Not so, however, with the method of agreement. The conclusions which that yields, when the number of instances compared is small, are of no real value, except as, in the character of suggestions, they may lead either to experiments bringing them to the test of the method of difference, or to reasonings which may explain and verify them deductively. It is only when the instances, being indefinitely multiplied and varied, continue to suggest the same result, that this result acquires any high degree of independent value. If there are but two instances, A, B, C and A, D, E, though these instances have no antecedent in common except A, yet as the effect may possibly have been produced in the two cases by different causes, the result is at most only a slight probability in favor of A. There may be causation, but it is almost equally probable that there was only a coincidence. But the oftener we repeat the observation, varying the circumstances, the more we advance toward a solution of this doubt. For if we try A, F, G, A, H, K, etc., all unlike one another except in containing the circumstance A, and if we find the effect A entering into the result in all these cases, we must suppose one of two things, either that it is caused by A, or that it has as many different causes as there are instances. With each addition, therefore, to the number of instances, the presumption is strengthened in favor of A. The inquirer, of course, will not neglect, if an opportunity present itself, to exclude A from some one of these combinations, from A, H, K for instance, and by trying H, K separately, appeal to the method of difference in aid of the method of agreement. By the method of difference alone can it be ascertained that A is the cause of A. But that it is either the cause, or another effect of the same cause, may be placed beyond any reasonable doubt by the method of agreement, provided the instances are very numerous as well as sufficiently various. After how great a multiplication, then, of varied instances, all agreeing in no other antecedent except A, is the supposition of a plurality of causes sufficiently rebutted. And the conclusion that A is connected with A divested of the characteristic imperfection, and reduced to a virtual certainty? This is a question which we cannot be exempted from answering, but the consideration of it belongs to what is called the theory of probability, which will form the subject of a chapter hereafter. It is seen, however, at once, that the conclusion does amount to a practical certainty after a sufficient number of instances, and that the method, therefore, is not radically vitiated by the characteristic imperfection. The result of these considerations is only, in the first place, to point out a new source of inferiority in the method of agreement as compared with other modes of investigation, and new reasons for never resting contented with the results obtained by it, without attempting to confirm them either by the method of difference, or by connecting them deductively with some law or laws already ascertained by that superior method. And, in the second place, we learn from this the true theory of the value of mere number of instances in inductive inquiry. The plurality of causes is the only reason why mere number is of any importance. The tendency of unscientific inquirers is to rely too much on number, without analyzing the instances, without looking closely enough into their nature to ascertain what circumstances are or are not eliminated by means of them. Most people hold their conclusions with a degree of assurance proportioned to the mere mass of the experience on which they appear to rest. Not considering that by the addition of instances to instances, all of the same kind, that is, differing from one another only in points already recognized as immaterial, nothing whatever is added to the evidence of the conclusion. A single instance eliminating some antecedent which existed in all the other cases, is of more value than the greatest multitude of instances which are reckoned by their number alone. It is necessary, no doubt, to assure ourselves, by repetition of the observation or experiment, that no error has been committed concerning the individual facts observed. And until we have assured ourselves of this, instead of varying the circumstances, we cannot too scrupulously repeat the same experiment or observation without any change. But when once this assurance has been obtained, the multiplication of instances which do not exclude any more circumstances is entirely useless, provided there have been already enough to exclude the supposition of plurality of causes. It is of importance to remark, that the peculiar modification of the method of agreement, which, as partaking in some degree of the nature of the method of difference, I have called the joint method of agreement and difference, is not affected by the characteristic imperfection now pointed out. For, in the joint method, it is supposed not only that the instances in which A is, agree only in containing A, but also that the instances in which A is not, agree only in not containing A. Now, if this be so, A must be not only the cause of A, but the only possible cause, for if there were another, as for example B, then in the instances in which A is not, B must have been absent as well as A. And it would not be true that these instances agree only in not containing A. This, therefore, constitutes an immense advantage of the joint method over the simple method of agreement. It may seem, indeed, that the advantage does not belong so much to the joint method, as to one of its two premises, if they may be so called, the negative premise. The method of agreement, when applied to negative instances, or those in which a phenomenon does not take place, is certainly free from the characteristic imperfection which affects it in the affirmative case. The negative premise, it might therefore be supposed, could be worked as a simple case of the method of agreement, without requiring an affirmative premise to be joined with it. But though this is true in principle, it is generally altogether impossible to work the method of agreement by negative instances without positive ones. It is so much more difficult to exhaust the field of negation than that of affirmation. For instance, let the question be what is the cause of the transparency of bodies, with what prospect of success could we set ourselves to inquire directly in what the multifarious substances which are not transparent agree? But we might hope much sooner to see some point of resemblance among the comparatively few and definite species of objects which are transparent. And this being attained, we should quite naturally be put upon examining whether the absence of this one circumstance be not precisely the point in which all opaque substances will be found to resemble. The joint method of agreement and difference, therefore, or as I have otherwise called it, the indirect method of difference, because, like the method of difference properly so called, it proceeds by ascertaining how and in what the cases where the phenomenon is present differ from those in which it is absent, is, after the direct method of difference, the most powerful of the remaining instruments of inductive investigation. And in the sciences which depend on pure observation, with little or no aid from experiment, this method, so well exemplified in the speculation on the cause of do, is the primary resource, so far as direct appeals to experience are concerned. Section 3. We have thus far treated plurality of causes only as a possible supposition, which, until removed, renders our inductions uncertain. And have only considered by what means, where the plurality does not really exist, we may be enabled to disprove it. But we must also consider it as a case actually occurring in nature, and which, as often as it does occur, our methods of induction ought to be capable of ascertaining and establishing. For this, however, there is required no peculiar method. When an effect is really producible by two or more causes, the process for detecting them is in no way different from that by which we discover single causes. They may, first, be discovered as separate sequences, by separate sets of instances. One set of observations or experiments shows that the sun is a cause of heat, another that friction is a source of it, another that percussion, another that electricity, another that chemical action is such a source. Or, secondly, the plurality may come to light in the course of collating a number of instances, when we attempt to find some circumstance in which they all agree, and fail in doing so. We find it impossible to trace, in all the cases in which the effect is met with, any common circumstance. We find that we can eliminate all the antecedents. That no one of them is present in all the instances, no one of them indispensable to the effect. On closer scrutiny, however, it appears that though no one is always present, one or other of several always is. If, on further analysis, we can detect in these any common element, we may be able to ascend from them to some one cause which is the really operative circumstance in them all. Thus it is now thought that in the production of heat by friction, percussion, chemical action, etc., the ultimate source is one and the same. But if, as continually happens, we cannot take this ulterior step, the different antecedents must be set down provisionally as distinct causes, each sufficient of itself to produce the effect. We here close our remarks on the plurality of causes, and proceed to the still more peculiar and more complex case of the intermixture of effects, and the interference of causes with one another, a case constituting the principal part of the complication and difficulty of the study of nature, and with which the four only possible methods of directly inductive investigation by observation and experiment are, for the most part, as will appear presently, quite unequal to cope. The instrument of deduction alone is adequate to unravel the complexities proceeding from this source, and the four methods have little more in their power than to supply premises for, and a verification of, our deductions. Section 4. A concurrence of two or more causes, not separately producing each its own effect, but interfering with or modifying the effects of one another, takes place, as has already been explained in two different ways. In the one, which is exemplified by the joint operation of different forces in mechanics, the separate effects of all the causes continue to be produced, but are compounded with one another, and disappear in one total. In the other, illustrated by the case of chemical action, the separate effects cease entirely, and are succeeded by phenomena altogether different, and governed by different laws. Of these cases the former is by far the more frequent, and this case it is which, for the most part, eludes the grasp of our experimental methods. The other an exceptional case is essentially amenable to them. When the laws of the original agents cease entirely, and a phenomenon makes its appearance, which, with reference to those laws, is quite heterogeneous. When, for example, two gaseous substances, hydrogen and oxygen, on being brought together, throw off their peculiar properties, and produce the substance called water. In such cases the new fact may be subjected to experimental inquiry, like any other phenomenon. And the elements which are said to compose it may be considered as the mere agents of its production, the conditions on which it depends, the facts which make up its cause. The effects of the new phenomenon, the properties of water, for instance, are as easily found by experiment as the effects of any other cause. But to discover the cause of it, that is, the particular conjunction of agents from which it results, is often difficult enough. In the first place, the origin and actual production of the phenomenon are most frequently inaccessible to our observation. If we could not have learned the composition of water until we found instances in which it was actually produced from oxygen and hydrogen, we should have been forced to wait until the casual thought struck someone of passing an electric spark through a mixture of the two gases, or inserting a lighted taper into it, merely to try what would happen. Besides, many substances, though they can be analyzed, cannot by any known artificial means be recompounded. Further, even if we could have ascertained, by the method of agreement, that oxygen and hydrogen were both present when water is produced, no experimentation on oxygen and hydrogen separately, no knowledge of their laws. could have enabled us deductively to infer that they would produce water. We require a specific experiment on the two combined. Under these difficulties, we should generally have been indebted for our knowledge of the causes of this class of effects, not to any inquiry directed specifically toward that end, but either to accident, or to the gradual progress of experimentation on the different combinations of which the producing agents are susceptible. If it were not for a peculiarity belonging to effects of this description, that they often, under some particular combination of circumstances, reproduce their causes. If water results from the juxtaposition of hydrogen and oxygen whenever this can be made sufficiently close and intimate, so, on the other hand, if water itself be placed in certain situations, hydrogen and oxygen are reproduced from it, an abrupt termination is put to the new laws, and the agents reappear separately with their own properties as at first. What is called chemical analysis is the process of searching for the causes of a phenomenon among its effects, or rather among the effects produced by the action of some other causes upon it. Lavoisier, by heating mercury to a high temperature in a close vessel containing air, found that the mercury increased in weight, and became what was then called red precipitate, while the air, on being examined after the experiment, proved to have lost weight, and to have become incapable of supporting life or combustion. When red precipitate was exposed to a still greater heat, it became mercury again, and gave off a gas which did support life and flame. Thus the agents which by their combination produced red precipitate, namely, the mercury and the gas, reappear as effects resulting from that precipitate when acted upon by heat. So, if we decompose water by means of iron filings, we produce two effects, rust and hydrogen. Now rust is already known, by experiments upon the component substances, to be an effect of the union of iron and oxygen. The iron we ourselves supplied, but the oxygen must have been produced from the water. The result, therefore, is that water has disappeared, and hydrogen and oxygen have appeared in its stead. Or, in other words, the original laws of these gaseous agents, which had been suspended by the superinduction of the new laws called the properties of water, have again started into existence, and the causes of water are found among its effects. Where two phenomena, between the laws or properties of which, considered in themselves, no connection can be traced, are thus reciprocally cause and effect, each capable in its turn of being produced from the other, and each, when it produces the other, ceasing itself to exist, as water is produced from oxygen and hydrogen are reproduced from water. This causation of the two phenomena by one another, each being generated by the other's destruction, is properly transformation. The idea of chemical composition is an idea of transformation, but of a transformation which is incomplete. Since we consider the oxygen and hydrogen to be present in the water as oxygen and hydrogen, and capable of being discovered in it if our senses were sufficiently keen, a supposition, for it is no more, grounded solely on the fact that the weight of the water is the sum of the separate weights of the two ingredients. If there had not been this exception to the entire disappearance, in the compound, of the laws of the separate ingredients. If the combined agents had not, in this one particular of weight, preserved their own laws, and produced a joint result equal to the sum of their separate results, we should never, probably, have had the notion now implied by the words chemical composition. And, in the facts of water produced from hydrogen and oxygen produced from water, as the transformation would have been complete, we should have seen only a transformation. In these cases, where the heteropathic effect, as we called it in a former chapter, 147 is but a transformation of its cause, or in other words, where the effect and its cause are reciprocally such, and mutually convertible into each other, the problem of finding the cause resolves itself into the far easier one of finding an effect, which is the kind of inquiry that admits of being prosecuted by direct experiment. But there are other cases of heteropathic effects to which this mode of investigation is not applicable. Take, for instance, the heteropathic laws of mind. That portion of the phenomena of our mental nature which are analogous to chemical rather than to dynamical phenomena. As when a complex passion is formed by the coalition of several elementary impulses, or a complex emotion by several simple pleasures or pains, of which it is the result without being the aggregate, or in any respect homogeneous with them. The product, in these cases, is generated by its various factors, but the factors cannot be reproduced from the product, just as a youth can grow into an old man, but an old man cannot grow into a youth. We cannot ascertain from what simple feelings any of our complex states of mind are generated, as we ascertain the ingredients of a chemical compound, by making it, in its turn, generate them. We can only, therefore, discover these laws by the slow process of studying the simple feelings themselves, and ascertaining synthetically, by experimenting on the various combinations of which they are susceptible, what they, by their mutual action upon one another, are capable of generating. Section 5. It might have been supposed that the other, an apparently simpler variety of the mutual interference of causes, where each cause continues to produce its own proper effect according to the same laws to which it conforms in its separate state, would have presented fewer difficulties to the inductive inquirer than that of which we have just finished the consideration. It presents, however, so far as direct induction apart from deduction is concerned, infinitely greater difficulties. When a concurrence of causes gives rise to a new effect, bearing no relation to the separate effects of those causes, the resulting phenomenon stands forth undisguised, inviting attention to its peculiarity, and presenting no obstacle to our recognizing its presence or absence among any number of surrounding phenomena. It admits, therefore, of being easily brought under the canons of induction, provided instances can be obtained such as those canons require. And the non-occurrence of such instances, or the want of means to produce them artificially, is the real and only difficulty in such investigations, a difficulty not logical but in some sort physical. It is otherwise with cases of what, in a preceding chapter, has been denominated the composition of causes. There, the effects of the separate causes do not terminate and give place to others, thereby ceasing to form any part of the phenomenon to be investigated. On the contrary, they still take place, but are intermingled with, and disguised by, the homogeneous and closely allied effects of other causes. They are no longer A, B, C, D, E, existing side by side, and continuing to be separately discernible. They are plus A, 1/2 B, B, 2B, etc., some of which cancel one another, while many others do not appear distinguishably, but merge in one sum, forming altogether a result, between which and the causes whereby it was produced there is often an insurmountable difficulty in tracing by observation any fixed relation whatever. The general idea of the composition of causes has been seen to be, that though two or more laws interfere with one another, and apparently frustrate or modify one another's operation, yet in reality all are fulfilled, the collective effect being the exact sum of the effects of the causes taken separately. A familiar instance is that of a body kept in equilibrium by two equal and contrary forces. One of the forces if acting alone would carry the body in a given time a certain distance to the west, the other if acting alone would carry it exactly as far toward the east. And the result is the same as if it had been first carried to the west as far as the one force would carry it, and then back toward the east as far as the other would carry it, that is, precisely the same distance, being ultimately left where it was found at first. All laws of causation are liable to be in this manner counteracted, and seemingly frustrated, by coming into conflict with other laws, the separate result of which is opposite to theirs, or more or less inconsistent with it. And hence, with almost every law, many instances in which it really is entirely fulfilled, do not, at first sight, appear to be cases of its operation at all. It is so in the example just adduced. A force in mechanics means neither more nor less than a cause of motion, yet the sum of the effects of two causes of motion may be rest. Again, a body solicited by two forces in directions making an angle with one another, moves in the diagonal, and it seems a paradox to say that motion in the diagonal is the sum of two motions in two other lines. Motion, however, is but change of place. And at every instant the body is in the exact place it would have been in if the forces had acted during alternate instants instead of acting in the same instant, saving that if we suppose two forces to act successively which are in truth simultaneous we must of course allow them double the time. It is evident, therefore, that each force has had, during each instant, all the effect which belonged to it. And that the modifying influence which one of two concurrent causes is said to exercise with respect to the other may be considered as exerted not over the action of the cause itself, but over the effect after it is completed. For all purposes of predicting, calculating, or explaining their joint result, causes which compound their effects may be treated as if they produced simultaneously each of them its own effect, and all these effects coexisted visibly. Since the laws of causes are as really fulfilled and the causes are said to be counteracted by opposing causes, as when they are left to their own undisturbed action, we must be cautious not to express the laws in such terms as would render the assertion of their being fulfilled in those cases a contradiction. If, for instance, it were stated as a law of nature that a body to which a force is applied moves in the direction of the force, with a velocity proportioned to the force directly, and to its own mass inversely. When in point of fact some bodies to which a force is applied do not move at all, and those which do move, at least in the region of our earth, are, from the very first, retarded by the action of gravity and other resisting forces, and at last stopped altogether. It is clear that the general proposition, though it would be true under a certain hypothesis, would not express the facts as they actually occur. To accommodate the expression of the law to the real phenomena, we must say, not that the object moves, but that it tends to move, in the direction and with the velocity specified. We might, indeed, guard our expression in a different mode, by saying that the body moves in that manner unless prevented, or except in so far as prevented, by some counteracting cause. But the body does not only move in that manner unless counteracted, it tends to move in that manner even when counteracted. It still exerts, in the original direction, the same energy of movement as if its first impulse had been undisturbed, and produces, by that energy, an exactly equivalent quantity of effect. This is true even when the force leaves the body as it found it, in a state of absolute rest, as when we attempt to raise a body of 3 tons weight with a force equal to 1 ton. For if, while we are applying this force, wind or water or any other agent supplies an additional force just exceeding 2 tons, the body will be raised. Thus proving that the force we applied exerted its full effect, by neutralizing an equivalent portion of the weight which it was insufficient altogether to overcome. And if, while we are exerting this force of 1 ton upon the object in a direction contrary to that of gravity, it be put into a scale and weighed, it will be found to have lost a ton of its weight, or, in other words, to press downward with a force only equal to the difference of the two forces. These facts are correctly indicated by the expression tendency. All laws of causation, in consequence of their liability to be counteracted, require to be stated in words affirmative of tendencies only, and not of actual results. In those sciences of causation which have an accurate nomenclature, there are special words which signify a tendency to the particular effect with which the science is conversant. Thus pressure, in mechanics, is synonymous with tendency to motion, and forces are not reasoned on as causing actual motion, but as exerting pressure. A similar improvement in terminology would be very salutary in many other branches of science. The habit of neglecting this necessary element in the precise expression of the laws of nature, has given birth to the popular prejudice that all general truths have exceptions. And much unmerited distrust has thence accrued to the conclusions of science, when they have been submitted to the judgment of minds insufficiently disciplined and cultivated. The rough generalizations suggested by common observation usually have exceptions, but principles of science, or, in other words, laws of causation, have not. What is thought to be an exception to a principle, to quote words used on a different occasion, is always some other and distinct principle cutting into the former. Some other force which impinges 148 against the first force, and deflects it from its direction. There are not a law and an exception to that law, the law acting in 99 cases, and the exception in 1. There are 2 laws, each possibly acting in the whole 100 cases, and bringing about a common effect by their conjunct operation. If the force which, being the less conspicuous of the 2, is called the disturbing force, prevails sufficiently over the other force in some one case, to constitute that case what is commonly called an exception. The same disturbing force probably acts as a modifying cause in many other cases which no one will call exceptions. Thus if it were stated to be a law of nature that all heavy bodies fall to the ground, it would probably be said that the resistance of the atmosphere, which prevents a balloon from falling, constitutes the balloon an exception to that pretended law of nature. But the real law is, that all heavy bodies tend to fall, and to this there is no exception, not even the sun and moon. For even they, as every astronomer knows, tend toward the earth, with a force exactly equal to that with which the earth tends toward them. The resistance of the atmosphere might, in the particular case of the balloon, from a misapprehension of what the law of gravitation is, be said to prevail over the law. But its disturbing effect is quite as real in every other case, since though it does not prevent, it retards the fall of all bodies whatever. The rule, and the so-called exception, do not divide the cases between them. Each of them is a comprehensive rule extending to all cases. To call one of these concurrent principles an exception to the other, is superficial, and contrary to the correct principles of nomenclature and arrangement. An effect of precisely the same kind, and arising from the same cause, ought not to be placed in two different categories, merely as there does or does not exist another cause preponderating over it. 149. Section 6. We have now to consider according to what method these complex effects, compounded of the effects of many causes, are to be studied. How we are enabled to trace each effect to the concurrence of causes in which it originated, and ascertain the conditions of its recurrence, the circumstances in which it may be expected again to occur. The conditions of a phenomenon which arises from a composition of causes, may be investigated either deductively or experimentally. The case, it is evident, is naturally susceptible of the deductive mode of investigation. The law of an effect of this description is a result of the laws of the separate causes on the combination of which it depends, and is, therefore, in itself capable of being deduced from these laws. This is called the method a priori. The other, or a posteriori method, professes to proceed according to the canons of experimental inquiry. Considering the whole assemblage of concurrent causes which produced the phenomenon, as one single cause, it attempts to ascertain the cause in the ordinary manner, by a comparison of instances. This second method subdivides itself into two different varieties. If it merely collates instances of the effect, it is a method of pure observation. If it operates upon the causes, and tries different combinations of them, in hopes of ultimately hitting the precise combination which will produce the given total effect, it is a method of experiment. In order more completely to clear up the nature of each of these three methods, and determine which of them deserves the preference, it will be expedient, conformably to a favorite maxim of Lord Chancellor Eldon, to which, though it has often incurred philosophical ridicule, a deeper philosophy will not refuse its sanction, to clothe them in circumstances. We shall select for this purpose a case which as yet furnishes no very brilliant example of the success of any of the three methods, but which is all the more suited to illustrate the difficulties inherent in them. Let the subject of inquiry be, the conditions of health and disease in the human body, or, for greater simplicity, the conditions of recovery from a given disease. And in order to narrow the question still more, let it be limited, in the first instance, to this one inquiry, is, or is not, some particular medicament, mercury, for instance, a remedy for the given disease. Now, the deductive method would set out from known properties of mercury, and known laws of the human body, and by reasoning from these, would attempt to discover whether mercury will act upon the body when in the morbid condition supposed, in such a manner as would tend to restore health. The experimental method would simply administer mercury in as many cases as possible, noting the age, sex, temperament, and other peculiarities of bodily constitution, the particular form or variety of the disease, the particular stage of its progress, etc. Remarking in which of these cases it was attended with a salutary effect, and with what circumstances it was on those occasions combined. The method of simple observation would compare instances of recovery, to find whether they agreed in having been preceded by the administration of mercury. Or would compare instances of recovery with instances of failure, to find cases which, agreeing in all other respects, differed only in the fact that mercury had been administered, or that it had not. Section 7. That the last of these three modes of investigation is applicable to the case, no one has ever seriously contended. No conclusions of value on a subject of such intricacy ever were obtained in that way. The utmost that could result would be a vague general impression for or against the efficacy of mercury, of no avail for guidance unless confirmed by one of the other two methods. Not that the results, which this method strives to obtain, would not be of the utmost possible value if they could be obtained. If all the cases of recovery which presented themselves, in an examination extending to a great number of instances, were cases in which mercury had been administered, we might generalize with confidence from this experience, and should have obtained a conclusion of real value. But no such basis for generalization can we, in a case of this description, hope to obtain. The reason is that which we have spoken of as constituting the characteristic imperfection of the method of agreement, plurality of causes. Supposing even that mercury does tend to cure the disease, so many other causes, both natural and artificial, also tend to cure it, that there are sure to be abundant instances of recovery in which mercury has not been administered, unless, indeed, the practice be to administer it in all cases. On which supposition it will equally be found in the cases of failure. When an effect results from the union of many causes, the share which each has in the determination of the effect cannot in general be great, and the effect is not likely, even in its presence or absence, still less in its variations, to follow, even approximately, any one of the causes. Recovery from a disease is an event to which, in every case, many influences must concur. Mercury may be one such influence. But from the very fact that there are many other such, it will necessarily happen that although mercury is administered, the patient, for want of other concurring influences, will often not recover. And that he often will recover when it is not administered, the other favorable influences being sufficiently powerful without it. Neither, therefore, will the instances of recovery agree in the administration of mercury, nor will the instances of failure agree in its non-administration. It is much if, by multiplied and accurate returns from hospitals and the like, we can collect that there are rather more recoveries and rather fewer failures when mercury is administered than when it is not. A result of very secondary value even as a guide to practice, and almost worthless as a contribution to the theory of the subject. 150. Section 8. The inapplicability of the method of simple observation to ascertain the conditions of effects dependent on many concurring causes, being thus recognized. We shall next inquire whether any greater benefit can be expected from the other branch of the a posteriori method, that which proceeds by directly trying different combinations of causes, either artificially produced or found in nature, and taking notice what is their effect. As, for example, by actually trying the effect of mercury in as many different circumstances as possible. This method differs from the one which we have just examined in turning our attention directly to the causes or agents, instead of turning it to the effect, recovery from the disease. And since, as a general rule, the effects of causes are far more accessible to our study than the causes of effects, it is natural to think that this method has a much better chance of proving successful than the former. The method now under consideration is called the empirical method, and in order to estimate it fairly, we must suppose it to be completely, not incompletely, empirical. We must exclude from it everything which partakes of the nature not of an experimental but of a deductive operation. If, for instance, we try experiments with mercury upon a person in health, in order to ascertain the general laws of its action upon the human body, and then reason from these laws to determine how it will act upon persons affected with a particular disease, this may be a really effectual method. But this is deduction. The experimental method does not derive the law of a complex case from the simpler laws which conspire to produce it, but makes its experiments directly upon the complex case. We must make entire abstraction of all knowledge of the simpler tendencies, the modi operandi of mercury in detail. Our experimentation must aim at obtaining a direct answer to the specific question, does or does not mercury tend to cure the particular disease? Let us see, therefore, how far the case admits of the observance of those rules of experimentation which it is found necessary to observe in other cases. When we devise an experiment to ascertain the effect of a given agent, there are certain precautions which we never, if we can help it, omit. In the first place, we introduce the agent into the midst of a set of circumstances which we have exactly ascertained. It needs hardly be remarked how far this condition is from being realized in any case connected with the phenomena of life. How far we are from knowing what are all the circumstances which pre-exist in any instance in which mercury is administered to a living being. This difficulty, however, though insuperable in most cases, may not be so in all. There are sometimes concurrences of many causes, in which we yet know accurately what the causes are. Moreover, the difficulty may be attenuated by sufficient multiplication of experiments, in circumstances rendering it improbable that any of the unknown causes should exist in them all. But when we have got clear of this obstacle, we encounter another still more serious. In other cases, when we intend to try an experiment, we do not reckon it enough that there be no circumstance in the case the presence of which is unknown to us. We require, also, that none of the circumstances which we do know shall have effects susceptible of being confounded with those of the agents whose properties we wish to study. We take the utmost pains to exclude all causes capable of composition with the given cause. Or, if forced to let in any such causes, we take care to make them such that we can compute and allow for their influence, so that the effect of the given cause may, after the subduction of those other effects, be apparent as a residual phenomenon. These precautions are inapplicable to such cases as we are now considering. The mercury of our experiment being tried with an unknown multitude, or even let it be a known multitude, of other influencing circumstances. The mere fact of there being influencing circumstances implies that they disguise the effect of the mercury, and preclude us from knowing whether it has any effect or not. Unless we already knew what and how much is owing to every other circumstance, that is, unless we suppose the very problem solved which we are considering the means of solving, we cannot tell that those other circumstances may not have produced the whole of the effect, independently or even in spite of the mercury. The method of difference, in the ordinary mode of its use, namely, by comparing the state of things following the experiment with the state which preceded it, is thus, in the case of intermixture of effects, entirely unavailing. Because other causes than that whose effect we are seeking to determine have been operating during the transition. As for the other mode of employing the method of difference, namely, by comparing, not the same case at two different periods, but different cases, this in the present instance is quite chimerical. In phenomena so complicated it is questionable if two cases, similar in all respects but one, ever occurred, and were they to occur, we could not possibly know that they were so exactly similar. Anything like a scientific use of the method of experiment, in these complicated cases, is therefore out of the question. We can generally, even in the most favorable cases, only discover by a succession of trials, that a certain cause is very often followed by a certain effect. For, in one of these conjunct effects, the portion which is determined by any one of the influencing agents, is usually, as we before remarked, but small. And it must be a more potent cause than most, if even the tendency which it really exerts is not thwarted by other tendencies in nearly as many cases as it is fulfilled. Some causes indeed there are which are more potent than any counteracting causes to which they are commonly exposed, and accordingly there are some truths in medicine which are sufficiently proved by direct experiment. Of these the most familiar are those that relate to the efficacy of the substances known as specifics for particular diseases, quinine, colchicum, lime juice, cod liver oil, 151 and a few others. Even these are not invariably followed by success. But they succeed in so large a proportion of cases, and against such powerful obstacles, that their tendency to restore health in the disorders for which they are prescribed may be regarded as an experimental truth. 152. If so little can be done by the experimental method to determine the conditions of an effect of many combined causes, in the case of medical science, still less is this method applicable to a class of phenomena more complicated than even those of physiology, the phenomena of politics and history. There, plurality of causes exists in almost boundless excess, and effects are, for the most part, inextricably interwoven with one another. To add to the embarrassment, most of the inquiries in political science relate to the production of effects of a most comprehensive description, such as the public wealth, public security, public morality, and the like, results liable to be affected directly or indirectly either in plus or in minus by nearly every fact which exists, or event which occurs, in human society. The vulgar notion, that the safe methods on political subjects are those of Baconian induction, that the true guide is not general reasoning, but specific experience, will one day be quoted as among the most unequivocal marks of a low state of the speculative faculties in any age in which it is accredited. Nothing can be more ludicrous than the sort of parodies on experimental reasoning which one is accustomed to meet with, not in popular discussion only, but in grave treatises, when the affairs of nations are the theme. How, it is asked, can an institution be bad, when the country has prospered under it? How can such or such causes have contributed to the prosperity of one country, when another has prospered without them? Whoever makes use of an argument of this kind, not intending to deceive, should be sent back to learn the elements of some one of the more easy physical sciences. Such reasoners ignore the fact of plurality of causes in the very case which affords the most signal example of it. So little could be concluded, in such a case, from any possible collation of individual instances, that even the impossibility, in social phenomena, of making artificial experiments, a circumstance otherwise so prejudicial to directly inductive inquiry, hardly affords, in this case, additional reason of regret. For even if we could try experiments upon a nation or upon the human race, with as little scruple as M. Magendie tried them on dogs and rabbits, we should never succeed in making two instances identical in every respect except the presence or absence of some one definite circumstance. The nearest approach to an experiment in the philosophical sense, which takes place in politics, is the introduction of a new operative element into national affairs by some special and assignable measure of government, such as the enactment or repeal of a particular law. But where there are so many influences at work, it requires some time for the influence of any new cause upon national phenomena to become apparent. And as the causes operating in so extensive a sphere are not only infinitely numerous, but in a state of perpetual alteration, it is always certain that before the effect of the new cause becomes conspicuous enough to be a subject of induction, so many of the other influencing circumstances will have changed as to vitiate the experiment. 153. 2. Therefore, of the three possible methods for the study of phenomena resulting from the composition of many causes, being, from the very nature of the case, inefficient and illusory, there remains only the third, that which considers the causes separately, and infers the effect from the balance of the different tendencies which produce it, in short, the deductive, or a priori method. The more particular consideration of this intellectual process requires a chapter to itself. 11. Of the Deductive Method. Section 1. The mode of investigation which, from the proved inapplicability of direct methods of observation and experiment, remains to us as the main source of the knowledge we possess or can acquire respecting the conditions and laws of recurrence of the more complex phenomena, is called, in its most general expression, the deductive method, and consists of three operations, the first, one of direct induction, the second, of ratiocination, the third, of verification. I call the first step in the process an inductive operation, because there must be a direct induction as the basis of the whole, though in many particular investigations the place of the induction may be supplied by a prior deduction. But the premises of this prior deduction must have been derived from induction. The problem of the deductive method is, to find the law of an effect, from the laws of the different tendencies of which it is the joint result. The first requisite, therefore, is to know the laws of those tendencies, the law of each of the concurrent causes, and this supposes a previous process of observation or experiment upon each cause separately. Or else a previous deduction, which also must depend for its ultimate premises on observation or experiment. Thus, if the subject be social or historical phenomena, the premises of the deductive method must be the laws of the causes which determine that class of phenomena. And those causes are human actions, together with the general outward circumstances under the influence of which mankind are placed, and which constitute man's position on the earth. The deductive method, applied to social phenomena, must begin, therefore, by investigating, or must suppose to have been already investigated, the laws of human action, and those properties of outward things by which the actions of human beings in society are determined. Some of these general truths will naturally be obtained by observation and experiment, others by deduction. The more complex laws of human action, for example, may be deduced from the simpler ones. But the simple or elementary laws will always, and necessarily, have been obtained by a directly inductive process. To ascertain, then, the laws of each separate cause which takes a share in producing the effect, is the first desideratum of the deductive method. To know what the causes are which must be subjected to this process of study, may or may not be difficult. In the case last mentioned, this first condition is of easy fulfillment. That social phenomena depend on the acts and mental impressions of human beings, never could have been a matter of any doubt, however imperfectly it may have been known either by what laws those impressions and actions are governed, or to what social consequences their laws naturally lead. Neither, again, after physical science had attained a certain development, could there be any real doubt where to look for the laws on which the phenomena of life depend, since they must be the mechanical and chemical laws of the solid and fluid substances composing the organized body and the medium in which it subsists, together with the peculiar vital laws of the different tissues constituting the organic structure. In other cases, really far more simple than these, it was much less obvious in what quarter the causes were to be looked for, as in the case of the celestial phenomena. Until, by combining the laws of certain causes, it was found that those laws explained all the facts which experience had proved concerning the heavenly motions, and led to predictions which it always verified. Mankind never knew that those were the causes. But whether we are able to put the question before, or not until after, we have become capable of answering it, in either case it must be answered. The laws of the different causes must be ascertained, before we can proceed to deduce from them the conditions of the effect. The mode of ascertaining those laws neither is, nor can be any other than the fourfold method of experimental inquiry, already discussed. A few remarks on the application of that method to cases of the composition of causes are all that is requisite. It is obvious that we cannot expect to find the law of a tendency by an induction from cases in which the tendency is counteracted. The laws of motion could never have been brought to light from the observation of bodies kept at rest by the equilibrium of opposing forces. Even where the tendency is not, in the ordinary sense of the word, counteracted, but only modified, by having its effects compounded with the effects arising from some other tendency or tendencies, we are still in an unfavorable position for tracing, by means of such cases, the law of the tendency itself. It would have been scarcely possible to discover the law that every body in motion tends to continue moving in a straight line, by an induction from instances in which the motion is deflected into a curve, by being compounded with the effect of an accelerating force. Notwithstanding the resources afforded in this description of cases by the method of concomitant variations, the principles of a judicious experimentation prescribe that the law of each of the tendencies should be studied, if possible. In cases in which that tendency operates alone, or in combination with no agencies but those of which the effect can, from previous knowledge, be calculated and allowed for. Accordingly, in the cases, unfortunately very numerous and important, in which the causes do not suffer themselves to be separated and observed apart, there is much difficulty in laying down with due certainty the inductive foundation necessary to support the deductive method. This difficulty is most of all conspicuous in the case of physiological phenomena. It being seldom possible to separate the different agencies which collectively compose an organized body, without destroying the very phenomena which it is our object to investigate. Following life, in creatures we dissect. We lose it. In the moment we detect. And for this reason I am inclined to the opinion that physiology, greatly and rapidly progressive as it now is embarrassed by greater natural difficulties, and is probably susceptible of a less degree of ultimate perfection than even the social science. Inasmuch as it is possible to study the laws and operations of one human mind apart from other minds, much less imperfectly than we can study the laws of one organ or tissue of the human body apart from the other organs or tissues. It has been judiciously remarked that pathological facts, or, to speak in common language, diseases in their different forms and degrees afford in the case of physiological investigation the most valuable equivalent to experimentation properly so called. Inasmuch as they often exhibit to us a definite disturbance in some one organ or organic function, the remaining organs and functions being, in the first instance at least, unaffected. It is true that from the perpetual actions and reactions which are going on among all parts of the organic economy, there can be no prolonged disturbance in any one function without ultimately involving many of the others. And when once it has done so, the experiment for the most part loses its scientific value. All depends on observing the early stages of the derangement, which, unfortunately, are of necessity the least marked. If, however, the organs and functions not disturbed in the first instance become affected in a fixed order of succession, some light is thereby thrown upon the action which one organ exercises over another, and we occasionally obtain a series of effects which we can refer with some confidence to the original local derangement. But for this it is necessary that we should know that the original derangement was local. If it was what is termed constitutional. That is, if we do not know in what part of the animal economy it took its rise, or the precise nature of the disturbance which took place in that part, we are unable to determine which of the various derangements was cause and which effect. Which of them were produced by one another, and which by the direct, though perhaps tardy, action of the original cause. Besides natural pathological facts, we can produce pathological facts artificially. We can try experiments, even in the popular sense of the term, by subjecting the living being to some external agent, such as the mercury of our former example, or the section of a nerve to ascertain the functions of different parts of the nervous system. As this experimentation is not intended to obtain a direct solution of any practical question, but to discover general laws, from which afterward the conditions of any particular effect may be obtained by deduction. The best cases to select are those of which the circumstances can be best ascertained, and such are generally not those in which there is any practical object in view. The experiments are best tried, not in a state of disease, which is essentially a changeable state, but in the condition of health, comparatively a fixed state. In the one, unusual agencies are at work, the results of which we have no means of predicting; in the other, the course of the accustomed physiological phenomena would, it may generally be presumed, remain undisturbed, were it not for the disturbing cause which we introduce. Such, with the occasional aid of the method of concomitant variations, the latter not less encumbered than the more elementary methods by the peculiar difficulties of the subject, are our inductive resources for ascertaining the laws of the causes considered separately, when we have it not in our power to make trial of them in a state of actual separation. The insufficiency of these resources is so glaring, that no one can be surprised at the backward state of the science of physiology, in which indeed our knowledge of causes is so imperfect, that we can neither explain, nor could without specific experience have predicted, many of the facts which are certified to us by the most ordinary observation. Fortunately, we are much better informed as to the empirical laws of the phenomena, that is, the uniformities respecting which we cannot yet decide whether they are cases of causation, or mere results of it. Not only has the order in which the facts of organization and life successively manifest themselves, from the first germ of existence to death, been found to be uniform, and very accurately ascertainable, but, by a great application of the method of concomitant variations to the entire facts of comparative anatomy and physiology, the characteristic organic structure corresponding to each class of functions has been determined with considerable precision. Whether these organic conditions are the whole of the conditions, and in many cases whether they are conditions at all, or mere collateral effects of some common cause, we are quite ignorant. Nor are we ever likely to know, unless we could construct an organized body and try whether it would live. Under such disadvantages do we, in cases of this description, attempt the initial, or inductive step, in the application of the deductive method to complex phenomena. But such, fortunately, is not the common case. In general, the laws of the causes on which the effect depends may be obtained by an induction from comparatively simple instances, or, at the worst, by deduction from the laws of simpler causes, so obtained. By simple instances are meant, of course, those in which the action of each cause was not intermixed or interfered with, or not to any great extent, by other causes whose laws were unknown. And only when the induction which furnished the premises to the deductive method rested on such instances has the application of such a method to the ascertainment of the laws of a complex effect been attended with brilliant results. Section 2. When the laws of the causes have been ascertained, and the first stage of the great logical operation now under discussion satisfactorily accomplished, the second part follows. That of determining from the laws of the causes what effect any given combination of those causes will produce. This is a process of calculation, in the wider sense of the term. And very often involves processes of calculation in the narrowest sense. It is a ratiocination. And when our knowledge of the causes is so perfect as to extend to the exact numerical laws which they observe in producing their effects, the ratiocination may reckon among its premises the theorems of the science of number. In the whole immense extent of that science, not only are the most advanced truths of mathematics often required to enable us to compute an effect, the numerical law of which we already know, but, even by the aid of those most advanced truths, we can go but a little way. In so simple a case as the common problem of three bodies gravitating toward one another, with a force directly as their mass and inversely as the square of the distance. All the resources of the calculus have not hitherto sufficed to obtain any general solution, but an approximate one. In a case a little more complex, but still one of the simplest which arise in practice, that of the motion of a projectile. The causes which affect the velocity and range, for example, of a cannonball may be all known and estimated, the force of the gunpowder, the angle of elevation, the density of the air, the strength and direction of the wind. But it is one of the most difficult of mathematical problems to combine all these, so as to determine the effect resulting from their collective action. Besides the theorems of number, those of geometry also come in as premises, where the effects take place in space, and involve motion and extension, as in mechanics, optics, acoustics, astronomy. But when the complication increases, and the effects are under the influence of so many and such shifting causes as to give no room either for fixed numbers, or for straight lines and regular curves, as in the case of physiological, to say nothing of mental and social phenomena, the laws of number and extension are applicable, if at all, only on that large scale on which precision of details becomes unimportant. Although these laws play a conspicuous part in the most striking examples of the investigation of nature by the deductive method, as for example in the Newtonian theory of the celestial motions, they are by no means an indispensable part of every such process. All that is essential in it is reasoning from a general law to a particular case, that is, determining by means of the particular circumstances of that case, what result is required in that instance to fulfill the law. Thus in the Torricellian experiment, if the fact that air has weight had been previously known, it would have been easy, without any numerical data, to deduce from the general law of equilibrium that the mercury would stand in the tube at such a height that the column of mercury would exactly balance a column of the atmosphere of equal diameter. Because, otherwise, equilibrium would not exist. By such ratiocinations from the separate laws of the causes, we may, to a certain extent, succeed in answering either of the following questions: given a certain combination of causes, what effect will follow? And, what combination of causes, if it existed, would produce a given effect? In the one case, we determine the effect to be expected in any complex circumstances of which the different elements are known. In the other case we learn, according to what law, under what antecedent conditions, a given complex effect will occur. Section 3. But, it may here be asked, are not the same arguments by which the methods of direct observation and experiment were set aside as illusory when applied to the laws of complex phenomena, applicable with equal force against the method of deduction? When in every single instance a multitude, often an unknown multitude, of agencies, are clashing and combining, what security have we that in our computation a priori we have taken all these into our reckoning? how many must we not generally be ignorant of? Among those which we know, how probable that some have been overlooked. And, even were all included, how vain the pretense of summing up the effects of many causes, unless we know accurately the numerical law of each, a condition in most cases not to be fulfilled. And even when it is fulfilled, to make the calculation transcends, in any but very simple cases, the utmost power of mathematical science with all its most modern improvements. These objections have real weight, and would be altogether unanswerable, if there were no test by which, when we employ the deductive method, we might judge whether an error of any of the above descriptions had been committed or not. Such a test, however, there is, and its application forms, under the name of verification, the third essential component part of the deductive method, without which all the results it can give have little other value than that of conjecture. To warrant reliance on the general conclusions arrived at by deduction, these conclusions must be found, on careful comparison, to accord with the results of direct observation wherever it can be had. If, when we have experience to compare with them, this experience confirms them, we may safely trust to them in other cases of which our specific experience is yet to come. But if our deductions have led to the conclusion that from a particular combination of causes a given effect would result, then in all known cases where that combination can be shown to have existed, and where the effect has not followed, we must be able to show, or at least to make a probable surmise, what frustrated it. If we cannot, the theory is imperfect, and not yet to be relied upon. Nor is the verification complete, unless some of the cases in which the theory is borne out by the observed result are of at least equal complexity with any other cases in which its application could be called for. If direct observation and collation of instances have furnished us with any empirical laws of the effect, whether true in all observed cases, or only true for the most part, the most effectual verification of which the theory could be susceptible would be, that it led deductively to those empirical laws. That the uniformities, whether complete or incomplete, which were observed to exist among the phenomena, were accounted for by the laws of the causes, were such as could not but exist if those be really the causes by which the phenomena are produced. Thus it was very reasonably deemed an essential requisite of any true theory of the causes of the celestial motions, that it should lead by deduction to Kepler's laws, which, accordingly, the Newtonian theory did. In order, therefore, to facilitate the verification of theories obtained by deduction, it is important that as many as possible of the empirical laws of the phenomena should be ascertained, by a comparison of instances. Conformably to the method of agreement, as well as, it must be added, that the phenomena themselves should be described, in the most comprehensive as well as accurate manner possible. By collecting from the observation of parts, the simplest possible correct expressions for the corresponding wholes, as when the series of the observed places of a planet was first expressed by a circle, then by a system of epicycles, and subsequently by an ellipse. It is worth remarking, that complex instances which would have been of no use for the discovery of the simple laws into which we ultimately analyze their phenomena, nevertheless, when they have served to verify the analysis, become additional evidence of the laws themselves. Although we could not have got at the law from complex cases, still when the law, got at otherwise, is found to be in accordance with the result of a complex case, that case becomes a new experiment on the law, and helps to confirm what it did not assist to discover. It is a new trial of the principle in a different set of circumstances, and occasionally serves to eliminate some circumstance not previously excluded, and the exclusion of which might require an experiment impossible to be executed. This was strikingly conspicuous in the example formerly quoted, in which the difference between the observed and the calculated velocity of sound was ascertained to result from the heat extricated by the condensation which takes place in each sonorous vibration. This was a trial, in new circumstances, of the law of the development of heat by compression, and it added materially to the proof of the universality of that law. Accordingly, any law of nature is deemed to have gained in point of certainty, by being found to explain some complex case which had not previously been thought of in connection with it. And this indeed is a consideration to which it is the habit of scientific inquirers to attach rather too much value than too little. To the deductive method, thus characterized in its three constituent parts, induction, ratiocination, and verification, the human mind is indebted for its most conspicuous triumphs in the investigation of nature. To it we owe all the theories by which vast and complicated phenomena are embraced under a few simple laws, which, considered as the laws of those great phenomena, could never have been detected by their direct study. We may form some conception of what the method has done for us from the case of the celestial motions, one of the simplest among the greater instances of the composition of causes. Since, except in a few cases not of primary importance, each of the heavenly bodies may be considered, without material inaccuracy, to be never at one time influenced by the attraction of more than two bodies, the Sun and one other planet or satellite, making, with the reaction of the body itself, and the force generated by the body's own motion acting in the direction of the tangent, only four different agents on the concurrence of which the motions of that body depend. A much smaller number, no doubt, than that by which any other of the great phenomena of nature is determined or modified. Yet how could we ever have ascertained the combination of forces on which the motions of the earth and planets are dependent, by merely comparing the orbits or velocities of different planets? Or the different velocities or positions of the same planet? Notwithstanding the regularity which manifests itself in those motions, in a degree so rare among the effects of concurrence of causes. And although the periodical recurrence of exactly the same effect, affords positive proof that all the combinations of causes which occur at all, recur periodically. We should not have known what the causes were, if the existence of agencies precisely similar on our own earth had not, fortunately, brought the causes themselves within the reach of experimentation under simple circumstances. As we shall have occasion to analyze, further on, this great example of the method of deduction, we shall not occupy any time with it here, but shall proceed to that secondary application of the deductive method, the result of which is not to prove laws of phenomena, but to explain them. 12. Of the explanation of laws of nature. Section 1. The deductive operation by which we derive the law of an effect from the laws of the causes, the concurrence of which gives rise to it, may be undertaken either for the purpose of discovering the law or of explaining a law already discovered. The word explanation occurs so continually, and holds so important a place in philosophy, that a little time spent in fixing the meaning of it will be profitably employed. An individual fact is said to be explained, by pointing out its cause, that is, by stating the law or laws of causation, of which its production is an instance. Thus, a conflagration is explained, when it is proved to have arisen from a spark falling into the midst of a heap of combustibles. And in a similar manner, a law or uniformity in nature is said to be explained, when another law or laws are pointed out, of which that law itself is but a case, and from which it could be deduced. Section 2. There are three distinguishable sets of circumstances in which a law of causation may be explained from, or, as it also is often expressed, resolved into, other laws. The first is the case already so fully considered. An intermixture of laws, producing a joint effect equal to the sum of the effects of the causes taken separately. The law of the complex effect is explained, by being resolved into the separate laws of the causes which contribute to it. Thus, the law of the motion of a planet is resolved into the law of the acquired force, which tends to produce a uniform motion in the tangent, and the law of the centripetal force, which tends to produce an accelerating motion toward the Sun. The real motion being a compound of the two. It is necessary here to remark, that in this resolution of the law of a complex effect, the laws of which it is compounded are not the only elements. It is resolved into the laws of the separate causes, together with the fact of their coexistence. The one is as essential an ingredient as the other, whether the object be to discover the law of the effect, or only to explain it. To deduce the laws of the heavenly motions, we require not only to know the law of a rectilineal and that of a gravitative force, but the existence of both these forces in the celestial regions, and even their relative amount. The complex laws of causation are thus resolved into two distinct kinds of elements, the one, simpler laws of causation, the other, in the aptly selected expression of Dr. Chalmers, collocations. The collocations consisting in the existence of certain agents or powers, in certain circumstances of place and time. We shall hereafter have occasion to return to this distinction, and to dwell on it at such length as dispenses with the necessity of further insisting on it here. The first mode, then, of the explanation of laws of causation, is when the law of an effect is resolved into the various tendencies of which it is the result, together with the laws of those tendencies. Section 3. A second case is when, between what seemed the cause and what was supposed to be its effect, further observation detects an intermediate link, a fact caused by the antecedent, and in its turn causing the consequent. So that the cause at first assigned is but the remote cause, operating through the intermediate phenomenon. A seemed the cause of C, but it subsequently appeared that A was only the cause of B, and that it is B which was the cause of C. For example, mankind were aware that the act of touching an outward object caused a sensation. It was subsequently discovered that after we have touched the object, and before we experience the sensation, some change takes place in a kind of thread called a nerve, which extends from our outward organs to the brain. Touching the object, therefore, is only the remote cause of our sensation, that is, not the cause, properly speaking, but the cause of the cause. The real cause of the sensation is the change in the state of the nerve. Future experience may not only give us more knowledge than we now have of the particular nature of this change, but may also interpolate another link, between the contact, for example, of the object with our outward organs, and the production of the change of state in the nerve. There may take place some electric phenomenon, or some phenomenon of a nature not resembling the effects of any known agency. Hitherto, however, no such intermediate link has been discovered, and the touch of the object must be considered, provisionally, as the proximate cause of the affection of the nerve. The sequence, therefore, of a sensation of touch on contact with an object is ascertained not to be an ultimate law. It is resolved, as the phrase is, into two other laws, the law that contact with an object produces an affection of the nerve, and the law that an affection of the nerve produces sensation. To take another example, the more powerful acids corrode or blacken organic compounds. This is a case of causation, but of remote causation, and is said to be explained when it is shown that there is an intermediate link, namely, the separation of some of the chemical elements of the organic structure from the rest, and their entering into combination with the acid. The acid causes this separation of the elements, and the separation of the elements causes the disorganization, and often the charring of the structure. So, again, chlorine extracts coloring matters, whence its efficacy in bleaching, and purifies the air from infection. This law is resolved into the two following laws. Chlorine has a powerful affinity for bases of all kinds, particularly metallic bases and hydrogen. Such bases are essential elements of coloring matters and contagious compounds, which substances, therefore, are decomposed and destroyed by chlorine. Section 4. It is of importance to remark, that when a sequence of phenomena is thus resolved into other laws, they are always laws more general than itself. The law that A is followed by C, is less general than either of the laws which connect B with C and A with B. This will appear from very simple considerations. All laws of causation are liable to be counteracted or frustrated, by the non-fulfillment of some negative condition. The tendency, therefore, of B to produce C may be defeated. Now the law that A produces B, is equally fulfilled whether B is followed by C or not. But the law that A produces C by means of B, is of course only fulfilled when B is really followed by C, and is, therefore, less general than the law that A produces B. It is also less general than the law that B produces C. For B may have other causes besides A. And as A produces C only by means of B, while B produces C, whether it has itself been produced by A or by anything else, the second law embraces a greater number of instances, covers as it were a greater space of ground, than the first. Thus, in our former example, the law that the contact of an object causes a change in the state of the nerve, is more general than the law that contact with an object causes sensation, since, for aught we know, the change in the nerve may equally take place when, from a counteracting cause, as, for instance, strong mental excitement, the sensation does not follow. As in a battle, where wounds are sometimes received without any consciousness of receiving them. And again, the law that change in the state of a nerve produces sensation, is more general than the law that contact with an object produces sensation. Since the sensation equally follows the change in the nerve when not produced by contact with an object, but by some other cause. As in the well-known case, when a person who has lost a limb feels the same sensation which he has been accustomed to call a pain in the limb. Not only are the laws of more immediate sequence into which the law of a remote sequence is resolved, laws of greater generality than that law is, but, as a consequence of, or rather as implied in, their greater generality, they are more to be relied on. There are fewer chances of their being ultimately found not to be universally true. From the moment when the sequence of A and C is shown not to be immediate, but to depend on an intervening phenomenon, then, however constant and invariable the sequence of A and C has hitherto been found, possibilities arise of its failure. Exceeding those which can affect either of the more immediate sequences, A, B, and B, C. The tendency of A to produce C may be defeated by whatever is capable of defeating either the tendency of A to produce B, or the tendency of B to produce C. It is, therefore, twice as liable to failure as either of those more elementary tendencies. And the generalization that A is always followed by C, is twice as likely to be found erroneous. And so of the converse generalization, that C is always preceded and caused by A. Which will be erroneous not only if there should happen to be a second immediate mode of production of C itself, but moreover if there be a second mode of production of B, the immediate antecedent of C in the sequence. The resolution of the one generalization into the other two, not only shows that there are possible limitations of the former, from which its two elements are exempt, but shows also where these are to be looked for. As soon as we know that B intervenes between A and C, we also know that if there be cases in which the sequence of A and C does not hold, these are most likely to be found by studying the effects or the conditions of the phenomenon B. It appears, then, that in the second of the three modes in which a law may be resolved into other laws, the latter are more general, that is, extend to more cases, and are also less likely to require limitation from subsequent experience than the law which they serve to explain. They are more nearly unconditional, they are defeated by fewer contingencies, they are a nearer approach to the universal truth of nature. The same observations are still more evidently true with regard to the first of the three modes of resolution. When the law of an effect of combined forces is resolved into the separate laws of the causes, the nature of the case implies that the law of the effect is less general than the law of any of the causes, since it only holds when they are combined. While the law of any one of the causes holds good both then, and also when that cause acts apart from the rest. It is also manifest that the complex law is liable to be oftener unfulfilled than any one of the simpler laws of which it is the result, since every contingency which defeats any of the laws prevents so much of the effect as depends on it, and thereby defeats the complex law. The mere rusting, for example, of some small part of a great machine, often suffices entirely to prevent the effect which ought to result from the joint action of all the parts. The law of the effect of a combination of causes is always subject to the whole of the negative conditions which attach to the action of all the causes severally. There is another and an equally strong reason why the law of a complex effect must be less general than the laws of the causes which conspire to produce it. The same causes, acting according to the same laws, and differing only in the proportions in which they are combined, often produce effects which differ not merely in quantity, but in kind. The combination of a centripetal with a projectile force, in the proportions which obtain in all the planets and satellites of our solar system, gives rise to an elliptical motion. But if the ratio of the two forces to each other were slightly altered, it is demonstrated that the motion produced would be in a circle, or a parabola, or an hyperbola. And it is thought that in the case of some comets one of these is probably the fact. Yet the law of the parabolic motion would be resolvable into the very same simple laws into which that of the elliptical motion is resolved, namely, the law of the permanence of rectilineal motion, and the law of gravitation. If, therefore, in the course of ages, some circumstance were to manifest itself which, without defeating the law of either of those forces, should merely alter their proportion to one another, such as the shock of some solid body, Or even the accumulating effect of the resistance of the medium in which astronomers have been led to surmise that the motions of the heavenly bodies take place, the elliptical motion might be changed into a motion in some other conic section. And the complex law, that the planetary motions take place in ellipses, would be deprived of its universality, though the discovery would not at all detract from the universality of the simpler laws into which that complex law is resolved. The law, in short, of each of the concurrent causes remains the same, however their collocations may vary, but the law of their joint effect varies with every difference in the collocations. There needs no more to show how much more general the elementary laws must be than any of the complex laws which are derived from them. Section 5. Besides the two modes which have been treated of, there is a third mode in which laws are resolved into one another, and in this it is self-evident that they are resolved into laws more general than themselves. This third mode is the subsumption, as it has been called, of one law under another, or, what comes to the same thing, the gathering up of several laws into one more general law which includes them all. The most splendid example of this operation was when terrestrial gravity and the central force of the solar system were brought together under the general law of gravitation. It had been proved antecedently that the Earth and the other planets tend to the Sun, and it had been known from the earliest times that terrestrial bodies tend toward the Earth. These were similar phenomena. And to enable them both to be subsumed under one law, it was only necessary to prove that, as the effects were similar in quality so also they, as to quantity, conformed to the same rules. This was first shown to be true of the Moon, which agreed with terrestrial objects not only in tending to a center, but in the fact that this center was the Earth. The tendency of the Moon toward the Earth being ascertained to vary as the inverse square of the distance, it was deduced from this, by direct calculation, that if the Moon were as near to the Earth as terrestrial objects are, and the acquired force in the direction of the tangent were suspended, the Moon would fall toward the Earth through exactly as many feet in a second as those objects do by virtue of their weight. Hence the inference was irresistible, that the Moon also tends to the Earth by virtue of its weight, and that the two phenomena, the tendency of the Moon to the Earth and the tendency of terrestrial objects to the Earth, being not only similar in quality, but, when in the same circumstances, identical in quantity, are cases of one and the same law of causation. But the tendency of the Moon to the Earth, and the tendency of the Earth and planets to the Sun, were already known to be cases of the same law of causation. And thus the law of all these tendencies, and the law of terrestrial gravity, were recognized as identical, and were subsumed under one general law, that of gravitation. In a similar manner, the laws of magnetic phenomena have more recently been subsumed under known laws of electricity. It is thus that the most general laws of nature are usually arrived at, we mount to them by successive steps. For, to arrive by correct induction at laws which hold under such an immense variety of circumstances, laws so general as to be independent of any varieties of space or time which we are able to observe, requires for the most part many distinct sets of experiments or observations, conducted at different times and by different people. One part of the law is first ascertained, afterward another part. One set of observations teaches us that the law holds good under some conditions, another that it holds good under other conditions. By combining which observations we find that it holds good under conditions much more general, or even universally. The general law, in this case, is literally the sum of all the partial ones. It is a recognition of the same sequence in different sets of instances, and may, in fact, be regarded as merely one step in the process of elimination. The tendency of bodies toward one another, which we now call gravity, had at first been observed only on the Earth's surface, where it manifested itself only as a tendency of all bodies toward the Earth, and might, therefore, be ascribed to a peculiar property of the Earth itself. One of the circumstances, namely, the proximity of the Earth, had not been eliminated. To eliminate this circumstance required a fresh set of instances in other parts of the universe. These we could not ourselves create, and though nature had created them for us, we were placed in very unfavorable circumstances for observing them. To make these observations, fell naturally to the lot of a different set of persons from those who studied terrestrial phenomena. And had, indeed, been a matter of great interest at a time when the idea of explaining celestial facts by terrestrial laws was looked upon as the confounding of an indefeasible distinction. When, however, the celestial motions were accurately ascertained, and the deductive processes performed, from which it appeared that their laws and those of terrestrial gravity corresponded, those celestial observations became a set of instances which exactly eliminated the circumstance of proximity to the earth, and proved that in the original case, that of terrestrial objects, it was not the earth, as such, that caused the motion or the pressure, but the circumstance common to that case with the celestial instances, namely, the presence of some great body within certain limits of distance. Section 6. There are, then, three modes of explaining laws of causation, or, which is the same thing, resolving them into other laws. First, when the law of an effect of combined causes is resolved into the separate laws of the causes, together with the fact of their combination. Secondly, when the law which connects any two links, not proximate, in a chain of causation, is resolved into the laws which connect each with the intermediate links. Both of these are cases of resolving one law into two or more. In the third, two or more are resolved into one, when, after the law has been shown to hold good in several different classes of cases, we decide that what is true in each of these classes of cases, is true under some more general supposition, consisting of what all those classes of cases have in common. We may here remark that this last operation involves none of the uncertainties attendant on induction by the method of agreement, since we need not suppose the result to be extended by way of inference to any new class of cases different from those by the comparison of which it was engendered. In all these three processes, laws are, as we have seen, resolved into laws more general than themselves, laws extending to all the cases which the former extended to, and others besides. In the first two modes they are also resolved into laws more certain, in other words, more universally true than themselves. They are, in fact, proved not to be themselves laws of nature, the character of which is to be universally true, but results of laws of nature, which may be only true conditionally, and for the most part. No difference of this sort exists in the third case, since here the partial laws are, in fact, the very same law as the general one, and any exception to them would be an exception to it too. By all the three processes, the range of deductive science is extended, since the laws, thus resolved, may be thenceforth deduced demonstratively from the laws into which they are resolved. As already remarked, the same deductive process which proves a law or fact of causation if unknown, serves to explain it when known. The word explanation is here used in its philosophical sense. What is called explaining one law of nature by another, is but substituting one mystery for another, and does nothing to render the general course of nature other than mysterious. We can no more assign a why for the more extensive laws than for the partial ones. The explanation may substitute a mystery which has become familiar, and has grown to seem not mysterious, for one which is still strange. And this is the meaning of explanation, in common parlance. But the process with which we are here concerned often does the very contrary. It resolves a phenomenon with which we are familiar into one of which we previously knew little or nothing. As when the common fact of the fall of heavy bodies was resolved into the tendency of all particles of matter toward one another. It must be kept constantly in view, therefore, that in science, those who speak of explaining any phenomenon mean, or should mean, pointing out not some more familiar, but merely some more general, phenomenon, of which it is a partial exemplification, or some laws of causation which produce it by their joint or successive action, and from which, therefore, its conditions may be determined deductively. Every such operation brings us a step nearer toward answering the question which was stated in a previous chapter as comprehending the whole problem of the investigation of nature, viz. What are the fewest assumptions, which being granted, the order of nature as it exists would be the result? What are the fewest, general propositions from which all the uniformities existing in nature could be deduced? The laws, thus explained or resolved, are sometimes said to be accounted for, but the expression is incorrect, if taken to mean anything more than what has been already stated. In minds not habituated to accurate thinking, there is often a confused notion that the general laws are the causes of the partial ones, that the law of general gravitation, for example, causes the phenomenon of the fall of bodies to the earth. But to assert this would be a misuse of the word cause. Terrestrial gravity is not an effect of general gravitation, but a case of it, that is, one kind of the particular instances in which that general law obtains. To account for a law of nature means, and can mean, nothing more than to assign other laws more general, together with collocations, which laws and collocations being supposed, the partial law follows without any additional supposition. 13. Miscellaneous examples of the explanation of laws of nature. Section 1. The most striking example which the history of science presents, of the explanation of laws of causation and other uniformities of sequence among special phenomena, by resolving them into laws of greater simplicity and generality, is the great Newtonian generalization. Respecting which typical instance, so much having already been said, it is sufficient to call attention to the great number and variety of the special observed uniformities, which are in this case accounted for either as particular cases, or as consequences, of one very simple law of universal nature. The simple fact of a tendency of every particle of matter toward every other particle, varying inversely as the square of the distance, explains the fall of bodies to the earth, the revolutions of the planets and satellites, the motions, so far as known, of comets, and all the various regularities which have been observed in these special phenomena, such as the elliptical orbits, and the variations from exact ellipses, the relation between the solar distances of the planets and the duration of their revolutions, the precession of the equinoxes, the tides, and a vast number of minor astronomical truths. Mention has also been made in the preceding chapter of the explanation of the phenomena of magnetism from laws of electricity. The special laws of magnetic agency having been affiliated by deduction to observed laws of electric action, in which they have ever since been considered to be included as special cases. An example not so complete in itself, but even more fertile in consequences, having been the starting point of the really scientific study of physiology, is the affiliation, commenced by Bichat, and carried on by subsequent biologists, of the properties of the bodily organs, to the elementary properties of the tissues into which they are anatomically decomposed. Another striking instance is afforded by Dalton's generalization, commonly known as the atomic theory. It had been known from the very commencement of accurate chemical observation, that any two bodies combine chemically with one another in only a certain number of proportions. But those proportions were in each case expressed by a percentage, so many parts, by weight, of each ingredient, in 100 of the compound, say 35 and a fraction of one element, 64 and a fraction of the other. In which mode of statement no relation was perceived between the proportion in which a given element combines with one substance, and that in which it combines with others. The great step made by Dalton consisted in perceiving that a unit of weight might be established for each substance, such that by supposing the substance to enter into all its combinations in the ratio either of that unit, or of some low multiple of that unit, all the different proportions, previously expressed by percentages, were found to result. Thus one being assumed as the unit of hydrogen, if 8 were then taken as that of oxygen. The combination of 1 unit of hydrogen with 1 unit of oxygen would produce the exact proportion of weight between the two substances which is known to exist in water. The combination of 1 unit of hydrogen with 2 units of oxygen would produce the proportion which exists in the other compound of the same two elements, called peroxide of hydrogen. And the combinations of hydrogen and of oxygen with all other substances, would correspond with the supposition that those elements enter into combination by single units, or twos, or threes, of the numbers assigned to them, 1 and 8. And the other substances by ones or twos or threes of other determinate numbers proper to each. The result is that a table of the equivalent numbers, or, as they are called, atomic weights, of all the elementary substances, comprises in itself and scientifically explains all the proportions in which any substance, elementary or compound, is found capable of entering into chemical combination with any other substance whatever. Section 2. Some interesting cases of the explanation of old uniformities by newly ascertained laws are afforded by the researches of Professor Graham. That eminent chemist was the first who drew attention to the distinction which may be made of all substances into two classes, termed by him crystalloids and colloids. Or rather, of all states of matter into the crystalloid and the colloidal states, for many substances are capable of existing in either. When in the colloidal state, their sensible properties are very different from those of the same substance when crystallized, or when in a state easily susceptible of crystallization. Colloid substances pass with extreme difficulty and slowness into the crystalline state, and are extremely inert in all the ordinary chemical relations. Substances in the colloid state are almost always, when combined with water, more or less viscous or gelatinous. The most prominent examples of the state are certain animal and vegetable substances, particularly gelatin, albumin, starch, the gums, caramel, tannin, and some others. Among substances not of organic origin, the most notable instances are hydrated silicic acid, and hydrated alumina, with other metallic peroxides of the aluminous class. Now it is found, that while colloidal substances are easily penetrated by water, and by the solutions of crystalloid substances, they are very little penetrable by one another, which enabled Professor Graham to introduce a highly effective process, termed dialysis, for separating the crystalloid substances contained in any liquid mixture. By passing them through a thin septum of colloidal matter, which does not suffer anything colloidal to pass, or suffers it only in very minute quantity. This property of colloids enabled Mr. Graham to account for a number of special results of observation, not previously explained. For instance, while soluble crystalloids are always highly sapid, soluble colloids are singularly insipid, as might be expected. For, as the sentient extremities of the nerves of the palate are probably protected by a colloidal membrane, impermeable to other colloids, a colloid, when tasted, probably never reaches those nerves. Again, it has been observed that vegetable gum is not digested in the stomach, the coats of that organ dialyze the soluble food, absorbing crystalloids, and rejecting all colloids. One of the mysterious processes accompanying digestion, the secretion of free muriatic acid by the coats of the stomach, obtains a probable hypothetical explanation through the same law. Finally, much light is thrown upon the observed phenomena of osmose, the passage of fluids outward and inward through animal membranes, by the fact that the membranes are colloidal. In consequence, the water and saline solutions contained in the animal body pass easily and rapidly through the membranes, while the substances directly applicable to nutrition, which are mostly colloidal, are detained by them. 154. The property which salt possesses of preserving animal substances from putrefaction is resolved by Liebig into two more general laws, the strong attraction of salt for water, and the necessity of the presence of water as a condition of putrefaction. The intermediate phenomenon which is interpolated between the remote cause and the effect, can here be not merely inferred but seen, for it is a familiar fact, that flesh upon which salt has been thrown is speedily found swimming in brine. The second of the two factors, as they may be termed, into which the preceding law has been resolved, the necessity of water to putrefaction, itself affords an additional example of the resolution of laws. The law itself is proved by the method of difference, since flesh completely dried and kept in a dry atmosphere does not putrefy, as we see in the case of dried provisions in human bodies in very dry climates. A deductive explanation of this same law results from Liebig's speculations. The putrefaction of animal and other azotized bodies is a chemical process, by which they are gradually dissipated in a gaseous form, chiefly in that of carbonic acid and ammonia. Now to convert the carbon of the animal substance into carbonic acid requires oxygen, and to convert the azote into ammonia requires hydrogen, which are the elements of water. The extreme rapidity of the putrefaction of azotized substances, compared with the gradual decay of non-azotized bodies, such as wood and the like, by the action of oxygen alone. He explains from the general law that substances are much more easily decomposed by the action of two different affinities upon two of their elements than by the action of only one. Section 3. Among the many important properties of the nervous system which have either been first discovered or strikingly illustrated by Dr. Brown-Sequard, I select the reflex influence of the nervous system on nutrition and secretion. By reflex nervous action is meant, action which one part of the nervous system exerts over another part, without any intermediate action on the brain, and consequently without consciousness. Or which, if it does pass through the brain, at least produces its effects independently of the will. There are many experiments which prove that irritation of a nerve in one part of the body may in this manner excite powerful action in another part. For example, food injected into the stomach through a divided esophagus, nevertheless produces secretion of saliva. Warm water injected into the bowels, and various other irritations of the lower intestines, have been found to excite secretion of the gastric juice, and so forth. The reality of the power being thus proved, its agency explains a great variety of apparently anomalous phenomena, of which I select the following from Dr. Brown-Sequard's lectures on the nervous system. The production of tears by irritation of the eye, or of the mucous membrane of the nose. The secretions of the eye and nose increased by exposure of other parts of the body to cold. Inflammation of the eye, especially when of traumatic origin, very frequently excites a similar affection in the other eye, which may be cured by section of the intervening nerve. Loss of sight sometimes produced by neuralgia, and has been known to be at once cured by the extirpation, for instance, of a carious tooth. Even cataract has been produced in a healthy eye by cataract in the other eye, or by neuralgia, or by a wound of the frontal nerve. The well-known phenomenon of a sudden stoppage of the heart's action, and consequent death, produced by irritation of some of the nervous extremities, e.g. by drinking very cold water, or by a blow on the abdomen, or other sudden excitation of the abdominal sympathetic nerve, though this nerve may be irritated to any extent without stopping the heart's action. If a section be made of the communicating nerves, the extraordinary effects produced on the internal organs by an extensive burn on the surface of the body, consisting in violent inflammation of the tissues of the abdomen, chest, or head, which, when death ensues from this kind of injury, is one of the most frequent causes of it. Paralysis and anesthesia of one part of the body from neuralgia in another part, and muscular atrophy from neuralgia, even when there is no paralysis. Tetanus produced by the lesion of a nerve. Dr. Brown-Sequard thinks it highly probable that hydrophobia is a phenomenon of a similar nature. Morbid changes in the nutrition of the brain and spinal cord, manifesting themselves by epilepsy, chorea, hysteria, and other diseases, occasioned by lesion of some of the nervous extremities in remote places, as by worms, calculi, tumors, carious bones, and in some cases even by very slight irritations of the skin. Section 4. From the foregoing and similar instances, we may see the importance, when a law of nature previously unknown has been brought to light, or when new light has been thrown upon a known law by experiment, of examining all cases which present the conditions necessary for bringing that law into action. A process fertile in demonstrations of special laws previously unsuspected, and explanations of others already empirically known. For instance, Faraday discovered by experiment, that voltaic electricity could be evolved from a natural magnet, provided a conducting body were set in motion at right angles to the direction of the magnet. And this he found to hold not only of small magnets, but of that great magnet, the Earth. The law being thus established experimentally, that electricity is evolved, by a magnet, and a conductor moving at right angles to the direction of its poles, we may now look out for fresh instances in which these conditions meet. Wherever a conductor moves or revolves at right angles to the direction of the Earth's magnetic poles, there we may expect an evolution of electricity. In the northern regions, where the polar direction is nearly perpendicular to the horizon, all horizontal motions of conductors will produce electricity, horizontal wheels, for example, made of metal. Likewise all running streams will evolve a current of electricity, which will circulate round them, and the air thus charged with electricity may be one of the causes of the aurora borealis. In the equatorial regions, on the contrary, upright wheels placed parallel to the equator will originate a voltaic circuit, and waterfalls will naturally become electric. For a second example, it has been proved, chiefly by the researches of Professor Graham, that gases have a strong tendency to permeate animal membranes, and diffuse themselves through the spaces which such membranes enclose, notwithstanding the presence of other gases in those spaces. Proceeding from this general law, and reviewing a variety of cases in which gases lie contiguous to membranes, we are enabled to demonstrate or to explain the following more special laws. First, the human or animal body, when surrounded with any gas not already contained within the body, absorbs it rapidly, such, for instance, as the gases of putrefying matters, which helps to explain malaria. 2d. The carbonic acid gas of effervescing drinks, evolved in the stomach, permeates its membranes, and rapidly spreads through the system. 3d. Alcohol taken into the stomach passes into vapor, and spreads through the system with great rapidity, which, combined with the high combustibility of alcohol, or in other words its ready combination with oxygen, may perhaps help to explain the bodily warmth immediately consequent on drinking spirituous liquors. Fourth, in any state of the body in which peculiar gases are formed within it, these will rapidly exhale through all parts of the body, and hence the rapidity with which, in certain states of disease, the surrounding atmosphere becomes tainted. Fifth, the putrefaction of the interior parts of a carcass will proceed as rapidly as that of the exterior, from the ready passage outward of the gaseous products. Sixth, the exchange of oxygen and carbonic acid in the lungs is not prevented, but rather promoted, by the intervention of the membrane of the lungs and the coats of the blood vessels between the blood and the air. It is necessary, however, that there should be a substance in the blood with which the oxygen of the air may immediately combine. Otherwise, instead of passing into the blood, it would permeate the whole organism, and it is necessary that the carbonic acid, as it is formed in the capillaries, should also find a substance in the blood with which it can combine. Otherwise it would leave the body at all points, instead of being discharged through the lungs. Section 5. The following is a deduction which confirms, by explaining, the empirical generalization, that soda powders weaken the human system. These powders, consisting of a mixture of tartaric acid with bicarbonate of soda, from which the carbonic acid is set free, must pass into the stomach as tartrate of soda. Now, neutral tartrates, citrates, and acetates of the alkalis are found, in their passage through the system, to be changed into carbonates. And to convert a tartrate into a carbonate requires an additional quantity of oxygen, the abstraction of which must lessen the oxygen destined for assimilation with the blood, on the quantity of which the vigorous action of the human system partly depends. The instances of new theories agreeing with and explaining old empiricisms are innumerable. All the just remarks made by experienced persons on human character and conduct are so many special laws, which the general laws of the human mind explain and resolve. The empirical generalizations on which the operations of the arts have usually been founded, are continually justified and confirmed on the one hand, or corrected and improved on the other, by the discovery of the simpler scientific laws on which the efficacy of those operations depends. The effects of the rotation of crops, of the various manures, and other processes of improved agriculture, have been for the first time resolved in our own day into known laws of chemical and organic action, by Davy, Liebig, and others. The processes of the medical art are even now mostly empirical, their efficacy is concluded, in each instance, from a special and most precarious experimental generalization, but as science advances in discovering the simple laws of chemistry and physiology, progress is made in ascertaining the intermediate links in the series of phenomena, and the more general laws on which they depend. And thus, while the old processes are either exploded, or their efficacy, in so far as real, explained, better processes, founded on the knowledge of proximate causes, are continually suggested and brought into use. 155 Many even of the truths of geometry were generalizations from experience before they were deduced from first principles. The quadrature of the cycloid is said to have been first effected by measurement, or rather by weighing a cycloidal card, and comparing its weight with that of a piece of similar card of known dimensions. Section 6. To the foregoing examples from physical science, let us add another from mental. The following is one of the simple laws of mind. Ideas of a pleasurable or painful character form associations more easily and strongly than other ideas, that is, they become associated after fewer repetitions, and the association is more durable. This is an experimental law, grounded on the method of difference. By deduction from this law, many of the more special laws which experience shows to exist among particular mental phenomena may be demonstrated and explained, the ease and rapidity, for instance, with which thoughts connected with our passions or our more cherished interests are excited, and the firm hold which the facts relating to them have on our memory. The vivid recollection we retain of minute circumstances which accompanied any object or event that deeply interested us, and of the times and places in which we have been very happy or very miserable. The horror with which we view the accidental instrument of any occurrence which shocked us, or the locality where it took place, and the pleasure we derive from any memorial of past enjoyment. All these effects being proportional to the sensibility of the individual mind, and to the consequent intensity of the pain or pleasure from which the association originated. It has been suggested by the able writer of a biographical sketch of Dr. Priestley in a monthly periodical 156 that the same elementary law of our mental constitution, suitably followed out, would explain a variety of mental phenomena previously inexplicable, and in particular some of the fundamental diversities of human character and genius. Associations being of two sorts, either between synchronous, or between successive impressions. And the influence of the law which renders associations stronger in proportion to the pleasurable or painful character of the impressions, being felt with peculiar force in the synchronous class of associations. It is remarked by the writer referred to, that in minds of strong organic sensibility synchronous associations will be likely to predominate, producing a tendency to conceive things in pictures and in the concrete. Richly clothed in attributes and circumstances, a mental habit which is commonly called imagination, and is one of the peculiarities of the painter and the poet. While persons of more moderate susceptibility to pleasure and pain will have a tendency to associate facts chiefly in the order of their succession, and such persons, if they possess mental superiority, will addict themselves to history or science rather than to creative art. This interesting speculation the author of the present work has endeavored, on another occasion, to pursue further, and to examine how far it will avail toward explaining the peculiarities of the poetical temperament. 157 It is at least an example which may serve, instead of many others, to show the extensive scope which exists for deductive investigation in the important and hitherto so imperfect science of mind. Section 7. The copiousness with which the discovery and explanation of special laws of phenomena by deduction from simpler and more general ones has here been exemplified, was prompted by a desire to characterize clearly, and place in its due position of importance, the deductive method, which, in the present state of knowledge, is destined henceforth irrevocably to predominate in the course of scientific investigation. A revolution is peaceably and progressively effecting itself in philosophy, the reverse of that to which Bacon has attached his name. That great man changed the method of the sciences from deductive to experimental, and it is now rapidly reverting from experimental to deductive. But the deductions which Bacon abolished were from premises hastily snatched up, or arbitrarily assumed. The principles were neither established by legitimate canons of experimental inquiry, nor the results tested by that indispensable element of a rational deductive method, verification by specific experience. Between the primitive method of deduction and that which I have attempted to characterize, there is all the difference which exists between the Aristotelian physics and the Newtonian theory of the heavens. It would, however, be a mistake to expect that those great generalizations, from which the subordinate truths of the more backward sciences will probably at some future period be deduced by reasoning, as the truths of astronomy are deduced from the generalities of the Newtonian theory, will be found in all, or even in most cases, among truths now known and admitted. We may rest assured, that many of the most general laws of nature are as yet entirely unthought of, and that many others, destined hereafter to assume the same character, are known, if at all, only as laws or properties of some limited class of phenomena. Just as electricity, now recognized as one of the most universal of natural agencies, was once known only as a curious property which certain substances acquired by friction, of first attracting and then repelling light bodies. If the theories of heat, cohesion, crystallization, and chemical action are destined, as there can be little doubt that they are, to become deductive, the truths which will then be regarded as the principia of those sciences would probably, if now announced, appear quite as novel 158 as the law of gravitation appeared to the contemporaries of Newton. Possibly even more so, since Newton's law, after all, was but an extension of the law of weight, that is, of a generalization familiar from of old, and which already comprehended a not inconsiderable body of natural phenomena. The general laws of a similarly commanding character, which we still look forward to the discovery of, may not always find so much of their foundations already laid. These general truths will doubtless make their first appearance in the character of hypotheses. Not proved, nor even admitting of proof, in the first instance, but assumed as premises for the purpose of deducing from them the known laws of concrete phenomena. But this, though their initial, cannot be their final state. To entitle an hypothesis to be received as one of the truths of nature, and not as a mere technical help to the human faculties, it must be capable of being tested by the canons of legitimate induction, and must actually have been submitted to that test. When this shall have been done, and done successfully, premises will have been obtained from which all the other propositions of the science will thenceforth be presented as conclusions, and the science will, by means of a new and unexpected induction, be rendered deductive. 14. Of the limits to the explanation of laws of nature, and of hypotheses. Section 1. The preceding considerations have led us to recognize a distinction between two kinds of laws, or observed uniformities in nature, ultimate laws, and what may be termed derivative laws. Derivative laws are such as are deducible from, and may, in any of the modes which we have pointed out, be resolved into, other and more general ones. Ultimate laws are those which cannot. We are not sure that any of the uniformities with which we are yet acquainted are ultimate laws, but we know that there must be ultimate laws, and that every resolution of a derivative law into more general laws brings us nearer to them. Since we are continually discovering that uniformities, not previously known to be other than ultimate, are derivative, and resolvable into more general laws. Since, in other words, we are continually discovering the explanation of some sequence which was previously known only as a fact, it becomes an interesting question whether there are any necessary limits to this philosophical operation, or whether it may proceed until all the uniform sequences in nature are resolved into some one universal law. For this seems, at first sight, to be the ultimatum toward which the progress of induction by the deductive method, resting on a basis of observation and experiment, is tending. Projects of this kind were universal in the infancy of philosophy. Any speculations which held out a less brilliant prospect being in these early times deemed not worth pursuing. And the idea receives so much apparent countenance from the nature of the most remarkable achievements of modern science, that speculators are even now frequently appearing, who profess either to have solved the problem, or to suggest modes in which it may one day be solved. Even where pretensions of this magnitude are not made, the character of the solutions which are given or sought of particular classes of phenomena, often involve such conceptions of what constitutes explanation, as would render the notion of explaining all phenomena whatever by means of some one cause or law, perfectly admissible. Section 2. It is, therefore, useful to remark that the ultimate laws of nature cannot possibly be less numerous than the distinguishable sensations or other feelings of our nature. Those, I mean, which are distinguishable from one another in quality, and not merely in quantity or degree. For example, since there is a phenomenon sui generis, called color, which our consciousness testifies to be not a particular degree of some other phenomenon, as heat or odor or motion, but intrinsically unlike all others, it follows that there are ultimate laws of color. That though the facts of color may admit of explanation, they never can be explained from laws of heat or odor alone, or of motion alone, but that, however far the explanation may be carried, there will always remain in it a law of color. I do not mean that it might not possibly be shown that some other phenomenon, some chemical or mechanical action, for example, invariably precedes, and is the cause of, every phenomenon of color. But though this, if proved, would be an important extension of our knowledge of nature, it would not explain how or why a motion, or a chemical action, can produce a sensation of color. And, however diligent might be our scrutiny of the phenomena, whatever number of hidden links we might detect in the chain of causation terminating in the color, the last link would still be a law of color, not a law of motion. Nor of any other phenomenon whatever. Nor does this observation apply only to color, as compared with any other of the great classes of sensations, it applies to every particular color, as compared with others. White color can in no manner be explained exclusively by the laws of the production of red color. In any attempt to explain it, we cannot but introduce, as one element of the explanation, the proposition that some antecedent or other produces the sensation of white. The ideal limit, therefore, of the explanation of natural phenomena, toward which as toward other ideal limits we are constantly tending, without the prospect of ever completely attaining it, would be to show that each distinguishable variety of our sensations, or other states of consciousness, has only one sort of cause. That, for example, whenever we perceive a white color, there is some one condition or set of conditions which is always present, and the presence of which always produces in us that sensation. As long as there are several known modes of production of a phenomenon, several different substances, for instance, which have the property of whiteness, and between which we cannot trace any other resemblance, so long it is not impossible that one of these modes of production may be resolved into another, or that all of them may be resolved into some more general mode of production not hitherto recognized. But when the modes of production are reduced to one, we cannot, in point of simplification, go any further. This one may not, after all, be the ultimate mode, there may be other links to be discovered between the supposed cause and the effect. But we can only further resolve the known law, by introducing some other law hitherto unknown, which will not diminish the number of ultimate laws. In what cases, accordingly, has science been most successful in explaining phenomena, by resolving their complex laws into laws of greater simplicity and generality? Hitherto chiefly in cases of the propagation of various phenomena through space. And, first and principally, the most extensive and important of all facts of that description, mechanical motion. Now this is exactly what might be expected from the principles here laid down. Not only is motion one of the most universal of all phenomena, it is also, as might be expected from that circumstance, one of those which, apparently at least, are produced in the greatest number of ways. But the phenomenon itself is always, to our sensations, the same in every respect but degree. Differences of duration or of velocity, are evidently differences in degree only. And differences of direction in space, which alone has any semblance of being a distinction in kind, entirely disappear, so far as our sensations are concerned, by a change in our own position. Indeed, the very same motion appears to us, according to our position, to take place in every variety of direction, and motions in every different direction to take place in the same. And again, motion in a straight line and in a curve are no otherwise distinct than that the one is motion continuing in the same direction, the other is motion which at each instant changes its direction. There is, therefore, according to the principles I have stated, no absurdity in supposing that all motion may be produced in one and the same way, by the same kind of cause. Accordingly, the greatest achievements in physical science have consisted in resolving one observed law of the production of motion into the laws of other known modes of production, or the laws of several such modes into one more general mode. As when the fall of bodies to the earth, and the motions of the planets, were brought under the one law of the mutual attraction of all particles of matter, when the motions said to be produced by magnetism were shown to be produced by electricity. When the motions of fluids in a lateral direction, or even contrary to the direction of gravity, were shown to be produced by gravity, and the like. There is an abundance of distinct causes of motion still unresolved into one another, gravitation, heat, electricity, chemical action, nervous action, and so forth. But whether the efforts of the present generation of savants to resolve all these different modes of production into one are ultimately successful or not, the attempt so to resolve them is perfectly legitimate. For, though these various causes produce, in other respects, sensations intrinsically different, and are not, therefore, capable of being resolved into one another, yet, in so far as they all produce motion, it is quite possible that the immediate antecedent of the motion may in all these different cases be the same. Nor is it impossible that these various agencies themselves may, as the new doctrines assert, all of them have for their own immediate antecedent modes of molecular motion. We need not extend our illustration to other cases, as, for instance, to the propagation of light, sound, heat, electricity, etc. through space, or any of the other phenomena which have been found susceptible of explanation by the resolution of their observed laws into more general laws. Enough has been said to display the difference between the kind of explanation and resolution of laws which is chimerical, and that of which the accomplishment is the great aim of science. And to show into what sort of elements the resolution must be effected, if at all. 159. Section 3. As, however, there is scarcely any one of the principles of a true method of philosophizing which does not require to be guarded against errors on both sides, I must enter a caveat against another misapprehension, of a kind directly contrary to the preceding. M. Kant, among other occasions on which he has condemned, with some asperity, any attempt to explain phenomena which are evidently primordial, meaning, apparently, no more than that every peculiar phenomenon must have at least one peculiar and therefore inexplicable law, has spoken of the attempt to furnish any explanation of the color belonging to each substance. La couleur élémentaire propre à chaque substance, as essentially illusory. No one, says he, in our time attempts to explain the particular specific gravity of each substance or of each structure. Why should it be otherwise as to the specific color, the notion of which is undoubtedly no less primordial? 160. Now although, as he elsewhere observes, a color must always remain a different thing from a weight or a sound, varieties of color might nevertheless follow, or correspond to, given varieties of weight, or sound, or some other phenomenon as different as these are from color itself. It is one question what a thing is, and another what it depends on. And though to ascertain the conditions of an elementary phenomenon is not to obtain any new insight into the nature of the phenomenon itself, that is no reason against attempting to discover the conditions. The interdict against endeavoring to reduce distinctions of color to any common principle, would have held equally good against a like attempt on the subject of distinctions of sound, which nevertheless have been found to be immediately preceded and caused by distinguishable varieties in the vibrations of elastic bodies. Though a sound, no doubt, is quite as different as a color is from any motion of particles, vibratory or otherwise. We might add, that, in the case of colors, there are strong positive indications that they are not ultimate properties of the different kinds of substances, but depend on conditions capable of being superinduced upon all substances. Since there is no substance which cannot, according to the kind of light thrown upon it, be made to assume almost any color. And since almost every change in the mode of aggregation of the particles of the same substance is attended with alterations in its color, and in its optical properties generally, the really weak point in the attempts which have been made to account for colors by the vibrations of a fluid, is not that the attempt itself is unphilosophical, but that the existence of the fluid, and the fact of its vibratory motion, are not proved, but are assumed, on no other ground than the facility they are supposed to afford of explaining the phenomena. And this consideration leads to the important question of the proper use of scientific hypotheses, the connection of which with the subject of the explanation of the phenomena of nature, and of the necessary limits to that explanation, need not be pointed out. Section 4. An hypothesis is any supposition which we make either without actual evidence, or on evidence avowedly insufficient, in order to endeavor to deduce from it conclusions in accordance with facts which are known to be real. Under the idea that if the conclusions to which the hypothesis leads are known truths, the hypothesis itself either must be, or at least is likely to be, true. If the hypothesis relates to the cause or mode of production of a phenomenon, it will serve, if admitted, to explain such facts as are found capable of being deduced from it. And this explanation is the purpose of many, if not most hypotheses. Since explaining, in the scientific sense, means resolving a uniformity which is not a law of causation, into the laws of causation from which it results. Or a complex law of causation into simpler and more general ones from which it is capable of being deductively inferred, if there do not exist any known laws which fulfill this requirement, we may feign or imagine some which would fulfill it. And this is making an hypothesis. An hypothesis being a mere supposition, there are no other limits to hypotheses than those of the human imagination. We may, if we please, imagine, by way of accounting for an effect, some cause of a kind utterly unknown, and acting according to a law altogether fictitious. But as hypotheses of this sort would not have any of the plausibility belonging to those which ally themselves by analogy with known laws of nature, and besides would not supply the want which arbitrary hypotheses are generally invented to satisfy. By enabling the imagination to represent to itself an obscure phenomenon in a familiar light, there is probably no hypothesis in the history of science in which both the agent itself and the law of its operation were fictitious. Either the phenomenon assigned as the cause is real, but the law according to which it acts merely supposed, or the cause is fictitious, but is supposed to produce its effects according to laws similar to those of some known class of phenomena. An instance of the first kind is afforded by the different suppositions made respecting the law of the planetary central force, anterior to the discovery of the true law, that the force varies as the inverse square of the distance. Which also suggested itself to Newton, in the first instance, as an hypothesis, and was verified by proving that it led deductively to Kepler's laws. Hypotheses of the second kind are such as the vortices of Descartes, which were fictitious, but were supposed to obey the known laws of rotatory motion. Or the two rival hypotheses respecting the nature of light, the one ascribing the phenomena to a fluid emitted from all luminous bodies. The other, now generally received, attributing them to vibratory motions among the particles of an ether pervading all space. Of the existence of either fluid there is no evidence, save the explanation they are calculated to afford of some of the phenomena. But they are supposed to produce their effects according to known laws, the ordinary laws of continued locomotion in the one case, and in the other those of the propagation of undulatory movements among the particles of an elastic fluid. According to the foregoing remarks, hypotheses are invented to enable the deductive method to be earlier applied to phenomena. But 161 In order to discover the cause of any phenomenon by the deductive method, the process must consist of three parts: induction, ratiocination, and verification. Induction, the place of which, however, may be supplied by a prior deduction, to ascertain the laws of the causes. Ratiocination, to compute from those laws how the causes will operate in the particular combination known to exist in the case in hand. Verification, by comparing this calculated effect with the actual phenomenon. No one of these three parts of the process can be dispensed with. In the deduction which proves the identity of gravity with the central force of the solar system, all the three are found. First, it is proved from the moon's motions, that the earth attracts her with a force varying as the inverse square of the distance. This, though partly dependent on prior deductions, corresponds to the first, or purely inductive, step, the ascertainment of the law of the cause. Secondly, from this law, and from the knowledge previously obtained of the moon's mean distance from the earth, and of the actual amount of her deflection from the tangent, it is ascertained with what rapidity the earth's attraction would cause the moon to fall, if she were no further off, and no more acted upon by extraneous forces, than terrestrial bodies are, that is the second step, the ratiocination. Finally, this calculated velocity being compared with the observed velocity with which all heavy bodies fall, by mere gravity, toward the surface of the earth, 16 feet in the first second, 48 in the second, and so forth. In the ratio of the odd numbers, 1, 3, 5, etc. The two quantities are found to agree. The order in which the steps are here presented was not that of their discovery. But it is their correct logical order, as portions of the proof that the same attraction of the earth which causes the moon's motion causes also the fall of heavy bodies to the earth, a proof which is thus complete in all its parts. Now, the hypothetical method suppresses the first of the three steps, the induction to ascertain the law, and contents itself with the other two operations, ratiocination and verification. The law which is reason from being assumed instead of proved. This process may evidently be legitimate on one supposition, namely, if the nature of the case be such that the final step, the verification, shall amount to, and fulfill the conditions of, a complete induction. We want to be assured that the law we have hypothetically assumed is a true one, and its leading deductively to true results will afford this assurance, provided the case be such that a false law cannot lead to a true result. Provided no law, except the very one which we have assumed, can lead deductively to the same conclusions which that leads to. And this proviso is often realized. For example, in the very complete specimen of deduction which we just cited, the original major premise of the ratiocination, the law of the attractive force, was ascertained in this mode, by this legitimate employment of the hypothetical method. Newton began by an assumption that the force which at each instant deflects a planet from its rectilineal course, and makes it describe a curve round the sun, is a force tending directly toward the sun. He then proved that if this be so, the planet will describe, as we know by Kepler's first law that it does describe, equal areas in equal times. And, lastly, he proved that if the force acted in any other direction whatever, the planet would not describe equal areas in equal times. It being thus shown that no other hypothesis would accord with the facts, the assumption was proved. The hypothesis became an inductive truth. Not only did Newton ascertain by this hypothetical process the direction of the deflecting force, he proceeded in exactly the same manner to ascertain the law of variation of the quantity of that force. He assumed that the force varied inversely as the square of the distance, showed that from this assumption the remaining two of Kepler's laws might be deduced. And, finally, that any other law of variation would give results inconsistent with those laws, and inconsistent, therefore, with the real motions of the planets, of which Kepler's laws were known to be a correct expression. I have said that in this case the verification fulfills the conditions of an induction, but an induction of what sort? On examination we find that it conforms to the canon of the method of difference. It affords the two instances, A, B, C, and B, C, B, C. A represents central force, A, B, C, the planets plus a central force, B, C, the planets apart from a central force. The planets with a central force give A, areas proportional to the times. The planets without a central force give B, C, a set of motions, without A, or with something else instead of A. This is the method of difference in all its strictness. It is true, the two instances which the method requires are obtained in this case, not by experiment, but by a prior deduction. But that is of no consequence. It is immaterial what is the nature of the evidence from which we derive the assurance that ABC will produce ABC, and BC only BC, it is enough that we have that assurance. In the present case, a process of reasoning furnished Newton with the very instances which, if the nature of the case had admitted of it, he would have sought by experiment. It is thus perfectly possible, and indeed is a very common occurrence, that what was an hypothesis at the beginning of the inquiry becomes a proved law of nature before its close. But in order that this should happen, we must be able, either by deduction or experiment, to obtain both the instances which the method of difference requires. That we are able from the hypothesis to deduce the known facts, gives only the affirmative instance, A, B, C, A, B, C. It is equally necessary that we should be able to obtain, as Newton did, the negative instance B, C, B, C. By showing that no antecedent, except the one assumed in the hypothesis, would in conjunction with B, C produce A. Now it appears to me that this assurance cannot be obtained, when the cause assumed in the hypothesis is an unknown cause imagined solely to account for A. When we are only seeking to determine the precise law of a cause already ascertained, or to distinguish the particular agent which is in fact the cause, among several agents of the same kind, one or other of which it is already known to be. We may then obtain the negative instance. An inquiry which of the bodies of the solar system causes by its attraction some particular irregularity in the orbit or periodic time of some satellite or comet, would be a case of the second description. Newton's was a case of the first. If it had not been previously known that the planets were hindered from moving in straight lines by some force tending toward the interior of their orbit, though the exact direction was doubtful. Or if it had not been known that the force increased in some proportion or other as the distance diminished, and diminished as it increased, Newton's argument would not have proved his conclusion. These facts, however, being already certain, the range of admissible suppositions was limited to the various possible directions of a line, and the various possible numerical relations between the variations of the distance and the variations of the attractive force. Now among these it was easily shown that different suppositions could not lead to identical consequences. Accordingly, Newton could not have performed his second great scientific operation, that of identifying terrestrial gravity with the central force of the solar system by the same hypothetical method. When the law of the moon's attraction had been proved from the data of the moon itself, then, on finding the same law to accord with the phenomena of terrestrial gravity, he was warranted in adopting it as the law of those phenomena likewise. But it would not have been allowable for him, without any lunar data, to assume that the moon was attracted toward the earth with a force as the inverse square of the distance, merely because that ratio would enable him to account for terrestrial gravity. For it would have been impossible for him to prove that the observed law of the fall of heavy bodies to the earth could not result from any force, save one extending to the moon, and proportional to the inverse square. It appears, then, to be a condition of the most genuinely scientific hypothesis, that it be not destined always to remain an hypothesis, but be of such a nature as to be either proved or disproved by comparison with observed facts. This condition is fulfilled when the effect is already known to depend on the very cause supposed, and the hypothesis relates only to the precise mode of dependence. The law of the variation of the effect according to the variations in the quantity or in the relations of the cause. With these may be classed the hypotheses which do not make any supposition with regard to causation, but only with regard to the law of correspondence between facts which accompany each other in their variations, though there may be no relation of cause and effect between them. Such were the different false hypotheses which Kepler made respecting the law of the refraction of light. It was known that the direction of the line of refraction varied with every variation in the direction of the line of incidence, but it was not known how, that is, what changes of the one corresponded to the different changes of the other. In this case any law different from the true one must have led to false results. And, lastly, we must add to these all hypothetical modes of merely representing or describing phenomena, such as the hypothesis of the ancient astronomers that the heavenly bodies moved in circles, the various hypotheses of eccentrics, deferents, and epicycles, which were added to that original hypothesis. The 19 false hypotheses which Kepler made and abandoned respecting the form of the planetary orbits. And even the doctrine in which he finally rested, that those orbits are ellipses, which was but an hypothesis like the rest until verified by facts. In all these cases, verification is proof. If the supposition accords with the phenomena there needs no other evidence of it. But in order that this may be the case, I conceive it to be necessary, when the hypothesis relates to causation, that the supposed cause should not only be a real phenomenon, something actually existing in nature, but should be already known to exercise, or at least to be capable of exercising, an influence of some sort over the effect. In any other case, it is no sufficient evidence of the truth of the hypothesis that we are able to deduce the real phenomena from it. Is it, then, never allowable, in a scientific hypothesis, to assume a cause, but only to ascribe an assumed law to a known cause? I do not assert this. I only say, that in the latter case alone can the hypothesis be received as true merely because it explains the phenomena. In the former case it may be very useful by suggesting a line of investigation which may possibly terminate in obtaining real proof. But for this purpose, as is justly remarked by M. Kant, it is indispensable that the cause suggested by the hypothesis should be in its own nature susceptible of being proved by other evidence. This seems to be the philosophical import of Newton's maxim, so often cited with approbation by subsequent writers, that the cause assigned for any phenomenon must not only be such as if admitted would explain the phenomenon, but must also be a vera causa. What he meant by a vera causa Newton did not indeed very explicitly define, and Dr. Whewell, who dissents from the propriety of any such restriction upon the latitude of framing hypotheses, has had little difficulty in showing 162 that his conception of it was neither precise nor consistent with itself. Accordingly his optical theory was a signal instance of the violation of his own rule. It is certainly not necessary that the cause assigned should be a cause already known. Otherwise we should sacrifice our best opportunities of becoming acquainted with new causes. But what is true in the maxim is, that the cause, though not known previously, should be capable of being known thereafter. That its existence should be capable of being detected, and its connection with the effect ascribed to it should be susceptible of being proved, by independent evidence. The hypothesis, by suggesting observations and experiments, puts us on the road to that independent evidence, if it be really attainable. Until it be attained, the hypothesis ought only to count for a more or less plausible conjecture. Section 5. This function, however, of hypotheses, is one which must be reckoned absolutely indispensable in science. When Newton said, hypotheses non fingo, he did not mean that he deprived himself of the facilities of investigation afforded by assuming in the first instance what he hoped ultimately to be able to prove. Without such assumptions, science could never have attained its present state. They are necessary steps in the progress to something more certain, and nearly everything which is now theory was once hypothesis. Even in purely experimental science, some inducement is necessary for trying one experiment rather than another. And though it is abstractedly possible that all the experiments which have been tried, might have been produced by the mere desire to ascertain what would happen in certain circumstances, without any previous conjecture as to the result. Yet, in point of fact, those unobvious, delicate, and often cumbrous and tedious processes of experiment, which have thrown most light upon the general constitution of nature, would hardly ever have been undertaken by the persons or at the time they were, unless it had seemed to depend on them whether some general doctrine or theory which had been suggested, but not yet proved, should be admitted or not. If this be true even of merely experimental inquiry, the conversion of experimental into deductive truths could still less have been effected without large temporary assistance from hypotheses. The process of tracing regularity in any complicated, and at first sight confused, set of appearances, is necessarily tentative. We begin by making any supposition, even a false one, to see what consequences will follow from it. And by observing how these differ from the real phenomena, we learn what corrections to make in our assumption. The simplest supposition which accords with the more obvious facts is the best to begin with, because its consequences are the most easily traced. This rude hypothesis is then rudely corrected, and the operation repeated. And the comparison of the consequences deducible from the corrected hypothesis, with the observed facts, suggests still further correction, until the deductive results are at last made to tally with the phenomena. Some fact is as yet little understood, or some law is unknown, we frame on the subject an hypothesis as accordant as possible with the whole of the data already possessed. And the science, being thus enabled to move forward freely, always ends by leading to new consequences capable of observation, which either confirm or refute, unequivocally, the first supposition. Neither induction nor deduction would enable us to understand even the simplest phenomena, if we did not often commence by anticipating on the results. By making a provisional supposition, at first essentially conjectural, as to some of the very notions which constitute the final object of the inquiry. 163 Let anyone watch the manner in which he himself unravels a complicated mass of evidence. Let him observe how, for instance, he elicits the true history of any occurrence from the involved statements of one or of many witnesses. He will find that he does not take all the items of evidence into his mind at once, and attempt to weave them together. He extemporizes, from a few of the particulars, a first rude theory of the mode in which the facts took place, and then looks at the other statements one by one, to try whether they can be reconciled with that provisional theory, or what alterations or additions it requires to make it square with them. In this way, which has been justly compared to the methods of approximation of mathematicians, we arrive, by means of hypotheses, at conclusions not hypothetical. 164. Section 6. It is perfectly consistent with the spirit of the method, to assume in this provisional manner not only an hypothesis respecting the law of what we already know to be the cause, but an hypothesis respecting the cause itself. It is allowable, useful, and often even necessary, to begin by asking ourselves what cause may have produced the effect, in order that we may know in what direction to look out for evidence to determine whether it actually did. The vortices of Descartes would have been a perfectly legitimate hypothesis, if it had been possible, by any mode of exploration which we could entertain the hope of ever possessing, to bring the reality of the vortices, as a fact in nature, conclusively to the test of observation. The vice of the hypothesis was that it could not lead to any course of investigation capable of converting it from an hypothesis into a proved fact. It might chance to be disproved, either by some want of correspondence with the phenomena it purported to explain, or, as actually happened, by some extraneous fact. The free passage of comets through the spaces in which these vortices should have been, convinced men that these vortices did not exist. 165. But the hypothesis would have been false, though no such direct evidence of its falsity had been procurable. Direct evidence of its truth there could not be. The prevailing hypothesis of a luminiferous ether, in other respects not without analogy to that of Descartes, is not in its own nature entirely cut off from the possibility of direct evidence in its favor. It is well known that the difference between the calculated and the observed times of the periodical return of Encke's comet, has led to a conjecture that a medium capable of opposing resistance to motion is diffused through space. If this surmise should be confirmed, in the course of ages, by the gradual accumulation of a similar variance in the case of the other bodies of the solar system, the luminiferous ether would have made a considerable advance toward the character of a vera causa, since the existence would have been ascertained of a great cosmical agent, possessing some of the attributes which the hypothesis assumes. Though there would still remain many difficulties, and the identification of the ether with the resisting medium would even, I imagine, give rise to new ones. At present, however, this supposition cannot be looked upon as more than a conjecture. The existence of the ether still rests on the possibility of deducing from its assumed laws a considerable number of actual phenomena. And this evidence I cannot regard as conclusive, because we cannot have, in the case of such an hypothesis, the assurance that if the hypothesis be false it must lead to results at variance with the true facts. Accordingly, most thinkers of any degree of sobriety allow that an hypothesis of this kind is not to be received as probably true because it accounts for all the known phenomena. Since this is a condition sometimes fulfilled tolerably well by two conflicting hypotheses. While there are probably many others which are equally possible, but which, for want of anything analogous in our experience, our minds are unfitted to conceive. But it seems to be thought that an hypothesis of the sort in question is entitled to a more favorable reception, if, besides accounting for all the facts previously known, it has led to the anticipation and prediction of others which experience afterward verified. As the undulatory theory of light led to the prediction, subsequently realized by experiment, that two luminous rays might meet each other in such a manner as to produce darkness. Such predictions and their fulfillment are, indeed, well calculated to impress the uninformed, whose faith in science rests solely on similar coincidences between its prophecies and what comes to pass. But it is strange that any considerable stress should be laid upon such a coincidence by persons of scientific attainments. If the laws of the propagation of light accord with those of the vibrations of an elastic fluid in as many respects as is necessary to make the hypothesis afford a correct expression of all or most of the phenomena known at the time, it is nothing strange that they should accord with each other in one respect more. Though 20 such coincidences should occur, they would not prove the reality of the undulatory ether. It would not follow that the phenomena of light were results of the laws of elastic fluids, but at most that they are governed by laws partially identical with these. Which, we may observe, is already certain, from the fact that the hypothesis in question could be for a moment tenable. 166 cases may be cited, even in our imperfect acquaintance with nature, where agencies that we have good reason to consider as radically distinct produce their effects or some of their effects, according to laws which are identical. The law, for example, of the inverse square of the distance, is the measure of the intensity not only of gravitation, but, it is believed, of illumination, and of heat diffused from a center. Yet no one looks upon this identity as proving similarity in the mechanism by which the three kinds of phenomena are produced. According to Dr. Whewell, the coincidence of results predicted from an hypothesis with facts afterward observed, amounts to a conclusive proof of the truth of the theory. If I copy a long series of letters, of which the last half dozen are concealed, and if I guess these are right, as is found to be the case when they are afterward uncovered, this must be because I have made out the import of the inscription. To say that because I have copied all that I could see, it is nothing strange that I should guess those which I cannot see, would be absurd, without supposing such a ground for guessing. 167 If any one, from examining the greater part of a long inscription, can interpret the characters so that the inscription gives a rational meaning in a known language, there is a strong presumption that his interpretation is correct. But I do not think the presumption much increased by his being able to guess the few remaining letters without seeing them. For we should naturally expect, when the nature of the case excludes chance, that even an erroneous interpretation which accorded with all the visible parts of the inscription would accord also with the small remainder. As would be the case, for example, if the inscription had been designedly so contrived as to admit of a double sense. I assume that the uncovered characters afford an amount of coincidence too great to be merely casual. Otherwise the illustration is not a fair one. No one supposes the agreement of the phenomena of light with the theory of undulations to be merely fortuitous. It must arise from the actual identity of some of the laws of undulations with some of those of light. And if there be that identity, it is reasonable to suppose that its consequences would not end with the phenomena which first suggested the identification, nor be even confined to such phenomena as were known at the time. But it does not follow, because some of the laws agree with those of undulations, that there are any actual undulations. No more than it followed because some, though not so many, of the same laws agreed with those of the projection of particles, that there was actual emission of particles. Even the undulatory hypothesis does not account for all the phenomena of light. The natural colors of objects, the compound nature of the solar ray, the absorption of light, and its chemical and vital action, the hypothesis leaves as mysterious as it found them. And some of these facts are, at least apparently, more reconcilable with the emission theory than with that of Young and Fresnel. Who knows but that some third hypothesis, including all these phenomena, may in time leave the undulatory theory as far behind as that has left the theory of Newton and his successors. To the statement, that the condition of accounting for all the known phenomena is often fulfilled equally well by two conflicting hypotheses, Dr. Whewell makes answer that he knows of no such case in the history of science, where the phenomena are at all numerous and complicated. 168 Such an affirmation, by a writer of Dr. Whewell's minute acquaintance with the history of science, would carry great authority, if he had not, a few pages before, taken pains to refute it. 169 By maintaining that even the exploded scientific hypotheses might always, or almost always, have been so modified as to make them correct representations of the phenomena. The hypothesis of vortices, he tells us, was, by successive modifications, brought to coincide in its results with the Newtonian theory and with the facts. The vortices did not, indeed, explain all the phenomena which the Newtonian theory was ultimately found to account for, such as the precession of the equinoxes. But this phenomenon was not, at the time, in the contemplation of either party, as one of the facts to be accounted for. All the facts which they did contemplate, we may believe on Dr. Whewell's authority to have accorded as accurately with the Cartesian hypothesis, in its finally improved state, as with Newton's. But it is not, I conceive, a valid reason for accepting any given hypothesis, that we are unable to imagine any other which will account for the facts. There is no necessity for supposing that the true explanation must be one which, with only our present experience, we could imagine. Among the natural agents with which we are acquainted, the vibrations of an elastic fluid may be the only one whose laws bear a close resemblance to those of light. But we cannot tell that there does not exist an unknown cause, other than an elastic ether diffused through space, yet producing effects identical in some respects with those which would result from the undulations of such an ether. To assume that no such cause can exist, appears to me an extreme case of assumption without evidence. And at the risk of being charged with want of modesty, I cannot help expressing astonishment that a philosopher of Dr. Wooll's abilities and attainments should have written an elaborate treatise on the philosophy of induction, in which he recognizes absolutely no mode of induction except that of trying hypothesis after hypothesis until one is found which fits the phenomena. Which one, when found, is to be assumed as true, with no other reservation than that if, on re-examination, it should appear to assume more than is needful for explaining the phenomena, the superfluous part of the assumption should be cut off. And this without the slightest distinction between the cases in which it may be known beforehand that two different hypotheses cannot lead to the same result, and those in which, for aught we can ever know, the range of suppositions, all equally consistent with the phenomena, may be infinite. 170. Nevertheless, I do not agree with M. Kant in condemning those who employ themselves in working out into detail the application of these hypotheses to the explanation of ascertained facts, provided they bear in mind that the utmost they can prove is, not that the hypothesis is, but that it may be true. The ether hypothesis has a very strong claim to be so followed out, a claim greatly strengthened since it has been shown to afford a mechanism which would explain the mode of production, not of light only, but also of heat. Indeed, the speculation has a smaller element of hypothesis in its application to heat, than in the case for which it was originally framed. We have proof by our senses of the existence of molecular movement among the particles of all heated bodies, while we have no similar experience in the case of light. When, therefore, heat is communicated from the sun to the earth across apparently empty space, the chain of causation has molecular motion both at the beginning and end. The hypothesis only makes the motion continuous by extending it to the middle. Now, motion in a body is known to be capable of being imparted to another body contiguous to it. And the intervention of a hypothetical elastic fluid occupying the space between the sun and the earth, supplies the contiguity which is the only condition wanting, and which can be supplied by no supposition but that of an intervening medium. The supposition, notwithstanding, is at best a probable conjecture, not a proved truth. For there is no proof that contiguity is absolutely required for the communication of motion from one body to another. Contiguity does not always exist, to our senses at least, in the cases in which motion produces motion. The forces which go under the name of attraction, especially the greatest of all, gravitation, are examples of motion producing motion without apparent contiguity. When a planet moves, its distant satellites accompany its motion. The sun carries the whole solar system along with it in the progress which it is ascertained to be executing through space. And even if we were to accept as conclusive the geometrical reasonings, strikingly similar to those by which the Cartesians defended their vortices, by which it has been attempted to show that the motions of the ether may account for gravitation itself, even then it would only have been proved that the supposed mode of production may be, but not that no other mode can be, the true one. Section 7. It is necessary, before quitting the subject of hypotheses, to guard against the appearance of reflecting upon the scientific value of several branches of physical inquiry, which, though only in their infancy, I hold to be strictly inductive. There is a great difference between inventing agencies to account for classes of phenomena, and endeavoring, in conformity with known laws, to conjecture what former collocations of known agents may have given birth to individual facts still in existence. The latter is the legitimate operation of inferring from an observed effect the existence, in time past, of a cause similar to that by which we know it to be produced in all cases in which we have actual experience of its origin. This, for example, is the scope of the inquiries of geology, and they are no more illogical or visionary than judicial inquiries, which also aim at discovering a past event by inference from those of its effects which still subsist. As we can ascertain whether a man was murdered or died a natural death, from the indications exhibited by the corpse, the presence or absence of signs of struggling on the ground or on the adjacent objects, the marks of blood, the footsteps of the supposed murderers, and so on, proceeding throughout on uniformities ascertained by a perfect induction without any mixture of hypothesis. So if we find, on and beneath the surface of our planet, masses exactly similar to deposits from water, or to results of the cooling of matter melted by fire, we may justly conclude that such has been their origin. And if the effects, though similar in kind, are on a far larger scale than any which are now produced, we may rationally, and without hypothesis, conclude either that the causes existed formerly with greater intensity, or that they have operated during an enormous length of time. Further than this no geologist of authority has, since the rise of the present enlightened school of geological speculation, attempted to go. In many geological inquiries it doubtless happens that though the laws to which the phenomena are ascribed are known laws, and the agents known agents, those agents are not known to have been present in a particular case. In the speculation respecting the igneous origin of trap or granite, the fact does not admit of direct proof that those substances have been actually subjected to intense heat. But the same thing might be said of all judicial inquiries which proceed on circumstantial evidence. We can conclude that a man was murdered, though it is not proved by the testimony of eyewitnesses that some person who had the intention of murdering him was present on the spot. It is enough for most purposes, if no other known cause could have generated the effects shown to have been produced. The celebrated speculation of Laplace concerning the origin of the earth and planets, participates essentially in the inductive character of modern geological theory. The speculation is, that the atmosphere of the Sun originally extended to the present limits of the solar system, from which, by the process of cooling, it has contracted to its present dimensions. And since, by the general principles of mechanics the rotation of the Sun and of its accompanying atmosphere must increase in rapidity as its volume diminishes, the increased centrifugal force generated by the more rapid rotation, overbalancing the action of gravitation, has caused the Sun to abandon successive rings of vaporous matter, which are supposed to have condensed by cooling, and to have become the planets. There is in this theory no unknown substance introduced on supposition, nor any unknown property or law ascribed to a known substance. The known laws of matter authorize us to suppose that a body which is constantly giving out so large an amount of heat as the Sun is, must be progressively cooling, and that, by the process of cooling it must contract. If, therefore, we endeavor, from the present state of that luminary, to infer its state in a time long past, we must necessarily suppose that its atmosphere extended much farther than at present. And we are entitled to suppose that it extended as far as we can trace effects such as it might naturally leave behind it on retiring. And such the planets are. These suppositions being made, it follows from known laws that successive zones of the solar atmosphere might be abandoned. That these would continue to revolve round the Sun with the same velocity as when they formed part of its substance. And that they would cool down, long before the Sun itself, to any given temperature, and consequently to that at which the greater part of the vaporous matter of which they consisted would become liquid or solid. The known law of gravitation would then cause them to agglomerate in masses, which would assume the shape our planets actually exhibit, would acquire, each about its own axis, a rotatory movement, and would in that state revolve, as the planets actually do, about the Sun, in the same direction with the Sun's rotation, but with less velocity. Because in the same periodic time which the Sun's rotation occupied when his atmosphere extended to that point. There is thus, in Laplace's theory, nothing, strictly speaking, hypothetical. It is an example of legitimate reasoning from a present effect to a possible past cause, according to the known laws of that cause. The theory, therefore, is, as I have said, of a similar character to the theories of geologists, but considerably inferior to them in point of evidence. Even if it were proved, which it is not, that the conditions necessary for determining the breaking off of successive rings would certainly occur, there would still be a much greater chance of error in assuming that the existing laws of nature are the same which existed at the origin of the solar system, than in merely presuming, with geologists, that those laws have lasted through a few revolutions and transformations of a single one among the bodies of which that system is composed. 15. Of progressive effects, and of the continued action of causes. Section 1. In the last 4 chapters we have traced the general outlines of the theory of the generation of derivative laws from ultimate ones. In the present chapter our attention will be directed to a particular case of the derivation of laws from other laws, but a case so general, and so important as not only to repay, but to require, a separate examination. This is the case of a complex phenomenon resulting from one simple law, by the continual addition of an effect to itself. There are some phenomena, some bodily sensations, for example, which are essentially instantaneous, and whose existence can only be prolonged by the prolongation of the existence of the cause by which they are produced. But most phenomena are in their own nature permanent. Having begun to exist, they would exist forever unless some cause intervened having a tendency to alter or destroy them. Such, for example, are all the facts of phenomena which we call bodies. Water, once produced, will not of itself relapse into a state of hydrogen and oxygen. Such a change requires some agent having the power of decomposing the compound. Such, again, are the positions in space and the movements of bodies. No object at rest alters its position without the intervention of some conditions extraneous to itself. And when once in motion, no object returns to a state of rest, or alters either its direction or its velocity, unless some new external conditions are superinduced. It, therefore, perpetually happens that a temporary cause gives rise to a permanent effect. The contact of iron with moist air for a few hours produces a rust which may endure for centuries. Or a projectile force which launches a cannonball into space produces a motion which would continue forever unless some other force counteracted it. Between the 2 examples which we have here given, there is a difference worth pointing out. In the former, in which the phenomenon produced is a substance, and not a motion of a substance, since the rust remains forever and unaltered unless some new cause supervenes. We may speak of the contact of air 100 years ago as even the proximate cause of the rust which has existed from that time until now. But when the effect is motion, which is itself a change, we must use a different language. The permanency of the effect is now only the permanency of a series of changes. The second foot, or inch, or mile of motion is not the mere prolonged duration of the first foot, or inch, or mile, but another fact which succeeds, and which may in some respects be very unlike the former. Since it carries the body through a different region of space. Now, the original projectile force which set the body moving is the remote cause of all its motion, however long continued, but the proximate cause of no motion except that which took place at the first instant. The motion at any subsequent instant is proximately caused by the motion which took place at the instant preceding. It is on that, and not on the original moving cause, that the motion at any given moment depends. For, suppose that the body passes through some resisting medium, which partially counteracts the effect of the original impulse, and retards the motion. This counteraction, it need scarcely here be repeated, is as strict an example of obedience to the law of the impulse, as if the body had gone on moving with its original velocity. But the motion which results is different, being now a compound of the effects of 2 causes acting in contrary directions, instead of the single effect of one cause. Now, what cause does the body obey in its subsequent motion? The original cause of motion, or the actual motion at the preceding instant? The latter, for when the object issues from the resisting medium, it continues moving, not with its original, but with its retarded velocity. The motion having once been diminished, all that which follows is diminished. The effect changes, because the cause which it really obeys, the proximate cause, the real cause in fact, has changed. This principle is recognized by mathematicians when they enumerate among the causes by which the motion of a body is at any instant determined the force generated by the previous motion. An expression which would be absurd if taken to imply that this force was an intermediate link between the cause and the effect, but which really means only the previous motion itself, considered as a cause of further motion. We must, therefore, if we would speak with perfect precision, consider each link in the succession of motions as the effect of the link preceding it. But if, for the convenience of discourse, we speak of the whole series as one effect, it must be as an effect produced by the original impelling force. A permanent effect produced by an instantaneous cause, and possessing the property of self-perpetuation. Let us now suppose that the original agent or cause, instead of being instantaneous, is permanent. Whatever effect has been produced up to a given time, would, unless prevented by the intervention of some new cause, subsist permanently, even if the cause were to perish. Since, however, the cause does not perish, but continues to exist and to operate, it must go on producing more and more of the effect. And instead of a uniform effect, we have a progressive series of effects, arising from the accumulated influence of a permanent cause. Thus, the contact of iron with the atmosphere causes a portion of it to rust. And if the cause ceased, the effect already produced would be permanent, but no further effect would be added. If, however, the cause, namely, exposure to moist air, continues, more and more of the iron becomes rusted, until all which is exposed is converted into a red powder, when one of the conditions of the production of rust, namely, the presence of unoxidized iron, has ceased, and the effect cannot any longer be produced. Again, the earth causes bodies to fall toward it, that is, the existence of the earth at a given instant causes an unsupported body to move toward it at the succeeding instant. And if the earth were annihilated, as much of the effect as is already produced would continue, the object would go on moving in the same direction, with its acquired velocity, until intercepted by some body or deflected by some other force. The earth, however, not being annihilated, goes on producing in the second instant an effect similar and of equal amount with the first, which two effects being added together, there results an accelerated velocity. And this operation being repeated at each successive instant, the mere permanence of the cause, though without increase, gives rise to a constant progressive increase of the effect, so long as all the conditions, negative and positive, of the production of that effect continue to be realized. It is obvious that this state of things is merely a case of the composition of causes. A cause which continues in action must on a strict analysis be considered as a number of causes exactly similar, successively introduced, and producing by their combination the sum of the effects which they would severally produce if they acted singly. The progressive rusting of the iron is in strictness the sum of the effects of many particles of air acting in succession upon corresponding particles of iron. The continued action of the earth upon a falling body is equivalent to a series of forces, applied in successive instants, each tending to produce a certain constant quantity of motion. And the motion at each instant is the sum of the effects of the new force applied at the preceding instant, and the motion already acquired. In each instant a fresh effect, of which gravity is the proximate cause, is added to the effect of which it was the remote cause. Or, to express the same thing in another manner, the effect produced by the earth's influence at the instant last elapsed is added to the sum of the effects of which the remote causes were the influences exerted by the earth at all the previous instants since the motion began. The case, therefore, comes under the principle of a concurrence of causes producing an effect equal to the sum of their separate effects. But as the causes come into play not all at once, but successively, and as the effect at each instant is the sum of the effects of those causes only which have come into action up to that instant, the result assumes the form of an ascending series. A succession of sums, each greater than that which preceded it, and we have thus a progressive effect from the continued action of a cause. Since the continuance of the cause influences the effect only by adding to its quantity, and since the addition takes place according to a fixed law, equal quantities in equal times, the result is capable of being computed on mathematical principles. In fact, this case, being that of infinitesimal increments, is precisely the case which the differential calculus was invented to meet. The questions, what effect will result from the continual addition of a given cause to itself, and what amount of the cause, being continually added to itself, will produce a given amount of the effect, are evidently mathematical questions, and to be treated, therefore, deductively. If, as we have seen, cases of the composition of causes are seldom adapted for any other than deductive investigation, this is especially true in the case now examined, the continual composition of a cause with its own previous effects. Since such a case is peculiarly amenable to the deductive method, while the undistinguishable manner in which the effects are blended with one another and with the causes must make the treatment of such an instance experimentally still more chimerical than in any other case. Section 2. We shall next advert to a rather more intricate operation of the same principle, namely, when the cause does not merely continue in action, but undergoes, during the same time, a progressive change in those of its circumstances which contribute to determine the effect. In this case, as in the former, the total effect goes on accumulating by the continual addition of a fresh effect to that already produced, but it is no longer by the addition of equal quantities in equal times. The quantities added are unequal, and even the quality may now be different. If the change in the state of the permanent cause be progressive, the effect will go through a double series of changes, arising partly from the accumulated action of the cause, and partly from the changes in its action. The effect is still a progressive effect, produced, however, not by the mere continuance of a cause, but by its continuance and its progressiveness combined. A familiar example is afforded by the increase of the temperature as summer advances, that is, as the sun draws nearer to a vertical position, and remains a greater number of hours above the horizon. This instance exemplifies in a very interesting manner the twofold operation on the effect, arising from the continuance of the cause, and from its progressive change. When once the sun has come near enough to the zenith, and remains above the horizon long enough, to give more warmth during one diurnal rotation than the counteracting cause, the Earth's radiation, can carry off. The mere continuance of the cause would progressively increase the effect, even if the sun came no nearer and the days grew no longer. But in addition to this, a change takes place in the accidents of the cause, its series of diurnal positions, tending to increase the quantity of the effect. When the summer solstice has passed, the progressive change in the cause begins to take place the reverse way, but, for some time, the accumulating effect of the mere continuance of the cause exceeds the effect of the changes in it. And the temperature continues to increase. Again, the motion of a planet is a progressive effect, produced by causes at once permanent and progressive. The orbit of a planet is determined, omitting perturbations, by two causes. First, the action of the central body, a permanent cause, which alternately increases and diminishes as the planet draws nearer to or goes farther from its perihelion, and which acts at every point in a different direction. And, secondly, the tendency of the planet to continue moving in the direction and with the velocity which it has already acquired. This force also grows greater as the planet draws nearer to its perihelion, because as it does so its velocity increases, and less, as it recedes from its perihelion. And this force as well as the other acts at each point in a different direction, because at every point the action of the central force, by deflecting the planet from its previous direction, alters the line in which it tends to continue moving. The motion at each instant is determined by the amount and direction of the motion, and the amount and direction of the sun's action, at the previous instant. And if we speak of the entire revolution of the planet as one phenomenon, which, as it is periodical and similar to itself, we often find it convenient to do, that phenomenon is the progressive effect of two permanent and progressive causes: the central force and the acquired motion. Those causes happening to be progressive in the particular way which is called periodical, the effect necessarily is so too, because the quantities to be added together returning in a regular order, the same sums must also regularly return. This example is worthy of consideration also in another respect. Though the causes themselves are permanent, and independent of all conditions known to us, the changes which take place in the quantities and relations of the causes are actually caused by the periodical changes in the effects. The causes, as they exist at any moment, having produced a certain motion, that motion, becoming itself a cause, reacts upon the causes, and produces a change in them. By altering the distance and direction of the central body relatively to the planet, and the direction and quantity of the force in the direction of the tangent, it alters the elements which determine the motion at the next succeeding instant. This change renders the next motion somewhat different, and this difference, by a fresh reaction upon the causes, renders the next motion again different, and so on. The original state of the causes might have been such that this series of actions modified by reactions would not have been periodical. The sun's action, and the original impelling force, might have been in such a ratio to one another, that the reaction of the effect would have been such as to alter the causes more and more, without ever bringing them back to what they were at any former time. The planet would then have moved in a parabola, or in hyperbola, curves not returning into themselves. The quantities of the two forces were, however, originally such, that the successive reactions of the effect bring back the causes, after a certain time, to what they were before. And from that time all the variations continued to recur again and again in the same periodical order, and must so continue while the causes subsist and are not counteracted. Section 3. In all cases of progressive effects, whether arising from the accumulation of unchanging or of changing elements, there is a uniformity of succession not merely between the cause and the effect, but between the first stages of the effect and its subsequent stages. That a body in vacuo falls 16 feet in the first second, 48 in the second, and so on in the ratio of the odd numbers, is as much a uniform sequence as that when the supports are removed the body falls. The sequence of spring and summer is as regular and invariable as that of the approach of the sun and spring, but we do not consider spring to be the cause of summer. It is evident that both are successive effects of the heat received from the sun, and that, considered merely in itself, spring might continue forever without having the slightest tendency to produce summer. As we have so often remarked, not the conditional, but the unconditional invariable antecedent is termed the cause. That which would not be followed by the effect unless something else had preceded, and which if that something else had preceded, would not have been required, is not the cause, however invaluable the sequence may in fact be. It is in this way that most of those uniformities of succession are generated, which are not cases of causation. When a phenomenon goes on increasing, or periodically increases and diminishes, or goes through any continued and unceasing process of variation reducible to a uniform rule or law of succession, we do not on this account presume that any two successive terms of the series are cause and effect. We presume the contrary. We expect to find that the whole series originates either from the continued action of fixed causes or from causes which go through a corresponding process of continuous change. A tree grows from half an inch high to 100 feet, and some trees will generally grow to that height unless prevented by some counteracting cause. But we do not call the seedling the cause of the full-grown tree. The invariable antecedent it certainly is, and we know very imperfectly on what other antecedents the sequence is contingent, but we are convinced that it is contingent on something. Because the homogeneousness of the antecedent with the consequent, the close resemblance of the seedling to the tree in all respects except magnitude, and the graduality of the growth, so exactly resembling the progressively accumulating effect produced by the long action of some one cause, leave no possibility of doubting that the seedling and the tree are two terms in a series of that description, the first term of which is yet to seek. The conclusion is further confirmed by this, that we are able to prove by strict induction the dependence of the growth of the tree, and even of the continuance of its existence, upon the continued repetition of certain processes of nutrition. The rise of the sap, the absorptions and exhalations by the leaves, etc. And the same experiments would probably prove to us that the growth of the tree is the accumulated sum of the effects of these continued processes, were we not, for want of sufficiently microscopic eyes, unable to observe correctly and in detail what those effects are. This supposition by no means requires that the effect should not, during its progress, undergo many modifications besides those of quantity, or that it should not sometimes appear to undergo a very marked change of character. This may be either because the unknown cause consists of several component elements or agents, whose effects, accumulating according to different laws, are compounded in different proportions at different periods in the existence of the organized being. Or because, at certain points in its progress, fresh causes or agencies come in, or are evolved, which intermix their laws with those of the prime agent. 16. Of Empirical Laws. Section 1. Scientific inquirers give the name of empirical laws to those uniformities which observation or experiment has shown to exist, but on which they hesitate to rely in cases varying much from those which have been actually observed, for want of seeing any reason why such a law should exist. It is implied, therefore, in the notion of an empirical law, that it is not an ultimate law, that if true at all, its truth is capable of being, and requires to be, accounted for. It is a derivative law, the derivation of which is not yet known. To state the explanation, the why, of the empirical law, would be to state the laws from which it is derived, the ultimate causes on which it is contingent. And if we knew these, we should also know what are its limits. Under what conditions it would cease to be fulfilled. The periodical return of eclipses, as originally ascertained by the persevering observation of the early Eastern astronomers, was an empirical law, until the general laws of the celestial motions had accounted for it. The following are empirical laws still waiting to be resolved into the simpler laws from which they are derived, the local laws of the flux and reflux of the tides in different places. The succession of certain kinds of weather to certain appearances of sky, the apparent exceptions to the almost universal truth that bodies expand by increase of temperature, the law that breeds, both animal and vegetable, are improved by crossing. That gases have a strong tendency to permeate animal membranes, that substances containing a very high proportion of nitrogen, such as hydrocyanic acid and morphia, are powerful poisons. That when different metals are fused together the alloy is harder than the various elements, that the number of atoms of acid required to neutralize one atom of any base is equal to the number of atoms of oxygen in the base. That the solubility of substances in one another depends, 171 at least in some degree, on the similarity of their elements. An empirical law, then, is an observed uniformity, presumed to be resolvable into simpler laws, but not yet resolved into them. The ascertainment of the empirical laws of phenomena often precedes by a long interval the explanation of those laws by the deductive method. And the verification of a deduction usually consists in the comparison of its results with empirical laws previously ascertained. Section 2. From a limited number of ultimate laws of causation, there are necessarily generated a vast number of derivative uniformities, both of succession and coexistence. Some are laws of succession or of coexistence between different effects of the same cause, of these we had examples in the last chapter. Some are laws of succession between effects and their remote causes, resolvable into the laws which connect each with the intermediate link. Thirdly, when causes act together and compound their effects, the laws of those causes generate the fundamental law of the effect, namely, that it depends on the coexistence of those causes. And, finally, the order of succession or of coexistence which obtains among effects necessarily depends on their causes. If they are effects of the same cause, it depends on the laws of that cause. If on different causes, it depends on the laws of those causes severally, and on the circumstances which determine their coexistence. If we inquire further when and how the causes will coexist, that, again, depends on their causes. And we may thus trace back the phenomena higher and higher, until the different series of effects meet in a point, and the whole is shown to have depended ultimately on some common cause. Or until, instead of converging to one point, they terminate in different points, and the order of the effects is proved to have arisen from the collocation of some of the primeval causes, or natural agents. For example, the order of succession and of coexistence among the heavenly motions, which is expressed by Kepler's laws, is derived from the coexistence of two primeval causes, the Sun, and the original impulse or projectile force belonging to each planet. 172 Kepler's laws are resolved into the laws of these causes and the fact of their coexistence. Derivative laws, therefore, do not depend solely on the ultimate laws into which they are resolvable. They mostly depend on those ultimate laws, and an ultimate fact, namely, the mode of coexistence of some of the component elements of the universe. The ultimate laws of causation might be the same as at present, and yet the derivative laws completely different, if the causes coexisted in different proportions. Or with any difference in those of their relations by which the effects are influenced. If, for example, the Sun's attraction, and the original projectile force, had existed in some other ratio to one another than they did, and we know of no reason why this should not have been the case. The derivative laws of the heavenly motions might have been quite different from what they are. The proportions which exist happen to be such as to produce regular elliptical motions. Any other proportions would have produced different ellipses, or circular, or parabolic, or hyperbolic motions, but still regular ones. Because the effects of each of the agents accumulate according to a uniform law, and two regular series of quantities, when their corresponding terms are added, must produce a regular series of some sort, whatever the quantities themselves are. Section 3. Now this last mentioned element in the resolution of a derivative law, the element which is not a law of causation, but a collocation of causes, cannot itself be reduced to any law. There is, as formerly remarked, 173 no uniformity, no norma, principle, or rule, perceivable in the distribution of the primeval natural agents through the universe. The different substances composing the earth, the powers that pervade the universe, stand in no constant relation to one another. One substance is more abundant than others, one power acts through a larger extent of space than others, without any pervading analogy that we can discover. We not only do not know of any reason why the sun's attraction and the force in the direction of the tangent coexist in the exact proportion they do, but we can trace no coincidence between it and the proportions in which any other elementary powers in the universe are intermingled. The utmost disorder is apparent in the combination of the causes, which is consistent with the most regular order in their effects. For when each agent carries on its own operations according to a uniform law, even the most capricious combination of agencies will generate a regularity of some sort. As we see in the kaleidoscope, where any casual arrangement of colored bits of glass produces by the laws of reflection a beautiful regularity in the effect. Section 4. In the above considerations lies the justification of the limited degree of reliance which scientific inquirers are accustomed to place in empirical laws. A derivative law which results wholly from the operation of some one cause, will be as universally true as the laws of the cause itself. That is, it will always be true except where some one of those effects of the cause, on which the derivative law depends, is defeated by a counteracting cause. But when the derivative law results not from different effects of one cause, but from effects of several causes, we cannot be certain that it will be true under any variation in the mode of coexistence of those causes, or of the primitive natural agents on which the causes ultimately depend. The proposition that coal beds rest on certain descriptions of strata exclusively, though true on the earth, so far as our observation has reached, cannot be extended to the moon or the other planets, supposing coal to exist there. Because we cannot be assured that the original constitution of any other planet was such as to produce the different depositions in the same order as in our globe. The derivative law in this case depends not solely on laws, but on a collocation. And collocations cannot be reduced to any law. Now it is the very nature of a derivative law which has not yet been resolved into its elements, in other words, an empirical law, that we do not know whether it results from the different effects of one cause, or from effects of different causes. We cannot tell whether it depends wholly on laws, or partly on laws and partly on a collocation. If it depends on a collocation, it will be true in all the cases in which that particular collocation exists. But, since we are entirely ignorant, in case of its depending on a collocation, what the collocation is, we are not safe in extending the law beyond the limits of time and place in which we have actual experience of its truth. Since within those limits the law has always been found true, we have evidence that the collocations, whatever they are, on which it depends, do really exist within those limits. But, knowing of no rule or principle to which the collocations themselves conform, we cannot conclude that because a collocation is proved to exist within certain limits of place or time, it will exist beyond those limits. Empirical laws, therefore, can only be received as true within the limits of time and place in which they have been found true by observation, and not merely the limits of time and place, but of time, place, and circumstance. For, since it is the very meaning of an empirical law that we do not know the ultimate laws of causation on which it is dependent, we cannot foresee, without actual trial, In what manner or to what extent the introduction of any new circumstance may affect it. Section 5. But how are we to know that a uniformity ascertained by experience is only an empirical law? Since, by the supposition, we have not been able to resolve it into any other laws, how do we know that it is not an ultimate law of causation? I answer that no generalization amounts to more than an empirical law when the only proof on which it rests is that of the method of agreement. For it has been seen that by that method alone we never can arrive at causes. The utmost that the method of agreement can do is, to ascertain the whole of the circumstances common to all cases in which a phenomenon is produced. And this aggregate includes not only the cause of the phenomenon, but all phenomena with which it is connected by any derivative uniformity, whether as being collateral effects of the same cause, or effects of any other cause which, in all the instances we have been able to observe, coexisted with it. The method affords no means of determining which of these uniformities are laws of causation, and which are merely derivative laws, resulting from those laws of causation and from the collocation of the causes. None of them, therefore, can be received in any other character than that of derivative laws, the derivation of which has not been traced. In other words, empirical laws, in which light all results obtained by the method of agreement, and therefore almost all truths obtained by simple observation without experiment, must be considered, until either confirmed by the method of difference or explained deductively. In other words, accounted for a priori. These empirical laws may be of greater or less authority, according as there is reason to presume that they are resolvable into laws only, or into laws and collocations together. The sequences which we observe in the production and subsequent life of an animal or a vegetable, resting on the method of agreement only, are mere empirical laws. But though the antecedents in those sequences may not be the causes of the consequence, both the one and the other are doubtless, in the main, successive stages of a progressive effect originating in a common cause, and therefore independent of collocations. The uniformities, on the other hand, in the order of superposition of strata on the earth, are empirical laws of a much weaker kind, since they not only are not laws of causation, but there is no reason to believe that they depend on any common cause. All appearances are in favor of their depending on the particular collocation of natural agents which at some time or other existed on our globe, and from which no inference can be drawn as to the collocation which exists or has existed in any other portion of the universe. Section 6. Our definition of an empirical law, including not only those uniformities which are not known to be laws of causation, but also those which are, provided there be reason to presume that they are not ultimate laws. This is the proper place to consider by what signs we may judge that even if an observed uniformity be a law of causation, it is not an ultimate, but a derivative law. The first sign is, if between the antecedent A and the consequent B there be evidence of some intermediate link. Some phenomenon of which we can surmise the existence, though from the imperfection of our senses or of our instruments we are unable to ascertain its precise nature and laws. If there be such a phenomenon, which may be denoted by the letter X, it follows that even if A be the cause of B, it is but the remote cause, and that the law, A causes B, is resolvable into at least two laws, A causes X, and X causes B. This is a very frequent case, since the operations of nature mostly take place on so minute a scale, that many of the successive steps are either imperceptible, or very indistinctly perceived. Take, for example, the laws of the chemical composition of substances, as that hydrogen and oxygen being combined, water is produced. All we see of the process is, that the two gases being mixed in certain proportions, and heat or electricity being applied, an explosion takes place, the gases disappear, and water remains. There is no doubt about the law, or about its being a law of causation. But between the antecedent, the gases in a state of mechanical mixture, heated or electrified, and the consequent, the production of water, there must be an intermediate process which we do not see. For if we take any portion whatever of the water, and subject it to analysis, we find that it always contains hydrogen and oxygen, nay, the very same proportions of them, namely, 2/3, in volume, of hydrogen, and 1/3 oxygen. This is true of a single drop, it is true of the minutest portion which our instruments are capable of appreciating. Since, then, the smallest perceptible portion of the water contains both those substances, portions of hydrogen and oxygen smaller than the smallest perceptible must have come together in every such minute portion of space. Must have come closer together than when the gases were in a state of mechanical mixture, since, to mention no other reasons, the water occupies far less space than the gases. Now, as we cannot see this contact or close approach of the minute particles, we cannot observe with what circumstances it is attended, or according to what laws it produces its effects. The production of water, that is, of the sensible phenomena which characterize the compound, may be a very remote effect of those laws. There may be innumerable intervening links, and we are sure that there must be some. Having full proof that corpuscular action of some kind takes place previous to any of the great transformations in the sensible properties of substances, we can have no doubt that the laws of chemical action, as at present known, are not ultimate, but derivative laws. However ignorant we may be, and even though we should forever remain ignorant, of the nature of the laws of corpuscular action from which they are derived. In like manner, all the processes of vegetative life, whether in the vegetable properly so called or in the animal body, are corpuscular processes. Nutrition is the addition of particles to one another, sometimes merely replacing other particles separated and excreted, sometimes occasioning an increase of bulk or weight so gradual that only after a long continuance does it become perceptible. Various organs, by means of peculiar vessels, secrete from the blood fluids, the component particles of which must have been in the blood, but which differ from it most widely both in mechanical properties and in chemical composition. Here, then, are abundance of unknown links to be filled up. And there can be no doubt that the laws of the phenomena of vegetative or organic life are derivative laws, dependent on properties of the corpuscles, and of those elementary tissues which are comparatively simple combinations of corpuscles. The first sign, then, from which a law of causation, though hitherto unresolved, may be inferred to be a derivative law, is any indication of the existence of an intermediate link or links between the antecedent and the consequent. The second is, when the antecedent is an extremely complex phenomenon, and its effects, therefore, probably in part at least, compounded of the effects of its different elements. Since we know that the case in which the effect of the whole is not made up of the effects of its parts is exceptional, the composition of causes being by far the more ordinary case. We will illustrate this by two examples, in one of which the antecedent is the sum of many homogeneous, in the other of heterogeneous, parts. The weight of a body is made up of the weights of its minute particles. A truth which astronomers express in its most general terms when they say that bodies, at equal distances, gravitate to one another in proportion to their quantity of matter. All true propositions, therefore, which can be made concerning gravity, are derivative laws, the ultimate law into which they are all resolvable being, that every particle of matter attracts every other. As our second example, we may take any of the sequences observed in meteorology, for instance, a diminution of the pressure of the atmosphere, indicated by a fall of the barometer, is followed by rain. The antecedent is here a complex phenomenon, made up of heterogeneous elements, the column of the atmosphere over any particular place consisting of two parts, a column of air, and a column of aqueous vapor mixed with it. And the change in the two together manifested by a fall of the barometer, and followed by rain, must be either a change in one of these, or in the other, or in both. We might, then, even in the absence of any other evidence, form a reasonable presumption, from the invariable presence of both these elements in the antecedent, that the sequence is probably not an ultimate law, but a result of the laws of the two different agents. A presumption only to be destroyed when we had made ourselves so well acquainted with the laws of both, as to be able to affirm that those laws could not by themselves produce the observed result. There are but few known cases of succession from very complex antecedents which have not either been actually accounted for from simpler laws, or inferred with great probability, from the ascertained existence of intermediate links of causation not yet understood, to be capable of being so accounted for. It is, therefore, highly probable that all sequences from complex antecedents are thus resolvable, and that ultimate laws are in all cases comparatively simple. If there were not the other reasons already mentioned for believing that the laws of organized nature are resolvable into simpler laws, it would be almost a sufficient reason that the antecedents in most of the sequences are so very complex. Section 7. In the preceding discussion we have recognized two kinds of empirical laws, those known to be laws of causation, but presumed to be resolvable into simpler laws, and those not known to be laws of causation at all. Both these kinds of laws agree in the demand which they make for being explained by deduction, and agree in being the appropriate means of verifying such deduction. Since they represent the experience with which the result of the deduction must be compared. They agree, further, in this, that until explained, and connected with the ultimate laws from which they result, they have not attained the highest degree of certainty of which laws are susceptible. It has been shown on a former occasion that laws of causation which are derivative, and compounded of simpler laws, are not only, as the nature of the case implies, less general, but even less certain, than the simpler laws from which they result. Not in the same degree to be relied on as universally true. The inferiority of evidence, however, which attaches to this class of laws, is trifling, compared with that which is inherent in uniformities not known to be laws of causation at all. So long as these are unresolved, we cannot tell on how many collocations, as well as laws, their truth may be dependent. We can never, therefore, extend them with any confidence to cases in which we have not assured ourselves, by trial, that the necessary collocation of causes, whatever it may be, exists. It is to this class of laws alone that the property, which philosophers usually consider as characteristic of empirical laws, belongs in all its strictness, the property of being unfit to be relied on beyond the limits of time, place, and circumstance in which the observations have been made. These are empirical laws in a more emphatic sense. And when I employ that term, except where the context manifestly indicates the reverse, I shall generally mean to designate those uniformities only, whether of succession or of coexistence, which are not known to be laws of causation. 17. Of chance and its elimination. Section 1. Considering, then, as empirical laws only those observed uniformities respecting which the question whether they are laws of causation must remain undecided until they can be explained deductively. Or until some means are found of applying the method of difference to the case, it has been shown in the preceding chapter that until a uniformity can, in one or the other of these modes, be taken out of the class of empirical laws, and brought either into that of laws of causation or of the demonstrated results of laws of causation, it cannot with any assurance be pronounced true beyond the local and other limits within which it has been found so by actual observation. It remains to consider how we are to assure ourselves of its truth even within those limits. After what quantity of experience a generalization which rests solely on the method of agreement can be considered sufficiently established, even as an empirical law. In a former chapter, when treating of the methods of direct induction, we expressly reserved this question, 174, and the time is now come for endeavoring to solve it. We found that the method of agreement has the defect of not proving causation, and can, therefore, only be employed for the ascertainment of empirical laws. But we also found that besides this deficiency, it labors under a characteristic imperfection, tending to render uncertain even such conclusions as it is in itself adapted to prove. This imperfection arises from plurality of causes. Although two or more cases in which the phenomenon has been met with may have no common antecedent except A, this does not prove that there is any connection between A and A, since A may have many causes, and may have been produced in these different instances, not by anything which the instances had in common, but by some of those elements in them which were different. We nevertheless observed, that in proportion to the multiplication of instances pointing to A as the antecedent, the characteristic uncertainty of the method diminishes. And the existence of a law of connection between A and A more nearly approaches to certainty. It is now to be determined after what amount of experience this certainty may be deemed to be practically attained, and the connection between A and A may be received as an empirical law. This question may be otherwise stated in more familiar terms. After how many and what sort of instances may it be concluded that an observed coincidence between two phenomena is not the effect of chance? It is of the utmost importance for understanding the logic of induction, that we should form a distinct conception of what is meant by chance, and how the phenomena which common language ascribes to that abstraction are really produced. Section 2. Chance is usually spoken of in direct antithesis to law. Whatever, it is supposed, cannot be ascribed to any law is attributed to chance. It is, however, certain that whatever happens is the result of some law. Is an effect of causes, and could have been predicted from a knowledge of the existence of those causes, and from their laws. If I turn up a particular card, that is a consequence of its place in the pack. Its place in the pack was a consequence of the manner in which the cards were shuffled, or of the order in which they were played in the last game, which, again, were effects of prior causes. At every stage, if we had possessed an accurate knowledge of the causes in existence, it would have been abstractedly possible to foretell the effect. An event occurring by chance may be better described as a coincidence from which we have no ground to infer a uniformity, the occurrence of a phenomenon in certain circumstances, without our having reason on that account to infer that it will happen again in those circumstances. This, however, when looked closely into, implies that the enumeration of the circumstances is not complete. Whatever the fact be, since it has occurred once, we may be sure that if all the same circumstances were repeated it would occur again. And not only if all, but there is some particular portion of those circumstances on which the phenomenon is invariably consequent. With most of them, however, it is not connected in any permanent manner. Its conjunction with those is said to be the effect of chance, to be merely casual. Facts casually conjoined are separately the effects of causes, and therefore of laws, but of different causes, and causes not connected by any law. It is incorrect, then, to say that any phenomenon is produced by chance, but we may say that two or more phenomena are conjoined by chance, that they coexist or succeed one another only by chance. Meaning that they are in no way related through causation. That they are neither cause and effect, nor effects of the same cause, nor effects of causes between which there subsists any law of coexistence, nor even effects of the same collocation of primeval causes. If the same casual coincidence never occurred a second time, we should have an easy test for distinguishing such from the coincidences which are the results of a law. As long as the phenomena had been found together only once, so long, unless we knew some more general laws from which the coincidence might have resulted, we could not distinguish it from a casual one. But if it occurred twice, we should know that the phenomena so conjoined must be in some way connected through their causes. There is, however, no such test. A coincidence may occur again and yet be only casual. Nay, it would be inconsistent with what we know of the order of nature to doubt that every casual coincidence will sooner or later be repeated, as long as the phenomena between which it occurred do not cease to exist, or to be reproduced. The recurrence, therefore, of the same coincidence more than once, or even its frequent recurrence, does not prove that it is an instance of any law, does not prove that it is not casual, or, in common language, the effect of chance. And yet, when a coincidence cannot be deduced from known laws, nor proved by experiment to be itself a case of causation, the frequency of its occurrence is the only evidence from which we can infer that it is the result of a law. Not, however, its absolute frequency. The question is not whether the coincidence occurs often or seldom, in the ordinary sense of those terms, but whether it occurs more often than chance will account for. More often than might rationally be expected if the coincidence were casual. We have to decide, therefore, what degree of frequency in a coincidence chance will account for, and to this there can be no general answer. We can only state the principle by which the answer must be determined. The answer itself will be different in every different case. Suppose that one of the phenomena, A, exists always, and the other phenomenon, B, only occasionally. It follows that every instance of B will be an instance of its coincidence with A, and yet the coincidence will be merely casual, not the result of any connection between them. The fixed stars have been constantly in existence since the beginning of human experience, and all phenomena that have come under human observation have, in every single instance, coexisted with them. Yet this coincidence, though equally invariable with that which exists between any of those phenomena and its own cause, does not prove that the stars are its cause, nor that they are in anywise connected with it. As strong a case of coincidence, therefore, as can possibly exist, and a much stronger one in point of mere frequency than most of those which prove laws, does not here prove a law. Why? Because, since the stars exist always, they must coexist with every other phenomenon, whether connected with them by causation or not. The uniformity, great though it be, is no greater than would occur on the supposition that no such connection exists. On the other hand, suppose that we were inquiring whether there be any connection between rain and any particular wind. Rain, we know, occasionally occurs with every wind, therefore, the connection, if it exists, cannot be an actual law, but still rain may be connected with some particular wind through causation. That is, though they cannot be always effects of the same cause, for if so they would regularly coexist, there may be some causes common to the two, so that in so far as either is produced by those common causes, they will, from the laws of the causes, be found to coexist. How, then, shall we ascertain this? The obvious answer is, by observing whether rain occurs with one wind more frequently than with any other. That, however, is not enough, for perhaps that one wind blows more frequently than any other. So that its blowing more frequently in rainy weather is no more than would happen, although it had no connection with the causes of rain, provided it were not connected with causes adverse to rain. In England, westerly winds blow during about twice as great a portion of the year as easterly. If, therefore, it rains only twice as often with a westerly as with an easterly wind, we have no reason to infer that any law of nature is concerned in the coincidence. If it rains more than twice as often, we may be sure that some law is concerned. Either there is some cause in nature which, in this climate, tends to produce both rain and a westerly wind, or a westerly wind has itself some tendency to produce rain. But if it rains less than twice as often, we may draw a directly opposite inference: the one, instead of being a cause, or connected with causes of the other, must be connected with causes adverse to it, or with the absence of some cause which produces it. And though it may still rain much oftener with a westerly wind than with an easterly, so far would this be from proving any connection between the phenomena, that the connection proved would be between rain and an easterly wind, to which, in mere frequency of coincidence, it is less allied. Here, then, are two examples: in one, the greatest possible frequency of coincidence, with no instance whatever to the contrary, does not prove that there is any law. In the other, a much less frequency of coincidence, even when non-coincidence is still more frequent, does prove that there is a law. In both cases the principle is the same. In both we consider the positive frequency of the phenomena themselves, and how great frequency of coincidence that must of itself bring about, without supposing any connection between them, provided there be no repugnance. Provided neither be connected with any cause tending to frustrate the other. If we find a greater frequency of coincidence than this, we conclude that there is some connection; if a less frequency, that there is some repugnance. In the former case, we conclude that one of the phenomena can under some circumstances cause the other, or that there exists something capable of causing them both. In the latter, that one of them, or some cause which produces one of them, is capable of counteracting the production of the other. We have thus to deduct from the observed frequency of coincidence as much as may be the effect of chance, that is, of the mere frequency of the phenomena themselves. And if anything remains, what does remain is the residual fact which proves the existence of a law. The frequency of the phenomena can only be ascertained within definite limits of space and time. Depending as it does on the quantity and distribution of the primeval natural agents, of which we can know nothing beyond the boundaries of human observation, since no law, no regularity, can be traced in it, enabling us to infer the unknown from the known. But for the present purpose this is no disadvantage, the question being confined within the same limits as the data. The coincidences occurred in certain places and times, and within those we can estimate the frequency with which such coincidences would be produced by chance. If, then, we find from observation that A exists in one case out of every two, and B in one case out of every three. Then, if there be neither connection nor repugnance between them, or between any of their causes, the instances in which A and B will both exist, that is to say will coexist, will be one case in every 6. For A exists in 3 cases out of 6. And B, existing in one case out of every 3 without regard to the presence or absence of A, will exist in one case out of those 3. There will therefore be, of the whole number of cases, 2 in which A exists without B. 1 case of B without A, 2 in which neither B nor A exists, and 1 case out of 6 in which they both exist. If, then, in point of fact, they are found to coexist oftener than in 1 case out of 6. And, consequently, A does not exist without B so often as twice in 3 times, nor B without A so often as once in every twice, there is some cause in existence which tends to produce a conjunction between A and B. Generalizing the result, we may say that if A occurs in a larger proportion of the cases where B is than of the cases where B is not, then will B also occur in a larger proportion of the cases where A is than of the cases where A is not. And there is some connection, through causation, between A and B. If we could ascend to the causes of the 2 phenomena, we should find, at some stage either proximate or remote, some cause or causes common to both. And if we could ascertain what these are, we could frame a generalization which would be true without restriction of place or time, but until we can do so, the fact of a connection between the 2 phenomena remains an empirical law. Section 3. Having considered in what manner it may be determined whether any given conjunction of phenomena is causal, or the result of some law. To complete the theory of chance it is necessary that we should now consider those effects which are partly the result of chance and partly of law, or, in other words, in which the effects of casual conjunctions of causes are habitually blended in one result with the effects of a constant cause. This is a case of composition of causes. And the peculiarity of it is, that instead of 2 or more causes intermixing their effects in a regular manner with those of one another, we have now one constant cause, producing an effect which is successively modified by a series of variable causes. Thus, as summer advances, the approach of the sun to a vertical position tends to produce a constant increase of temperature. But with this effect of a constant cause, there are blended the effects of many variable causes, winds, clouds, evaporation, electric agencies, and the like, so that the temperature of any given day depends in part on these fleeting causes, and only in part on the constant cause. If the effect of the constant cause is always accompanied and disguised by effects of variable causes, it is impossible to ascertain the law of the constant cause in the ordinary manner by separating it from all other causes and observing it apart. Hence arises the necessity of an additional rule of experimental inquiry. When the action of a cause A is liable to be interfered with, not steadily by the same cause or causes, but by different causes at different times, and when these are so frequent, or so indeterminate, that we cannot possibly exclude all of them from any experiment, though we may vary them. Our resource is, to endeavor to ascertain what is the effect of all the variable causes taken together. In order to do this, we make as many trials as possible, preserving A invariable. The results of these different trials will naturally be different, since the indeterminate modifying causes are different in each. If, then, we do not find these results to be progressive, but, on the contrary, to oscillate about a certain point, one experiment giving a result a little greater, another a little less, one a result tending a little more in one direction, another a little more in the contrary direction, while the average or middle point does not vary, but different sets of experiments, taken in as great a variety of circumstances as possible, yield the same mean, provided only they be sufficiently numerous. Then that mean, or average result, is the part, in each experiment, which is due to the cause A, and is the effect which would have been obtained if A could have acted alone. The variable remainder is the effect of chance, that is, of causes the coexistence of which with the cause A was merely casual. The test of the sufficiency of the induction in this case is, when any increase of the number of trials from which the average is struck does not materially alter the average. This kind of elimination, in which we do not eliminate any one assignable cause, but the multitude of floating unassignable ones, may be termed the elimination of chance. We afford an example of it when we repeat an experiment, in order, by taking the mean of different results, to get rid of the effects of the unavoidable errors of each individual experiment. When there is no permanent cause, such as would produce a tendency to error peculiarly in one direction, we are warranted by experience in assuming that the errors on one side will, in a certain number of experiments, about balance the errors on the contrary side. We therefore repeat the experiment, until any change which is produced in the average of the whole by further repetition, falls within limits of error consistent with the degree of accuracy required by the purpose we have in view. 175. Section 4. In the supposition hitherto made, the effect of the constant cause A has been assumed to form so great and conspicuous a part of the general result, that its existence never could be a matter of uncertainty. And the object of the eliminating process was only to ascertain how much is attributable to that cause. What is its exact law? Cases, however, occur in which the effect of a constant cause is so small, compared with that of some of the changeable causes with which it is liable to be casually conjoined, that of itself it escapes notice. And the very existence of any effect arising from a constant cause is first learned by the process which in general serves only for ascertaining the quantity of that effect. This case of induction may be characterized as follows: a given effect is known to be chiefly, and not known not to be wholly, determined by changeable causes. If it be wholly so produced, then if the aggregate be taken of a sufficient number of instances, the effects of these different causes will cancel one another. If, therefore, we do not find this to be the case, but, on the contrary, after such a number of trials has been made that no further increase alters the average result, we find that average to be, not zero, but some other quantity, about which, though small in comparison with the total effect, the effect nevertheless oscillates, and which is the middle point in its oscillation. We may conclude this to be the effect of some constant cause, which cause, by some of the methods already treated of, we may hope to detect. This may be called the discovery of a residual phenomenon by eliminating the effects of chance. It is in this manner, for example, that loaded dice may be discovered. Of course, no dice are so clumsily loaded that they must always throw certain numbers, otherwise the fraud would be instantly detected. The loading, a constant cause, mingles with the changeable causes which determine what cast will be thrown in each individual instance. If the dice were not loaded, and the throw were left to depend entirely on the changeable causes, these in a sufficient number of instances would balance one another, and there would be no preponderant number of throws of any one kind. If, therefore, after such a number of trials that no further increase of their number has any material effect upon the average, we find a preponderance in favor of a particular throw, we may conclude with assurance that there is some constant cause acting in favor of that throw, or, in other words, that the dice are not fair, and the exact amount of the unfairness. In a similar manner, what is called the diurnal variation of the barometer, which is very small compared with the variations arising from the irregular changes in the state of the atmosphere, was discovered by comparing the average height of the barometer at different hours of the day. When this comparison was made, it was found that there was a small difference, which on the average was constant, however the absolute quantities might vary, and which difference, therefore, must be the effect of a constant cause. This cause was afterward ascertained, deductively, to be the rarefaction of the air, occasioned by the increase of temperature as the day advances. Section 5. After these general remarks on the nature of chance, we are prepared to consider in what manner assurance may be obtained that a conjunction between two phenomena, which has been observed a certain number of times, is not casual, but a result of causation, and to be received, therefore, as one of the uniformities of nature, though, until accounted for a priori, only as an empirical law. We will suppose the strongest case, namely, that the phenomenon B has never been observed except in conjunction with A. Even then, the probability that they are connected is not measured by the total number of instances in which they have been found together, but by the excess of that number above the number due to the absolutely frequency of A. If, for example, A exists always, and therefore coexists with everything, no number of instances of its coexistence with B would prove a connection, as in our example of the fixed stars. If A be a fact of such common occurrence that it may be presumed to be present in half of all the cases that occur, and therefore in half the cases in which B occurs, it is only the proportional excess above half that is to be reckoned as evidence toward proving a connection between A and B. In addition to the question, what is the number of coincidences which, on an average of a great multitude of trials, may be expected to arise from chance alone? There is also another question, namely, of what extent of deviation from that average is the occurrence credible, from chance alone, in some number of instances smaller than that required for striking a fair average. It is not only to be considered what is the general result of the chances in the long run, but also what are the extreme limits of variation from the general result, which may occasionally be expected as the result of some smaller number of instances. The consideration of the latter question, and any consideration of the former beyond that already given to it, belong to what mathematicians term the doctrine of chances, or, in a phrase of greater pretension, the theory of probabilities. 18. Of the calculation of chances. Section 1. Probability, says Laplace 176, has reference partly to our ignorance, partly to our knowledge. We know that among three or more events, one, and only one, must happen. But there is nothing leading us to believe that any one of them will happen rather than the others. In this state of indecision, it is impossible for us to pronounce with certainty on their occurrence. It is, however, probable that any one of these events, selected at pleasure, will not take place, because we perceive several cases, all equally possible, which exclude its occurrence, and only one which favors it. The theory of chances consists in reducing all events of the same kind to a certain number of cases equally possible, that is, such that we are equally undecided as to their existence. And in determining the number of these cases which are favorable to the event of which the probability is sought. The ratio of that number to the number of all the possible cases is the measure of the probability, which is thus a fraction, having for its numerator the number of cases favorable to the event, and for its denominator the number of all the cases which are possible. To a calculation of chances, then, according to Laplace, two things are necessary. We must know that of several events some one will certainly happen, and no more than one. And we must not know, nor have any reason to expect, that it will be one of these events rather than another. It has been contended that these are not the only requisites, and that Laplace has overlooked, in the general theoretical statement, a necessary part of the foundation of the doctrine of chances. To be able, it has been said, to pronounce two events equally probable, it is not enough that we should know that one or the other must happen, and should have no grounds for conjecturing which. Experience must have shown that the two events are of equally frequent occurrence. Why, in tossing up a halfpenny, do we reckon it equally probable that we shall throw cross or pile? Because we know that in any great number of throws, cross and pile are thrown about equally often, and that the more throws we make, the more nearly the equality is perfect. We may know this if we please by actual experiment, or by the daily experience which life affords of events of the same general character, or, deductively, from the effect of mechanical laws on a symmetrical body acted upon by forces varying indefinitely in quantity and direction. We may know it, in short, either by specific experience, or on the evidence of our general knowledge of nature. But, in one way or the other, we must know it, to justify us in calling the two events equally probable. And if we knew it not, we should proceed as much at haphazard in staking equal sums on the result, as in laying odds. This view of the subject was taken in the first edition of the present work. But I have since become convinced that the theory of chances, as conceived by Laplace and by mathematicians generally, has not the fundamental fallacy which I had ascribed to it. We must remember that the probability of an event is not a quality of the event itself, but a mere name for the degree of ground which we, or someone else, have for expecting it. The probability of an event to one person is a different thing from the probability of the same event to another, or to the same person after he has acquired additional evidence. The probability to me, that an individual of whom I know nothing but his name will die within the year, is totally altered by my being told the next minute that he is in the last stage of a consumption. Yet this makes no difference in the event itself, nor in any of the causes on which it depends. Every event is in itself certain, not probable. If we knew all, we should either know positively that it will happen, or positively that it will not. But its probability to us means the degree of expectation of its occurrence, which we are warranted in entertaining by our present evidence. Bearing this in mind, I think it must be admitted, that even when we have no knowledge whatever to guide our expectations, except the knowledge that what happens must be some one of a certain number of possibilities, we may still reasonably judge that one supposition is more probable to us than another supposition. And if we have any interest at stake, we shall best provide for it by acting conformably to that judgment. Section 2. Suppose that we are required to take a ball from a box, of which we only know that it contains balls both black and white, and none of any other color. We know that the ball we select will be either a black or a white ball. But we have no ground for expecting black rather than white, or white rather than black. In that case, if we are obliged to make a choice, and to stake something on one or the other supposition, it will, as a question of prudence, be perfectly indifferent which. And we shall act precisely as we should have acted if we had known beforehand that the box contained an equal number of black and white balls. But though our conduct would be the same, it would not be founded on any surmise that the balls were in fact thus equally divided. For we might, on the contrary, know by authentic information that the box contained 99 balls of one color, and only one of the other. Still, if we are not told which color has only one, and which has 99, the drawing of a white and of a black ball will be equally probable to us. We shall have no reason for staking anything on the one event rather than on the other. The option between the two will be a matter of indifference, in other words, it will be an even chance. But let it now be supposed that instead of two there are three colors, white, black, and red. And that we are entirely ignorant of the proportion in which they are mingled. We should then have no reason for expecting one more than another, and if obliged to bet, should venture our stake on red, white, or black with equal indifference. But should we be indifferent whether we bet for or against some one color, as, for instance, white? Surely not. From the very fact that black and red are each of them separately equally probable to us with white, the two together must be twice as probable. We should in this case expect not white rather than white, and so much rather that we would lay 2 to 1 upon it. It is true, there might, for aught we knew, be more white balls than black and red together. And if so, our bet would, if we knew more, be seen to be a disadvantageous one. But so also, for aught we knew, might there be more red balls than black and white, or more black balls than white and red. And in such case the effect of additional knowledge would be to prove to us that our bet was more advantageous than we had supposed it to be. There is in the existing state of our knowledge a rational probability of 2 to 1 against white, a probability fit to be made a basis of conduct. No reasonable person would lay an even wager in favor of white against black and red. Though against black alone or red alone he might do so without imprudence. The common theory, therefore, of the calculation of chances, appears to be tenable. Even when we know nothing except the number of the possible and mutually excluding contingencies, and are entirely ignorant of their comparative frequency, we may have grounds, and grounds numerically appreciable, for acting on one supposition rather than on another. And this is the meaning of probability. Section 3. The principle, however, on which the reasoning proceeds, is sufficiently evident. It is the obvious one that when the cases which exist are shared among several kinds, it is impossible that each of those kinds should be a majority of the whole. On the contrary, there must be a majority against each kind, except one at most. And if any kind has more than its share in proportion to the total number, the others collectively must have less. Granting this axiom, and assuming that we have no ground for selecting any one kind as more likely than the rest to surpass the average proportion, it follows that we cannot rationally presume this of any. Which we should do if we were to bet in favor of it, receiving less odds than in the ratio of the number of the other kinds. Even, therefore, in this extreme case of the calculation of probabilities, which does not rest on special experience at all. The logical ground of the process is our knowledge, such knowledge as we then have, of the laws governing the frequency of occurrence of the different cases. But in this case the knowledge is limited to that which, being universal and axiomatic, does not require reference to specific experience, or to any considerations arising out of the special nature of the problem under discussion. Except, however, in such cases as games of chance, where the very purpose in view requires ignorance instead of knowledge. I can conceive no case in which we ought to be satisfied with such an estimate of chances as this, an estimate founded on the absolute minimum of knowledge respecting the subject. It is plain that, in the case of the colored balls, a very slight ground of surmise that the white balls were really more numerous than either of the other colors would suffice to vitiate the whole of the calculations made in our previous state of indifference. It would place us in that position of more advanced knowledge, in which the probabilities, to us, would be different from what they were before. And in estimating these new probabilities we should have to proceed on a totally different set of data, furnished no longer by mere counting of possible suppositions, but by specific knowledge of facts. Such data it should always be our endeavor to obtain, and in all inquiries, unless on subjects equally beyond the range of our means of knowledge and our practical uses, they may be obtained, if not good, at least better than none at all. 177. It is obvious, too, that even when the probabilities are derived from observation and experiment, a very slight improvement in the data, by better observations, or by taking into fuller consideration the special circumstances of the case, is of more use than the most elaborate application of the calculus to probabilities founded on the data in their previous state of inferiority. The neglect of this obvious reflection has given rise to misapplications of the calculus of probabilities which have made it the real opprobrium of mathematics. It is sufficient to refer to the applications made of it to the credibility of witnesses, and to the correctness of the verdicts of juries. In regard to the first, common sense would dictate that it is impossible to strike a general average of the veracity in other qualifications for true testimony of mankind, or of any class of them. And even if it were possible, the employment of it for such a purpose implies a misapprehension of the use of averages, which serve, indeed, to protect those whose interest is at stake against mistaking the general result of large masses of instances, but are of extremely small value as grounds of expectation in any one individual instance. Unless the case be one of those in which the great majority of individual instances do not differ much from the average. In the case of a witness, persons of common sense would draw their conclusions from the degree of consistency of his statements, his conduct under cross-examination, and the relation of the case itself to his interests, his partialities, and his mental capacity, instead of applying so rude a standard, even if it were capable of being verified, as the ratio between the number of true and the number of erroneous statements which he may be supposed to make in the course of his life. Again, on the subject of juries or other tribunals, some mathematicians have set out from the proposition that the judgment of any one judge or juryman is, at least in some small degree, more likely to be right than wrong, and have concluded that the chance of a number of persons concurring in a wrong verdict is diminished the more the number is increased. So that if the judges are only made sufficiently numerous, the correctness of the judgment may be reduced almost to certainty. I say nothing of the disregard shown to the effect produced on the moral position of the judges by multiplying their numbers, the virtual destruction of their individual responsibility, and weakening of the application of their minds to the subject. I remark only the fallacy of reasoning from a wide average to cases necessarily differing greatly from any average. It may be true that, taking all causes one with another, the opinion of any one of the judges would be oftener right than wrong. But the argument forgets that in all but the more simple cases, in all cases in which it is really of much consequence what the tribunal is, the proposition might probably be reversed. Besides which, the cause of error, whether arising from the intricacy of the case or from some common prejudice or mental infirmity, if it acted upon one judge, would be extremely likely to affect all the others in the same manner. Or at least a majority, and thus render a wrong instead of a right decision more probable the more the number was increased. These are but samples of the errors frequently committed by men who, having made themselves familiar with the difficult formulae which algebra affords for the estimation of chances under suppositions of a complex character, like better to employ those formulae in computing what are the probabilities to a person half informed about a case than to look out for means of being better informed. Before applying the doctrine of chances to any scientific purpose, the foundation must be laid for an evaluation of the chances, by possessing ourselves of the utmost attainable amount of positive knowledge. The knowledge required is that of the comparative frequency with which the different events in fact occur. For the purposes, therefore, of the present work, it is allowable to suppose that conclusions respecting the probability of a fact of a particular kind rest on our knowledge of the proportion between the cases in which facts of that kind occur, and those in which they do not occur. This knowledge being either derived from specific experiment, or deduced from our knowledge of the causes in operation which tend to produce, compared with those which tend to prevent, the fact in question. Such calculation of chances is grounded on an induction, and to render the calculation legitimate, the induction must be a valid one. It is not less an induction, though it does not prove that the event occurs in all cases of a given description, but only that out of a given number of such cases it occurs in about so many. The fraction which mathematicians use to designate the probability of an event is the ratio of these two numbers. The ascertained proportion between the number of cases in which the event occurs and the sum of all the cases, those in which it occurs and in which it does not occur, taken together. In playing at cross and pile, the description of cases concerned are throws, and the probability of cross is 1/2, because if we throw often enough cross is thrown about once in every 2 throws. In the cast of a die, the probability of ace is 1/6. Not simply because there are 6 possible throws, of which ace is 1. And because we do not know any reason why one should turn up rather than another, though I have admitted the validity of this ground in default of a better, but because we do actually know, either by reasoning or by experience, that in 100 or 1,000,000 of throws ace is thrown in about 1/6 of that number, or once in 6 times. Section 4. I say, either by reasoning or by experience, meaning specific experience. But in estimating probabilities, it is not a matter of indifference from which of these two sources we derive our assurance. The probability of events, as calculated from their mere frequency in past experience, affords a less secure basis for practical guidance than their probability as deduced from an equally accurate knowledge of the frequency of occurrence of their causes. The generalization that an event occurs in 10 out of every 100 cases of a given description, is as real an induction as if the generalization were that it occurs in all cases. But when we arrive at the conclusion by merely counting instances in actual experience, and comparing the number of cases in which A has been present with the number in which it has been absent, the evidence is only that of the method of agreement. And the conclusion amounts only to an empirical law. We can make a step beyond this when we can ascend to the causes on which the occurrence of A or its non-occurrence will depend, and form an estimate of the comparative frequency of the causes favorable and of those unfavorable to the occurrence. These are data of a higher order, by which the empirical law derived from a mere numerical comparison of affirmative and negative instances will be either corrected or confirmed. And in either case we shall obtain a more correct measure of probability than is given by that numerical comparison. It has been well remarked that in the kind of examples by which the doctrine of chances is usually illustrated, that of balls in a box, the estimate of probabilities is supported by reasons of causation, stronger than specific experience. What is the reason that in a box where there are 9 black balls and 1 white, we expect to draw a black ball 9 times as much, in other words, 9 times as often, frequency being the gauge of intensity in expectation, as a white? Obviously because the local conditions are 9 times as favorable, because the hand may alight in 9 places and get a black ball, while it can only alight in 1 place and find a white ball. Just for the same reason that we do not expect to succeed in finding a friend in a crowd, the conditions in order that we and he should come together being many and difficult. This of course would not hold to the same extent were the white balls of smaller size than the black, neither would the probability remain the same. The larger ball would be much more likely to meet the hand. 178. It is, in fact, evident that when once causation is admitted as a universal law, our expectation of events can only be rationally grounded on that law. To a person who recognizes that every event depends on causes, a thing's having happened once is a reason for expecting it to happen again, only because proving that there exists, or is liable to exist, a cause adequate to produce it. 179 The frequency of the particular event, apart from all surmise respecting its cause, can give rise to no other induction than that per enumerationem simplicem. And the precarious inferences derived from this are superseded, and disappear from the field as soon as the principle of causation makes its appearance there. Notwithstanding, however, the abstract superiority of an estimate of probability grounded on causes. It is a fact that in almost all cases in which chances admit of estimation sufficiently precise to render their numerical appreciation of any practical value, the numerical data are not drawn from knowledge of the causes, but from experience of the events themselves. The probabilities of life at different ages or in different climates, the probabilities of recovery from a particular disease, the chances of the birth of male or female offspring, the chances of the destruction of houses or other property by fire, the chances of the loss of a ship in a particular voyage, are deduced from bills of mortality, returns from hospitals, registers of births, of shipwrecks, etc., that is, from the observed frequency not of the causes, but of the effects. The reason is, that in all these classes of facts the causes are either not amenable to direct observation at all, or not with the requisite precision. And we have no means of judging of their frequency except from the empirical law afforded by the frequency of the effects. The inference does not the less depend on causation alone. We reason from an effect to a similar effect by passing through the cause. If the actuary of an insurance office infers from his tables that among 100 persons now living of a particular age, 5 on the average will attain the age of 70, his inference is legitimate. Not for the simple reason that this is the proportion who have lived till 70 in times past, but because the fact of their having so lived shows that this is the proportion existing, at that place and time, between the causes which prolong life to the age of 70 and those tending to bring it to an earlier close. 180. Section 5. From the preceding principles it is easy to deduce the demonstration of that theorem of the doctrine of probabilities which is the foundation of its application to inquiries for ascertaining the occurrence of a given event, or the reality of an individual fact. The signs or evidences by which a fact is usually proved are some of its consequences, and the inquiry hinges upon determining what cause is most likely to have produced a given effect. The theorem applicable to such investigations is the sixth principle in Laplace's Essai philosophique sur les probabilités, which is described by him as the fundamental principle of that branch of the analysis of chances which consists in ascending from events to their causes. 181. Given an effect to be accounted for, and there being several causes which might have produced it, but of the presence of which in the particular case nothing is known, the probability that the effect was produced by any one of these causes is as the antecedent probability of the cause, multiplied by the probability that the cause, if it existed, would have produced the given effect. Let M be the effect, and A, B, two causes, by either of which it might have been produced. To find the probability that it was produced by the one and not by the other, ascertain which of the two is most likely to have existed, and which of them, if it did exist, was most likely to produce the effect M. The probability sought is a compound of these two probabilities. Case I. Let the causes be both alike in the second respect, either A or B, when it exists, being supposed equally likely, or equally certain, to produce M. But let A be in itself twice as likely as B to exist, that is, twice as frequent a phenomenon. Then it is twice as likely to have existed in this case, and to have been the cause which produced M. For, since A exists in nature twice as often as B, in any 300 cases in which one or other existed, A has existed 200 times and B 100. But either A or B must have existed wherever M is produced. Therefore, in 300 times that M is produced, A was the producing cause 200 times, B only 100, that is, in the ratio of 2 to 1. Thus, then, if the causes are alike in their capacity of producing the effect, the probability as to which actually produced it is in the ratio of their antecedent probabilities. Case 2. Reversing the last hypothesis, let us suppose that the causes are equally frequent, equally likely to have existed, but not equally likely, if they did exist, to produce M. That in 3 times in which A occurs, it produces that effect twice, while B, in 3 times, produces it only once. Since the 2 causes are equally frequent in their occurrence. In every 6 times that either one or the other exists, A exists 3 times and B 3 times. A, of its 3 times, produces M in 2, B, of its 3 times, produces M in 1. Thus, in the whole 6 times, M is only produced thrice. But of that thrice it is produced twice by A, once only by B. Consequently, when the antecedent probabilities of the causes are equal, the chances that the effect was produced by them are in the ratio of the probabilities that if they did exist they would produce the effect. Case 3. The third case, that in which the causes are unlike in both respects, is solved by what has preceded. For, when a quantity depends on 2 other quantities, in such a manner that while either of them remains constant it is proportional to the other, it must necessarily be proportional to the product of the 2 quantities. The product being the only function of the 2 which obeys that law of variation. Therefore, the probability that M was produced by either cause, is as the antecedent probability of the cause, multiplied by the probability that if it existed it would produce M. Which was to be demonstrated. Or we may prove the third case as we proved the first and second. Let A be twice as frequent as B, and let them also be unequally likely, when they exist, to produce M, let A produce it twice in 4 times, B thrice in 4 times. The antecedent probability of A is to that of B as 2 to 1, the probabilities of their producing M are as 2 to 3, the product of these ratios is the ratio of 4 to 3. And this will be the ratio of the probabilities that A or B was the producing cause in the given instance. For, since A is twice as frequent as B, out of 12 cases in which one or other exists, A exists in 8 and B in 4. But of its 8 cases, A, by the supposition, produces M in only 4, while B of its 4 cases produces M in 3. M, therefore, is only produced at all in 7 of the 12 cases, but in 4 of these it is produced by A, in 3 by B. Hence the probabilities of its being produced by A and by B are as 4 to 3, and are expressed by the fractions 4/7 and 3/7. Which was to be demonstrated. Section 6. It remains to examine the bearing of the doctrine of chances on the peculiar problem which occupied us in the preceding chapter, namely, how to distinguish coincidences which are casual from those which are the result of law. From those in which the facts which accompany or follow one another are somehow connected through causation. The doctrine of chances affords means by which, if we knew the average number of coincidences to be looked for between 2 phenomena connected only casually, we could determine how often any given deviation from that average will occur by chance. If the probability of any casual coincidence, considered in itself, be 1/m, the probability that the same coincidence will be repeated n times in succession is 1/mn. For example, in one throw of a die the probability of ace being 1 to 6. The probability of throwing ace twice in succession will be 1 divided by the square of 6, or 1/36. For ace is thrown at the first throw once in 6, or 6 in 36 times, and of those 6, the die being cast again, ace will be thrown but once. Being altogether once in 36 times. The chance of the same cast 3 times successively is, by a similar reasoning, 1/63 or 1/216, that is, the event will happen, on a large average, only once in 216 throws. We have thus a rule by which to estimate the probability that any given series of coincidences arises from chance, provided we can measure correctly the probability of a single coincidence. If we can obtain an equally precise expression for the probability that the same series of coincidences arises from causation, we should only have to compare the numbers. This, however, can rarely be done. Let us see what degree of approximation can practically be made to the necessary precision. The question falls within Laplace's sixth principle, just demonstrated. The given fact, that is to say, the series of coincidences, may have originated either in a casual conjunction of causes or in a law of nature. The probabilities, therefore, that the fact originated in these two modes, are as their antecedent probabilities, multiplied by the probabilities that if they existed they would produce the effect. But the particular combination of chances, if it occurred, or the law of nature if real, would certainly produce the series of coincidences. The probabilities, therefore, that the coincidences are produced by the two causes in question are as the antecedent probabilities of the causes. One of these, the antecedent probability of the combination of mere chances which would produce the given result, is an appreciable quantity. The antecedent probability of the other supposition may be susceptible of a more or less exact estimation, according to the nature of the case. In some cases, the coincidence, supposing it to be the result of causation at all, must be the result of a known cause, as the succession of aces, if not accidental, must arise from the loading of the die. In such cases we may be able to form a conjecture as to the antecedent probability of such a circumstance from the characters of the parties concerned, or other such evidence. But it would be impossible to estimate that probability with anything like numerical precision. The counter-probability, however, that of the accidental origin of the coincidence, dwindling so rapidly as it does at each new trial, the stage is soon reached at which the chance of unfairness in the die, however small in itself, must be greater than that of a casual coincidence. And on this ground, a practical decision can generally be come to without much hesitation, if there be the power of repeating the experiment. When, however, the coincidence is one which cannot be accounted for by any known cause, and the connection between the two phenomena, if produced by causation, must be the result of some law of nature hitherto unknown. Which is the case we had in view in the last chapter. Then, though the probability of a casual coincidence may be capable of appreciation, that of the countersupposition, the existence of an undiscovered law of nature, is clearly unsusceptible of even an approximate valuation. In order to have the data which such a case would require, it would be necessary to know what proportion of all the individual sequences or coexistences occurring in nature are the result of law, and what proportion are mere casual coincidences. It being evident that we cannot form any plausible conjecture as to this proportion, much less appreciate it numerically, we cannot attempt any precise estimation of the comparative probabilities. But of this we are sure, that the detection of an unknown law of nature, of some previously unrecognized constancy of conjunction among phenomena, is no uncommon event. If, therefore, the number of instances in which a coincidence is observed, over and above that which would arise on the average from the mere concurrence of chances, be such that so great an amount of coincidences from accident alone would be an extremely uncommon event, we have reason to conclude that the coincidence is the effect of causation, and may be received, subject to correction from further experience, as an empirical law. Further than this, in point of precision, we cannot go. Nor, in most cases, is greater precision required, for the solution of any practical doubt. 182. 19. Of the extension of derivative laws to adjacent cases. Section 1. We have had frequent occasion to notice the inferior generality of derivative laws, compared with the ultimate laws from which they are derived. This inferiority, which affects not only the extent of the propositions themselves, but their degree of certainty within that extent, is most conspicuous in the uniformities of coexistence and sequence obtaining between effects which depend ultimately on different primeval causes. Such uniformities will only obtain where there exists the same collocation of those primeval causes. If the collocation varies, though the laws themselves remain the same, a totally different set of derivative uniformities may, and generally will, be the result. Even where the derivative uniformity is between different effects of the same cause, it will by no means obtain as universally as the law of the cause itself. If A and B accompany or succeed one another as effects of the cause A, it by no means follows that A is the only cause which can produce them, or that if there be another cause, as B, capable of producing A, it must produce B likewise. The conjunction, therefore, of A and B perhaps does not hold universally, but only in the instances in which A arises from A. When it is produced by a cause other than A and B may be dissevered. Day, for example, is always in our experience followed by night, but day is not the cause of night. Both are successive effects of a common cause, the periodical passage of the spectator into and out of the Earth's shadow, consequent on the Earth's rotation, and on the illuminating property of the sun. If, therefore, day is ever produced by a different cause or set of causes from this, day will not, or at least may not, be followed by night. On the sun's own surface, for instance, this may be the case. Finally, even when the derivative uniformity is itself a law of causation, resulting from the combination of several causes, it is not altogether independent of collocations. If a cause supervenes, capable of wholly or partially counteracting the effect of any one of the conjoined causes, the effect will no longer conform to the derivative law. While, therefore, each ultimate law is only liable to frustration from one set of counteracting causes, the derivative law is liable to it from several. Now, the possibility of the occurrence of counteracting causes which do not arise from any of the conditions involved in the law itself depends on the original collocations. It is true that, as we formerly remarked, laws of causation, whether ultimate or derivative, are, in most cases, fulfilled even when counteracted. The cause produces its effect, though that effect is destroyed by something else. That the effect may be frustrated, is, therefore, no objection to the universality of laws of causation. But it is fatal to the universality of the sequences or coexistences of effects, which compose the greater part of the derivative laws flowing from laws of causation. When, from the law of a certain combination of causes, there results a certain order in the effects. As from the combination of a single sun with the rotation of an opaque body round its axis, there results, on the whole surface of that opaque body, an alternation of day and night. Then, if we suppose one of the combined causes counteracted, the rotation stopped, the sun extinguished, or a second sun superadded, the truth of that particular law of causation is in no way affected. It is still true that one sun shining on an opaque revolving body will alternately produce day and night. But since the sun no longer does shine on such a body, the derivative uniformity, the succession of day and night on the given planet, is no longer true. Those derivative uniformities, therefore, which are not laws of causation, are, except in the rare case of their depending on one cause alone, not on a combination of causes, always more or less contingent on collocations. And are hence subject to the characteristic infirmity of empirical laws, that of being admissible only where the collocations are known by experience to be such as are requisite for the truth of the law. That is, only within the conditions of time and place confirmed by actual observation. Section 2. This principle, when stated in general terms, seems clear and indisputable. Yet many of the ordinary judgments of mankind, the propriety of which is not questioned, have at least the semblance of being inconsistent with it. On what grounds, it may be asked, do we expect that the sun will rise tomorrow? Tomorrow is beyond the limits of time comprehended in our observations. They have extended over some thousands of years past, but they do not include the future. Yet we infer with confidence that the sun will rise tomorrow. And nobody doubts that we are entitled to do so. Let us consider what is the warrant for this confidence. In the example in question, we know the causes on which the derivative uniformity depends. They are, the sun giving out light, the earth in a state of rotation and intercepting light. The induction which shows these to be the real causes, and not merely prior effects of a common cause, being complete. The only circumstances which could defeat the derivative law are such as would destroy or counteract one or other of the combined causes. While the causes exist and are not counteracted, the effect will continue. If they exist and are not counteracted tomorrow, the sun will rise tomorrow. Since the causes, namely, the sun and the earth, the one in the state of giving out light, the other in a state of rotation, will exist until something destroys them, all depends on the probabilities of their destruction, or of their counteraction. We know by observation, omitting the inferential proofs of an existence for thousands of ages anterior, that these phenomena have continued for, say, 5,000 years. Within that time there has existed no cause sufficient to diminish them appreciably, nor which has counteracted their effect in any appreciable degree. The chance, therefore, that the sun may not rise tomorrow amounts to the chance that some cause, which has not manifested itself in the smallest degree during 5,000 years, will exist tomorrow in such intensity as to destroy the sun or the earth, the sun's light or the earth's rotation, or to produce an immense disturbance in the effect resulting from those causes. Now, if such a cause will exist tomorrow, or at any future time, some cause, proximate or remote, of that cause must exist now, and must have existed during the whole of the 5,000 years. If, therefore, the sun do not rise tomorrow, it will be because some cause has existed, the effects of which, though during 5,000 years they have not amounted to a perceptible quantity, will in one day become overwhelming. Since this cause has not been recognized during such an interval of time by observers stationed on our earth, it must, if it be a single agent, be either one whose effects develop themselves gradually and very slowly, or one which existed in regions beyond our observation, and is now on the point of arriving in our part of the universe. Now all causes which we have experience of act according to laws incompatible with the supposition that their effects, after accumulating so slowly as to be imperceptible for 5,000 years, should start into immensity in a single day. No mathematical law of proportion between an effect and the quantity or relations of its cause could produce such contradictory results. The sudden development of an effect of which there was no previous trace always arises from the coming together of several distinct causes, not previously conjoined. But if such sudden conjunction is destined to take place, the causes, or their causes, must have existed during the entire 5,000 years, and their not having once come together during that period shows how rare that particular combination is. We have, therefore, the warrant of a rigid induction for considering it probable, in a degree undistinguishable from certainty, that the known conditions requisite for the sun's rising will exist tomorrow. Section 3. But this extension of derivative laws, not causative, beyond the limits of observation can only be to adjacent cases. If, instead of tomorrow, we had said this day 20,000 years, the inductions would have been anything but conclusive. That a cause which, in opposition to very powerful causes, produced no perceptible effect during 5,000 years, should produce a very considerable one by the end of 20,000. Has nothing in it which is not in conformity with our experience of causes. We know many agents, the effect of which in a short period does not amount to a perceptible quantity, but by accumulating for a much longer period becomes considerable. Besides, looking at the immense multitude of the heavenly bodies, their vast distances, and the rapidity of the motion of such of them as are known to move, it is a supposition not at all contradictory to experience that some body may be in motion toward us, or we toward it, within the limits of whose influence we have not come during 5,000 years. But which in 20,000 more may be producing effects upon us of the most extraordinary kind. Or the fact which is capable of preventing sunrise may be, not the cumulative effect of one cause, but some new combination of causes. And the chances favorable to that combination, though they have not produced it once in 5,000 years, may produce it once in 20,000. So that the inductions which authorize us to expect future events, grow weaker and weaker the further we look into the future, and at length become inappreciable. We have considered the probabilities of the sun's rising tomorrow, as derived from the real laws, that is, from the laws of the causes on which that uniformity is dependent. Let us now consider how the matter would have stood if the uniformity had been known only as an empirical law. If we had not been aware that the sun's light and the earth's rotation, or the sun's motion, were the causes on which the periodical occurrence of daylight depends, we could have extended this empirical law to cases adjacent in time, though not to so great a distance of time as we can now. Having evidence that the effects had remained unaltered and been punctually conjoined for 5,000 years, we could infer that the unknown causes on which the conjunction is dependent had existed undiminished and uncounteracted during the same period. The same conclusions, therefore, would follow as in the preceding case, except that we should only know that during 5,000 years nothing had occurred to defeat perceptibly this particular effect. While, when we know the causes, we have the additional assurance that during that interval no such change has been noticeable in the causes themselves as by any degree of multiplication or length of continuance could defeat the effect. To this must be added, that when we know the causes, we may be able to judge whether there exists any known cause capable of counteracting them, while as long as they are unknown, we cannot be sure but that if we did know them, we could predict their destruction from causes actually in existence. A bedridden savage, who had never seen the cataract of Niagara, but who lived within hearing of it, might imagine that the sound he heard would endure forever. But if he knew it to be the effect of a rush of waters over a barrier of rock which is progressively wearing away, he would know that within a number of ages which may be calculated it will be heard no more. In proportion, therefore, to our ignorance of the causes on which the empirical law depends, we can be less assured that it will continue to hold good. And the further we look into futurity, the less improbable is it that some one of the causes, whose coexistence gives rise to the derivative uniformity, may be destroyed or counteracted. With every prolongation of time the chances multiply of such an event, that is to say, its non-occurrence hitherto becomes a less guarantee of its not occurring within the given time. If, then, it is only to cases which in point of time are adjacent, or nearly adjacent, to those which we have actually observed, that any derivative law, not of causation, can be extended with an assurance equivalent to certainty. Much more is this true of a merely empirical law. Happily, for the purposes of life it is to such cases alone that we can almost ever have occasion to extend them. In respect of place, it might seem that a merely empirical law could not be extended even to adjacent cases. That we could have no assurance of its being true in any place where it has not been specially observed. The past duration of a cause is a guarantee for its future existence, unless something occurs to destroy it. But the existence of a cause in one or any number of places is no guarantee for its existence in any other place, since there is no uniformity in the collocations of primeval causes. When, therefore, an empirical law is extended beyond the local limits within which it has been found true by observation, the cases to which it is thus extended must be such as are presumably within the influence of the same individual agents. If we discover a new planet within the known bounds of the solar system, or even beyond those bounds, but indicating its connection with the system by revolving round the sun, we may conclude, with great probability, that it revolves on its axis. For all the known planets do so, and this uniformity points to some common cause, antecedent to the first records of astronomical observation. And though the nature of this cause can only be matter of conjecture, yet if it be, as is not unlikely, and as Laplace's theory supposes, not merely the same kind of cause, but the same individual cause, such as an impulse given to all the bodies at once, that cause, acting at the extreme points of the space occupied by the sun and planets, is likely, unless defeated by some counteracting cause, to have acted at every intermediate point, and probably somewhat beyond. And therefore acted, in all probability, upon the supposed newly discovered planet. When, therefore, effects which are always found conjoined can be traced with any probability to an identical, and not merely a similar, origin, we may with the same probability extend the empirical law of their conjunction to all places within the extreme local boundaries within which the fact has been observed, subject to the possibility of counteracting causes in some portion of the field. Still more confidently may we do so when the law is not merely empirical, when the phenomena which we find conjoined are effects of ascertained causes, from the laws of which the conjunction of their effects is deducible. In that case, we may both extend the derivative uniformity over a larger space, and with less abatement for the chance of counteracting causes. The first, because instead of the local boundaries of our observation of the fact itself, we may include the extreme boundaries of the ascertained influence of its causes. Thus the succession of day and night, we know, holds true of all the bodies of the solar system except the sun itself, but we know this only because we are acquainted with the causes. If we were not, we could not extend the proposition beyond the orbits of the earth and moon, at both extremities of which we have the evidence of observation for its truth. With respect to the probability of counteracting causes, it has been seen that this calls for a greater abatement of confidence, in proportion to our ignorance of the causes on which the phenomena depend. On both accounts, therefore, a derivative law which we know how to resolve, is susceptible of a greater extension to cases adjacent in place, than a merely empirical law. XXIII of Analogy. Section 1. The word analogy, as the name of a mode of reasoning, is generally taken for some kind of argument supposed to be of an inductive nature, but not amounting to a complete induction. There is no word, however, which is used more loosely, or in a greater variety of senses, than analogy. It sometimes stands for arguments which may be examples of the most rigorous induction. Archbishop Whately, for instance, following Ferguson and other writers, defines analogy conformably to its primitive acceptation, that which was given to it by mathematicians, resemblance of relations. In this sense, when a country which has sent out colonies is termed the mother country, the expression is analogical, signifying that the colonies of a country stand in the same relation to her in which children stand to their parents. And if any inference be drawn from this resemblance of relations, as, for instance, that obedience or affection is due from colonies to the mother country, this is called reasoning by analogy. Or, if it be argued that a nation is most beneficially governed by an assembly elected by the people, from the admitted fact that other associations for a common purpose, such as joint stock companies, are best managed by a committee chosen by the parties interested. This, too, is an argument from analogy in the preceding sense, because its foundation is, not that a nation is like a joint stock company, or Parliament like a board of directors, but that Parliament stands in the same relation to the nation in which a board of directors stands to a joint stock company. Now, in an argument of this nature, there is no inherent inferiority of conclusiveness. Like other arguments from resemblance, it may amount to nothing, or it may be a perfect and conclusive induction. The circumstance in which the two cases resemble, may be capable of being shown to be the material circumstance, to be that on which all the consequences, necessary to be taken into account in the particular discussion, depend. In the example last given, the resemblance is one of relation, the fundamentum relationis being the management, by a few persons, of affairs in which a much greater number are interested along with them. Now, some may contend that this circumstance which is common to the two cases, and the various consequences which follow from it, have the chief share in determining all the effects which make up what we term good or bad administration. If they can establish this, their argument has the force of a rigorous induction; if they cannot, they are said to have failed in proving the analogy between the two cases. A mode of speech which implies that when the analogy can be proved, the argument founded on it cannot be resisted. Section 2. It is on the whole more usual, however, to extend the name of analogical evidence to arguments from any sort of resemblance, provided they do not amount to a complete induction, without peculiarly distinguishing resemblance of relations. Analogical reasoning, in this sense, may be reduced to the following formula: two things resemble each other in one or more respects, a certain proposition is true of the one, therefore it is true of the other. But we have nothing here by which to discriminate analogy from induction, since this type will serve for all reasoning from experience. In the strictest induction, equally with the faintest analogy, we conclude because A resembles B in one or more properties, that it does so in a certain other property. The difference is, that in the case of a complete induction it has been previously shown, by due comparison of instances, that there is an invariable conjunction between the former property or properties and the latter property. But in what is called analogical reasoning, no such conjunction has been made out. There have been no opportunities of putting in practice the method of difference, or even the method of agreement. But we conclude, and that is all which the argument of analogy amounts to, that a fact M, known to be true of A, is more likely to be true of B if B agrees with A in some of its properties, even though no connection is known to exist between M and those properties, than if no resemblance at all could be traced between B and any other thing known to possess the attribute M. To this argument it is of course requisite that the properties common to A with B shall be merely not known to be connected with M, they must not be properties known to be unconnected with it. If, either by processes of elimination, or by deduction from previous knowledge of the laws of the properties in question, it can be concluded that they have nothing to do with M, the argument of analogy is put out of court. The supposition must be that M is in effect really dependent on some property of A, but we know not on which. We cannot point out any of the properties of A, which is the cause of M, or united with it by any law. After rejecting all which we know to have nothing to do with it, there remain several between which we are unable to decide, of which remaining properties, B possesses one or more. This, accordingly, we consider as affording grounds, of more or less strength, for concluding by analogy that B possesses the attribute M. There can be no doubt that every such resemblance which can be pointed out between B and A, affords some degree of probability, beyond what would otherwise exist, in favor of the conclusion drawn from it. If B resembled A in all its ultimate properties, its possessing the attribute M would be a certainty, not a probability, and every resemblance which can be shown to exist between them, places it by so much the nearer to that point. If the resemblance be in an ultimate property, there will be resemblance in all the derivative properties dependent on that ultimate property, and of these M may be one. If the resemblance be in a derivative property, there is reason to expect resemblance in the ultimate property on which it depends, and in the other derivative properties dependent on the same ultimate property. Every resemblance which can be shown to exist, affords ground for expecting an indefinite number of other resemblances. The particular resemblance sought will, therefore, be oftener found among things thus known to resemble, than among things between which we know of no resemblance. For example, I might infer that there are probably inhabitants in the moon, because there are inhabitants on the earth, in the sea, and in the air, and this is the evidence of analogy. The circumstance of having inhabitants is here assumed not to be an ultimate property, but, as is reasonable to suppose, a consequence of other properties. And depending, therefore, in the case of the earth, on some of its properties as a portion of the universe, but on which of those properties we know not. Now the moon resembles the earth in being a solid, opaque, nearly spherical substance, appearing to contain, or to have contained, active volcanoes, receiving heat and light from the sun, in about the same quantity as our earth. Revolving on its axis, composed of materials which gravitate, and obeying all the various laws resulting from that property. And I think no one will deny that if this were all that was known of the moon, the existence of inhabitants in that luminary would derive from these various resemblances to the earth, a greater degree of probability than it would otherwise have. Though the amount of the augmentation it would be useless to attempt to estimate. If, however, every resemblance proved between B and A, in any point not known to be immaterial with respect to M, forms some additional reason for presuming that B has the attribute M. It is clear, a contra, that every dissimilarity which can be proved between them furnishes a counterprobability of the same nature on the other side. It is not, indeed, unusual that different ultimate properties should, in some particular instances, produce the same derivative property. But on the whole it is certain that things which differ in their ultimate properties, will differ at least as much in the aggregate of their derivative properties, and that the differences which are unknown will, on the average of cases, bear some proportion to those which are known. There will, therefore, be a competition between the known points of agreement and the known points of difference in A and B. And according as the one or the other may be deemed to preponderate, the probability derived from analogy will be for or against B's having the property M. The moon, for instance, agrees with the earth in the circumstances already mentioned, but differs in being smaller, in having its surface more unequal, and apparently volcanic throughout, in having, at least on the side next the earth, no atmosphere sufficient to refract light, no clouds, and, it is therefore concluded, no water. These differences, considered merely as such, might perhaps balance the resemblances, so that analogy would afford no presumption either way. But considering that some of the circumstances which are wanting on the moon are among those which, on the earth, are found to be indispensable conditions of animal life, we may conclude that if that phenomenon does exist in the moon, or at all events on the nearer side, it must be as an effect of causes totally different from those on which it depends here. As a consequence, therefore, of the moon's differences from the earth, not of the points of agreement. Viewed in this light, all the resemblances which exist become presumptions against, not in favor of, the moon's being inhabited. Since life cannot exist there in the manner in which it exists here, the greater the resemblance of the lunar world to the terrestrial in other respects, the less reason we have to believe that it can contain life. There are, however, other bodies in our system, between which and the Earth there is a much closer resemblance, which possess an atmosphere, clouds, consequently water, or some fluid analogous to it, and even give strong indications of snow in their polar regions. While the cold, or heat, though differing greatly on the average from ours, is, in some parts at least of those planets, possibly not more extreme than in some regions of our own which are habitable. To balance these agreements, the ascertained differences are chiefly in the average light and heat, velocity of rotation, density of material, intensity of gravity, and similar circumstances of a secondary kind. With regard to these planets, therefore, the argument of analogy gives a decided preponderance in favor of their resembling the Earth in any of its derivative properties, such as that of having inhabitants. Though when we consider how immeasurably multitudinous are those of their properties which we are entirely ignorant of, compared with the few which we know, we can attach but trifling weight to any considerations of resemblance in which the known elements bear so inconsiderable a proportion to the unknown. Besides the competition between analogy and diversity, there may be a competition of conflicting analogies. The new case may be similar in some of its circumstances to cases in which the fact M exists, but in others to cases in which it is known not to exist. Amber has some properties in common with vegetable, others with mineral products. A painting of unknown origin may resemble, in certain of its characters, known works of a particular master, but in others it may as strikingly resemble those of some other painter. A vase may bear some analogy to works of Grecian, and some to those of Etruscan, or Egyptian art. We are of course supposing that it does not possess any quality which has been ascertained, by a sufficient induction, to be a conclusive mark either of the one or of the other. Section 3. Since the value of an analogical argument inferring one resemblance from other resemblances without any antecedent evidence of a connection between them, depends on the extent of ascertained resemblance. Compared first with the amount of ascertained difference, and next with the extent of the unexplored region of unascertained properties. It follows that where the resemblance is very great, the ascertained difference very small, and our knowledge of the subject matter tolerably extensive, the argument from analogy may approach in strength very near to a valid induction. If, after much observation of B, we find that it agrees with A in 9 out of 10 of its known properties, we may conclude with a probability of 9 to 1, that it will possess any given derivative property of A. If we discover, for example, an unknown animal or plant, resembling closely some known one in the greater number of the properties we observe in it, but differing in some few, we may reasonably expect to find in the unobserved remainder of its properties, a general agreement with those of the former, but also a difference corresponding proportionately to the amount of observed diversity. It thus appears that the conclusions derived from analogy are only of any considerable value, when the case to which we reason is an adjacent case. Adjacent, not as before, in place or time, but in circumstances. In the case of effects of which the causes are imperfectly or not at all known, when consequently the observed order of their occurrence amounts only to an empirical law. It often happens that the conditions which have coexisted whenever the effect was observed, have been very numerous. Now if a new case presents itself, in which all these conditions do not exist, but the far greater part of them do, some one or a few only being wanting, the inference that the effect will occur. Notwithstanding this deficiency of complete resemblance to the cases in which it has been observed, may, though of the nature of analogy, possess a high degree of probability. It is hardly necessary to add that, however considerable this probability may be, no competent inquirer into nature will rest satisfied with it when a complete induction is attainable, but will consider the analogy as a mere guidepost, pointing out the direction in which more rigorous investigations should be prosecuted. It is in this last respect that considerations of analogy have the highest scientific value. The cases in which analogical evidence affords in itself any very high degree of probability, are, as we have observed, only those in which the resemblance is very close and extensive. But there is no analogy, however faint, which may not be of the utmost value in suggesting experiments or observations that may lead to more positive conclusions. When the agents and their effects are out of the reach of further observation and experiment, as in the speculations already alluded to respecting the moon and planets, such slight probabilities are no more than an interesting theme for the pleasant exercise of imagination. But any suspicion, however slight, that sets an ingenious person at work to contrive an experiment, or affords a reason for trying one experiment rather than another, may be of the greatest benefit to science. On this ground, though I cannot accept as positive truths any of those scientific hypotheses which are unsusceptible of being ultimately brought to the test of actual induction, such, for instance, as the two theories of light, the emission theory of the last century, and the undulatory theory which predominates in the present, I am yet unable to agree with those who consider such hypotheses to be worthy of entire disregard. As is well said by Hartley, and concurred in by a thinker in general so diametrically opposed to Hartley's opinions as Douglas Stuart, any hypothesis which has so much plausibility as to explain a considerable number of facts, helps us to digest these facts in proper order, to bring new ones to light, and make experimenta crucis for the sake of future inquirers. 183 If an hypothesis both explains known facts, and has led to the prediction of others previously unknown, and since verified by experience, the laws of the phenomenon which is the subject of inquiry must bear at least a great similarity to those of the class of phenomena to which the hypothesis assimilates it. And since the analogy which extends so far may probably extend further, nothing is more likely to suggest experiments tending to throw light upon the real properties of the phenomenon, than the following out such an hypothesis. But to this end it is by no means necessary that the hypothesis be mistaken for a scientific truth. On the contrary, that illusion is in this respect, as in every other, an impediment to the progress of real knowledge, by leading inquirers to restrict themselves arbitrarily to the particular hypothesis which is most accredited at the time, instead of looking out for every class of phenomena between the laws of which and those of the given phenomenon any analogy exists, and trying all such experiments as may tend to the discovery of ulterior analogies pointing in the same direction. XXII of the evidence of the law of universal causation. Section 1. We have now completed our review of the logical processes by which the laws, or uniformities, of the sequence of phenomena, and those uniformities in their coexistence which depend on the laws of their sequence, are ascertained or tested. As we recognized in the commencement, and have been enabled to see more clearly in the progress of the investigation, the basis of all these logical operations is the law of causation. The validity of all the inductive methods depends on the assumption that every event, or the beginning of every phenomenon, must have some cause, some antecedent, on the existence of which it is invariably and unconditionally consequent. In the method of agreement this is obvious, that method avowedly proceeding on the supposition that we have found the true cause as soon as we have negatived every other. The assertion is equally true of the method of difference. That method authorizes us to infer a general law from two instances, one, in which A exists together with a multitude of other circumstances, and B follows. Another, in which, A being removed, and all other circumstances remaining the same, B is prevented. What, however, does this prove? It proves that B, in the particular instance, cannot have had any other cause than A. But to conclude from this that A was the cause, or that A will on other occasions be followed by B, is only allowable on the assumption that B must have some cause. That among its antecedents in any single instance in which it occurs, there must be one which has the capacity of producing it at other times. This being admitted, it is seen that in the case in question that antecedent can be no other than A. But that if it be no other than A it must be A, is not proved, by these instances at least, but taken for granted. There is no need to spend time in proving that the same thing is true of the other inductive methods. The universality of the law of causation is assumed in them all. But is this assumption warranted? Doubtless, it may be said, most phenomena are connected as effects with some antecedent or cause, that is, are never produced unless some assignable fact has preceded them. But the very circumstance that complicated processes of induction are sometimes necessary, shows that cases exist in which this regular order of succession is not apparent to our unaided apprehension. If, then, the processes which bring these cases within the same category with the rest, require that we should assume the universality of the very law which they do not at first sight appear to exemplify, is not this a petitio principii? Can we prove a proposition, by an argument which takes it for granted? And if not so proved, on what evidence does it rest? For this difficulty, which I have purposely stated in the strongest terms it will admit of, the school of metaphysicians who have long predominated in this country find a ready salvo. They affirm, that the universality of causation is a truth which we cannot help believing, that the belief in it is an instinct, one of the laws of our believing faculty. As the proof of this, they say, and they have nothing else to say, that every body does believe it. And they number it among the propositions, rather numerous in their catalogue, which may be logically argued against and perhaps cannot be logically proved, but which are of higher authority than logic. And so essentially inherent in the human mind, that even he who denies them in speculation, shows by his habitual practice that his arguments make no impression upon himself. Into the merits of this question, considered as one of psychology, it would be foreign to my purpose to enter here. But I must protest against adducing, as evidence of the truth of a fact in external nature, the disposition, however strong or however general, of the human mind to believe it. Belief is not proof, and does not dispense with the necessity of proof. I am aware, that to ask for evidence of a proposition which we are supposed to believe instinctively, is to expose one's self to the charge of rejecting the authority of the human faculties. Which of course no one can consistently do, since the human faculties are all which any one has to judge by, and inasmuch as the meaning of the word evidence is supposed to be, something which when laid before the mind, induces it to believe. To demand evidence when the belief is ensured by the mind's own laws, is supposed to be appealing to the intellect against the intellect. But this, I apprehend, is a misunderstanding of the nature of evidence. By evidence is not meant anything and everything which produces belief. There are many things which generate belief besides evidence. A mere strong association of ideas often causes a belief so intense as to be unshakable by experience or argument. Evidence is not that which the mind does or must yield to, but that which it ought to yield to, namely, that, by yielding to which its belief is kept conformable to fact. There is no appeal from the human faculties generally, but there is an appeal from one human faculty to another, from the judging faculty, to those which take cognizance of fact, the faculties of sense and consciousness. The legitimacy of this appeal is admitted whenever it is allowed that our judgments ought to be conformable to fact. To say that belief suffices for its own justification is making opinion the test of opinion. It is denying the existence of any outward standard, the conformity of an opinion to which constitutes its truth. We call one mode of forming opinions right and another wrong, because the one does, and the other does not, tend to make the opinion agree with the fact, to make people believe what really is, and expect what really will be. Now a mere disposition to believe, even if supposed instinctive, is no guarantee for the truth of the thing believed. If, indeed, the belief ever amounted to an irresistible necessity, there would then be no use in appealing from it, because there would be no possibility of altering it. But even then the truth of the belief would not follow. It would only follow that mankind were under a permanent necessity of believing what might possibly not be true. In other words, that a case might occur in which our senses or consciousness, if they could be appealed to, might testify one thing, and our reason believe another. But in fact there is no such permanent necessity. There is no proposition of which it can be asserted that every human mind must eternally and irrevocably believe it. Many of the propositions of which this is most confidently stated, great numbers of human beings have disbelieved. The things which it has been supposed that nobody could possibly help believing, are innumerable, but no two generations would make out the same catalogue of them. One age or nation believes implicitly what to another seems incredible and inconceivable, one individual has not a vestige of a belief which another deems to be absolutely inherent in humanity. There is not one of these supposed instinctive beliefs which is really inevitable. It is in the power of every one to cultivate habits of thought which make him independent of them. The habit of philosophical analysis, of which it is the surest effect to enable the mind to command, instead of being commanded by, the laws of the merely passive part of its own nature. By showing to us that things are not necessarily connected in fact because their ideas are connected in our minds, is able to loosen innumerable associations which reign despotically over the undisciplined or early prejudiced mind. And this habit is not without power even over those associations which the school of which I have been speaking regard as connate and instinctive. I am convinced that any one accustomed to abstraction and analysis, who will fairly exert his faculties for the purpose, will, when his imagination has once learned to entertain the notion, find no difficulty in conceiving that in some one. For instance, of the many firmaments into which sidereal astronomy now divides the universe, events may succeed one another at random, without any fixed law. Nor can anything in our experience, or in our mental nature, constitute a sufficient, or indeed any, reason for believing that this is nowhere the case. Were we to suppose, what it is perfectly possible to imagine, that the present order of the universe were brought to an end, and that a chaos succeeded in which there was no fixed succession of events, and the past gave no assurance of the future. If a human being were miraculously kept alive to witness this change, he surely would soon cease to believe in any uniformity, the uniformity itself no longer existing. If this be admitted, the belief in uniformity either is not an instinct, or it is an instinct conquerable, like all other instincts, by acquired knowledge. But there is no need to speculate on what might be, when we have positive and certain knowledge of what has been. It is not true, as a matter of fact, that mankind have always believed that all the successions of events were uniform and according to fixed laws. The Greek philosophers, not even excepting Aristotle, recognized chance and spontaneity, tau chi eta and tau alpha tau omicron mu tau omicron nu, as among the agents in nature. In other words, they believed that to that extent there was no guarantee that the past had been similar to itself, or that the future would resemble the past. Even now a full half of the philosophical world, including the very same metaphysicians who contend most for the instinctive character of the belief in uniformity, consider one important class of phenomena, volitions, to be an exception to the uniformity, and not governed by a fixed law. 184. Section 2. As was observed in a former place, 185. The belief we entertain in the universality, throughout nature, of the law of cause and effect, is itself an instance of induction. And by no means one of the earliest which any of us, or which mankind in general, can have made. We arrive at this universal law, by generalization from many laws of inferior generality. We should never have had the notion of causation, in the philosophical meaning of the term, as a condition of all phenomena, unless many cases of causation, or in other words, many partial uniformities of sequence, had previously become familiar. The more obvious of the particular uniformities suggest, and give evidence of, the general uniformity, and the general uniformity, once established, enables us to prove the remainder of the particular uniformities of which it is made up. As, however, all rigorous processes of induction presuppose the general uniformity, our knowledge of the particular uniformities from which it was first inferred was not, of course, derived from rigorous induction, but from the loose and uncertain mode of induction per enumerationem simplicem. And the law of universal causation, being collected from results so obtained, cannot itself rest on any better foundation. It would seem, therefore, that induction per enumerationem simplicem not only is not necessarily an illicit logical process, but is in reality the only kind of induction possible. Since the more elaborate process depends for its validity on a law, itself obtained in that inartificial mode. Is there not then an inconsistency in contrasting the looseness of one method with the rigidity of another, when that other is indebted to the looser method for its own foundation? The inconsistency, however, is only apparent. Assuredly, if induction by simple enumeration were an invalid process, no process grounded on it could be valid, just as no reliance could be placed on telescopes, if we could not trust our eyes. But though a valid process, it is a fallible one, and fallible in very different degrees, if, therefore, we can substitute for the more fallible forms of the process, an operation grounded on the same process in a less fallible form, we shall have effected a very material improvement. And this is what scientific induction does. A mode of concluding from experience must be pronounced untrustworthy when subsequent experience refuses to confirm it. According to this criterion, induction by simple enumeration, in other words, generalization of an observed fact from the mere absence of any known instance to the contrary, affords in general a precarious and unsafe ground of assurance. For such generalizations are incessantly discovered, on further experience, to be false. Still, however, it affords some assurance, sufficient, in many cases, for the ordinary guidance of conduct. It would be absurd to say, that the generalizations arrived at by mankind in the outset of their experience, such as these, food nourishes, fire burns, water drowns, were unworthy of reliance. 186 There is a scale of trustworthiness in the results of the original unscientific induction, and on this diversity, as observed in the 4th chapter of the present book, depend the rules for the improvement of the process. The improvement consists in correcting one of these inartificial generalizations by means of another. As has been already pointed out, this is all that art can do. To test a generalization, by showing that it either follows from, or conflicts with, some stronger induction, some generalization resting on a broader foundation of experience, is the beginning and end of the logic of induction. Section 3. Now the precariousness of the method of simple enumeration is in an inverse ratio to the largeness of the generalization. The process is delusive and insufficient, exactly in proportion as the subject matter of the observation is special and limited in extent. As the sphere widens, this unscientific method becomes less and less liable to mislead. And the most universal class of truths, the law of causation, for instance, and the principles of number and of geometry, are duly and satisfactorily proved by that method alone, nor are they susceptible of any other proof. With respect to the whole class of generalizations of which we have recently treated, the uniformities which depend on causation, the truth of the remark just made follows by obvious inference from the principles laid down in the preceding chapters. When a fact has been observed a certain number of times to be true, and is not in any instance known to be false, if we at once affirm that fact as a universal truth or law of nature, without either testing it by any of the 4 methods of induction, or deducing it from other known laws, we shall in general err grossly. But we are perfectly justified in affirming it as an empirical law, true within certain limits of time, place, and circumstance, provided the number of coincidences be greater than can with any probability be ascribed to chance. The reason for not extending it beyond those limits is, that the fact of its holding true within them may be a consequence of collocations, which cannot be concluded to exist in one place because they exist in another. Or may be dependent on the accidental absence of counteracting agencies, which any variation of time, or the smallest change of circumstances, may possibly bring into play. If we suppose, then, the subject matter of any generalization to be so widely diffused that there is no time, no place, and no combination of circumstances, but must afford an example either of its truth or of its falsity. And if it be never found otherwise than true, its truth cannot be contingent on any collocations, unless such as exist at all times and places. Nor can it be frustrated by any counteracting agencies, unless by such as never actually occur. It is, therefore, an empirical law coextensive with all human experience. At which point the distinction between empirical laws and laws of nature vanishes, and the proposition takes its place among the most firmly established as well as largest truths accessible to science. Now, the most extensive in its subject matter of all generalizations which experience warrants, respecting the sequences and coexistences of phenomena, is the law of causation. It stands at the head of all observed uniformities, in point of universality, and therefore, if the preceding observations are correct, in point of certainty. And if we consider, not what mankind would have been justified in believing in the infancy of their knowledge, but what may rationally be believed in its present more advanced state, we shall find ourselves warranted in considering this fundamental law, though itself obtained by induction from particular laws of causation, as not less certain, but on the contrary, more so, than any of those from which it was drawn. It adds to them as much proof as it receives from them. For there is probably no one even of the best established laws of causation which is not sometimes counteracted, and to which, therefore, apparent exceptions do not present themselves. Which would have necessarily and justly shaken the confidence of mankind in the universality of those laws, if inductive processes founded on the universal law had not enabled us to refer those exceptions to the agency of counteracting causes, and thereby reconcile them with the law with which they apparently conflict. Errors, moreover, may have slipped into the statement of any one of the special laws, through inattention to some material circumstance, and instead of the true proposition, another may have been enunciated, false as a universal law, though leading, in all cases hitherto observed, to the same result. To the law of causation, on the contrary, we not only do not know of any exception, but the exceptions which limit or apparently invalidate the special laws, are so far from contradicting the universal one, that they confirm it. Since in all cases which are sufficiently open to our observation, we are able to trace the difference of result, either to the absence of a cause which had been present in ordinary cases, or to the presence of one which had been absent. The law of cause and effect, being thus certain, is capable of imparting its certainty to all other inductive propositions which can be deduced from it. And the narrower inductions may be regarded as receiving their ultimate sanction from that law, since there is no one of them which is not rendered more certain than it was before, when we are able to connect it with that larger induction. And to show that it cannot be denied, consistently with the law that everything which begins to exist has a cause. And hence we are justified in the seeming inconsistency, of holding induction by simple enumeration to be good for proving this general truth, the foundation of scientific induction, and yet refusing to rely on it for any of the narrower inductions. I fully admit that if the law of causation were unknown, generalization in the more obvious cases of uniformity in phenomena would nevertheless be possible, and though in all cases more or less precarious, and in some extremely so, would suffice to constitute a certain measure of probability. But what the amount of this probability might be, we are dispensed from estimating, since it never could amount to the degree of assurance which the proposition acquires, when, by the application to it of the four methods, the supposition of its falsity is shown to be inconsistent with the law of causation. We are therefore logically entitled, and, by the necessities of scientific induction, required, to disregard the probabilities derived from the early rude method of generalizing, and to consider no minor generalization as proved except so far as the law of causation confirms it, nor probable except so far as it may reasonably be expected to be so confirmed. Section 4. The assertion, that our inductive processes assume the law of causation, while the law of causation is itself a case of induction, is a paradox, only on the old theory of reasoning, which supposes the universal truth, or major premise, in a ratiocination, to be the real proof of the particular truths which are ostensibly inferred from it. According to the doctrine maintained in the present treatise 187, the major premise is not the proof of the conclusion, but is itself proved, along with the conclusion from the same evidence. All men are mortal is not the proof that Lord Palmerston is mortal, but our past experience of mortality authorizes us to infer both the general truth and the particular fact, and the one with exactly the same degree of assurance as the other. The mortality of Lord Palmerston is not an inference from the mortality of all men, but from the experience which proves the mortality of all men, and is a correct inference from experience, if that general truth is so too. This relation between our general beliefs and their particular applications holds equally true in the more comprehensive case which we are now discussing. Any new fact of causation inferred by induction, is rightly inferred, if no other objection can be made to the inference than can be made to the general truth that every event has a cause. The utmost certainty which can be given to a conclusion arrived at in the way of inference, stops at this point. When we have ascertained that the particular conclusion must stand or fall with the general uniformity of the laws of nature, that it is liable to no doubt except the doubt whether every event has a cause, we have done all that can be done for it. The strongest assurance we can obtain of any theory respecting the cause of a given phenomenon, is that the phenomenon has either that cause or none. The latter supposition might have been an admissible one in a very early period of our study of nature. But we have been able to perceive that in the stage which mankind have now reached, the generalization which gives the law of universal causation has grown into a stronger and better induction, one deserving of greater reliance than any of the subordinate generalizations. We may even, I think, go a step further than this, and regard the certainty of that great induction as not merely comparative, but, for all practical purposes, complete. The considerations, which, as I apprehend, give, at the present day, to the proof of the law of uniformity of succession as true of all phenomena without exception, this character of completeness and conclusiveness, are the following. First, that we now know it directly to be true of far the greatest number of phenomena. That there are none of which we know it not to be true, the utmost that can be said being, that of some we cannot positively from direct evidence affirm its truth. While phenomenon after phenomenon, as they become better known to us, are constantly passing from the latter class into the former. And in all cases in which that transition has not yet taken place, the absence of direct proof is accounted for by the rarity or the obscurity of the phenomena, our deficient means of observing them, or the logical difficulties arising from the complication of the circumstances in which they occur. Insomuch that, notwithstanding as rigid a dependence on given conditions as exists in the case of any other phenomenon, it was not likely that we should be better acquainted with those conditions than we are. Besides this first class of considerations, there is a second, which still further corroborates the conclusion. Although there are phenomena the production and changes of which elude all our attempts to reduce them universally to any ascertained law, yet in every such case, the phenomenon, or the objects concerned in it, are found in some instances to obey the known laws of nature. The wind, for example, is the type of uncertainty and caprice. Yet we find it in some cases obeying with as much constancy as any phenomenon in nature the law of the tendency of fluids to distribute themselves so as to equalize the pressure on every side of each of their particles. As in the case of the trade winds and the monsoons. Lightning might once have been supposed to obey no laws. But since it has been ascertained to be identical with electricity, we know that the very same phenomenon in some of its manifestations is implicitly obedient to the action of fixed causes. I do not believe that there is now one object or event in all our experience of nature, within the bounds of the solar system at least, which has not either been ascertained by direct observation to follow laws of its own, or been proved to be closely similar to objects and events which, in more familiar manifestations, or on a more limited scale, follow strict laws. Our inability to trace the same laws on a larger scale and in the more recondite instances, being accounted for by the number and complication of the modifying causes, or by their inaccessibility to observation. The progress of experience, therefore, has dissipated the doubt which must have rested on the universality of the law of causation while there were phenomena which seemed to be sui generis, not subject to the same laws with any other class of phenomena, and not as yet ascertained to have peculiar laws of their own. This great generalization, however, might reasonably have been, as it in fact was, acted on as a probability of the highest order, before there were sufficient grounds for receiving it as a certainty. In matters of evidence, as in all other human things, we neither require, nor can attain, the absolute. We must hold even our strongest convictions with an opening left in our minds for the reception of facts which contradict them. And only when we have taken this precaution, have we earned the right to act upon our convictions with complete confidence when no such contradiction appears. Whatever has been found true in innumerable instances, and never found to be false after due examination in any, we are safe in acting on as universal provisionally, until an undoubted exception appears. Provided the nature of the case be such that a real exception could scarcely have escaped notice. When every phenomenon that we ever knew sufficiently well to be able to answer the question, had a cause on which it was invariably consequent. It was more rational to suppose that our inability to assign the causes of other phenomena arose from our ignorance, than that there were phenomena which were uncaused. and which happened to be exactly those which we had hitherto had no sufficient opportunity of studying. It must, at the same time, be remarked, that the reasons for this reliance do not hold in circumstances unknown to us, and beyond the possible range of our experience. In distant parts of the stellar regions, where the phenomena may be entirely unlike those with which we are acquainted, it would be folly to affirm confidently that this general law prevails, any more than those special ones which we have found to hold universally on our own planet. The uniformity in the succession of events, otherwise called the law of causation, must be received not as a law of the universe, but of that portion of it only which is within the range of our means of sure observation, with a reasonable degree of extension to adjacent cases. To extend it further is to make a supposition without evidence, and to which, in the absence of any ground from experience for estimating its degree of probability, it would be idle to attempt to assign any point. 188. XXIII of uniformities of coexistence not dependent on causation. Section 1. The order of the occurrence of phenomena in time is either successive or simultaneous. The uniformities, therefore, which obtain in their occurrence, are either uniformities of succession or of coexistence. Uniformities of succession are all comprehended under the law of causation and its consequences. Every phenomenon has a cause, which it invariably follows. And from this are derived other invariable sequences among the successive stages of the same effect, as well as between the effects resulting from causes which invariably succeed one another. In the same manner with these derivative uniformities of succession, a great variety of uniformities of coexistence also take their rise. Coordinate effects of the same cause naturally coexist with one another. High water at any point on the Earth's surface, and high water at the point diametrically opposite to it, are effects uniformly simultaneous, resulting from the direction in which the combined attractions of the sun and moon act upon the waters of the ocean. An eclipse of the sun to us, and an eclipse of the earth to a spectator situated in the moon, are in like manner phenomena invariably coexistent, and their coexistence can equally be deduced from the laws of their production. It is an obvious question, therefore, whether all the uniformities of coexistence among phenomena may not be accounted for in this manner. And it cannot be doubted that between phenomena which are themselves effects, the coexistences must necessarily depend on the causes of those phenomena. If they are effects immediately or remotely of the same cause, they cannot coexist except by virtue of some laws or properties of that cause. If they are effects of different causes, they cannot coexist unless it be because their causes coexist. And the uniformity of coexistence, if such there be, between the effects, proves that those particular causes, within the limits of our observation, have uniformly been coexistent. Section 2. But these same considerations compel us to recognize that there must be one class of coexistences which cannot depend on causation, the coexistences between the ultimate properties of things, those properties which are the causes of all phenomena, but are not themselves caused by any phenomenon, and a cause for which could only be sought by ascending to the origin of all things. Yet among these ultimate properties there are not only coexistences, but uniformities of coexistence. General propositions may be, and are, formed, which assert that whenever certain properties are found, certain others are found along with them. We perceive an object, say, for instance, water. We recognize it to be water, of course by certain of its properties. Having recognized it, we are able to affirm of it innumerable other properties, which we could not do unless it were a general truth, a law or uniformity in nature, that the set of properties by which we identify the substance as water always have those other properties conjoined with them. In a former place 189 it has been explained, in some detail, what is meant by the kinds of objects, those classes which differ from one another not by a limited and definite, but by an indefinite and unknown, number of distinctions. To this we have now to add, that every proposition by which any thing is asserted of a kind, affirms a uniformity of coexistence. Since we know nothing of kinds but their properties, the kind, to us, is the set of properties by which it is identified, and which must of course be sufficient to distinguish it from every other kind. 190 In affirming anything, therefore, of a kind, we are affirming something to be uniformly coexistent with the properties by which the kind is recognized, and that is the sole meaning of the assertion. Among the uniformities of coexistence which exist in nature, may hence be numbered all the properties of kinds. The whole of these, however, are not independent of causation, but only a portion of them. Some are ultimate properties, others derivative, of some, no cause can be assigned, but others are manifestly dependent on causes. Thus, pure oxygen gas is a kind, and one of its most unequivocal properties is its gaseous form. This property, however, has for its cause the presence of a certain quantity of latent heat. And if that heat could be taken away, as has been done from so many gases in Faraday's experiments, the gaseous form would doubtless disappear, together with numerous other properties which depend on, or are caused by, that property. In regard to all substances which are chemical compounds, and which therefore may be regarded as products of the juxtaposition of substances different in kind from themselves, there is considerable reason to presume that the specific properties of the compound are consequent, as effects, on some of the properties of the elements. Though little progress has yet been made in tracing any invariable relation between the latter and the former, still more strongly will a similar presumption exist, when the object itself, as in the case of organized beings, is no primeval agent, but an effect, which depends on a cause or causes for its very existence. The kinds, therefore, which are called in chemistry simple substances, or elementary natural agents, are the only ones, any of whose properties can with certainty be considered ultimate. And of these the ultimate properties are probably much more numerous than we at present recognize, since every successful instance of the resolution of the properties of their compounds into simpler laws generally leads to the recognition of properties in the elements distinct from any previously known. The resolution of the laws of the heavenly motions established the previously unknown ultimate property of a mutual attraction between all bodies. The resolution, so far as it has yet proceeded, of the laws of crystallization, of chemical composition, electricity, magnetism, etc., points to various polarities, ultimately inherent in the particles of which bodies are composed. The comparative atomic weights of different kinds of bodies were ascertained by resolving into more general laws the uniformities observed in the proportions in which substances combine with one another, and so forth. Thus, although every resolution of a complex uniformity into simpler and more elementary laws has an apparent tendency to diminish the number of the ultimate properties, and really does remove many properties from the list, yet, since the result of this simplifying process is to trace up an ever greater variety of different effects to the same agents, the further we advance in this direction, the greater number of distinct properties we are forced to recognize in one and the same object, the coexistences of which properties must accordingly be ranked among the ultimate generalities of nature. Section 3. There are, therefore, only two kinds of propositions which assert uniformity of coexistence between properties. Either the properties depend on causes or they do not. If they do, the proposition which affirms them to be coexistent is a derivative law of coexistence between effects, and, until resolved into the laws of causation on which it depends, is an empirical law, and to be tried by the principles of induction to which such laws are amenable. If, on the other hand, the properties do not depend on causes, but are ultimate properties, then, if it be true that they invariably coexist, they must all be ultimate properties of one and the same kind. And it is of these only that the coexistences can be classed as a peculiar sort of laws of nature. When we affirm that all crows are black, or that all Negroes have woolly hair, we assert a uniformity of coexistence. We assert that the property of blackness or of having woolly hair invariably coexists with the properties which, in common language, or in the scientific classification that we adopt, are taken to constitute the class crow, or the class Negro. Now, supposing blackness to be an ultimate property of black objects, or woolly hair an ultimate property of the animals which possess it. Supposing that these properties are not results of causation, are not connected with antecedent phenomena by any law. Then if all crows are black, and all Negroes have woolly hair, these must be ultimate properties of the kind crow, or Negro, or of some kind which includes them. If, on the contrary, blackness or woolly hair be an effect depending on causes, these general propositions are manifestly empirical laws. And all that has already been said respecting that class of generalizations may be applied without modification to these. Now, we have seen that in the case of all compounds, of all things, in short, except the elementary substances and primary powers of nature, the presumption is, that the properties do really depend upon causes. And it is impossible in any case whatever to be certain that they do not. We therefore should not be safe in claiming for any generalization respecting the coexistence of properties, a degree of certainty to which, if the properties should happen to be the result of causes, it would have no claim. A generalization respecting coexistence, or, in other words, respecting the properties of kinds, may be an ultimate truth, but it may also be merely a derivative one. And since, if so, it is one of those derivative laws which are neither laws of causation nor have been resolved into the laws of causation on which they depend, it can possess no higher degree of evidence than belongs to an empirical law. Section 4. This conclusion will be confirmed by the consideration of one great deficiency, which precludes the application to the ultimate uniformities of coexistence, of a system of rigorous scientific induction. Such as the uniformities in the succession of phenomena have been found to admit of. The basis of such a system is wanting. There is no general axiom standing in the same relation to the uniformities of coexistence as the law of causation does to those of succession. The methods of induction applicable to the ascertainment of causes and effects are grounded on the principle that everything which has a beginning must have some cause or other. That among the circumstances which actually existed at the time of its commencement, there is certainly some one combination, on which the effect in question is unconditionally consequent. And on the repetition of which it would certainly again recur. But in an inquiry whether some kind, as XVIII, universally possesses a certain property, as blackness, there is no room for any assumption analogous to this. We have no previous certainty that the property must have something which constantly coexists with it, must have an invariable coexistent, in the same manner as an event must have an invariable antecedent. When we feel pain, we must be in some circumstances under which, if exactly repeated, we should always feel pain. But when we are conscious of blackness, it does not follow that there is something else present of which blackness is a constant accompaniment. There is, therefore, no room for elimination. No method of agreement or difference, or of concomitant variations, which is but a modification either of the method of agreement or of the method of difference. We cannot conclude that the blackness we see in crows must be an invariable property of crows merely because there is nothing else present of which it can be an invariable property. We therefore inquire into the truth of a proposition like all crows are black, under the same disadvantage as if, in our inquiries into causation, we were compelled to let in, as one of the possibilities, that the effect may in that particular instance have arisen without any cause at all. To overlook this grand distinction was, as it seems to me, the capital error in Bacon's view of inductive philosophy. The principle of elimination, that great logical instrument which he had the immense merit of first bringing into general use, he deemed applicable in the same sense, and in as unqualified a manner, to the investigation of the coexistences, as to that of the successions of phenomena. He seems to have thought that as every event has a cause, or invariable antecedent, so every property of an object has an invariable coexistent, which he called its form. And the examples he chiefly selected for the application and illustration of his method, were inquiries into such forms. Attempts to determine in what else all those objects resembled, which agreed in some one general property, as hardness or softness, dryness or moistness, heat or coldness. Such inquiries could lead to no result. The objects seldom have any such circumstances in common. They usually agree in the one point inquired into, and in nothing else. A great proportion of the properties which, so far as we can conjecture, are the likeliest to be really ultimate, would seem to be inherently properties of many different kinds of things not allied in any other respect. And as for the properties which, being effects of causes, we are able to give some account of, they have generally nothing to do with the ultimate resemblances or diversities in the objects themselves, but depend on some outward circumstances, under the influence of which any objects whatever are capable of manifesting those properties. As is emphatically the case with those favorite subjects of Bacon's scientific inquiries, hotness and coldness, as well as with hardness and softness, solidity and fluidity, and many other conspicuous qualities. In the absence, then, of any universal law of coexistence similar to the universal law of causation which regulates sequence, we are thrown back upon the unscientific induction of the ancients, per enumerationem simplicem. Ubi non reparatur instantia contradictoria. The reason we have for believing that all crows are black, is simply that we have seen and heard of many black crows, and never one of any other color. It remains to be considered how far this evidence can reach, and how we are to measure its strength in any given case. Section 5. It sometimes happens that a mere change in the mode of verbally enunciating a question, though nothing is really added to the meaning expressed, is of itself a considerable step toward its solution. This, I think, happens in the present instance. The degree of certainty of any generalization which rests on no other evidence than the agreement, so far as it goes, of all past observation, is but another phrase for the degree of improbability that an exception, if any existed, could have hitherto remained unobserved. The reason for believing that all crows are black, is measured by the improbability that crows of any other color should have existed to the present time without our being aware of it. Let us state the question in this last mode, and consider what is implied in the supposition that there may be crows which are not black, and under what conditions we can be justified in regarding this as incredible. If there really exist crows which are not black, one of two things must be the fact. Either the circumstance of blackness, in all crows hitherto observed, must be, as it were, an accident, not connected with any distinction of kind. Or if it be a property of kind, the crows which are not black must be a new kind, a kind hitherto overlooked, though coming under the same general description by which crows have hitherto been characterized. The first supposition would be proved true if we were to discover casually a white crow among black ones, or if it were found that black crows sometimes turn white. The second would be shown to be the fact if in Australia or Central Africa a species or a race of white or grey crows were found to exist. Section 6. The former of these suppositions necessarily implies that the color is an effect of causation. If blackness, in the crows in which it has been observed, be not a property of kind, but can be present or absent without any difference generally in the properties of the object, then it is not an ultimate fact in the individuals themselves, but is certainly dependent on a cause. There are, no doubt, many properties which vary from individual to individual of the same kind, even the same infima species, or lowest kind. Some flowers may be either white or red, without differing in any other respect. But these properties are not ultimate, they depend on causes. So far as the properties of a thing belong to its own nature, and do not arise from some cause extrinsic to it, they are always the same in the same kind. Take, for instance, all simple substances and elementary powers, the only things of which we are certain that some at least of their properties are really ultimate. Color is generally esteemed the most variable of all properties, yet we do not find that sulfur is sometimes yellow and sometimes white, or that it varies in color at all, except so far as color is the effect of some extrinsic cause. As of the sort of light thrown upon it, the mechanical arrangement of the particles, as after fusion, etc. We do not find that iron is sometimes fluid and sometimes solid at the same temperature, gold sometimes malleable and sometimes brittle, that hydrogen will sometimes combine with oxygen and sometimes not, or the like. If from simple substances we pass to any of their definite compounds, as water, lime, or sulfuric acid, there is the same constancy in their properties. When properties vary from individual to individual, it is either in the case of miscellaneous aggregations, such as atmospheric air or rock, composed of heterogeneous substances, and not constituting or belonging to any real kind. 191 Or it is in the case of organic beings. In them, indeed, there is variability in a high degree. Animals of the same species and race, human beings of the same age, sex, and country, will be most different, for example, in face and figure. But organized beings, from the extreme complication of the laws by which they are regulated, being more eminently modifiable, that is, liable to be influenced by a greater number and variety of causes, than any other phenomena whatever. Having also themselves had a beginning, and therefore a cause, there is reason to believe that none of their properties are ultimate, but all of them derivative, and produced by causation. And the presumption is confirmed, by the fact that the properties which vary from one individual to another, also generally vary more or less at different times in the same individual. Which variation, like any other event, supposes a cause, and implies, consequently, that the properties are not independent of causation. If, therefore, blackness be merely accidental in crows, and capable of varying while the kind remains the same, its presence or absence is doubtless no ultimate fact. But the effect of some unknown cause, and in that case the universality of the experience that all crows are black is sufficient proof of a common cause, and establishes the generalization as an empirical law. Since there are innumerable instances in the affirmative, and hitherto none at all in the negative, the causes on which the property depends must exist everywhere in the limits of the observations which have been made. And the proposition may be received as universal within those limits, and with the allowable degree of extension to adjacent cases. Section 7. If, in the second place, the property, in the instances in which it has been observed, is not an effect of causation, it is a property of kind. And in that case the generalization can only be set aside by the discovery of a new kind of crow. That, however, a peculiar kind not hitherto discovered should exist in nature, is a supposition so often realized that it cannot be considered at all improbable. We have nothing to authorize us in attempting to limit the kinds of things which exist in nature. The only unlikelihood would be that a new kind should be discovered in localities which there was previously reason to believe had been thoroughly explored. And even this improbability depends on the degree of conspicuousness of the difference between the newly discovered kind and all others, since new kinds of minerals, plants, and even animals, previously overlooked or confounded with known species, are still continually detected in the most frequented situations. On this second ground, therefore, as well as on the first, the observed uniformity of coexistence can only hold good as an empirical law, within the limits not only of actual observation, but of an observation as accurate as the nature of the case required. And hence it is that, as remarked in an early chapter of the present book, we so often give up generalizations of this class at the first summons. If any credible witness stated that he had seen a white crow, under circumstances which made it not incredible that it should have escaped notice previously, we should give full credence to the statement. It appears, then, that the uniformities which obtain in the coexistence of phenomena, those which we have reason to consider as ultimate, no less than those which arise from the laws of causes yet undetected, are entitled to reception only as empirical laws, are not to be presumed true except within the limits of time, place, and circumstance, in which the observations were made, or except in cases strictly adjacent. Section 8. We have seen in the last chapter that there is a point of generality at which empirical laws become as certain as laws of nature, or, rather, at which there is no longer any distinction between empirical laws and laws of nature. As empirical laws approach this point, in other words, as they rise in their degree of generality, they become more certain, their universality may be more strongly relied on. For, in the first place, if they are results of causation, which, even in the class of uniformities treated of in the present chapter, we never can be certain that they are not, the more general they are, the greater is proved to be the space over which the necessary collocations prevail, and within which no causes exist capable of counteracting the unknown causes on which the empirical law depends. To say that anything is an invariable property of some very limited class of objects, is to say that it invariably accompanies some very numerous and complex group of distinguishing properties, which, if causation be at all concerned in the matter, argues a combination of many causes, and therefore a great liability to counteraction. While the comparatively narrow range of the observations renders it impossible to predict to what extent unknown counteracting causes may be distributed throughout nature. But when a generalization has been found to hold good of a very large proportion of all things whatever, it is already proved that nearly all the causes which exist in nature have no power over it. That very few changes in the combination of causes can affect it, since the greater number of possible combinations must have already existed in some one or other of the instances in which it has been found true. If, therefore, any empirical law is a result of causation, the more general it is, the more it may be depended on. And even if it be no result of causation, but an ultimate coexistence, the more general it is, the greater amount of experience it is derived from, and the greater therefore is the probability that if exceptions had existed, some would already have presented themselves. For these reasons, it requires much more evidence to establish an exception to one of the more general empirical laws than to the more special ones. We should not have any difficulty in believing that there might be a new kind of crow, or a new kind of bird resembling a crow in the properties hitherto considered distinctive of that kind. But it would require stronger proof to convince us of the existence of a kind of crow having properties at variance with any generally recognized universal property of birds, and a still higher degree if the properties conflict with any recognized universal property of animals. And this is conformable to the mode of judgment recommended by the common sense and general practice of mankind, who are more incredulous as to any novelties in nature, according to the degree of generality of the experience which these novelties seem to contradict. Section 9. It is conceivable that the alleged properties might conflict with some recognized universal property of all matter. In that case their improbability would be at the highest, but would not even then amount to incredibility. There are only two known properties common to all matter. In other words, there is but one known uniformity of coexistence of properties coextensive with all physical nature, namely, that whatever opposes resistance to movement gravitates, or, as Professor Bain expresses it, inertia and gravity are coexistent through all matter, and proportionate in their amount. These properties, as he truly says, are not mutually implicated, from neither of them could we, on grounds of causation, presume the other. But, for this very reason, we are never certain that a kind may not be discovered possessing one of the properties without the other. The hypothetical ether, if it exists, may be such a kind. Our senses cannot recognize in it either resistance or gravity. But if the reality of a resisting medium should eventually be proved, by alteration, for example, in the times of revolution of periodic comets, combined with the evidences afforded by the phenomena of light and heat, it would be rash to conclude from this alone, without other proofs, that it must gravitate. For even the greater generalizations, which embrace comprehensive kinds containing under them a great number and variety of infamy species, are only empirical laws, resting on induction by simple enumeration merely, and not on any process of elimination, a process wholly inapplicable to this sort of case. Such generalizations, therefore, ought to be grounded on an examination of all the infamy species comprehended in them, and not of a portion only. We cannot conclude, where causation is not concerned, because a proposition is true of a number of things resembling one another only in being animals, that it is therefore true of all animals. If, indeed, anything be true of species which differ more from one another than either differs from a third, especially if that third species occupies in most of its known properties a position between the two former, there is some probability that the same thing will also be true of that intermediate species. For it is often, though by no means universally, found, that there is a sort of parallelism in the properties of different kinds, and that their degree of unlikeness in one respect bears some proportion to their unlikeness in others. We see this parallelism in the properties of the different metals, in those of sulfur, phosphorus, and carbon, of chlorine, iodine, and bromine, in the natural orders of plants and animals, etc. But there are innumerable anomalies and exceptions to this sort of conformity, if indeed the conformity itself be anything but an anomaly and an exception in nature. Universal propositions, therefore, respecting the properties of superior kinds, unless grounded on proved or presumed connection by causation, ought not to be hazarded except after separately examining every known subkind included in the larger kind. And even then such generalizations must be held in readiness to be given up on the occurrence of some new anomaly, which, when the uniformity is not derived from causation, can never, even in the case of the most general of these empirical laws, be considered very improbable. Thus, all the universal propositions which it has been attempted to lay down respecting simple substances, or concerning any of the classes which have been formed among simple substances, and the attempt has been often made, have, with the progress of experience, either faded into inanity, or been proved to be erroneous. And each kind of simple substance remains, with its own collection of properties apart from the rest, saving a certain parallelism with a few other kinds, the most similar to itself. In organized beings, indeed, there are abundance of propositions ascertained to be universally true of superior genera, to many of which the discovery hereafter of any exceptions must be regarded as extremely improbable. But these, as already observed, are, we have every reason to believe, properties dependent on causation. 192. Uniformities of coexistence, then, not only when they are consequences of laws of succession, but also when they are ultimate truths, must be ranked, for the purpose of logic, among empirical laws, and are amenable in every respect to the same rules with those unresolved uniformities which are known to be dependent on causation. 193. XIII of Approximate Generalizations, and Probable Evidence. Section 1. In our inquiries into the nature of the inductive process, we must not confine our notice to such generalizations from experience as profess to be universally true. There is a class of inductive truths avowedly not universal, in which it is not pretended that the predicate is always true of the subject, but the value of which, as generalizations, is nevertheless extremely great. An important portion of the field of inductive knowledge does not consist of universal truths, but of approximations to such truths. And when a conclusion is said to rest on probable evidence, the premises it is drawn from are usually generalizations of this sort. As every certain inference respecting a particular case implies that there is ground for a general proposition of the form, every A is B, so does every probable inference suppose that there is ground for a proposition of the form, most A are B. And the degree of probability of the inference in an average case will depend on the proportion between the number of instances existing in nature which accord with the generalization, and the number of those which conflict with it. Section 2. Propositions in the form, most A are B, are of a very different degree of importance in science, and in the practice of life. To the scientific inquirer they are valuable chiefly as materials for, and steps toward universal truths. The discovery of these is the proper end of science. Its work is not done if it stops at the proposition that a majority of A are B, without circumscribing that majority by some common character, fitted to distinguish them from the minority. Independently of the inferior precision of such imperfect generalizations, and the inferior assurance with which they can be applied to individual cases, it is plain that, compared with exact generalizations, they are almost useless as means of discovering ulterior truths by way of deduction. We may, it is true, by combining the proposition most A are B, with a universal proposition, every B is C, arrive at the conclusion that most A are C. But when a second proposition of the approximate kind is introduced, or even when there is but one, if that one be the major premise, nothing can, in general, be positively concluded. When the major is most B are D, then, even if the minor be every A is B, we cannot infer that most A are D, or with any certainty that even some A are D. Though the majority of the class B have the attribute signified by D, the whole of the subclass A may belong to the minority. 194. Though so little use can be made, in science, of approximate generalizations, except as a stage on the road to something better, for practical guidance they are often all we have to rely on. Even when science has really determined the universal laws of any phenomenon, not only are those laws generally too much encumbered with conditions to be adapted for everyday use, but the cases which present themselves in life are too complicated. And our decisions require to be taken too rapidly, to admit of waiting till the existence of a phenomenon can be proved by what have been scientifically ascertained to be universal marks of it. To be indecisive and reluctant to act, because we have not evidence of a perfectly conclusive character to act on, is a defect sometimes incident to scientific minds, but which, wherever it exists, renders them unfit for practical emergencies. If we would succeed in action, we must judge by indications which, though they do not generally mislead us, sometimes do, and must make up, as far as possible, for the incomplete conclusiveness of any one indication, by obtaining others to corroborate it. The principles of induction applicable to approximate generalization are therefore a not less important subject of inquiry than the rules for the investigation of universal truths, and might reasonably be expected to detain us almost as long, were it not that these principles are mere corollaries from those which have been already treated of. Section 3. There are two sorts of cases in which we are forced to guide ourselves by generalizations of the imperfect form, most A or B. The first is, when we have no others. When we have not been able to carry our investigation of the laws of the phenomena any further, as in the following propositions: most dark-eyed persons have dark hair, most springs contain mineral substances, most stratified formations contain fossils. The importance of this class of generalizations is not very great. For, though it frequently happens that we see no reason why that which is true of most individuals of a class is not true of the remainder, nor are able to bring the former under any general description which can distinguish them from the latter, yet if we are willing to be satisfied with propositions of a less degree of generality, and to break down the class A into subclasses, we may generally obtain a collection of propositions exactly true. We do not know why most wood is lighter than water, nor can we point out any general property which discriminates wood that is lighter than water from that which is heavier. But we know exactly what species are the one and what the other. And if we meet with a specimen not conformable to any known species, the only case in which our previous knowledge affords no other guidance than the approximate generalization, we can generally make a specific experiment, which is a surer resource. It often happens, however, that the proposition, most A or B, is not the ultimatum of our scientific attainments, though the knowledge we possess beyond it cannot conveniently be brought to bear upon the particular instance. We may know well enough what circumstances distinguish the portion of A which has the attribute B from the portion which has it not, but may have no means, or may not have time, to examine whether those characteristic circumstances exist or not in the individual case. This is the situation we are generally in when the inquiry is of the kind called moral, that is, of the kind which has in view to predict human actions. To enable us to affirm anything universally concerning the actions of classes of human beings, the classification must be grounded on the circumstances of their mental culture and habits, which in an individual case are seldom exactly known. And classes grounded on these distinctions would never precisely accord with those into which mankind are divided for social purposes. All propositions which can be framed respecting the actions of human beings as ordinarily classified, or as classified according to any kind of outward indications, are merely approximate. We can only say, most persons of a particular age, profession, country, or rank in society, have such and such qualities, or, most persons, when placed in certain circumstances, act in such and such a way. Not that we do not often know well enough on what causes the qualities depend, or what sort of persons they are who act in that particular way. But we have seldom the means of knowing whether any individual person has been under the influence of those causes, or is a person of that particular sort. We could replace the approximate generalizations by propositions universally true. But these would hardly ever be capable of being applied to practice. We should be sure of our majors, but we should not be able to get minors to fit. We are forced, therefore, to draw our conclusions from coarser and more fallible indications. Section 4. Proceeding now to consider what is to be regarded as sufficient evidence of an approximate generalization, we can have no difficulty in at once recognizing that, when admissible at all, it is admissible only as an empirical law. Propositions of the form, every A is B, are not necessarily laws of causation, or ultimate uniformities of coexistence. Propositions like most A are B, cannot be so. Propositions hitherto found true in every observed instance may yet be no necessary consequence of laws of causation, or of ultimate uniformities, and unless they are so, may, for aught we know, be false beyond the limits of actual observation. Still more evidently must this be the case with propositions which are only true in a mere majority of the observed instances. There is some difference, however, in the degree of certainty of the proposition, most A or B, according as that approximate generalization composes the whole of our knowledge of the subject, or not. Suppose, first, that the former is the case. We know only that most A are B, not why they are so, nor in what respect those which are differ from those which are not. How, then, did we learn that most A are B? Precisely in the manner in which we should have learned, had such happened to be the fact that all A are B. We collected a number of instances sufficient to eliminate chance, and, having done so, compared the number of instances in the affirmative with the number in the negative. The result, like other unresolved derivative laws, can be relied on solely within the limits not only of place and time, but also of circumstance, under which its truth has been actually observed. For, as we are supposed to be ignorant of the causes which make the proposition true, we cannot tell in what manner any new circumstance might perhaps affect it. The proposition, most judges are inaccessible to bribes, would probably be found true of Englishmen, Frenchmen, Germans, North Americans, and so forth. But if on this evidence alone we extended the assertion to Orientals, we should step beyond the limits, not only of place but of circumstance, within which the fact had been observed. And should let in possibilities of the absence of the determining causes, or the presence of counteracting ones, which might be fatal to the approximate generalization. In the case where the approximate proposition is not the ultimatum of our scientific knowledge, but only the most available form of it for practical guidance. Where we know, not only that most A have the attribute B, but also the causes of B, or some properties by which the portion of A which has that attribute is distinguished from the portion which has it not. We are rather more favorably situated than in the preceding case. For we have now a double mode of ascertaining whether it be true that most A are B. The direct mode, as before, and an indirect one, that of examining whether the proposition admits of being deduced from the known cause, or from any known criterion, of B. Let the question, for example, be whether most Scotchmen can read. We may not have observed, or received the testimony of others respecting, a sufficient number and variety of Scotchmen to ascertain this fact. But when we consider that the cause of being able to read is the having been taught it, another mode of determining the question presents itself, namely, by inquiring whether most Scotchmen have been sent to schools where reading is effectually taught. Of these two modes, sometimes one and sometimes the other is the more available. In some cases, the frequency of the effect is the more accessible to that extensive and varied observation which is indispensable to the establishment of an empirical law. At other times, the frequency of the causes, or of some collateral indications. It commonly happens that neither is susceptible of so satisfactory an induction as could be desired, and that the grounds on which the conclusion is received are compounded of both. Thus a person may believe that most Scotchmen can read, because, so far as his information extends, most Scotchmen have been sent to school, and most Scotch schools teach reading effectually. And also because most of the Scotchmen whom he has known or heard of could read, though neither of these two sets of observations may by itself fulfill the necessary conditions of extent and variety. Although the approximate generalization may in most cases be indispensable for our guidance, even when we know the cause, or some certain mark, of the attribute predicated. It needs hardly be observed that we may always replace the uncertain indication by a certain one, in any case in which we can actually recognize the existence of the cause or mark. For example, an assertion is made by a witness, and the question is whether to believe it. If we do not look to any of the individual circumstances of the case, we have nothing to direct us but the approximate generalization, that truth is more common than falsehood, or, in other words, that most persons, on most occasions, speak truth. But if we consider in what circumstances the cases where truth is spoken differ from those in which it is not, we find, for instance, the following: the witnesses being an honest person or not, his being an accurate observer or not. His having an interest to serve in the matter or not. Now, not only may we be able to obtain other approximate generalizations respecting the degree of frequency of these various possibilities, but we may know which of them is positively realized in the individual case. That the witness has or has not an interest to serve, we perhaps know directly, and the other 2 points indirectly, by means of marks, as, for example, from his conduct on some former occasion. Or from his reputation, which, though a very uncertain mark, affords an approximate generalization, as, for instance, most persons who are believed to be honest by those with whom they have had frequent dealings, are really so. Which approaches nearer to a universal truth than the approximate general proposition with which we set out, viz. Most persons on most occasions speak truth. As it seems unnecessary to dwell further on the question of the evidence of approximate generalizations, we shall proceed to a not less important topic. That of the cautions to be observed in arguing from these incompletely universal propositions to particular cases. Section 5. So far as regards the direct application of an approximate generalization to an individual instance, this question presents no difficulty. If the proposition, most A are B, has been established, by a sufficient induction, as an empirical law, we may conclude that any particular A is B with a probability proportion to the preponderance of the number of affirmative instances over the number of exceptions. If it has been found practicable to attain numerical precision in the data, a corresponding degree of precision may be given to the evaluation of the chances of error in the conclusion. If it can be established as an empirical law that 9 out of every 10 A are B, there will be 1 chance in 10 of error in assuming that any A, not individually known to us, is AB, but this of course holds only within the limits of time, place, and circumstance, embraced in the observations, and therefore cannot be counted on for any subclass or variety of A, or for A in any set of external circumstances, which were not included in the average. It must be added, that we can guide ourselves by the proposition, 9 out of every 10 A are B, only in cases of which we know nothing except that they fall within the class A. For if we know, of any particular instances I, not only that it falls under A, but to what species or variety of A it belongs, we shall generally err in applying to I the average struck for the whole genus, from which the average corresponding to that species alone would, in all probability, materially differ. And so if I, instead of being a particular sort of instance, is an instance known to be under the influence of a particular set of circumstances, the presumption drawn from the numerical proportions in the whole genus would probably, in such a case, only mislead. A general average should only be applied to cases which are neither known, nor can be presumed, to be other than average cases. Such averages, therefore, are commonly of little use for the practical guidance of any affairs but those which concern large numbers. Tables of the chances of life are useful to insurance offices, but they go a very little way toward informing any one of the chances of his own life, or any other life in which he is interested. Since almost every life is either better or worse than the average. Such averages can only be considered as supplying the first term in a series of approximations, the subsequent terms proceeding on an appreciation of the circumstances belonging to the particular case. Section 6. From the application of a single approximate generalization to individual cases, we proceed to the application of 2 or more of them together to the same case. When a judgment applied to an individual instance is grounded on 2 approximate generalizations taken in conjunction, the propositions may cooperate toward the result in 2 different ways. In the one, each proposition is separately applicable to the case in hand, and our object in combining them is to give to the conclusion in that particular case the double probability arising from the 2 propositions separately. This may be called joining 2 probabilities by way of addition, and the result is a probability greater than either. The other mode is, when only one of the propositions is directly applicable to the case, the second being only applicable to it by virtue of the application of the first. This is joining 2 probabilities by way of ratiocination or deduction, the result of which is a less probability than either. The type of the first argument is, most A are B, most C are B. this thing is both an A and a C, therefore it is probably a B. The type of the second is, most A are B, most C are A, this is a C. Therefore it is probably an A, therefore it is probably a B. The first is exemplified when we prove a fact by the testimony of two unconnected witnesses. The second, when we adduce only the testimony of one witness that he has heard the thing asserted by another. Or again, in the first mode it may be argued that the accused committed the crime, because he concealed himself, and because his clothes were stained with blood. In the second, that he committed it because he washed or destroyed his clothes, which is supposed to render it probable that they were stained with blood. Instead of only two links, as in these instances, we may suppose chains of any length. A chain of the former kind was termed by Bentham 195 a self-corroborative chain of evidence, the second, a self-informative chain. When approximate generalizations are joined by way of addition, we may deduce from the theory of probabilities laid down in a former chapter, in what manner each of them adds to the probability of a conclusion which has the warrant of them all. If, on an average, 2 of every 3 as are BS, and 3 of every 4 CS are BS, the probability that something which is both an A and a C is a B, will be more than 2 in 3, or than 3 in 4. Of every 12 things which are as, all except 4 are BS by the supposition, and if the whole 12, and consequently those 4, have the characters of C likewise, 3 of these will be BS on that ground. Therefore, out of 12 which are both as and CS, 11 are BS. To state the argument in another way. A thing which is both an A and a C, but which is not a B, is found in only one of 3 sections of the class A, and in only one of 4 sections of the class C. But this fourth of C being spread over the whole of A indiscriminately, only 1/3 part of it, or 1/12 of the whole number, belongs to the 3rd section of A. Therefore a thing which is not a B occurs only once, among 12 things which are both as and CS. The argument would, in the language of the doctrine of chances, be thus expressed: the chance that an A is not a B is 1/3, the chance that a C is not a B is 1/4, hence if the thing be both an A and a C, the chance is 1/3 of 1/4 equals 1/12. 196. In this computation it is of course supposed that the probabilities arising from A and C are independent of each other. There must not be any such connection between A and C, that when a thing belongs to the one class it will therefore belong to the other, or even have a greater chance of doing so. Otherwise the not BS which are CS may be, most or even all of them, identical with the not BS which are as, in which last case the probability arising from A and C together will be no greater than that arising from A alone. When approximate generalizations are joined together in the other mode, that of deduction, the degree of probability of the inference, instead of increasing, diminishes at each step. From 2 such premises as most A are B, most B are C, we cannot with certainty conclude that even a single A is C, for the whole of the portion of A which in any way falls under B, may perhaps be comprised in the exceptional part of it. Still, the 2 propositions in question afford an appreciable probability that any given A is C, provided the average on which the second proposition is grounded was taken fairly with reference to the first. Provided the proposition, most B are C, was arrived at in a manner leaving no suspicion that the probability arising from it is otherwise than fairly distributed over the section of B which belongs to A. For though the instances which are A may be all in the minority, they may, also, be all in the majority, and the one possibility is to be set against the other. On the whole, the probability arising from the 2 propositions taken together, will be correctly measured by the probability arising from the one, abetted in the ratio of that arising from the other. If 9 out of 10 Swedes have light hair, and 8 out of 9 inhabitants of Stockholm are Swedes, the probability arising from these 2 propositions, that any given inhabitant of Stockholm is light-haired, will amount to 8 in 10. Though it is rigorously possible that the whole Swedish population of Stockholm might belong to that 10th section of the people of Sweden who are an exception to the rest. If the premises are known to be true not of a bare majority, but of nearly the whole, of their respective subjects, we may go on joining one such proposition to another for several steps. before we reach a conclusion not presumably true even of a majority. The error of the conclusion will amount to the aggregate of the errors of all the premises. Let the proposition, most A are B, be true of 9 in 10, most B are C, of 8 in 9. Then not only will one A in 10 not be C, because not B, but even of the 9/10 which are B, only 8/9 will be C, that is, the cases of A which are C will be only August 9th of 9/10, or 4/5. Let us now add most C are D, and suppose this to be true of 7 cases out of 8, the proportion of A which is D will be only 7/8 of 8/9 of 9/10, or 7/10. Thus the probability progressively dwindles. The experience, however, on which our approximate generalizations are grounded, has so rarely been subjected to, or admits of, accurate numerical estimation, that we cannot in general apply any measurement to the diminution of probability which takes place at each elation, but must be content with remembering that it does diminish at every step, and that unless the premises approach very nearly indeed to being universally true, the conclusion after a very few steps is worth nothing. A hearsay of a hearsay, or an argument from presumptive evidence depending not on immediate marks but on marks of marks, is worthless at a very few removes from the first stage. Section 7. There are, however, 2 cases in which reasonings depending on approximate generalizations may be carried to any length we please with as much assurance, and are as strictly scientific, as if they were composed of universal laws of nature. But these cases are exceptions of the sort which are currently said to prove the rule. The approximate generalizations are as suitable, in the cases in question, for purposes of ratiocination, as if they were complete generalizations, because they are capable of being transformed into complete generalizations exactly equivalent. First, if the approximate generalization is of the class in which our reason for stopping at the approximation is not the impossibility, but only the inconvenience, of going further. If we are cognizant of the character which distinguishes the cases that accord with the generalization from those which are exceptions to it, we may then substitute for the approximate proposition, a universal proposition with a proviso. The proposition, most persons who have uncontrolled power employ it ill, is a generalization of this class, and may be transformed into the following: all persons who have uncontrolled power employ it ill, provided they are not persons of unusual strength of judgment and rectitude of purpose. The proposition, carrying the hypothesis or proviso with it, may then be dealt with no longer as an approximate, but as a universal proposition. And to whatever number of steps the reasoning may reach, the hypothesis, being carried forward to the conclusion, will exactly indicate how far that conclusion is from being applicable universally. If in the course of the argument other approximate generalizations are introduced, each of them being in like manner expressed as a universal proposition with a condition annexed, the sum of all the conditions will appear at the end as the sum of all the errors which affect the conclusion. Thus, to the proposition last cited, let us add the following: all absolute monarchs have uncontrolled power, unless their position is such that they need the active support of their subjects, as was the case with Queen Elizabeth, Frederick of Prussia, and others. Combining these 2 propositions, we can deduce from them a universal conclusion, which will be subject to both the hypotheses in the premises. All absolute monarchs employ their power ill, unless their position makes them need the active support of their subjects, or unless they are persons of unusual strength of judgment and rectitude of purpose. It is of no consequence how rapidly the errors in our premises accumulate, if we are able in this manner to record each error, and keep an account of the aggregate as it swells up. Secondly, there is a case in which approximate propositions, even without our taking note of the conditions under which they are not true of individual cases, are yet, for the purposes of science, universal ones. Namely, in the inquiries which relate to the properties not of individuals, but of multitudes. The principal of these is the science of politics, or of human society. This science is principally concerned with the actions not of solitary individuals, but of masses, with the fortunes not of single persons, but of communities. For the statesman, therefore, it is generally enough to know that most persons act or are acted upon in a particular way. Since his speculations and his practical arrangements refer almost exclusively to cases in which the whole community, or some large portion of it, is acted upon at once, and in which, therefore, what is done or felt by most persons determines the result produced by or upon the body at large. He can get on well enough with approximate generalizations on human nature, since what is true approximately of all individuals is true absolutely of all masses. And even when the operations of individual men have a part to play in his deductions, as when he is reasoning of kings, or other single rulers, still, as he is providing for indefinite duration, involving an indefinite succession of such individuals, he must in general both reason and act as if what is true of most persons were true of all. The two kinds of considerations above adduced are a sufficient refutation of the popular error, that speculations on society and government, as resting on merely probable evidence, must be inferior in certainty and scientific accuracy to the conclusions of what are called the exact sciences, and less to be relied on in practice. There are reasons enough why the moral sciences must remain inferior to at least the more perfect of the physical. Why the laws of their more complicated phenomena cannot be so completely deciphered, nor the phenomena predicted with the same degree of assurance. But though we cannot attain to so many truths, there is no reason that those we can attain should deserve less reliance, or have less of a scientific character. Of this topic, however, I shall treat more systematically in the concluding book, to which place any further consideration of it must be deferred.